If you're interested in blockchain development, this in-depth course will teach you about the Tezos ecosystem and how to develop distributed applications for it. The only prerequisite for it is a little Python knowledge. This course was made possible through a grant from the Tezos Foundation back in 2022.
In this module, we will do a quick overview of the different applications a blockchain like Tezos already makes possible. The first type of application is to help the building of communities around brands or teams, and to make it possible to own an internal and unique piece of history. NFTs make it possible for fans or customers to own and collect a token specific to their favorite team or to their favorite brand. Then, marketplaces, exchanges, or DAOs make it possible to build communities around them and help give fans a sense of belonging. Tezos is used for this in all kinds of fields, for example fashion, soccer, Formula 1, esport, or even spring water. Another application of Tezos is in the field of games, where it can be used to add new features that help extend the life of games and provide a better experience for gamers. It can be used to eternally preserve a player's achievements. It can also be used to create multi-game challenges. And it also lets users collect and trade in-game assets. Tezos is also used a lot in the field of art. It helps give artists a much wider and international audience, and it brings new ways for artists to make a living thanks to direct sales or royalties. It also enables the production and sale of new forms of art, such as generative art. A very strong field for blockchains is decentralized finance, that brings new financial products and make them available to anyone. Some examples on Tezos include projects like Lug, a stablecoin pegged to the euro, or real estate tokenization projects that make it easy to own a piece of a property, and decentralized lending markets that make it easy to borrow different types of tokens. Tezos can also help people develop initiatives around causes, for example, around protecting the environment. It can be used to raise funds for nature preservation and to build communities around nature awareness. These are only a few examples of what's possible with Tezos, and it is only the beginning. By following this course and learning to develop your own smart contracts, you will be able to invent your own applications in one of these fields or in other fields. In this short module, we'll do a quick overview of what you will learn during this course. We'll start by showing you the different key components of a blockchain and its ecosystem. So we'll talk about accounts, about wallets, about blocks, etc., so that you can understand all of these different elements and their names. Then you will practice by creating an account and performing a few transactions, calling smart contracts, etc. In the next step, we'll have a video that shows you all the different steps that a transaction takes from the moment you decide, for example, to purchase an NFT to the moment that this transaction is final on the blockchain. So that will help you understand what really happens internally and how things work in the blockchain. Then we'll focus on the heart of this course, which is for you to learn to develop your own smart contracts using the SmartPy language, one of the several languages that are available to write smart contracts on Tezos. While you learn to write your smart contracts, you will also learn how to develop your own test scenarios for your smart contract to make sure that everything works and to avoid the main bugs. You will practice all this on a variety of concrete exercises and examples. This will be a very practice-oriented training, and we ask you to play along and really try to solve each exercise, because we really believe that this is by practicing that you really learn the best. So you will learn smart contract concepts from the very basic types, like basic numbers and strings, all the way to very advanced smart contract concepts, such as inter-contract calls or upgradable contracts. And you'll realize that smart contracts are usually small projects, so it's not very hard to write smart contracts, but the hard part is to avoid flaws. So to help you with that, we will spend quite a bit of time teaching you how to detect flaws, how to avoid them, and how to fix them. Because a flaw in a smart contract can mean potentially losing millions. You will be creating smart contracts in all kinds of areas. You will create NFT smart contract, marketplaces, auctions, yield farming smart contracts. You will learn to build oracles, decentralized autonomous organizations, or we will play with randomness through a lottery smart contract. Then you will work on decentralized finance contracts. So we'll talk about how flash loans work, how fungible tokens can be created, and how to exchange currencies using liquidity pools and take advantage of arbitrage opportunities, etc. So this will give you a good idea of what real smart contracts look like and put you on a path to write your own. There are very few prerequisites for this course, and what you really need is some basic experience with programming. We don't expect you to be a very good developer, but you do need some programming experience to be able to follow this course. What you don't need is specific knowledge about Python. It may be helpful if you already know Python, because SmartPy is based on Python, but you'll be okay if you're not familiar with Python. And you also don't need prior blockchain experience. We'll teach you the basics that you will need for this course. In this module, we'll give an overview of Tezos and its different components, and get an idea of what a blockchain is. Tezos is a public open source blockchain protocol. This means anybody can read the code of all the elements of the blockchain, and anybody can access the data of the blockchain and even join the blockchain by setting up their own node. We also say that Tezos is a smart contracts platform. This means it's a kind of blockchain where you can deploy and execute smart contracts. One of the key aspects of Tezos is that it relies on an energy-efficient proof-of-stake consensus algorithm that makes it very environmentally friendly compared to some other blockchains. Tezos has a self-amending governance that makes it easy for the protocol to evolve without the need for hard forks. The community itself decides through rules defined by the protocol on evolutions of the protocols that we call amendments. And Tezos has been designed to facilitate code safety through a number of design choices and the application of formal verification to the protocol. So let's talk quickly about the history of Tezos. When creating Tezos, the creators wanted to address the weakness of the first blockchains. There was a weakness in the governance, the way that blockchain could evolve and how the community could decide on how to evolve the protocol. It appears that the first blockchains didn't evolve as much as they could because they lacked a governance mechanism. Another weakness was the high energy consumption of blockchains due to the use of proof of work as a consensus algorithm. Finally, there were a number of security issues with existing blockchains that the creators of Tezos wanted to address. The first step in the creation of Tezos was the publication of a white paper in 2014 that described its principles. From 2014 to 2017, a prototype of the Tezos protocol was developed. Then in July 2017, 232 million USD were raised in Bitcoins and ETH to help develop the ecosystem. And the Tezos mainnet was launched in July 2018. After it's launched, between 2018 and so far 2023, the Tezos protocol was upgraded 14 times through the on-chain governance system. So when we talk about Tezos, we're talking about the Tezos blockchain or the Tezos network. If we talk about the underlying cryptocurrency, we will talk about the Tez. And when you talk about amounts, you talk about how many Tez you have. Or for example, Alice transfers 10 Tez to Bob. The ticker used when you want to check the conversion rates between different cryptocurrencies on exchanges is XTZ. And Tezos has a logo that you can see here. Now we will describe the different key elements of Tezos. We'll talk about accounts, transactions, smart contracts, the blockchain itself and its blocks. We'll also talk about wallets, nodes, and bakers. Tezos is based on a system of accounts where every account has its own balance in Tez. But there are two types of accounts on Tezos. Implicit accounts are the accounts directly held by users. They have addresses that start with TZ, then a digit, typically TZ1, but also TZ2 or TZ3 are possible. Then we have originated accounts. Those are smart contracts that are a special kind of account that also holds data and code. Originated account addresses start with KT, usually KT1. We'll talk a lot about transactions. A transaction is a transfer of Tez from one account to another, or it can be a call to a smart contract. And it can be both. You can call a smart contract while transferring Tez to the account of that smart contract. And transactions are digitally signed by the caller to authenticate that they are the ones really wanting to do that transaction. But transactions are one of many types of operations that can be applied on the blockchain. We can have other types of operations such as creating accounts, deploying smart contracts, voting for an amendment to the protocol, etc. Smart contracts are a special type of account that, like every account, has a balance of Tez and an address, but it also has some data that we call the storage of this smart contract, and it has some executable code, so a piece of code in the Michelson language that is executed whenever someone calls this smart contract. So when you call a smart contract, you may send some Tez to the smart contract and pass parameters for the code, and the code will be executed, and it may change the data, the storage of the smart contract, or generate new transactions and new operations that will be executed after the end of the execution. Once you deploy a smart contract, its code is immutable. You cannot change it anymore, so that people who call the smart contract can know for sure what code will be executed. We can take a small example of a smart contract. Let's imagine that we have a contract that tracks the ownership of tickets for a concert. Each ticket will have an owner, and the owner of a ticket can transfer it to someone else, or change the ownership of a ticket. So in the storage, we will store all of the different tickets, and for each ticket we could have a row, a seat number, and the address of the current owner. And then in the code of the smart contract, you could have an entry point, a function that can update the owner of a given ticket. So you indicate the row, the seat, and what new owner you want. Then we will fetch the corresponding data from the storage, verify that the caller is actually the current owner of the ticket, and then replace this owner with a new owner. The Tezos blockchain stores its data in a chain of blocks of data. So that's why you call it a blockchain. And the blockchain is maintained by a decentralized network of nodes. Every 15 seconds, at the moment at least, a new block is added to the chain. And each block will contain a sequence of operations. And since we have a sequence of blocks, the blockchain, a blockchain is basically a very long sequence of operations split into blocks that are generated every 15 seconds. And the state of the blockchain is the result of the execution of all these operations. For example, let's say that after the block number 1427, Bob's account has a balance of 1,000 Tez. If in block 1428, Alice adds the transaction, Alice transfers 100 Tez to Bob, and this transaction is validated, then in the state of the Tezos blockchain, after block 1428, Bob's balance will be 1,100 Tez. In the block, we have two parts. We have the header that contains the block number or the level, basically how many blocks we have since the beginning of the blockchain. Then we have the hash of the previous block, a timestamp, and we also have the hash of all of the data in the block. And the data consists in the list of all the operations of the block in a certain order. The fact that we store the hash of the previous block means that we are creating a chain of blocks. Each block references the previous block in the chain. That's why we call it the blockchain. And you can check what a block looks like at this address. That uses a block explorer to analyze the block that has this number, this level. So here we can see this block. We can even move to the next block or the previous block. We can see the timestamp, etc. And most of all, we can see all the operations in that block, so different transactions, and in particular, smart contract calls. To interact with the blockchain, we will use a wallet. It's a piece of software or a hardware device that keeps your private keys safe. We saw earlier that transactions need to be signed. So to sign your transaction, you will need your private key that you will sign using your wallet. So whenever you want to transfer some Tez or call a smart contract, you will need to create a transaction and then sign it with your wallet. The wallet doesn't store your Tez or any other asset. It only stores the keys to control these assets. If you ever lose your private keys, you basically lose all access to your assets. So make sure you keep your private keys really safe. As an example, if we have this transaction transfer 100 Tez from Alice to Bob, this transaction has to be signed by Alice using her wallet for it to be valid. On Tezos, we have a number of wallets that you can use. For example, Temple, Kukai, Umami, and more. Under the hood, the Tezos network consists of hundreds of nodes run by the community. Each node is a computer that runs the Tezos protocol and communicates with other nodes. And together, these nodes form a peer-to-peer decentralized network that we call the Gossip Network. These nodes share the responsibility of maintaining the blockchain, and all the operations and blocks are propagated through this network of nodes. And when your wallet interacts with a blockchain, in practice, it communicates with one of the nodes in this network. All of the nodes execute every single transaction in every block and store the associated metadata, update the state. But only one entity can create the next block and decide which operations to include. But as we want to keep Tezos decentralized, the responsibility of creating the next block has to be shared. So the hard part of the design of a blockchain is to decide who gets to create this next block and do it in a fair way, and then making sure that this block is valid and legitimate. On Tezos, the entities that create new blocks are called bakers. Anyone, as long as they have at least 6,000 Tez at the moment, can volunteer to be a baker, and the baker for each block is randomly selected. But to make it fair, the chance to be selected is proportional to the amount they staked. That's what we call proof of stake. And proof of stake is eco-friendly because we just need to pick randomly proportionally to some value. This costs a lot less energy than proof of work, where you need to do a lot of computations to determine who the next miner will be, for example, as is done on Bitcoin. In proof of work, the chance of selection is actually proportional to how much energy and computational resources you waste. When a new block is proposed by a baker, it has to be validated. So we have to check that it includes the correct hashes of the previous block and its own, that all operations have a valid signature, that the execution of transactions don't fail due to some limits or errors, that the maximum size of a block is not exceeded, etc. A block is officially added to the chain once it receives enough attestations from other bakers. The baker of a block is rewarded. They receive 10 new Tez and sometimes a bonus. They also receive the fees of all the transactions in the block. Each transaction comes with some fees that the user can change, a kind of a tip that is transferred to the baker. And to maximize their gains, bakers select among all of the transactions the most profitable ones, so the ones that have the highest fees compared to their execution time. If you're not a baker, you can delegate your Tez to a baker and get a share of the rewards that the baker gets. And there's also some Tez that are used as rewards for the bakers that attest the validity of the blocks. If a baker propagates fake data, in particular if a baker creates 2 blocks instead of 1 when it's their turn, they lose some of their stake. We say that their stake is slashed. But if you delegated your Tez to a baker, you have no risk of being slashed. You cannot be punished. So this was a key overview of the different elements of Tezos. We talked about accounts that can be either user accounts or smart contract accounts. We described what transactions are transfer of Tez or calls to smart contracts. We described what a smart contract is, a special type of account with not only a balance, but also storage and some code that can be executed. We described the blockchain as a sequence of operations grouped into blocks. We talked about interacting with the blockchain through a wallet that keeps your private keys safe and is used to sign all the transactions you want to send to the blockchain. We described the blockchain itself as a peer-to-peer network of nodes that each execute the Tezos protocol and execute every single transaction in the blocks they receive. And finally, we talked about bakers that share the responsibility of creating new blocks. In this video, you will learn how to set up your own wallet, create your private keys, and then with that, you will then be able to get some Tez, create and sign transactions, call smart contracts, etc. So using a wallet means creating an account. And the first step to create an account is to generate a pair of keys. Most importantly, you will generate your private key. That is what you will use to digitally sign all of your transactions and prove your identity. A private key has a corresponding public key that you make available to everyone so that they can verify your signatures and verify your identity. So you sign your transactions with your private key, and other people or software can verify that the transactions are signed by you by matching the signature with your public key. So a wallet can generate a private key as a random sequence of bytes. It's extremely important that you never lose your private key, but as a sequence of bytes is hard to write down or remember, the wallet will first generate a seed phrase. It's a sequence of random English words that represent a random value, but that are easy for you to write down and keep safely, for example, on a piece of paper. Then the wallet uses this sequence as a seed for the random generator to produce the private key. It then stores this private key locally, encrypted using a password of your choice, and will then use it to sign your transactions. On Tezos, there are a number of different wallets available. Some of the main ones include Kukai, Umami, Temple. In this presentation, we will be using the Kukai wallet. It is available on kukai.app, but for our test, we'll be using the GhostNet test network. So we will be using ghostnet.kukai.app. So the Tez we'll manipulate with this wallet will be fake Tez in a sense, not Tez from the main network. So if you go to ghostnet.kukai.app, this is what you will see, as the wallet will be directly in your browser. You have two ways to create a wallet. You can collect with one of several social networks, for example, Google, Facebook, Reddit, etc. In which case it will use your OAuth credentials as a way to safeguard your keys. That's the easiest way to do it. If you simply connect, for example, click continue with Google, your wallet will be instantly created and available. We will use a way that is slightly longer. You click on create new wallet here, and then it will generate this seed phrase composed of a sequence of English words. And the idea here is that you should write down these words on a piece of paper to keep them safe. Avoid storing them in a file because this file could be accessed if anyone ever gets access to your computer. So it's safer to simply use a piece of paper and keep that piece of paper safe and make maybe copies of it that you keep safely. Because if you ever lose them, then you are at risk of completely losing access to your private key, therefore to your assets. Once you have written down these words, you can click next, and then it will check, did you indeed save these words? And it will tell you, okay, did you write down the second word, the one that was between traffic and sustain? And so on our piece of paper, we see, yes, indeed, we had the word arrow. Then it asks, what's the third word? The one that was between arrow and midnight. And so that was sustain, etc. Then we have pulse. And we're done. So it checked that we really did store our passphrase. Then it asks you to provide a password so that it can store an encrypted version of your key store file. So that's a password that you remember so that your wallet can locally save your private key and public key and etc. and then decrypt it anytime you provide your password. So whenever you will need to sign a transaction, it will use your password to decrypt the key and then sign the transaction with the key. So you input a password, confirm your password, and then click next. Then your wallet is ready, and you have here your public account address. So that starts with TZ1 and then something's based on the hash of your public key. You can also download the encrypted key store file so that you can import it into this wallet or another wallet. and it will be as safe as the password you pick to encrypt it. So here we copy our public account address, we download our file, and then we can now open our wallet. In the wallet, we can see the balance of our account, we can see our address here, and of course we have no activity because we just created the account. For real wallet on the mainnet, you could get Tez using one of several providers, and for example convert from dollars or euros and buy some Tez and then have them into your account through Coinbase or other places. For a test account on Ghostnet, there's an easier way to get some Tez. You go to this website that we call a faucet, and from this website you will be able to request some Tez. So let's give it a try. So this is a Tezos Ghostnet faucet. That is a website that can give free fake Tez on a Ghostnet account. You can paste your address here and then select how many Tez you would like. Let's say 1,000 Tez, and then you can request. You need to wait a bit. The more Tez you request, the longer the competition will be, because that challenge needs to be solved, some proof of work. And if you request 1,000 Tez, it can take a while, so we'll maybe request a bit less. Let's say we only need 200 Tez. And after a couple of minutes, all the proof of work challenges are solved, and then the 200 Tez are transferred to our account. Another way would have been to connect our wallet to automatically obtain the TZ1 address, but that would be the same result. Then we can check on the block explorer that indeed our TZ1 address has 200 Tez. We can also go back to our wallet, and we can see here that the 200 Tez are there after reloading the page, and we can see that we received them from this address. It may take a little bit of time before we see it, because we need a couple blocks to be validated, but eventually we see the 200 Tez there. From this, you can already sign some transactions. For example, if you want to try to send a few Tez back to the faucet, we can take this address, that's the address that sent us some Tez, and you can send some Tez, let's say 2 Tez, to the address we just copied. Then we can preview the transaction. We can see that there is a fee of 369 microtez, and we can use our password to decrypt our private key and sign the transaction and send it to the blockchain. So we confirm, and we can now see this transaction has been confirmed, and we now have almost 198 Tez. Again, you can see the same thing in the blockchain explorer, and we see this transaction where we send 2 Tez to this address. And that's it, your wallet is set up. In this module, I will give you an overview of the Tezos Layer 1 architecture, and we will do that by following the path of a transaction from the moment it is created to the moment it is integrated forever in the Tezos blockchain. Imagine you want to buy an NFT, a unique digital artwork on Tezos, the cutting-edge blockchain platform. You use a DApp, a decentralized application that lets you browse and bid for NFTs. When you find the one you love, you click on the Buy button. But what happens next? How does your transaction get processed and recorded on the blockchain? Let's take a look behind the scenes. Tezos is powered by a network of nodes, computers that run the Tezos software and communicate with each other through a peer-to-peer network. These nodes are operated by the Tezos community, a diverse and global group of enthusiasts, developers, and organizations. Your transaction will travel through this network, undergo various checks and validations, and eventually be included in a block by a baker, a special node that creates new blocks. Once your block is added to the Tezos blockchain, your transaction is final and irreversible. But how does this work exactly? The DApp you use, an NFT marketplace, has a user interface, a web page that you can access from your browser. It lets you interact with the blockchain and the smart contracts, the programs that run on blockchain and define the rules and logic of the NFT marketplace. When you click on the Buy button, the DApp creates a transaction, a message that tells the smart contract to transfer the NFT to you and the Tez, the native cryptocurrency of Tezos, to the seller. The transaction is sent to your wallet, a piece of software or a hardware device that connects to your browser and the blockchain. Your wallet securely stores your private keys, the secret codes that prove your identity and ownership of your Tez and NFTs. Your wallet is your gateway to the blockchain and the protector of your assets. Before asking you to confirm the transaction, the wallet needs to test it, check that it's valid, and figure out how much it will cost you. To do that, it sends the transaction to one of the nodes of the network and asks this node to simulate what would happen if you sent it for real. This node has a copy of the blockchain, the history of all the transactions that have ever happened on Tezos. It also has the context, the current state of the blockchain, which includes the balance of every account and the code and data of every smart contract. The node simulates your transaction by running the code of the corresponding smart contract. It checks that the code doesn't cause errors, for example, that the NFT you want to buy is indeed for sale at the price you indicate, and that you have enough Tez on your account to pay for it. It then computes the amount of resources running this code will consume. On one side, the amount of gas, an estimation of how much computing time your transaction requires. On the other side, the amount of storage, how much extra data will need to be stored. The node computes the cost for this gas and storage, adds some fees, then calculates how much you will need to spend to get a baker to add your transaction to a block. All this information, like a quote for your order, is sent back to the wallet. The wallet then displays that information for you to check and lets you decide how much extra fee you want to add. This extra fee is like a tip you pay to the baker to increase the chances that a baker will pick your transaction and add it to the blockchain. Once you check everything and agree to sign the transaction, the wallet uses your secret private key to digitally sign your transaction using cryptography. It then sends it to a node. From then on, all you can do is wait and see if your transaction gets added to the chain. The node sends a hash of the operation back to the wallet so that the wallet can keep track of it and ask for updates on its status. Before sharing your transaction with the whole network, the node needs to check that it's legitimate to protect against attacks that would saturate the network. It checks that the signature is valid, that the fees are not too low, and that you have enough Tez on your account to pay for everything. The node then stores your transaction in its mempool, a memory space that stores all the transactions that are waiting to get included in a block. The mempool also stores other types of operations that the node has received, such as block attestations or votes for amendments to the protocol. The node also sends your transaction to its neighbors, which in turn check that your transaction is legitimate, add it to their own mempools, and send it to their neighbors, propagating it through the whole network. Every node needs to do these checks itself to make sure some bad nodes don't propagate malicious transactions. While all this takes place, one lucky baker is getting ready to take charge of creating the next block. It is lucky because it has randomly been assigned the first spot in a list of bakers that are responsible for making sure a block is created. The next baker in that list will wait a little longer, ready to take over in case the first baker doesn't do its job in time. This time, our first baker is up and running and is ready to do its job and get rewarded for it. It is carefully listening to all the transactions that arrive in the mempool of its node. When it's time to create the block, it sorts these transactions to decide which ones will end up in this block. Before it selects transactions, it needs to pick the other types of operations, such as attestations of the previous blocks or votes. The baker is trying to make money by collecting all the fees, so it selects transactions that have the highest fees compared to their cost in gas and storage. But before adding them to the new block, it does its own checks to make sure they are valid, especially when they are executed in that specific order. It adds the good ones to a new block until it's full, or it runs out of transactions it wants to include. It then executes all the transactions by applying them to the context produced by the previous block. The storage of contracts and balances of accounts are updated in the context after each transaction, as the validity of the next transactions depend on them. Once the block is full, the baker computes its hash and sends the block with all its transactions to its node. The node sends it to its neighbors, and the block propagates through the network. The node adds this block to the end of its copy of the blockchain in an unconfirmed state for now. It also executes all the transactions and updates its own context. Other nodes do exactly the same as they receive the block. A subset of the bakers have been randomly selected to form a consensus committee for this block. When the node that one of these bakers is attached to receives the block, this baker starts checking all the operations it contains to make sure everything is valid. If it's all good, it creates a pre-attestation message along with the hash of the block and sends it to the node. Other bakers from the consensus committee do the same and create their own pre-attestations. These are propagated through the whole network. The same bakers then start receiving all these pre-attestations, check them and count them. Once enough are received, a quorum is reached, and the baker considers that this block is attested. It creates an attestation message and sends it to its node. Nodes propagate them and add them to their mempool, as these attestations will be added to the next block. While all this is happening, your wallet is still checking with its node what the status of your transaction is. When the block that contains your transaction reaches this node, the wallet will update the status of the transaction and show it to you. When another block arrives and is added at the end of the chain after the block that contains your transaction, this new block contains attestations for that previous one. Having another block added in front of it brings it closer to a final state. Once a second block arrives and is added to the chain, then your block is definitely final. You can now be 100% sure that your transaction is permanently part of the Tezos blockchain. The wallet shows that the transaction is final, tells the DApp about it, and the DApp confirms to you that you now own this amazing NFT. Congratulations, you have just experienced the power and beauty of Tezos. In this module, we'll talk about some of the reasons why it's a good idea to develop your dApps on Tezos. There are many benefits that come with developing on Tezos. One of the key benefits of Tezos is the on-chain automated governance. Anyone who holds 6,000 Tez or more can vote for protocol amendments proposal. There's already been 14 successful upgrades of the protocol since the beginning of Tezos. This on-chain government makes Tezos very innovative, with frequent new capabilities that are added to the network. And the system reduces the need for hard work. There's always a single official branch of the network. Another benefit of Tezos is that it's energy efficient, thanks to its use of proof of stake. It was one of the first blockchains that uses proof of stake as part of its consensus mechanism. Tezos is focused on scaling, with a lot of work going on right now on scaling with smart rollups, data availability layer, and more, and that is done without compromising decentralization or security. A lot of work has been done to make sure that the security of Tezos is of top quality, and the Tezos ecosystem itself is very decentralized and benefits from a friendly and diverse community that focuses on long-term innovation. And it has a great ecosystem from blockchain enthusiasts, artists, but also multinational companies. It also benefits from great tooling and funding opportunities to help developers build their projects. In 2017, a large amount was raised to fund the development of the Tezos network, and this amount is managed by the Tezos Foundation. The mission of the Tezos Foundation is to grow the Tezos ecosystem through a system of grants in areas such as developer experience, education and training, security and privacy, and end users application. For more information about how to apply for grants and what the foundation does, visit tezos.foundation. In this module, you will learn how to write your first smart contract on Tezos using SmartPy. It will be a very basic smart contract, but a useful one. What is a smart contract? It's a type of account that, like any account on Tezos, has an address and has a balance in Tez. But on top of that, it will have some executable code, the program of the smart contract that says what it can do, and it will have its own storage, some data that the smart contract can store. To interact with the smart contract, we will use two new types of transactions. The first one consists in deploying the smart contract. It means putting it out on the blockchain. Once it is deployed, its code cannot be changed. We say that it is immutable. The second type of transaction is to call a smart contract. You call it like a function with some parameters that you pass, and you may send Tez to the contract, as you call it. Now let's look at our first smart contract. This is the smallest useful smart contract we can think of. All it does is to store a value on the blockchain forever, or at least as long as the blockchain exists. So here we will store this value in the blockchain forever when we deploy the smart contract. And that's all it does. We can see that to create a smart contract, we have to create a class. We give it a name, and we say that it inherits from sp.contract. Here, sp stands for SmartPy, and that's the name we gave to the SmartPy library when we import it. We need to create this class inside a module that we call main, like this. And inside the class, we create a constructor that is named init with 2 underscores before and after. And within this constructor, we can initialize the storage with an attribute that we decide to call value. And the attributes are stored in self.data. and the name of the attribute. So here, the contract doesn't execute anything on blockchain. We simply define its initial value of the storage that will be stored forever once it's deployed. It won't be doing anything else. If we want to test this smart contract in the SmartPy IDE, we will need to add tests. And you always want to add tests to any contract you write. And in SmartPy, you can add them in the same file as the contract itself. Here, we create a test by adding this test function with the add test decorator. And within this test, we create a scenario that basically will contain the sequence of tests, calls to smart contract, etc. We give it a name by calling the function test scenario, and we declare what module it uses. So here it will be using the main module. Then we create an instance of our store value contract like this. We store it in a variable, and then we add it to the scenario. When we run the test, it will simulate deploying the smart contract and show us the output. One thing you should keep in mind, especially if you're not a Python developer, is that every time in your code that you create a block, the content of this block should be indented compared to the parent. So for example, here we have a class, and inside the class we create a block that's the content of the class. All the content of this block should be indented. Here it's indented by 4 spaces. It could be more, it could be tabulations, but it has to be the same number for the whole block. And then here we can see that inside the constructor, we create another block with the content of the constructor, and again it is indented by 4 spaces. As soon as we reduce the number of indentation, so for example here when we have this decorator, it indicates that we close the previous opened block. So here we close this block, we also close this one and close this one. Let's test our contract inside the SmartPy IDE. In this online IDE, you can write your contract in an editor, and then on the side panel, you will be able to test it and see the output. So here I put our original smart contract. We see that if I just run it, nothing happens because I needed a test for anything to happen. So I'll add our test. Now I can run it, and I can see that on the side panel, I have this origination that is simulated. And I can see, for example, the address of my contract, and I can see the storage value. So here we can see that I originated a contract that has this value and will store it in the blockchain. We can check a few things. For example, we can see what the code of the smart contract in Michelson looks like. It doesn't really do anything. We can also check the content of the storage or the size of the storage, etc. We could even deploy the contract directly from the SmartPy IDE. Now it's your turn. Write your first smart contract. You can name it store value. It should store the value 42. And of course, you need to add a test scenario and run it to simulate the deployment of this contract. Once you're done, validate it on OpenTezos. Let's pause the video and give it a try before we continue. So far, our smart contract wasn't really doing anything except storing a value. If we want the smart contract to do something, we need to add entry points. They are like methods or functions that we can add to our smart contract. When you call an entry point, they cannot do much. They can only read the parameters that you pass to the function, the current value of the storage of the smart contract, a few special values like the balance of the contract or the amount that the caller sent to the contract or the address of that caller, and a few more. It will also have access to a global table of constants that all smart contracts have access to. It also cannot do much. It can only have two effects. The first one is to modify the content of its own storage. And the second one is to generate new transactions, such as transfer of Tez or calls to other smart contracts, that will be executed at the end of the execution of the entry point itself. And that's it. Now let's see how we can add an entry point to a smart contract. So we here created a contract called flipCoin that will store the current side of a coin, and then we'll have a flip entry point that can be used to switch this side from 0 to 1 and then from 1 to 0, etc. We can see here how we created an entry point. We created a function with a sp.entryPoint decorator, and then inside that function, well, we change the value of the side attribute of our storage to 1 minus this value. So if you start with 0, you get 1 minus 0 equals 1. And then if you call it again, it goes back to 1 minus 1 equals 0, etc. Every time you call it, it will flip the value of the coin. To add tests to our entry point, we can simply add calls to this entry point in our test function. So after we added the contract to the scenario, we can call contract.flip, so that's the name of our entry point, as many times as we like. Let's give it a try in the SmartPy IDE. So here we have our contract and our test. Let's run it. We can see again the origination with the initial value of side set to 0. And then we have here our first call to our flip entry point. And if we click on show details, we can see that the new value of the storage is now 1. Then we have the second call, and here we can see that the value is 0, and then 1 again, etc. Now, the issue with this is that if we make a change to this contract, we don't want to have to check again and click on show details, etc. to see that all the values of the storage are still correct. We would like to automate this and have SmartPy tell us immediately if what we get is what we expected. We can do that by automating those tests. So to check the outcome automatically, all we have to do is add this to our scenario after or before a call to an entry point. Scenario.verify, and then some conditions. So here, for example, we can check that the value of this field from the storage of our contract is equal to a specific value. Let's give it a try. Here, after flip, we can write scenario.verify contract.data.side equals, so after the first flip, it should be equal to 1. Then I can add it here. It should be equals to 0 again, and then to 1 again. Let's give it a try. All good. We get the same output. If we had here written 1, then SmartPy would tell us, hey, this comparison is incorrect, there's an error. So of course here that's just because the test is invalid, but we put 0 and we run it, and then we can make some changes and make sure that we never break these conditions. Now it's your turn. Write your own smart contract, call it count the calls, and the goal of the smart contract is to count how many times we will call it. So we will have an attribute nb calls in the storage that you initialize with 0. And then every time we call the contract, it should increment by 1. So to do so, you will create an entry point make call and then increment by 1 the value of nb calls. And then of course, add a test scenario and run it. Let's give it a try. And when you're done, you can validate it on OpenTezos. So please pause the video and give it a try. Let's take a look at the solution. We created a class countTheCalls that inherits from sp.contract. We have a constructor that initializes the value nbCalls to 0. Then we create an entry point, makeCall, and every time we call it, nbCalls will be incremented by 1. You could also write nbCall equals nbCalls plus 1, but this is a shorthand operator that makes it easier to increment. In our test, we instantiate the countTheCalls contract in the contract variable. We can verify immediately that the value is 0. We can use h2 to display a title that says what we're going to do next. We call the entry point make call, verify that the value is 1, then call it again, verify that the value is 2. Let's check if it works. And it's all good. We start with 0, then we make the first call. It's now 1, second call is now 2. Everything is good. And again, if I had changed it to 3, it would let me know that this condition is invalid. Testing a smart contract is really important. Smart contracts manipulate tokens and other digital assets that can have very large economic values. We can talk about millions of dollars in some cases, or tens of millions of dollars in a single smart contract. And the environment where you execute the code is what we call adversarial. That means other people can attack it. Anyone in the world could look at your contract, try to find a bug, and if there's a bug, someone will try to attack it and try to either steal some funds in it or make them stuck in the contract. And people have very strong incentive to exploit bugs that you may leave in the contract. And since once you deploy the contract, it cannot be changed anymore, it's immutable, then bugs cannot be fixed as soon as you see them. So that makes it even more dangerous. There are unfortunately many examples of cases where people lost millions of dollars collectively as a consequence of small bugs in smart contracts. So it's very important when you write a smart contract to spend a lot of time testing it, proofreading it, etc. In general, it's actually relatively simple to write a smart contract. Smart contracts are small projects compared to other types of software projects, but it's actually quite hard to make sure there are no bugs in those smart contracts. So testing them and avoiding bugs is the hardest part. In later modules, we will study different flaws and best practice on how to avoid typical kinds of bugs. In this module, you will learn how to add entry points to your smart contracts so that you can create contracts that do something. So far, our smart contract wasn't really doing anything except storing a value. If we want the smart contract to do something, we need to add entry points. They are like methods or functions that we can add to our smart contract. When you call an entry point, they cannot do much. They can only read the parameters that you pass to the function, the current value of the storage of the smart contract, a few special values like the balance of the contract or the amount that the caller sent to the contract or the address of that caller, and a few more. It will also have access to a global table of constants that all smart contracts have access to. It also cannot do much. It can only have two effects. The first one is to modify the content of its own storage. And the second one is to generate new transactions, such as transfer of Tez or calls to other smart contracts, that will be executed at the end of the execution of the entry point itself. And that's it. Now let's see how we can add an entry point to a smart contract. So we here created a contract called flipCoin that will store the current side of a coin, and then we'll have a flip entry point that can be used to switch this side from 0 to 1 and then from 1 to 0, etc. We can see here how we created an entry point. We created a function with a sp.entryPoint decorator, and then inside that function, well, we change the value of the side attribute of our storage to 1 minus this value. So if you start with 0, you get 1 minus 0 equals 1. And then if you call it again, it goes back to 1 minus 1 equals 0, etc. Every time you call it, it will flip the value of the coin. To add tests to our entry point, we can simply add calls to this entry point in our test function. So after we added the contract to the scenario, we can call contract.flip, so that's the name of our entry point, as many times as we like. Let's give it a try in the SmartPy IDE. So here we have our contract and our test. Let's run it. We can see again the origination with the initial value of side set to 0. And then we have here our first call to our flip entry point. And if we click on show details, we can see that the new value of the storage is now 1. Then we have the second call, and here we can see that the value is 0. And then 1 again, etc. Now, the issue with this is that if we make a change to this contract, we don't want to have to check again and click on show details, etc. to see that all the values of the storage are still correct. We would like to automate this and have SmartPy tell us immediately if what we get is what we expected. We can do that by automating those tests. So to check the outcome automatically, all we have to do is add this to our scenario after or before a call to an entry point. Scenario.verify, and then some conditions. So here, for example, we can check that the value of this field from the storage of our contract is equal to a specific value. Let's give it a try. Here, after flip, we can write scenario.verify contract.data.side equals, so after the first flip, it should be equal to 1. Then I can add it here. It should be equals to 0 again, and then to 1 again. Let's give it a try. All good. We get the same output. If we had here written 1, then SmartPy would tell us, hey, this comparison is incorrect, there's an error. So of course here, that's just because the test is invalid, but we put 0, and we run it, and then we can make some changes and make sure that we never break these conditions. Now it's your turn. Write your own smart contract, call it count the calls, and the goal of this smart contract is to count how many times we will call it. So we will have an attribute nb calls in the storage that you initialize with 0, and then every time we call the contract, it should increment by 1. So to do so, you will create an entry point make call, and then increment by 1 the value of nb calls, and then of course add a test scenario and run it. Let's give it a try, and when you're done, you can validate it on OpenTezos. So please pause the video and give it a try. Let's take a look at the solution. We created a class countTheCalls that inherits from sp.contract. We have a constructor that initializes the value nbCalls to 0. Then we create an entry point, makeCall, and every time we call it, nbCalls will be incremented by 1. You could also write nbCall equals nbCalls plus 1, but this is a shorthand operator that makes it easier to increment. In our test, we instantiate the countTheCalls contract in the contract variable. We can verify immediately that the value is 0. We can use h2 to display a title that says what we're going to do next. We call the entry point makeCall, verify that the value is 1, then call it again, verify that the value is 2. Let's check if it works. And it's all good. We start with 0, then we make the first call. It's now 1. Second call is now 2. Everything is good. And again, if I had changed it to 3, it would let me know that this condition is invalid. Testing a smart contract is really important. Smart contracts manipulate tokens and other digital assets that can have very large economic values. We can talk about millions of dollars in some cases, or tens of millions of dollars in a single smart contract. And the environment where you execute the code is what we call adversarial. That means other people can attack it. Anyone in the world could look at your contract, try to find a bug, and if there's a bug, someone will try to attack it and try to either steal some funds in it or make them stuck in the contract. And people have very strong incentive to exploit bugs that you may leave in the contract. And since once you deploy the contract, it cannot be changed anymore, it's immutable, then bugs cannot be fixed as soon as you see them. So that makes it even more dangerous. There are unfortunately many examples of cases where people lost millions of dollars collectively as a consequence of small bugs in smart contracts. So it's very important when you write a smart contract to spend a lot of time testing it, proofreading it, etc. In general, it's actually relatively simple to write a smart contract. Smart contracts are small projects compared to other types of software projects, but it's actually quite hard to make sure there are no bugs in those smart contracts. So testing them and avoiding bugs is the hardest part. In later modules, we will study different flaws and best practice on how to avoid typical kinds of bugs. In this module, you will learn how to deploy your contracts so that they are available on the chain for everyone to use. We will deploy our contracts on a test network so that you don't need to spend any tests to do the deployment, but the same approach will work on the main network. So the test network is called GhostNet, and it is very similar to the main network. So to originate, or we can say deploy your contract, you need to do 2 steps. The first step is to produce the Michelson contract. So compile your SmartPy contract into Michelson. Michelson is the low-level language of every Tezos smart contract. And SmartPy is a high-level language that makes contract easier to write, but when you run SmartPy, you compile the SmartPy code into Michelson. So you generate the Michelson contract. So that's the first step before you can deploy your contract. And the second step will be to create and sign a transaction to deploy that contract. The SmartPy IDE will help you prepare the transaction. And we will be able to use our wallet to sign this transaction, and then we'll set it to GhostNet. This operation is what we call the origination of the contract. So we start from the IDE with our contract, and to deploy it, we first need to run the code. And on the right side, in the top part, we have the origination. And here we can view the Michelson version of the contract. And then you can see at the bottom right, deploy contract button. So let's click on that. And here it will prepare everything you need to originate your contract. So here we'll select what network we use. We can use GhostNet or mainnet. Here you can provide the address of the node that you will be using to deploy the contract. So for example, by default, it's the SmartPy node, but I could use a node from another infrastructure. Then I can select my account, and here have a choice of a number of wallets. If I wanted to use my Kukai wallet, I could select Beacon and then Kukai. But SmartPy also offers its own system to manage accounts. So here you can create accounts, and here I have created a couple. So let's just use this one. So we can see that this account has almost 100 Tez in it, and it's revealed already on GhostNet. So I simply validate that account. Here I can provide any origination parameters. I can say how many Tez I put in the contract as I deploy it, and I can also set a delegate to indicate if I have Tez in the contract, which baker should they be delegated to. Then I have the estimates of the deployment cost that I obtain from RPC. So that's contacting the node, doing our RPC, remote procedure call, to the node. I can check, and it tells me, okay, this is how much the node expects that it will cost to deploy it. So it's very cheap to deploy this tiny contract. This is how much gas I will spend, how much storage I will spend, etc. And then I can simply click deploy contract. It shows me all the information about the contract I'm going to deploy. So it shows me the hash of the transaction, the parameter, so what account I use to originate it, what's the counter, what's the fee I'm going to be paying, the gas limit, the storage limit, etc. and the balance, initial balance for my contract. In the full version, I also have the full code of the contract in Michelson, plus the initial value of the storage. And then I can see the byte encoded version of that. So once I'm sure that this is the transaction I want to run, I can accept it, and then it contacts the node, originates the account, and I have the address here. If I copy this address and go to, for example, Better Call Dev, I can search that contract, and I can see here that Better Call Dev sees my contract on GhostNet, and we can see that the operation was done just now. Here it says a few seconds ago. So my contract is deployed. I can check the contract on GhostNet, see the current value of the storage, see the Michelson code, and I can even interact with it directly from GhostNet. So now that we have deployed it, our contract and the associated data are now public. So as we could see through Better Call Dev, anyone can read the code and the storage without asking for permission. The contract is immutable, it can never be changed, and it's eternal. So as long as a few nodes are running the Tezos blockchain, my contract will be available for anyone to use. This is because Tezos is run by hundreds of independent nodes that each maintain a copy of my contract and its data. And changes to the contract may only be made if a supermajority of participants will agree to make changes, which is something that doesn't actually happen. People don't really change contracts when they have been deployed. We will see later that we can integrate features in a contract to enable upgradability features of our contract. And so due to this decentralized structure of the blockchain, no single entity can cause my contract to fail and the network as a whole to fail. So my contract is pretty much available for anyone to use forever, and we'll keep counting how many times people call it. I could try directly from Better Call Dev, execute and directly using my wallet. Here it's sending to my KuCoin wallet. So here it says I'm waiting for confirmation. My KuCoin wallet is here. So I just need to accept the transaction. Then I go back. KuCoin wallet successfully submitted the operation. Transaction has been successful. And now if I see the storage, I can see, well, this contract has been called once. I can try it again, execute, confirm, successfully executed. I see the storage not updated yet. And that's it. Now it's 2, so my contract is available forever, and you could call it too using this address. In this module, you will learn that every value, variable, or parameter in SmartPy has a type. But most of the time, you won't need to tell SmartPy what the type of your variables are, thanks to a very powerful tool called Type Inference. But first, let's talk about parameters. We have already presented entry points. Since an entry point is a kind of method of your smart contract, they can take parameters. If you want to write an entry point with one parameter, here is how you do it. So when you define your entry point, next to self, you add a comma and the name of your parameter. And then within the code of your entry point, you can simply use the name of your parameter wherever you want to use this value. In your test, when you want to call an entry point with a parameter, if it's a single parameter, all you have to do is put the value of this parameter between the parentheses when you call the entry point of your contract. Let's take a look at an example. Here we modified our store value contract by adding 2 entry points. One entry point with a parameter called added value that we can call to add this value passed as a parameter to the stored value. And then we can compare it to another entry point that doesn't have any parameter, reset, that simply resets the value to 0. And then in our test scenario, here we call contract.add with a parameter 5, saying that we want to add 5 to the initial value 42. And then after the call, we can verify that the new value of stored value is 47. And then to really make sure that the entry point works well, if we call it several times, we have a second test where we this time add 2, and then we verify that the result is 49. Let's give it a try. So we can see that it was successful. We start with the origination with the value 42. Then we call our entry point. We see that the argument, so the value passed for the parameter added value, was 5. And then if you look at the detail, we can see that the new stored value is changed to 47. And then we have another call with the argument 2, and the new stored value is 49. In SmartPy, everything has a type, whether it's a value or a variable that always has the same type and can only contain values of the same type, and the same with the parameter. All of them have to have a type. So far we have manipulated whole numbers, but just for whole numbers, we actually have 2 different types available. The first one is int for integer, and a value of type int can hold a whole number that can be either positive or negative. But there is a second type for whole numbers called nat for natural numbers that can also hold a whole number, but this time only non-negative values. So values starting at 0, 1, 2, 3, etc., but not negative values. When we want to use a whole numbers, if we want to specify which one of those 2 we want, we can either write sp.int of 5 for the integer 5, or sp.nat of 5 for the natural 5. So those are 2 values of different types. Whenever we want to express the type itself in SmartPy, we will simply use sp.int and sp.nat. In short, when I talk about it, I will just say int and nat. In SmartPy, you cannot directly combine nat and int. So for example, if you have a variable of type int, you cannot assign a nat to it and vice versa. So if we take this example of a contract that has a value where we assign a type int and then has an increment variable to which we assigned 3, then we cannot have an entry point that adds those two together because they are of different types. But we can convert a nat into an int, for example, using sp.toInt of the value. So if this value is a nat, we can convert it to an integer with this function. Most of the time, if you feel like you need to convert a value from one type to another, it may be because you chose the wrong type to begin with. So most of the time, if you feel the need to convert, try to think first if there's a way you can change the initial type of the variable rather than converting it to another type. If every variable has a type, you may wonder why we never had to provide the type so far. And the idea is that SmartPy uses a very powerful tool called type inference to automatically determine the types of many variables and parameters. If you don't specify it, it can deduce it from other clues. And there's a number of information that it can use for that. The main one is the initial value you assign to the storage. So for example, if you have a variable in your storage and you say, I assign it to sp.int of 5, then SmartPy can deduce that the variable is of type int. If you combine operation in an operation, for example, if you add two values and one of them is of type nat, then that means the other one and the result both have to be of type nat. And sometimes you can provide explicit information about the type of a value. So for example, if we have a parameter factor and we want to say we know and we want this parameter to be of type int, then we can use sp.cast of factor and the type that we want to assign to this parameter. Note that this is not converting the type of this variable, whatever value it contains, to an int. It is simply saying that the type of this parameter or variable is an int and should always be an int. It uses those information that it finds here and there in your contract, and it propagates it to the rest of the contract whenever it can. One thing that you should know is that sometimes SmartPy cannot determine if a value is of type int or of type nat. So it temporarily propagates a value that has an intermediate type int or nat, and then only at the end it will determine which one of the two it is. And sometimes you may see error messages that tell you that it's expecting int or nat. That's because so far it doesn't know yet if a variable containing a number will be of type int or of type nat. So it is propagating this intermediate type, but eventually it will have to pick between int and nat. If we look at our smart contract as an example, here we saw that we didn't provide any type information. And that means when I look at the type of the storage, here we can see that the stored value is of type int or nat because it doesn't know if this 42 is an int or nat. Same thing with this parameter or this value. It could be both. But eventually, since it has to pick, when we look at the Michelson code, we see that it picked an int. So if there's a choice between int and nat at the end, it will pick an int. But we could force it to be a nat by here initializing the value with sp.nat of 42. So type inference will be used to deduce that the type of this variable is nat. Here, since we add the value of this parameter to the stored value, this means this parameter is also a nat. And here, since we assign another value to stored value, then it knows that 0 should be actually sp.nat of 0. So here, if we run it, we can see that stored value is now seen as a nat. And then in the Michelson contract, we see that we have nat everywhere as well. The type inference could be used starting from any point. So for example, we could use the reset entry point to say, hey, this 0 is a nat. And the result would be the same because it will deduce from this that stored value is a nut, therefore 42 is a nut, therefore the parameter added value is a nut. So from this single information that this value is a nut, it will propagate it to stored value, then to added value, then to other places. Like for example, the value 42, it knows that it is a nut. This is what we call type inference, using a set of clues to determine for sure what the type of each value is. Let's look at a different version of this contract that I prepared for an exercise. Here we have this add entry point, and we say that we don't want to allow negative numbers to be added to the value. And the reason is that we also have a sub entry point that subtracts a given value from the stored value. And so since we have this entry point, let's say we don't want add to be able to be used to add negative value, which would be the same as subtracting. So it's just a rule that we set for the purpose of this exercise. So for this reason, as a way to say I don't want negative value, I say that this parameter should be of type nut. So I use sp.cast to say added value is of type nut. Let's see what happens when I run. So here we have a type issue. On line 18, it's telling us that it's trying to combine an int and a nut. And as we said, we cannot combine those two types in the same operation for most operations. So here we have an issue because it deduced that stored value is a nut from adding a nut to it here, but it also deduces that stored value is an integer because, well, we subtracted a value to it, therefore it could become negative, therefore it can hold negative values and should be of type int. So your goal for this exercise is to try to find a way to fix this smart contract and make it compile while keeping this constraint of having added value be of type nut. You will find the content of this smart contract either in the Git repository associated with this course or in the type inference section on OpenTezos. Please pause the video and give it a try. Okay, so let's see how we can fix this. Here the issue is that when we add a nut to this value, it will deduce that this value should be a nut. But we want this value to be an int because we want to be able to subtract values to it and we want it to be potentially negative. So this has to be an int, but this has to be a nut, but we cannot combine the two together. So what we do is we convert this value to an int by writing sp.toInt of this value. Let's give it a try. So I still have an error, but a different one, line 30. And again, it says entry point expect parameter of type sp.unknown. But it got int, and it tells us that there is an int/nut mismatch. So the error message is not very clear on where the problem is, but let's look at what we have on line 30, and we can see the content of this line here. Here we see that in test we called add, but we passed an int as a parameter. So of course, if we pass an int as a parameter, and then it tells us, no, this parameter should be of type nut, then there's a discrepancy. We cannot pass an int when it expects a nut. So all we have to do here is change this to nut. Let's give it a try. And it works. So now the type inference doesn't have any conflict. It doesn't end up with a place where from one set of deductions it deduces that a value should be of a type int, and then from another set of deductions it deduces that it should be a nut. Everything is coherent, so it all works. One particularity of Tezos is that it cannot have bugs related to overflows. So if you're not familiar with overflows, the idea is that in most languages, values of different types have a minimum and a maximum value they can hold. So for example, in C++, if you use the type short, you can only store values between those two numbers included. If you use an operation that adds 1, for example, to the maximum value that they can have, it will loop back to the minimum negative value that you can have. So from this number, if you add 1, you go all the way back to the negative value, 32,768. And this can cause very dangerous bugs, right? If you add a number to a value, you expect it to increase. You don't expect it to become a very negative value. On Tezos, we cannot have this kind of bugs, contrary to many blockchains. And the reason is that on Tezos, most types don't have any limit. There is no upper limit to the value that an int can hold, and there is no negative limit to the value that an int can hold. Basically, that means the value of an int can be between -infinity and +infinity. There's only one type, the Tez, that has a limit. But in this case, if there's an overflow, if you try to add 1 to the maximum value for the type Tez, you will trigger an error instead of getting an invalid result. So you avoid very dangerous situations. So you may wonder, is there really no limit to values? Does it make any sense to talk about int being able to hold infinite values? Well, of course not. In practice, the types of value you can hold in an int are limited by the storage needed to hold these values. So you may wonder, how much storage is used by a value? And we can say that it's roughly proportional to the number of digits. So if you have a number with 100 digits, it will use about 50 bytes of memory. So it's about 1 byte for every 2 digits, approximately. So the next question will be to wonder, if the limit is the amount of storage, and there is no limit to how much you can put in a value, how do we prevent abuse? How do we prevent people from storing numbers with billions of digits, for example? And the idea is that users have to pay whenever they increase the size of the storage of a smart contract. So when you deploy a smart contract or when you call a smart contract, in some cases, the result of that is that you will change the value in the storage of the contract, and therefore you may increase the amount of storage needed to store these values. So whenever that happens, you have to pay for that storage. So now we may wonder, who gets paid? If we pay, who do we pay to? And the answer is no one. We actually burn those Tez, and that's because there's really no easy way to determine who should deserve that amount. And in a way, by burning the Tez, we pay everyone in the community, because if you burn Tez, you destroy them, you make them unavailable, you reduce the total amount of Tez available for everyone. So by doing that, indirectly, you increase the value of the Tez. So it's basically a value that is shared with the community. When do you pay? Well, when you call a smart contract, you're doing through a transaction that you will need to sign with your wallet. And your wallet will simulate the transaction, compute how much extra storage will be needed due to your transaction calling smart contracts and increasing their storage. And so compute how many bytes you may increase the storage, and then lets you know basically how many Tez you may burn. And you can specify the maximum amount of Tez that you are willing to burn for this transaction to happen. And when the transaction happens, the exact amount will be burned. Okay, now let's work on an exercise. So you will take the smart contract store value that we have used so far and add a multiply entry point to the contract. This multiply entry point should take a parameter called factor that should have type int. And the multiply entry point should multiply the value of the storage by this parameter. And of course, we ask for you to add the corresponding test to your scenario. So please pause the video and give it a try. And you can validate your solution on OpenTezos. Let's take a look at the solution. Here we added this entry point multiply that takes a factor parameter. And we multiply stored value by this factor. And then of course we call it in our scenario to verify. Let's give it a try, and we can see here that when we call multiply by 10, we started with a storage that was 5, multiply by 10, and we can see that the result is indeed 50. In this module, you will learn to manipulate text on Tezos using the type string. Tezos supports a string type that you can use to manipulate text, but it is limited to non-extended characters. So what you can use is the set of characters from the non-extended ASCII standard, composed of 128 different possible characters. When you want to express a string literal, You write it between double quotes, like this example. So double quote your text and then double quote again. And just like for int and nat, there is no limit to how long this text can be. You can write a string as long as you like. The only limitation is the storage and how much it costs to store this string on the blockchain. The most common operation we can do on strings is to concatenate different strings. So you can concatenate different elements like this using the plus operator. So here we show an example where we create a URL by concatenating this bit with this parameter, with this text, with this parameter. Let's directly try it on an exercise. So you will create a contract that will illustrate the concept of eternity and immutability of the blockchain. So for that, you create a smart contract called endless wall. And the idea is that it will store a string that we will call wall text. And anyone will be able to call an entry point called write message that will take a message as a parameter and will add it to this text. So basically, it's a very long string of text that anyone will be able to add to. So people like to leave their name, maybe carve their name on a rock for eternity or on a tree for a long time, etc. There's often a need for people to leave a trace. So this is a contract that will let people leave a trace forever without destroying the environment in any way. So the write message entry point should add a comma to the text, to wall text, then a space and the message, then the string forever. So for example, if you call write message of Tezos, it will add a comma, a space, and then Tezos forever to wall text. And so if we start with hello, and then we call write message, then we end up with hello Tezos forever. And of course, once you're done writing the contract, you should create the corresponding test scenario. And you can validate your contract on OpenTezos. Let's pause the video and give it a try. Okay, let's look at this solution. So we created this endless wall contract. We initialize the storage with a wall text variable that takes the parameter, initial text, that sets the initial value. We will initialize this value with hello in our test. Then we have this entry point, write message. It takes the message as a parameter, and it adds to wall text a comma and a space, then the message, then forever, and we use the plus operator to concatenate them, and then plus equal to add them to wall text. In our test, again, we initialize the contract with the initial text hello. Then we create our scenario, we add the contract to the scenario, we call write message the first time with Anna and Jack. We then verify that everything went well and the wall text contains hello, comma, Anna and Jack forever. Then we call it again with Tezos as the message, and we verify that wall text contains hello, Anna and Jack forever, then Tezos forever. Let's give it a try. So it works. We see that at the origination, the content is hello. Then after the first call with the argument Anna and Jack, then the result is hello, Anna and Jack forever. And then with another call with the argument Tezos, the new storage is hello, Anna and Jack forever, comma, Tezos forever. All good. In this very short module, we will talk a little bit about the history of smart contracts. The concept itself of smart contract was first proposed in 1996 by Nick Szabo. In the first blockchains, you only have a few types of transactions, but some of them could run very basic scripts. But those scripts are very limited on purpose. You couldn't do any loops, for example, for security reasons. Ethereum was the first blockchain with support for smart contracts, and it was launched in 2015. Tezos was launched in 2018 as a new smart contract blockchain that was built from scratch. It focuses on the security of smart contracts along with on-chain governance. In a way, the whole point of a smart contract is to say, if you do that, this will happen, no matter what. No one can stop it. In this module, you will learn how to write smart contracts that do that through performing verifications. The code of an entry point often have the same structure and should have the same structure First, it checks that the call is allowed, that you should be able to call at this time, with this address, with these parameters, etc. Then, after checking that everything is good, do stuff. Computations, changing the content of the storage, sending tests to people, do other kinds of transactions, and maybe check other things. To do the first part, checking that things should be allowed, we use the assert command, and we give it the condition that should be checked. So basically write assert, then the condition. So for example, we could write assert, this parameter should be lower than some maximum value. We can also provide an error message so that when the contract fails, we know why it failed. So we just write assert, the condition, comma, and the string containing the error message. If the assert fails, so if the condition is not met, everything that was done since the beginning of the transaction is cancelled. It's just as if nothing had happened. So if we take this example, we assign the value 42 to some attribute of the storage, and then we check, assert that this value is lower than 10. So of course, this assert will fail. So that means if you put this in a smart contract, the whole smart contract will fail and the value will never be set to 42. And this is no matter what the cause of the failure is. So if you cause a failure of the contract because of a false condition of an asset, or if you, for example, try to send more tests from the contract than the contract has in its balance, or if you call another contract and this other contract ends up failing for similar reasons, whatever the reason why the contract fails, or one of the transactions it's tried to do fails, then everything this contract was doing is cancelled and it's as if nothing at all had happened. So basically it's all or nothing. Either everything works or nothing happens. When you do verifications, you can use the regular Python comparison operators. So for example, if you have a variable c that contains an integer 4, we can check if it's greater than 3, lower than 3, greater or equal than 4, equal to 4, or different from 5. Let's look at this example where we take our store value contract and we have simply an add entry point that takes a parameter and adds it to the stored value. We don't specify any constraint. It could be a positive, negative value, anything you like. We can try it and we see that we start with 0. If we add 1, we end up with 1, and then add 9, we end up with 10, as we verify here. Now let's say we want to make sure whoever calls it doesn't add more than 10, for example. So we could have an assertion, assert, added value is lower than 10, let's say. And otherwise we display message to match. Okay, now if we run it again, it just works because we only try to add 1, 9, but now let's try to add 10. Here we see that it fails and it displays the unexpected error too much. We could also add an assertion that is positive, for example. And again, we can add -5. And then check and we will have the error needs to be positive. We can also use SmartPy's Boolean conditions. So we introduce a type Boolean where value can be true or false, and then we can create an expression A and B that is true if and only if both A and B are true. And then we can have the OR operator that is true if either A or B or both are true. And we can even use the exclusive OR using the binary Python operator. That means exclusive OR. That will be true if A is true or B is true, but not both. So exactly one of them has to be true for the whole expression to be true, otherwise it's false. And of course we have the not operator that takes the opposite of the value of A. So in our example, instead of having 2 values, we could just write here, let's put this here, added value is greater than 0, and added value below 10, and let's say put a message not between 0 and let's say 9 included. So now if we write it, we still have the error with the value -5 that is not between 0 and 9. And if we comment this line and try with 10, then we have the same value for add 10, then this message appears. So the issue here is that we do want to check that this fails when we add 10, but if we do that, then it just stops our test, right? If I want to check that both -5 and 10 return an error, well, when I run it, it stops at -5, so I don't know for sure that adding 10 also causes an error. So to help with that, we can add code in the scenario that will check when something should be failed. So we actually test that the failures work. So basically when we test a smart contract, we need to both check that the contract doesn't fail when it should succeed, so by testing with valid parameters, making sure that it works, but we should also check that if we pass wrong parameters or you call it the wrong time, etc., the smart contract actually fails. It's very important to test it. So to test that without having the whole scenario completely stop, we can make a call to a smart contract entry point by passing invalid parameters, but then we say we know that this is invalid and that's what we want to check. So to do that, you add an extra parameter with the underscore valid equals false to say, I know that this is false and this should fail and I expect it to fail. So when you run it, if it actually succeeds, you will get an error message. If it fails, then all good. It's going to continue to the rest of your scenario. And of course, if you put true here, it will be the other way around. True will mean I expect this to be valid, so it should work. But true is the default value, so you don't need to put it when you expect it to work. And you can also check what message is output by the error. So you can add underscore exception equals, and then the exact string that should be produced when this entry point fails with these parameters. So let's give it a try. Here, -5 should fail. So we can write valid equals false. So now it will run, -5 will work, and we only have the add 10 that doesn't do what is expected. So we change the expectation by adding valid equals false. Then everything works. So now you can see here, this transfer failed, but this is expected, so it doesn't cause an error. So it's displayed in the output of SmartPy. You even have the value of the expression here, not between 0 and 5. So you can still check everything, but it is tested automatically in your scenario. If we want to check the error message, we can add exception equals not between 0 and 9. So let's say I do the wrong exception, and it's going to tell me, no, that's not the exception I expected. I expected 0 and 9, and you sent 0 and 8. And of course, I can put the same right here for this call, and everything works. I don't have to use strings when I generate exceptions. Exceptions can actually be of any type. So for example, if I want to send 2 values, I cannot easily build a string using Python's f-strings. F-strings, if you know Python, are not supported, so I cannot concatenate a piece of string with a number in a Tezos smart contract. There's no easy way to convert a number into a string, for example. So you can create a mixed message that has text and numbers, but what you can do is generate an error that is not a string, but for example, that is a pair. I can use this syntax. I put 2 values between parentheses and with a comma between them. That is a pair. We'll talk about it later. And so instead of returning just this string, I return a pair that contains this string and then this value. Let's give it a try. So here, instead of putting not between 0 and 5, I can create a pair and add added value, comma, not between 0 and 9. And then here, if I run it, of course, it will tell me I was expecting the string, but I got a pair that contains -5 and not between 0 and 9. So here, I just change it to -5. and then same here, 10. Okay, so I can check here what the exact error was and including a value. Now it's your turn to give it a try. I'm asking you to change the endless for contract to add verifications to it. So the idea is to add verifications so that people only add strings that have a length between 3 and 30 characters included. This seems like a reasonable size for a message that will stay on the chain forever. And once you do that, in your scenario, please add tests that make sure your contract does this very well. You will need to get the length of a string, so for that you can use this syntax, sp.len, and then your string between parentheses. And then you can validate the whole thing on Open Tezos. Please pause the video and give it a try. Let's look at the solution. So we still have our endless for contract with a wall text that we initialize to this parameter. And then in the write message entry point, we add this line where we assert that the length of the message is lower or equal to 30, and the length of the message is greater or equal to 3. If not, we simply produce the error invalid length. If everything is good, then we add the message and forever to the text. In our test, here, we have to test both sides of each limit. So here we have a limit at 30, so 30 should be allowed, but 31 should be rejected. Same here, 3 should be allowed, but 2 should be rejected. So we test here with a message that contains 31 letters, and we make sure it is failing. Then we test with 2 characters, and we test that it is failing. Then we check that when the message is right above the limit, so 3 characters should be the smallest text that works, so we check that it works. And same thing with this 30 character text, we check that it works as well. Here it would be good to check that the message is invalid length, so let's add this, exception equals invalid length. And same here, let's give it a try. All good. You can see here those 2 errors, but it's just as expected. Block explorers like Better Call Dev provide a user interface to explore contracts and accounts. So you can find data about accounts, their balance, etc. Find information about contracts, what operations there have been on this contract, what's the current storage, and you can even interact with the contract. There's other kinds of explorers like tzkt and tzstats that have different types of features. The contract that we just saw has already been deployed on GhostNet with this address. So we can paste this address here and we will find this contract and we can explore. So we can see that it has been originated a long time ago and it's been used just a few times to call the write message entry point. We can see the Michelson code, we can see the current value of the storage, so we can see a few messages, and we can even interact with it. So here I can interact with the default entry point. So there's only one entry point called write message in this contract, so the name is not kept, it's just the default, the only entry point. And here I can put the value, let's say SmartPy, and then I don't need any options. I can simply execute it and I can use my wallet on GhostNet. Let's take Kukai. So it's asking me to confirm the transaction where I send 0 Tez to this contract to call the default entry point. So I confirm, so the call was made, it's confirmed. Can go back to Better Call Dev and I can check that a few seconds ago this write message was called. I can check to see the details. I can view the raw message. You can see that the value of the parameter was SmartPy, and I can see that it changes and added SmartPy forever. If I go back here and go to storage, I can see SmartPy forever. Can see that each operation has a hash that I can use if I want to track this operation, check that it's been added to the block, and check that it's final before I do anything else. So you can play around with Vertical Dev, call this contract, and see what happens. Now let's say we try to call it with an invalid value, for example, 2 characters. Let's give it a try. I'll use my wallet. Then we can see here, parameters invalid. Some of the parameters you provided are invalid and the request could not be completed. Please check your inputs and try again. So we can see that I cannot call it with Go, and the same thing if I try to put, let's say, 31 characters. Can do it like that, 10, 20, 31. Execute using my wallet. Again, it tells me parameters are invalid. So if I go back to the operation, I can see that this operation has never been run. I don't have this new operation. The last 2 that failed are not appearing. I didn't pay for them. The wallet just didn't let me run it because it simulated it, realized this is not going to work. Don't even try. Don't even send it to the blockchain. And so it was stopped before it was propagated and added to a block. So to recap, so far we have learned how to create our first smart contracts. We have learned how to create and deploy a smart contract, to store a value in the contract using the types nat, int, and string. And we have learned to create 1 or more entry points, each with a single parameter, that check the value of the parameter and then change the value of the storage of the smart contract. And finally, we have learned to do a test scenario that could check that everything was as expected. So far, our smart contracts only stored 1 value and we only had entry points with 1 parameter. It's pretty straightforward to add multiple parameters, but there's a few important things to pay attention to. If we want to put multiple values in the storage, it's pretty basic. We just need to have 1 line to assign a value to each value in the storage, and we give them different names, and we just have multiple parameters to the constructor. So min value will be stored in the min value variables of the storage, and same thing with max value. If we want to have multiple parameters for an entry point, it's the same. We just add another parameter with a comma behind the first parameter, and we just give it another name, and then we can use them, for example, to replace the values in the storage. The part where you should be really careful is that when you call a smart contract entry point from your test scenario, if the entry point has multiple parameters, you need to name them. So instead of just putting the 2 values separated by a comma, I give the name of the first value equals the value I want to pass, comma, the name of the second parameter equals the value I want to send. The syntax doesn't work if I only have 1 parameter. So if I only have 1 parameter, I simply put the value. If I add the name, it will not work. The reason is that entry points actually only have 1 parameter behind the scenes in the Michelson language. So when we do this, what we send is a single parameter in the form of a record. So we create a record that contains those 2 values, those 2 attributes, and we send that record as the single parameter of the smart contract. But we have a simplified syntax when we declare the entry point. Instead of saying we use a record that has multiple values, etc., we just simply give the list of the attributes of the record. And we'll talk later about exactly how we use record, but here records are used implicitly. Anyway, all you have to remember is that when you call an entry point from a test scenario, use the names if there's more than 1 parameter, and don't put the name if there's only 1 parameter. We can use an example. We will change our store value contract to store a range of value with 2 numbers, min value and max value. Then we will have an entry point set that will change these values. And we will also have an entry point add number that would add the same value to both the minimum and the maximum value of our range. And of course, we'll create a test scenario to check everything. And again, remember, in a test scenario, when we pass multiple parameters, we have to name them. Let's look at our example. So here we have our constructor, and as parameters, we have the 2 initial values that we want to set in the storage, min value and max value. We want to set that those are integers using sp.cast of min value sp.int. Then we just assign them to the storage. Then we have an entry point set that takes, again, two parameters. Actually, it's just one in the form of a record, but we see them as two parameters, new min value and new max value. We assign them to the two variables in the storage. Then we have add number, where we have one value that we will add to both min value and max value. And we have a test where we create an instance with min value equals 0, max value equals 5. Then we call set, again naming the parameters new min value and new max value. We verify that they have been set. And here I can show that if instead of calling this, I simply call this directly with the value, then I get an error because it says the entry point expects parameter of type of nonce, but it got int or not, and it says expected a record with two attributes, new max value and new my value, etc. But instead we got one number. So that's because it's just checking the first parameter. It sees that it's not a record, it's just a number, and it's checking that against the record that contains both parameters, and it doesn't like it because it doesn't look the same. So if you see this kind of error message that talks about records, then remember that it may be because you forgot to give names to your parameters in your scenario. Okay, so then we add a number, check the result, add a number, again, everything. So here you may wonder why explicitly said that min value was an integer. And the reason is that if I don't do that, SmartPy tells me that there is an unresolved constraint. So basically it says here those cannot be added. And basically that's because it doesn't really know the type of min value. So when I add something to min value, it doesn't really know what to type. We had no hint other than this to tell us if min value is a nut, an int, a string, or something else. So we have to give some information about what type it is. But if we only give the type of min value, the type inference system can infer that since min value is of type int, the parameter min value is of type int, therefore the storage is of type int, therefore A has to be of type int, therefore max value also has to be of type int, therefore this max value has to be of type int, this one has to be of type int, this one has to be of type int. So just by adding this single information that says min value is an int, everything else can be determined by the type inference. So we're starting to write contracts that are a little bit more complex, and that means sooner or later we will have bugs. So it's important to learn how you can debug smart contracts. One way to debug smart contracts is to cut them into pieces. For example, if I have an error that I don't understand, I could try to see, well, let's see in which entry point causes the error. So I could easily delete this entry point, delete the calls to this entry point, and check, do I still have my error? If I'm completely lost, I can just use binary search basically by deleting half of the contract to see if that helps. But another tool to help me debug is to get some information about what's going on inside of an entry point. And for that, I can use the trace function to print any value that I use in my entry point. If I'm using the SmartPy IDE, the output will be in the browser console. And if I run it on the command line, it will be simply sent to the standard output. So for example, I have this entry point make call. After I increment nb calls trace, so output on the console or on the standard output, the value that number call has now. Let's give it a try. Here, if right after nb calls plus equals 1, I use trace to output a string and then trace to output this value, I run it. I don't see anything special here, but if I open the browser console, so on Google Chrome it's Ctrl-Shift-J, I can see here the output, nb calls 1, nb calls 2. So I can clear it with Control L to make sure I only see what's the output of the execution. I run it, I see, okay, n equals 1, n equals 2. I could also use pairs. So for example, I put parentheses here, comma, here. I'll do Control L, and if I run it, I can see n equals 1, n equals 2. It's a bit easier to read. That can help me understand what's going on in my contract and fix bugs. Let's practice on an exercise. I will ask you to modify the endless wall contract so that it now counts the number of times it's been called, so the number of times that messages have been added to the text in a new variable in the storage. And then please change the write message entry point so that it takes two parameters, both a name and a message. It should check that the length of the name is between 3 and 10 letters. You should still check that the length of the message itself is between 3 and 30 letters, but you just add this new check on the name. And then with these parameters, it will add a comma, then the name, a colon, a space, then the message, and finally forever to the text. So we'll have the name, and then the message, and then forever. And of course, please check everything in your test scenario and use this as an opportunity to practice using trace and print internal values and see how it works. So please pause the video and give it a try. Let's take a look at a solution. So in the storage, we added this variable nbcalls that we initialize at 0. Then we modified the write message entry point to add a name parameter. We still have our assertions on the length of the message. We changed the error message to clarify that it's an invalid message length. And then we added a second assertion, this time on the length of the name, with a message that says invalid name length. And then we changed wall text to add comma, the name, colon, the message, and forever. And then finally, we increment the value of nbcalls at every call. In our test scenario, whenever we call write message, we need to give the name of the first parameter, message, equals the value we want to send. And same thing with the second parameter, the name equals and the value we want to send. So we make a couple calls that are valid. We verify that the output is what we expect. We verify that the number of calls is what we expect. And finally, we try a few calls that would fail. We try to send a message that is 31 letters long, and so this is false and should generate an invalid message length error. Same thing with a message that is too short, a name that is too short, a name that is too long. And then finally, we write some messages that are exactly the minimum we need. So 3 letters in the message, 3 letters in the name, and then the maximum, so 30 letters in the message, and then 10 letters in the name. This is exactly 10 letters. And we check again that the number of calls is correct. We can give it a try, and we see that it worked. We start with hello, then we call it with the message Anna and Jack and the name Anna. We can see that we now have hello, Anna, colon, Anna and Jack forever. Then after another call from Joe, we have Joe, Tezos forever, and then 2 calls. We have those 4 tests that didn't work, and then finally another 2 that worked. All good. In this module, you will learn how to manipulate addresses in a smart contract, which will make your smart contracts a lot more powerful. As Tezos is a public blockchain, it is permissionless. That means anyone can participate in the network, anyone can emit transactions, anyone can create accounts, etc. However, when they do so, they are authenticated based on their address. So their address is attached to their balance, and their transactions are attached to their balance. And whenever we execute a transaction, we can know for sure that this transaction has been emitted by whoever owns the private key of this address. So they are directly attached to a specific address. And when you use addresses in smart contract, that makes it very powerful. You can authenticate users that call the smart contract, so you can basically implement fine-grained access control. And you can also use these addresses to assign ownership to any digital asset. You have already manipulated addresses. You know that TZ addresses correspond to user accounts, and KT addresses correspond to the address of smart contracts you deploy. And each of these addresses uniquely identify either a user or a contract. And the TZ addresses are based on the hash of the public key of the users. They'll also include a checksum, so you cannot just write a random sequence of numbers after TZ. The checksum has to be valid. From a smart contract, you can manipulate addresses. For example, you can obtain the address of the direct caller of the contract. It could be a user or it could be another smart contract. You can also compare two addresses, so you can check if the address of the caller is equal to some expected address, so that enables access control. You can also send Tez to a given address, or you could call another smart contract based on its address. On the other hand, there's a few things you cannot do. You cannot check the Tez balance of some address, whether it's a user or a contract. From a smart contract, you only have access to your own balance. And you cannot read the storage of another contract either. You can only read the storage of the contract that you're executing. Let's look at some syntax to manipulate addresses. So if you want to create an address value, you simply write sp.address, and then between parentheses and between double quotes, you just give the actual value of the address, so a tz1 address or a key t1 address. If you want to express the type of an address, you simply write sp.address. You have access to the address of the direct caller of the smart contract through sp.sender. And if you want to know the address of the contract itself that you are currently running, you can use sp.self-address. So that's its own address. In your test scenario, you can create test accounts, so fake accounts, just for the purpose of the test, using sp.testaccount and then a name that you can give, so you can store it in a variable. Then, when you call a smart contract and need to send the address of one of these accounts as a parameter of your smart contract, you can simply use the name of the variable where you store the account, .address. So this will send the tz1 address of that user. And finally, if you want to call a smart contract and say this call has been made by this user, so the sender of this transaction is this specific user, you can add a parameter when you call a smart contract entry point, underscore sender equals, and then the variable that contains the account. So here you're saying, I'm calling the increment entry point with the parameter 5 as Alice, using Alice as the sender of this entry point. So from the smart contract, sp.sender will be the address of Alice. Let's work on an example. We will change the store value contract so that only the owner of the contract is able to call the reset entry point. And then of course we will add tests to this new version of the store value contract. Here is our modified store value contract. So on top of storing the value 42 initially, the constructor takes a parameter, owner, that we assigned to another variable in the storage. Then in the reset entry point, we add an assertion. We check the sender, so whoever is calling that entry point, we check that is actually the owner that we stored here. So we check that this address is equal to this address, so that only the owner can reset. In our test scenario, we create a couple of accounts, Alice and Bob. And then when we instantiate our contract, we say that the owner is Alice. And finally, when we call reset, we first try with the sender being Bob. So we call it with an address that's different from the owner that we defined here. So of course we say valid equals false because we expect this to fail. And then we try a call that should work by calling reset as Alice. So this is not sending in a parameter. This is just saying that we simulate this call to reset with no parameter, but where the transaction is emitted by Alice. Finally, we verify that reset was correct and we check that is equal to 0. Let's give it a try. Here we can see that when we instantiate the contract, the value of the owner is tz1wxr. So this is Alice's address. Then we call the add entry point. We see that here the sender is not defined because we didn't specify any sender here. When we try to reset as Bob, we can see that the sender here is a different address, so not Alice. Alice was tz1wx, etc. Here we call it as tz1rp, etc. So it doesn't work, only owner can reset. Then we do another transfer, this time as Alice, tz1wx, etc. And this one works, and of course we reset the value to 0. Now it's your turn. Modify the endless wall contract so that the same user can't add text twice in a row. Basically, we want to do a very basic spam prevention. So we don't want the same user to send 2 messages in a row, which means between 2 calls from a given user, at least one other user should have added text. Otherwise, we reject the call. Please pause the video and give it a try. Let's take a look at a solution. Here in the constructor, we take 2 parameters, the initial value of the text and the address of the owner. So we initialize wall text to this initial value, we initialize the number of calls to 0, and then we initialize the last sender as the owner. So this address, this is an address where we will store who is the last person who called write message, but we have to initialize it with some address. So we decided that we would use some address that is the owner of the smart contract. So we say the owner deploys their contract, they shouldn't be the one sending the first message. And if they want to be the one sending the first message, they can just send a different address here. Then in the write message entry point, so we have this version where we only send a message. We add an assertion that the value of the sender, so whoever is calling this entry point, should be different from whoever we have stored in last sender. Then we add the message to the wall, we increment the number of calls, and then we update last sender to whoever is calling this entry point. So this means that once we have a first call, the next call cannot be by the same person because the next call shouldn't have sp.sender equal to last sender. We can have our test scenario where we again create a few accounts, and then we first write a message using Eve as the sender. Then we write a second message where we use Bob as sender, so this should be fine. But then we add another message where it's Bob again, try to send some messages, so this should fail. And then the next one we send it at Alice again, so it works. And in between we tried with Alice, but with the wrong length of the message, so this entry point was never executed and is cancelled. So now Alice can send a message again because the previous person to send a message successfully was Bob. Let's give it a try. Okay, we can see here that initially we have last sender, that's the address of Alice, tz1wx, etc. Then we have write message sent by Eve, tz1nw. Then we have write message sent by Bob, so a different address, tz1rp. And every time we can see that the last sender has been updated to whoever is calling this message. Same here, last sender updated to Eve. So now again, we have Bob trying to call, but last sender is set to this value, so this is rejected. We can try again. Then we send a message that's too long, and then we have another person try to send it, etc. All good. In this module, you will learn how to create your own NFT smart contract, and you will find out that the few features we have presented in the previous modules already make smart contracts very powerful and useful. The few concepts we have presented so far, integers, naturals, strings, addresses, entry points, storage, and verifications, already give smart contracts a lot of power. You can use them to store data forever. You can attach users to data through their address, which can enable ownership and with verifications, access control. And smart contracts are unique thanks to their address on a unique blockchain. Finally, they can execute code that will change this data and perform transactions based on predefined and, most importantly, unalterable rules. All this makes it possible to create any type of digital asset with two properties, scarcity and ownership. Anyone can create their own unique digital assets on Tezos. You probably already have heard about NFT. So NFT stands for non-fungible tokens. And an NFT is a digital asset that is uniquely identifiable. It contains some information. It's metadata. That could be anything, an image, for example, or some text. It has an owner, and it can be transferred. And that's it. That's what defines an NFT, non-fungible token. So a token that cannot be split, that is unique, and that can be transferred. Because they clearly identify the ownership of an item, NFTs can identify the ownership of any digital or physical art or collectible, such as paintings, music, or in-game assets. They can also represent real estate or any other physical assets, or they could be used to represent more temporary assets, such as tickets for a concert or any event passes. NFT also provide a number of benefits. Like everything on a blockchain, when used well, they don't depend on a third party. So, for example, you could transfer an NFT without having a third party authorize or be the intermediate for this transfer. They also provide a tamper-proof record of the ownership of that item, which makes it easier to track if you're really buying the right thing. Basically, it prevents counterfeiting. So you know that what you're buying is the original NFT, and you can see who sold it first, etc. They make it possible to trade on new marketplaces that are available worldwide without restrictions. So this increases accessibility as well as liquidity and can increase the value of these assets. And finally, they offer the possibility to add a number of features, such as automatically paying royalties to artists when you transfer the NFTs. There's actually nothing new to learn for you to be able to create your own NFT contract. So based on what we just described, you can already write your first NFT contract. So the idea is to create a contract that will represent a single NFT. To do that, you have to keep in mind that the NFT needs to be uniquely identifiable, that it will contain some information that we call metadata, that it has an owner, and that it can be transferred. So give it a try, pause the video, and try to create your own NFT contract. If you're stuck, come back and we'll give you some hints. Okay, let's talk about some hints on how to create an NFT smart contract. When you create your smart contracts, the most important thing is to determine what you will store in your smart contract and what the different entry points will be. Then it gets easier to write the code of each entry point. So if we think about what the contract would store, we need to think about its different properties. We said that the NFT contract has to be unique, but every contract is already unique as it is identified by its address, so it makes it unique on a given blockchain. So we actually don't need to do anything about that. We just rely on the uniqueness of our smart contract. The NFT has to have an owner. We can simply store it as an address in our contract. Same thing for metadata. We can have metadata in the storage of a contract, for example, as a string. It could simply be your name's first NFT. Finally, it has to be transferable. So for that, we need to be able to change the owner. So that means we need an entry point that will update the address of owner. But of course, only the current owner should be able to initiate this transfer. With those hints in mind, pause the video, give it a try, make sure everything's good in your smart contract, and don't forget to test it well. Let's look at a solution. So we can see here this single basic NFT smart contract, and we can see that it's very lightweight. In the storage, as we described in the hints, we have the owner that we initialize with the first owner. So whoever is deploying this contract can set this value to their own address. Then we have the metadata. Here we simply hard-code it in the constructor. We could also pass it as a parameter, but the same thing is when you deploy your contract, you define what the value of the storage is initially. As we already described, the uniqueness of the NFT is already given by the unique address of the smart contract. So there's nothing you need to do about that. And finally, we create this transfer entry point where we pass the address of the new owner. Then the entry point checks that the current owner is indeed the one who's trying to do the transfer. So we check that the sender is equal to the owner, otherwise we have this exception. And if that's the case, we assign the new owner to the storage. That's it. And of course, we need to test it well. So we create a few accounts, we instantiate our NFT, we say Alice is the original owner, we keep this metadata as the original metadata. Then we can create our test scenario, and we try a few transfers. Here we transfer to Bob, we check that indeed it was transferred to Bob, we check that the metadata is what we think. Then Bob can transfer to Eve, so we check that the new owner is indeed Eve. Then Bob can transfer the NFT to Eve, and we check that Eve is indeed the new owner. And finally, Eve can transfer to Alice, and we check that this is good. So here we missed something, right? Our test is not complete. It's important to keep in mind that you should always test the case where everything goes well, but also test cases where people try to do things that are not allowed. So of course here we have this assertion that checks that whoever is trying to do the transfer is the current owner. We need to make sure we check this assertion in our test. So we need to add this verification of trying to transfer, for example, to Bob, but as someone who's not the current owner. So Alice is the current owner, so let's try to transfer to Bob as Eve. And we expect this to be failing, so we write valid equals false, and the exception equals not your property. Let's give it a try. All good. So we start with this owner. This is Alice, TZ1H4, etc. Metadata is first NFT. We have this unique address that identifies our contract, therefore our NFT. So Alice transfers to this person, that's Bob. And so we can show that the owner has changed. Then we transfer to Eve. We can see that the owner has changed, etc. And finally, we try transfer to Bob by Eve, but we have the exception, as expected, not your property. So everything is good. And now we have our first NFT smart contract. If we deploy this smart contract, we are creating an NFT that will be on the blockchain forever, that we can transfer, and that has its own metadata. Of course, you want to create NFTs with maybe more interesting metadata than this, but this is actually really an NFT. Of course, it's still a very lightweight NFT, and it's missing some features that we really expect to make NFTs convenient. The main one is that it doesn't make it easy to securely trade it against currency or other NFTs. In particular, you can transfer it, but there's no secure way to sell it without taking a risk. That's really the main issue with this smart contract. The next one is having one contract for each NFT is not very convenient. It makes it expensive because you have to pay for each deployment. And Tezos, the fees are reasonable enough, but still you have to pay for the storage of each contract. That's not ideal. And finally, it doesn't follow any standards. There are NFT standards that make it easy for NFTs to interact with different tools, with wallets, with marketplaces, etc. So if you use this very simple NFT contract, you really won't be able to trade it much and benefit from all the possibilities of NFTs. But in the next modules, you will learn how to address these issues and add these possibilities and more to your NFT smart contract. On blockchains, everything is about trust. On one side, it's about not having to rely and trust a third party for things to happen as expected. And on the other side, it's about trusting that things will happen exactly as they are supposed to, exactly as the smart contract announced things would happen. And blockchain is also about the underlying cryptocurrency. In the case of Tezos, it's all about Tez. In this module, we will see that both complement each other, and that Tez can increase the trust you have, and it's trust that gives the value to the cryptocurrency. A public blockchain is a system that anyone can use without necessarily revealing their identity. And it's also a system that has a lot of value at stake. So if anyone can use it without revealing who they are, and if there's a lot of value at stake, what could possibly go wrong? All this can only work if most participants behave well. So the question is, how can we make sure they do? Pause the video and think about it for a moment before you continue. If we take our previous example of a contract that allows people to post text on a wall forever, how can we prevent someone from flooding our wall with all kinds of messages? We tried preventing the same user from calling twice in a row as an example on how to use addresses. But this doesn't really protect from anything. It's very easy for a user to create many different addresses. And in our case, we only needed to create 2 addresses and switch back and forth between the 2 addresses to post as many messages as we wanted. Another approach could be to restrict access to a set of trusted people. But that would really defeat the purpose of the contract and the whole idea of blockchains where anyone can join. So it would be too limiting and complicated to use. It's possible, but it's not really the goal of this contract. It also wouldn't be 100% safe. Just because you think you trust someone doesn't mean they're going to behave well. Still focusing on this endless wall contract, can you think of an approach that could work to prevent people from spamming the wall with tons of messages? Give it a moment and pause the video before you continue. One way to prevent excessive use of a smart contract is to rely on a financial incentive. All you have to do is charge 1 Tez every time someone wants to add a message to the wall. If you really want to post a message and keep it forever, 1 Tez is not much. But if all you're trying to do is to spam the wall with all kinds of junk, then 1 Tez for every message is starting to be expensive. So by charging 1 Tez for each message, you make sure that people don't abuse it. At the same time, you can use this Tez as a way to fund the development of a nice app that showcases this wall contract and makes it easier for users to post their messages on it. As we're starting to see, cryptocurrency is useful for much more than speculation or simply storing value. You can use it as part of the blockchain security. You can use it as a punishment for bad behavior. That's what we do to prevent double baking through the slashing of the baker's deposits. You can use it as a reward for behaving well. So for bakers, it's about a reward for baking or denunciating bad behavior. And you can also use it as a way to prevent excessive use. That's what we do when we have this system of gas to prevent people from using excessive computation from the network, or storage fees to prevent people from using excessive data on the network. So we can see that cryptocurrency is used to increase the trust that we have in the blockchain and the fact that it behaves well and reliably. The same can be said about smart contract, and you can use cryptocurrency as a way to increase the security of smart contracts. You can use it as punishment by asking people to deposit some Tez that may not be returned if they don't behave correctly. You can use it as rewards that users can obtain for providing a service, or maybe denunciating bad behavior. And you can use it in your smart contract to prevent excessive abuse by charging fees, as we discussed, instead of setting strict limits and rules that may limit legitimate use of your smart contract. How do we do that? When you call a smart contract, the caller may send some Tez to this contract. These Tez are added to the balance of the contract, and they also may be sent to another address by the contract. So that's how we can have a contract that charges a fee, for example. Let's look at the syntax. We have type, new Tez, that can be used to express amounts of Tez that we manipulate in the contract. We can create values. For example, if we want to have a variable that stores 12 Tez, we can write sp.tez of 12, or we can write it in the actual unit that's underneath, that is the mu_tez, the millionth of tez. And so we can write sp.mu_tez of 12 million. This is the same as this. So sp.tez of 12 is a shortcut when you want to manipulate a whole number of tez. But the actual type is the millionth of tez, the mu_tez. Within a smart contract, you can check how much the caller of the smart contract transferred to this contract by using sp.amount. You can also check how much is currently in the balance of the contract with sp.balance. That includes the amount that has just been sent by the caller. And finally, you can send some tez to an address by using sp.send, the address, and then the amount that you want to send. Note that this is generating a transaction that is not immediately executed. It's added to a list of transactions that will happen after the end of your entry point. In your test, you can test the transfers of tez. So for example, when you call an entry point, you can specify who is calling it and how much they're sending to the entry point by adding _amount equals and the amount you want to send from this user to the contract. Within your test, you can also check the balance of the contract just simply by writing contract.balance. On the other hand, it's not currently possible in SmartPy to check the current balance of a test account. So after here Alice sends some tez to the entry point, you cannot check that the amount Alice has on her balance has indeed decreased by 5. You could do it by using a smart contract instead of a regular account. We'll see later how we can do that. So it's really important to understand that on Tezos, at least on the L1 that we're working on with SmartPy, when a contract charges a fee for a service, the contract doesn't take the tez from the account. It's the caller of the contract who is the one who sends the right amount of tez to the contract. All the contract does is to check if it's happy with the amount that the caller sent. And if it's not happy with it, it can fail and basically reject the call. But by default, any tez that are sent during a call are automatically added to the contract's balance. So the contract doesn't have anything to do to accept the tez. All it can do is potentially reject it if the amount is not what it wants. So this is important in particular because this is not the case for all blockchains, but that's how it works on Tezos. Let's look at a version of our endless wall contract where we charge 1 tez every time someone calls write message. All we had to change was to add this line where we check that the amount of tez sent by the sender is 1 tez. If not, we generate an error, incorrect amount, and everything is cancelled. That's all we need to make sure people pay 1 tez whenever they want to write a message. In our test scenario, we can check that if we indeed do send 1 tez, everything works. But to check that it's really exactly 1 tez, we can check a little bit less, and this should fail and cause the exception incorrect amount. And same thing, if we send a little bit more, it will cause the same error. And it's always good to have a second call to check that we can indeed call twice by paying the right amount. Let's give it a try. Everything worked, so we can check towards the end. This is the first call where we send 1 tez. And we can see that it added the text testing the right amount. And then here we tried with a tiny bit less and it generated the error. Same here with a tiny bit more. And then if we send 1 tez again, everything works. This contract actually has a very terrible flaw, and things would end sadly for the author of the contract. And it's a real flaw that people have made in the past and have lost large amounts of funds. So it's very important to have this flaw in mind and avoid having it in your own contract. So the question is, can you figure out what that flaw is? And then can you fix it? Take a good look at the contract, pause the video, and try to find the flaw. As we stated earlier, the tez sent to a contract are added to its balance. And by default, that means these tez are stuck forever in the contract. There is no notion of owner or author of a contract on Tezos unless you specifically assign a value to an owner variable in the smart contract. So that means by default, no one can get these Tez out of the contract. That means the Tez in the balance of the contract are wasted. If we want to avoid wasting them, we need to specify an owner of the smart contract that will receive this Tez and make it possible for this owner to collect the Tez. To do that, one way is every time someone writes a message to send the corresponding Tez to the owner. So we can send the amount received. And that's it. And we see here that after a call, where the caller sends one Tez to the contract, then the contract generates a transaction that sends one Tez to the owner. Unfortunately, this is not enough. There's another big flaw. Can you figure out why? Pause the video and think about it for a moment. I'll give you a hint. The idea is that this version of the contract doesn't really enjoy all of the benefits of decentralization. So I'll recap main benefits. Decentralization provides reliability. It gets rid of the dependence on a third party. And it prevents censorship. So one of these aspects has been lost in this version of a smart contract. Can you figure out which one and why and how to fix it? Take a look at the contract and think about what could go wrong. Pause the video and think about it for a moment. To find out what the flaw is, you have to remember that a smart contract is a kind of account. And like any account, its address can be the destination of some transfer. So instead of using a user account address as the owner, you could use a contract address as the owner. And so when you send some Tez, you can send them to a contract address if the address isn't that of a contract. In practice, sending Tez to a contract address will call the default entry point of that contract. It's simply an entry point called default that takes no parameter. And if you want to create a default entry point that accepts Tez, as Tez are by default accepted, all you need to do is to do nothing. And as a way to show that, we write pass as the only instruction in the contract to indicate that yes, we know we don't want to do anything in this entry point. So we write pass to say do nothing. This will be an entry point that accepts simple transfers of Tez to the contract. Now the issue is that if the owner of a contract is a smart contract, this smart contract could change the behavior of its default entry point and reject the Tez. If as the owner of the contract, you can reject the Tez, you can reject calls to write messages. That means users have to trust you. They have to trust the owner of the contract, that this owner will not disable the smart contract or prevent someone from posting their messages. The whole idea of decentralization and not relying on the third parties is that you don't want to have to trust that the owner of the contract will not stop the service for any reason. So here, if whoever deployed the contract made the owner another smart contract, and that smart contract can prevent transfers of Tez, then they have full control on whether our endless wall contract works or not. And that's a problem. We don't want that. To better understand this, let's look at an example. So we have our endless wall contract here that whenever we call write message, checks that the user sent one Tez and then sends that one Tez to the owner. So let's see how we can make this owner a smart contract that will then have full control on whether it's possible to call write message or not. The idea is that we can create this owner contract that will store the owner of this contract, and we'll have a boolean called blocked that says whether it's accepting or blocking transactions. So we set it as false. Initially, everything works. Then we have an entry point, set block, where the owner can change the value of blocked to true or false. Finally, we have our default entry point. If blocked is false, And this condition will be true, and then the contract will not only receive the Tez, but send in the balance back to the owner of this contract. But if blocked is set to true, then it will reject any transfer to it. So if this contract is the owner of this contract, then whoever owns this contract can decide to block any call to write message. We can write the corresponding test scenario. Here we create a scenario, we create an instance of our owner contract, and Alice is the owner of that owner contract. We add it to the scenario. Then we create an instance of our endless wall contract, and we say that the owner is actually this contract's address. We add that to the scenario as well. Then we can check that if we simply write a message and send one Tez, everything works. But if we then call set blocked of that contract as Alice, who's in charge of this contract, then the next call, the same call, is going to fail, with the exception wall is blocked, returned by this contract when we call the default entry point. Let's give it a try. So it worked, and we can see that indeed, when we did the second write message call, it called the default entry point of our owner contract and raised the exception wall is blocked. So the transfer didn't happen, and Eve was not able to write on the wall. This is not something we want. We don't want some unique person, some third party, to have full control on the contract and prevent other people from using this service. So how do we prevent that? Well, the issue here, and that you should always be careful about, is that this entry point, called by any regular person, is sending Tez to another address. And this is the dangerous part, because this could fail and prevent any call from write message. So the solution is to avoid calling send to another address as part of the entry point that the first person is calling. And to do that, we just split it into a separate entry point that this owner will have to call to get their money back. So we create a separate entry point. That we call claim. That can be used by the owner. To request the balance to be sent to them. Here we checked that it was actually the owner calling this, but we don't really need to. If someone else calls it, then it's going to send Tez to the owner, and that's fine. That's what we want in the end. We just didn't want it to happen as we write message, because this call could be blocked. So we don't actually need this assertion. So now we don't have an exception anymore. So expected exception, but not occurred. So we can change that and say, yes, now this works. But for Alice to get her money, she would have to call the claim entry point. So now that we know a little bit about transferring Tez to and from a smart contract, let's see how we can use it as a way to add a feature to our NFT smart contract so that the current owner of an NFT can sell it. With the transfer entry point that we already had in our basic NFT smart contract, we could imagine a sale that would take two steps, two transactions. The first transaction would be for the buyer to send a certain amount of Tez to the owner of the NFT to pay for that NFT. And then in the second transaction, the owner could say, okay, you paid me. Now I will call transfer on that NFT with the address of the buyer. So that's a typical transaction, right? If you go to the bakery and you want to buy some bread, you give €1 to the baker, and then the baker gives you your bread. So the question is, what could go wrong with such a system? And how could we change our basic NFT smart contract to fix this issue? Here was the contract. So pause the video and think about it for a moment. So the issue when you use two transactions is that it relies on the two parties to trust each other. That's the case no matter in which order the two steps are performed. If it's the buyer who sends the money first, then they have to trust that the seller will indeed transfer the item to them. On the other hand, if it's the seller who transfers the item first, then the seller needs to trust that the buyer will then send the money. Without the blockchain, so for example in our bakery, the same thing can happen. You could pay €1 for your bread and the baker could take your euro and not give you your bread. Or if the baker gives the bread first, you could take it, run away without paying the €1. In this situation, we can rely on the police, we can rely on the justice system, etc. as a way to handle conflicts. Or more generally, we can involve a third party, for example, an online shop, as an intermediate between the buyer and the seller. But again, you need to trust that the police will care about your bread or your €1 that you lost, that the justice system will be effective, etc. It's really a hassle and can be actually very expensive and time consuming. And you have to trust that the police or the justice system will do their job well. But thanks to decentralization, blockchains can provide this kind of trust without a third party. Within a smart contract, you can perform what we call an atomic exchange, where either the two steps of a transaction succeed or neither of them will happen. So either you both transfer the item and get the money, or nothing happens, simply by having the two steps within the same entry point, since any step that fails cancels the whole entry point. Let's put this in practice with an exercise where your goal is to change the basic NFT contract so that users can buy or sell their NFTs. So your goal is to add a buy feature such that the following can happen. The owner of the contract should be able to set a selling price for their NFT. The buyer should then send the corresponding amount of Tez. The seller should be able to get these Tez. And finally, the ownership of the NFT should be transferred to the buyer when everything goes well. The contract should make sure that the buyer only gets the NFT if they send the right amount, and the seller should only receive the paid amount if the NFT ownership was transferred. So how can we do that? Pause the video and try to work on it. So to help you, we can think of what entry points we will need. We will need two different entry points. One for the current owner of the NFT to be able to set the price at which they want to sell that NFT. And the second entry point will be the buy entry point that the buyer can call to purchase the NFT. It will have to check that the buyer transferred the correct amount using sp.amount. It will need to send that amount to the seller's address from the balance of the contract, and then it will have to transfer the ownership of the NFT to the buyer. So please implement this. You can then validate it on OpenTezos. Let's take a look at the solution. In our constructor, we added this new value, the price that we need to store. Then we have an entry point setPrice that takes the new price as parameter. We make sure only the owner of the NFT can call this entry point. And once we've done that, we simply replace the current value of price with the value of the parameter. Finally, we can have a buy entry point that doesn't need to take any parameter. The buyer doesn't need to say how much they send. They simply send it as they call the buy entry point. And it's the contract that checks that the amount sent is equal to the price. Because if it was a parameter, the buyer could just claim whatever amount without actually sending the Tez. So the amount they send is available from sp.amount, and that's the value you want to check. So once you check that the buyer sent the right amount, you can send that amount to the owner. So here, as we have seen, this could fail, but if that fails, it means the owner doesn't really want to sell it. So that's fine. We don't need to separate that into a claim entry point here. Finally, once we have created the transfer of price to the owner, we can change the owner to the address of the caller, who's the buyer. And that's it. Then we can test this. Here we call setPrice with a price of 7 from Alice, who's the original owner of the NFT. We check that if someone else, like Bob, tries to change the price, this will cause an exception. You cannot update the price. And finally, we try to buy the NFT as Bob, paying the right price, 7 Tez. And we check that if we try to buy it at the wrong price, this will cause an exception saying wrong price. Let's give it a try. All good. We change the price here. We can see that the price has changed. We can see that this failed. Then we actually purchase, and we can see that the amount was sent back to Alice. Then we can try to purchase with the wrong amount, and we get an exception. All good. So just by doing this, we made our NFT contract a lot more convenient. So now you can buy and sell NFTs. In this module, we'll give you the answer to a question you may already have asked yourself. What if I don't want to put any value? For example, what if I don't want to set a price for my NFT? It's not for sale. For that, we can use options. But we also see that in many cases, you probably shouldn't use them. So far, our variables always had a value, but sometimes you simply want to say that there is no value. For example, when you initialize the endless wall, and we keep track of who called the right message entry point for the last time, initially you want to set this last caller value to nothing, right? Nobody has called it yet. So how could we support this possibility? Pause the video and think about how you would support this possibility if it was up to you. So how can we allow variables of some type to have no value at all? One possibility could be to use a special null value, but this could be quite risky. If an int variable is new, then any arithmetic operation you apply to it would fail. If you want to avoid bugs, you want to make sure that if there's the possibility of a null case, your code always handles it. But you don't want to have to handle the null case even for variables that actually always have a value. How can we solve this dilemma? Again, pause the video and think about it for a minute. If we want to both force the code to always handle the possibility that a variable has no value, but at the same time avoid having to write such code for variables that will always have a value, then we would need to use a different type for both situations, right? So for any type, int, nat, tez, address, etc., we would have a version that always has a value, and then another variation of that type that sometimes may not have a value. How can we avoid having to support two versions of every type, but still handle both cases? So instead of having two versions of every type, the int that always has a value and then it that may have no value, we use a special type that wraps around all the types, and we call it options. An option is like a box that may or may not contain a value of a given type. So for example, an option on an int may contain either nothing or an int. All you can do with an option is create the option with or without a value, check if an option has a value, compare two options, unwrap the options. That basically means getting the value that it contains out of the option. And any other operation can't be done without first unwrapping the option. So for example, if you want to add two values of two options, so two options on an int, you need to unwrap both options and then add the actual values. So here's how you create an option. You simply write sp.sum and then between parentheses the value that you want to put inside an option. But of course, you also want to be able to create an option with no value. For that, we simply write none. Two options are equal if they contain the same value. So we can compare sp.sum of 42 to sp.sum of 42, and those would be equal. Or if they both contain nothing, so none equals none. Any other case, they are different. So for example, you could do assert my option equals sp.sum of 42 or assert my option equals none. You could also use the other type of comparison operators, lower than, greater than, etc. If the two options contain a value, it will compare these values. if at least one of the options is none, it will return false. So for example, sp.sum of 33 is lower than sp.sum of 42. But none is not lower than sp.sum of 42, and it's not greater either, or equal to sp.sum of 42. So those two will return false. If you want to extract the value out of an option, you can write your option.unwrapSum. And this will trigger an error if the value of the option is none, because there is no value to get out of it. The box doesn't contain anything. If you want to check if an option has a value, you can simply write assert my option different from none. It's usually a bad idea to use unwrapSum to compare an option to a value. For example, if you do if my option.unwrapSum equals my value, then this will fail if the option doesn't contain any value, which is probably not what you want. You just want to do something if it's exactly this value and not fail if it's not. So what you would rather do is compare to an option. So if my option equals sp.sum of the value you want to compare it to. So instead of unwrapping your option, you wrap the value that you want to compare it to. This will never fail. Whenever you need to describe the type of an option, you can write sp.option, and between square brackets, you put the type of the value inside the option. So for example, for a NAT, the type would be sp.option and square brackets sp.NAT. For none, type inference is used to determine the correct type. Let's check an example. In our endless wall contract, when we wanted to check that the same address was not used to call write message twice in a row, we used last sender. And before we initialize it to the address of the owner, but instead we could say the initial value of last sender is none, right? We haven't made any call yet. Then when we want to update it, instead of assigning it to sp.sender, we assign it to sp.sum of sp.sender. When we want to check if it's the same color as last time, we compare last sender to sp.sum of sp.sender. Again, you write the value you want to compare it to rather than unwrap your option, because this would fail if the value was none. So if we make that change and run it, everything works, and we can see that the initial value of last sender is none, and then sum and the address, etc. My recommendation is actually to avoid options when there is an alternative. The reason is that when you use an option, you need to add code every time you manipulate its value. You need to add code to verify if it's none, you need to add code to extract the value, you need to add code to compare it to a special value, etc. Every time there's something extra you need to do to handle the fact that it's an option. This overall makes the code longer, harder to read, slower, and more expensive. So if there's an alternative that works, we recommend using that alternative. What would an alternative be? Well, as we have done before we introduce option, we can simply use a default value if there is one that can do the job. So for an address, we can initialize the value with an invalid address and give it a name. So for example, this is a contract address that is correct, the checksum works, but it doesn't correspond to any actual contract. And so you could use this address, but most of the time, using the address of the owner also works. So that's what we had done for our endless wall contract and the last sender value. Here, if instead of using an option, we simply initialize with owner, then we remove code, right? We don't need to do this. We just directly compare to the sender. And here we remove code again. We directly compare to the sender, so it makes the code easier to write and to read. The only issue with this is that owner cannot be the one who makes the first call. But if we want owner to be able to make the first call to write message, we can just initialize with a different value that we know for sure will not be the one writing the first message, such as an invalid value. Of course, sometimes it's necessary to use options because there is no better choice. So for example, if you need to call another contract that has an entry point that takes an option as a parameter, of course you need to use an option. But sometimes you need to create your own entry point that has an optional parameter, maybe because you want to be compatible with a standard that uses options. If no matter what, you need to have some specific code to handle the case where there is no value, then you definitely want to use an option. It's a lot nicer to compare to none than to compare to some arbitrary value that you use instead of none. And finally, if there's no default value that would work nicely, then you should use an option. For example, for the NFT contract, if you want to make sure that nobody can buy your NFT, putting a very huge price on an NFT would look weird, would be a weird way to handle it. It would mean like you're pretending that your NFT is extremely expensive, so it's a lot better to say my NFT is not for sale, the current price is none. Finally, there's a number of cases where you need to access return values from instructions that may cause errors, and such instructions often return an option. Here are a few examples. If you use the function isNat to check if a value is a nat, this will return none if the value is negative, and it will return an option on the value if it is 0 or positive. Another example is sp.slice that extracts a substring of a given string, but it will return none if, for example, the offset or the length are invalid. There is no such extract and is beyond the bounds of the string, for example. But if it is valid, then it returns an option on the result. Another case is when you want to interact with another contract, you use sp.contract and provide the type of the contract, the address, and the entry point. And it will return none if there is no such entry point for the contract at this address. Otherwise, it will return an option on the contract. Let's put it in practice with an exercise. Change your NFT for sale contract so that it uses an option to indicate that the NFT is not for sale. So if you want to say it's not for sale, you will use the set price entry point, but pass none as a parameter to say, I don't want it to be on sale. And similarly, right after somebody buys it, you want to set the price back to none so that it cannot be bought again immediately by someone at the same price. Here's a smart contract that we're asking you to change. Pause the video and give it a try. So here, when we initialize the contract, we don't need to put any initial value. So we can remove the price and initialize it to none. When we set the price, well, we need to pass an option anyway, so we just save it as is. It's already an option. And when we buy, then we need to compare the amount sent to the price. So we don't unwrap the price, we wrap the amount using sp.sum. And finally, we need to set the price back to none. In our test, here we need to wrap this into an option. Same here. And line 21, we need to unwrap this because we need to send the value. But since we already compared the amount to the price, instead of unwrapping this, we can simply send the amount received. And so when we initialize the contract, we decided not to put any price. So all good. But now if we want to say it is not on sale, all we have to do is c1.setPrice none. And so we can see that at the end we put the price back to none. So options are pretty easy to use, but remember that when you can, it's better to avoid using them to simplify your code. In this module, we will talk about blockchains and time. Blockchains have a deep relationship with time. You could say that a blockchain has a pulse. It's like a heartbeat ticking very regularly from the genesis block towards eternity. Every few seconds we have a new block. Another connection between blockchain and time is that a blockchain can be used by anyone to safely store information forever. So to send information far in the future. It also has a relationship with the past, as a blockchain can be used to certifiably timestamp information and prove anteriority. Basically prove that at some time in the past you already had this information and you can prove it. Finally, it is possible to use a blockchain to lock assets until a specific time in the future. In a way, use it as a time capsule. The only issue is that a smart contract actually can't tell time. When you execute the smart contract, you cannot read the current time from the computer that executes it. The reason is that a smart contract should always produce the exact same result, no matter which node executes it, no matter when it executes it. So if you run the same program on different nodes and at different times, the current time will be different, right? So the code cannot depend on the actual current time of the computer that runs it. However, you really often need to manipulate time within a smart contract. You want a smart contract to be able to check if it's been called before or after a deadline. You want to be able to check how much time has passed between two given events. And you also want to be able to store and safeguard the date of specific events. So the question is, how can we solve this dilemma? We cannot access the time of the computer the contract is running on, but you do need to know the time. Pause the video and take a minute to think about it. So the solution is that every block includes its own timestamp, and a smart contract can access this timestamp using sp.now. And every smart contract call within the same block will read the exact same timestamp. And it doesn't matter which node executed or when we execute it, the timestamp of a block is always the same. So whenever you execute a contract from a block, the value of the timestamp is always the same. And of course, for the next block, it will be a different value corresponding to when this block was created. But the timestamp of a block is actually predictable. The value of sp.now is predetermined by a timestamp stored in the previous block. In practice, there's two timestamps in the block, the one that can be read through sp.now and the actual creation time of the block that will only be used by the next block to compute the value of sp.now in the next block. So the timestamp of a block is predictable based on the content on the previous block. But more than that, in practice, blocks are created very regularly. At the time of recording, there is a block being created every 15 seconds. And if you look at the actual time, the difference between two block creation is really precisely 15 seconds most of the time. There's very little variation. So that's something important to keep in mind. In SmartPy, we have a type dedicated to timestamps, sp.timestamp. And it represents a number of seconds relative to January 1st, 1970 at midnight. Internally, it's like an integer. It can be infinitely positive, so it can correspond to any date as far as you like in the future, but it can also be infinitely negative, so represent any time as far as you like in the past. If you want to create a timestamp, you can use sp.timestamp and provide the number of seconds since January 1st, 1970. Again, it could be a negative number. If you want to access the timestamp of the current block, you can use sp.now. If you want to add some time to a timestamp, you can use sp.addSeconds, your timestamp and the number of seconds. Or if you want to add a number of days, you can use sp.addDays, your timestamp and the number of days. Finally, if you want to compute the difference between two timestamps, you can subtract them and the result will be a number of seconds. So that's very convenient to measure how much time has elapsed since a given event. Finally, there's a way to create a timestamp using a list of parameters where you provide the year, the month, the day, the hours, minutes, and second. This is using sp.timestamp from UTC. So it's a time in the UTC time zone. When you test a smart contract, time doesn't pass between your different calls. It doesn't matter how long the computation takes. You can make as many calls to your smart contracts in your test. The time is not going to pass automatically. sp.now will always be 0 by default. But you can actually specify what value of sp.now you want to use by adding a parameter to your entry point calls, _now equals, and then the value of your timestamp. This way you can simulate time passing without actually having to wait. If you have a contract that has to wait 10 days for some event to happen, you don't have to test it by waiting 10 days. You can just simulate time passing by changing the value of now. Let's work on an example. We'll take our endless wall contract and add a deadline. The idea is that we will change the contract so that people only have until the end of 2025 to write a message on it. From then on, the wall won't change ever again. So how do we do that? Well, for one, we need to change our storage and add a deadline that we can initialize in the constructor. Then, in the write message entry point, we will add a check. Is this before the deadline? So we check if sp.now is lower or equal to our deadline. Otherwise, we have an exception after deadline. And that's it. That's all we need to have this feature that the endless wall expires after a given deadline. In our tests, to check that it does work right before the deadline but stops working after the deadline, we call write message with a date that is just before the end of 2025, December 31st at 11:59 and 58 seconds. This one should pass, but then a couple seconds later, on January 1st, 2026, after 1 second, this should fail, so we add valid equals false. We use _now to specify the time we can initialize using timestamp from UTC. Let's give it a try. It works. We can see here that this call was made at this time, so something that ends with 598, and it worked. But a little bit later, 3 seconds later, 6:01, this one failed because it's after the deadline. Now it's your turn to practice on an exercise. This time you will change your NFT contract to add some notion of time in it. And the idea is to make it so that you cannot sell an NFT less than 5 days after the last time it was bought. Pause the video and give it a try. Let's look at the solution. In the storage, we will need to add a date. That is the last time that somebody bought this NFT. So we initialize it in the constructor. And then in the buy entry point, we will store the new value, so assign it to sp.now. But before we allow the user to buy this NFT, we check that the current time is more than 5 days after the last date. So here we have the last date that it was bought, and we use sp.addDays to add 5 days to it. If this fails, then we have an exception that says you need at least 5 days. So here you may wonder, should we use options so that initially the buy date should be set to none? And the answer is no. As I said earlier, when you have a way to avoid using options, I recommend avoiding it. Here there's a very simple date that we can use as a default value, and that could be sp.timestamp of 0, so January 1st, 1970. So there's no need to use an option. Any call we could make, of course, will be more than 5 days after that date, so there's really no need for an option in this situation. Now let's look at our test. So here we have the test that check the deadline. When we initialize a smart contract, we initialize with sp.timestamp of 0. And then when we try to buy it the first time at the right price, we set a value for the current date that is 4 days. So that's 4 times the number of seconds in a day after the timestamp 0. So that's of course way in the past, but what matters is the difference. And so this one should fail because it's less than 5 days after the initial value of buy date. But then if we do a second call, this time 6 days after the timestamp 0, then it should work. Let's give it a try, and it's all good. We can see that this attempt was done at this time and didn't work, and a bit later this attempt was done and it passed. All good. So this is a good time for a recap of all the benefits of a smart contract that we have seen so far. We have seen that smart contracts add trust, in the sense that they allow us to eliminate the need for trusted third parties when we perform transactions. By eliminating these intermediaries, they also allow us to reduce costs. They also have the benefit of transparency. The code of a smart contract is public on a public blockchain, so it's possible to check everything that will happen before you call a smart contract and use its service. There is no surprise if you take the time to check the code. We also saw that smart contracts are immutable, and even the owner may not change the code, at least by default. So you are guaranteed that those rules will not change after you decided to use the service. Finally, one of the benefits of decentralization is that there can be no censorship. So nobody in particular can be stopped from calling a smart contract. Finally, there is no single point of failure. Thanks to decentralization, you can be certain that the service will always be available. In this module, you will learn to manipulate arithmetic operators, and we will take as an example our first decentralized finance contract, a yield farming contract. You have already manipulated some arithmetic operators, but let's take a look at all of the ones that are available. We already manipulated the addition using the plus operator, subtraction, and multiplication using the usual Python operators as you would expect. And we also have the negation to take the opposite of a value, the integer division, and that's the only division we have, and the single slash actually does an integer division on Tezos because we don't have any floating point operations. Those would be dangerous as they can lead to approximation issues, maybe a different result depending on the architecture you're running it on, etc. So to keep it safe, we only manipulate whole numbers on Tezos. You can do modulo using the sp.mod function that takes two values and returns the remainder of the division of the first one by the second one. And you already manipulated some shorthand operators, so we can use plus equals to add a value to this. So value plus equals x adds x to value. Same with minus equals or multiplied equal. Instead of having to write self-data.value equals self-data.value plus x, etc. So this can keep things short. For all these arithmetic operators, both operands have to be of the same type. This is because SmartPy is using Python and overloads the Python operators, and you can only overload operators if the two operands have the same type. If you need to do arithmetic operations that combine two different types, for example, if you want to mix int and nat operands, you have two choices. You can convert the nat value into an int using sp.toInt of the nat value, or you could convert the int value to a nat using sp.asInt if you know for sure that the value is positive or 0. Or you could use dedicated functions for multiplication, addition, or division, sp.add, sp.mul, and sp.ediv that work even if the two types are different. Now, the type of the result, it's usually what you would guess based on what the result can be. So for the addition, multiplication, and division, if both operands are naturals, the result will be a natural as well, right? You can never end up with a negative result if you add, multiply, or divide positive numbers. But if at least one operand is int, therefore could be negative, then the result could be negative, therefore it has to be of type int. So if you multiply an int with a nat, the result will be an int. Same with addition and division. For subtraction and negation, the result can always be negative. If you subtract two positive numbers, if the second number is bigger than the first one, then the result will be negative. So the result will always be of type int, whether the operands are nats or ints. For the modulo, it's always a nat. So the remainder of a division is always the positive remainder. For the ediv function, it returns an option on a pair of values, q and r, where q is the quotient, so the result of the division, and r is the remainder. And the reason why it's an option is because if you divide by 0, it could fail, and in this case, instead of raising an exception, it returns none. And if it doesn't fail, then it returns an option on this pair. We already discussed pairs a bit before. Let's look at it in more detail. So to create a pair of values, you put them between parentheses and with a comma in between. So A1, comma A2 between parentheses. And they can be of different types. So for example, you could have a pair where the first element is 42, an int, and the second element is a string. And there the type would be sp.pair, and between square brackets sp.int, comma, sp.string. If you want to extract values from the pair, you can extract the first element by using sp.fst for first. This would get you 42 here. And for the second element, you use sp.snd. This would give you abc. It's also possible to extract both components at once into two variables. So here, if on the right-hand side of the equal operator you have some pair, on the left-hand side you can put the name of two variables between parentheses. This will extract the first value of the pair in A and the second value of the pair in B. And of course here it could simply be a variable that contains a pair or anything else. It doesn't have to be the actual values. So that's a good way to obtain the content of a pair into two variables in one single instruction. This actually works for tuples, so values that have more than two elements. You could write a tuple with 3 elements like this, and you could extract all these 3 elements into 3 variables A, B, and C like this. If you want to do arithmetic operations on mutez, for the addition and subtraction, if you add or subtract mutez, the result will be a mutez. If you subtract and the result is negative, you will get an exception. If you want to multiply mutez, you have to multiply them with a nat. If you have 5 tez, you can have twice that. So 5 tez times the natural 2. Or you could do 2 times 5 tez. And the result will be a number of tez, 10 tez. For that, you use sp.mul, since the two operands are of different types. And so you multiply x by your natural value, where x is of type mutez. If you want to divide mutez by a nat, we have a special instruction for that. To do computations we will see in a little bit that we call sp.split tokens that can do divisions and more on mutez. If you want to do any other type of operations with mutez, you will need to convert the values into other kinds of types. When manipulating mutez, you need to be careful about overflows. For int and nat, we already saw that there is no upper limit or negative limit on how big or small a value can be, except for the storage and the cost of storing these values. But for mutez, it's different. Mutez are currently stored using 64 bits integers. And as mutez is a very small unit, it's a millionth of a tez, that means you pretty quickly end up with big values. So for example, if we take 5,000 tez, that's 5,000 times a million mutez. So the actual value you store is 5 billion. So if you need to square 5,000 tez, so for example, if you want to do some financial computation that involves the square of the price, etc., you may end up squaring a number of tez. But you only need to square 5,000 tez to get a result that won't fit in 64 bits, because you're squaring 5 billion mutez, and 5 billion squared doesn't fit in 64 bits. Of course, you cannot multiply 5,000 tez by 5,000 tez, so you would have to use a type conversion to multiply a number of tez with a number of nat, and that gets this result. But it's really important to keep in mind, because if you end up with a value that causes an overflow, then the call to the smart contract will fail. So you won't get the wrong result, but the call will fail. Therefore, you could be stuck and the funds would be stuck in your contract. So be really careful when multiplying tez with big values. Talking about type conversions, we already said that If you can avoid it, it's better to avoid any kind of type conversions. Usually it's a bad sign if you need to convert a type into another. But sometimes you really do need to convert types. So when you do need to convert types, here is how you do it. First, for some of them, you will need a special module, the sp.utils module. To make it available in your contract, you need to declare it in your test scenario. So in the test scenario, after the name of the test, we before had just main, the only module that contained your smart contract. But now we need a list of modules to have sp.utils and then still main. So between square brackets, you put the list of the modules separated by a comma. So now that you have the utils module available in your contract, you can do some conversions. You can convert a mutez value to a natural. So for example, if you convert one mutez, you will get the number 1 as a nat. And in the other direction, you can convert any nat to a number of mutez or to a number of tez. So if you use nat to mutez and then you pass 1, you will get 1 mutez. But if you want to avoid having to put big numbers, you can directly convert to tez. So if you call nat to mutez with the value 1, you will get 1 tez, which is 1,000,000 mutez. If you want to convert a nat to an int, you simply write sp.toInt of the natural. You don't need the sp.utils module. And then of course you will get an int. To convert an int to a nat, if you know for sure that the int is positive, you can use sp.asNat of your int value. If the number is negative, this will fail and make your contract fail. Let's play with an example. In storage, we will store an integer value that we initialize with the int 1 and a nat value that we initialize with a nat 0. The values don't really matter. And I've created one entry point per basic operation. So one for add, subtraction, multiplication, negation, division, and the module, and some with the shorthand operators that you can play with. And then we have some tests where we just call each of them. If I simply run it, it doesn't work. It tells me I cannot subtract unknown and unknown for the subtraction operator. So here, that's because when we do the subtraction, the result is an int, but the result of a subtraction is always an int. So we don't know what those are. They could be naturals, they could be integers. There's no way to know for sure what the type of x and the type of y are just by knowing that the result is an integer. So we have to help the type inference system. So we simply say that x, let's say it's a nat, and y, we could say it's int maybe. But now if we do that, it will say, no, there's a problem. The subtraction operators must have 2 arguments of the same type, and I put an int and a nat. So of course I could simply put a nat here and it would work. Now I have an issue with division. So similarly, it doesn't know what I'm dividing by. So I need to say what the types are. So I'll just say I'm dividing 2 naturals. So now it works. So here, since the result is an int, it deduces that x and y are ints. But let's say x is a nat. Now if I run this, it's telling me, nope, you cannot mismatch int and nat, because the result is an int. If one is a nat, maybe the other one may be an int, but we cannot add nat and int. And if the other one is a nat, then the result wouldn't be an int. So here, what I could do is either use sp.add x and y, but then it tells me I don't know what y is. So let's say y is an int, and it would work. Or we could say, well, we first convert x to an int. So let's say sp.toInt of x plus y, and this would work as well. So what I recommend you do is take this example and play with it. Change the types of different values and see what happens and find ways to fix it and look at what the error messages look like, etc. So for example, one thing we could do is try to put the result of the subtraction as a NAT. So this of course would fail because the result is an int and I try to store it in a NAT. But I could try to do sp.asNat of the result, which would work. But that's only because I'm subtracting 3 from 5. So if I subtract 7 here, then it would tell me, nope, it doesn't work, the result fails. But here the message is not very clear because internally it's using options to manipulate the result, because the underlying operation returns an option and is none if the result is invalid. So before I use asNat, I need to make sure I know for sure that x is greater than y. So play around with it. Now we can have a similar example where we play around with muTez. Here we have this financial value that's of type Tez, and then we have operators to add, subtract, multiply, and divide. If I simply run it like that, it's going to tell me it doesn't like multiplying 2 muTez, and that's because my example in multiply I did Tez times Tez, so this doesn't work. I can only multiply a muTez with a NAT. So let's say I want to do 5 Tez times 3, but it still doesn't work because again the operators expect the 2 values to be of the same type, and that's not the case here. So before it even tries to run my test, it's just inferring from the type of financial value that those 2 values should be of the same type and type Tez. So here I need to use sp.mul. And again, for the subtraction, it tells me I don't know what those are, so I need to cast them. And if I cast the first one, then it's going to deduct that the second one is the same type. And now it's telling me that the multiplication, it doesn't know what I'm trying to multiply, because with sp.mul I can multiply all kinds of things and obtain all kinds of types. So I should say that x is of type muTez and y is of type NAT. For division, same thing, I need to provide the types. Let's say x is a muTez, y, let's try with NAT, doesn't like it. I need to use ediv of x comma y. So this will return an option on a pair, so I can do dot unwrap sum. And if I want to get the result, I can do sp.fst of that pair. And here it's telling me it's expected a NAT, but got muTez. So that's because when I call it, I want to divide by a NAT, but I simply put a Tez here. And now it works. So again, play around with it and see what happens. One operation we really often want to do when manipulating money is compute percentages. But because there is no floating point type on Tezos, to avoid bugs related to approximations, etc., we cannot compute 20% of a value by simply multiplying by 0.2. So we have to multiply by 20, then divide by 100. To make that easier, especially when it comes to the types, we have a special operation that we can use to compute any kind of percentages. It's called split tokens. And split tokens will take 3 parameters, an amount, a quantity, and the total quantity, and it will do the computation amount times quantity divided by the total quantity, where amount is a number of Tez And quantity and total quantity are of type NAT. And so this can be used to compute percentages. So if we want to compute 20% of some amount, we can call sp.split tokens of that amount, comma 20, comma 100. Of course, we could also do the same with 1 and 5, as long as the ratio between this number and this number is what we want, 20%. It's not always 100, because we can consider having other kinds of percentages that are maybe smaller than 1%, for example, 0.1%. So here, all we would have to do is do 1 per 1,000. So we use quantity 1, total quantity 1,000, and this will compute 0.1% of 5,000 Tez. Okay, let's use all this in an example. And for an example, we'll create our first decentralized finance contract. I'm definitely not an expert in finance, and this is not a contract that we audited, etc. It's really for educational purposes, but we can show you how you can create a contract that people can lend money to for the purpose of gaining some interest over time. We already presented the idea of baking and the fact that while bakers put some Tez at stake to get the rewards, people who don't want to be bakers by themselves can delegate their own Tez to the baker of their choice to get a share of the rewards. When you pick a baker, you can pick them based on multiple criteria. You can check how much of the rewards they will share with you. Different bakers will share different percentages. You can also check if they do their job well. So if they ever miss the opportunity to create a block, because that's when they do create a block that they get their reward and then share them with you. So check how often this happens. And of course, you also want to check how they vote when there's a call for a vote for a new amendment. Usually, the reward you get when delegating your Tez is around 5% a year. But there is no guarantee of that. There's always a risk that after you delegate your Tez to a baker, this baker doesn't do their job well and misses a lot of blocks, or doesn't pay you your rewards, or simply disappears and stops being a baker, or changes address, for example. So when you delegate your Tez, if you want to make sure that you get your share of the rewards, you need to regularly check what your baker is doing. So you cannot just sit down, wait a year, and then get your profit. There's a risk you wouldn't get anything. Your Tez themselves are not at risk, because even if the baker behaves badly and gets slashed, your own Tez that you delegate don't get slashed. But the risk is that you won't get your rewards. So the example we will work on is a smart contract that offers the service for anyone who doesn't want to worry about that, still wants to delegate their Tez to some baker. They don't really necessarily want to worry about which baker, they just want to be assured to have some yearly interest without any risk at all. So pause the video and think how you would create such a contract that guarantees to whoever is putting their money that they will get their rewards. So what we will do is our first decentralized finance contract that will enable the externalization of the baker selection and monitoring, etc., making sure your baker does a good job. In exchange, it will take a small share of your rewards. So it will guarantee you that you will get a fixed reward of 4% a year. To make sure that whatever happens, you will get this 4%. This amount for a whole year will be deposited in advance in the contract and stuck there for you to get your guaranteed interest. But the owner, if they do their job well, delegate the balance of the contract to the right baker, monitor it, etc., and make sure they get 5%, then they will be able to keep anything that's beyond the 4% that they owe you in exchange for taking the risks. And we will do that in a contract that handles only one lender at a time. So only one person will be using this contract at a time. Pause the video and think a bit about how you would do that. Okay, so we will have two people interacting with this contract. The lender, so that's the one that has money to invest in the contract and want to get 4% back. So the lender will be able to deposit their funds using a deposit entry point and put some Tez on the contract. And at some point in the future, when they want to get their deposit back plus their earnings, they will call a withdraw entry point. On the other side, the owner will be able to control what baker to delegate the balance of the contract to. And they will have a set delegate entry point to say, I want to delegate to this baker. And they can change it at any time. It's their responsibility to make sure they pick the right baker, because it will impact how much they earn. Of course, at some point, they may want to withdraw their own funds. So we need to have an owner withdraw entry point for the owner to collect any amount that they are allowed to withdraw. They always need to make sure there's enough reserve in the contract to pay whatever the lender has deposited, plus 1 year of yield. Finally, since they need this reserve in the contract, they need to have a default entry point to deposit this reserve at the beginning before the lender deposits their own funds. But this is also the entry point that bakers use to send money to the contract. When a baker sends their rewards to an address that delegated to them, they simply send Tez to this address. So we need to make sure that our smart contract has a default entry point that accepts the rewards. Quick reminder, the default entry point of a smart contract is the entry point that is called whenever you simply send some Tez to the contract. If there is no such entry point, the transfer will fail. And if this entry point fails, then the transfer will fail and you won't get the Tez. So if all you want to do is accept direct transfers from anyone, you can create this entry point called default that doesn't take any parameter and doesn't do anything. So with the instruction pass. But remember that any entry point can accept Tez as long as the call is valid. Okay, so in our yield farming contract, we will do a number of computations. So first, we need to add a ramp-up period. So it's a period of time where you don't get any yield. And the reason is that when you delegate your Tez to a baker, you don't immediately start earning. You need to wait for the baker to get the opportunity to bake a block. So to keep it simple, we simply wait, let's say 3 weeks before we start paying interest to the lender. After that ramp-up period, the yield becomes proportional to the time between the deposit after that ramp-up period and the withdrawal. So if you leave your money for 1 year, you would get exactly the annual yield rate. If you wait for 6 months, you will get half of that as interest. As we said earlier, we always want the owner to leave a reserve so that they can always pay 1 year of interest. So we will have a computation to do that where we multiply the deposited amount. So deposited amount is whatever the lender has deposited. Multiply that by 1, because they at least should have that amount kept in the balance of the contract, plus the annual yield rate. So let's say 4% of that amount. When the lender withdraws from the contract, the amount they should get is their deposit times 1, plus their deposit multiplied by the annual yield rate and multiply by what percentage of the year passed since they deposited. So the duration since the deposit after the ramp-up period divided by 1 year. And here is how we compute this duration. So we take the current date minus the deposit date and we subtract the ramp-up duration. Now, if we look at the contract in more detail, we can focus on what we need to store. So we need to store the address of the owner, the address of the lender, how much money was deposited on the contract, when it was deposited. We can store the annual yield rate that we promise that we will give to the lender, and then how much time we need to wait before the yield starts. So the ramp-up duration. Then we have our different entry points. We already talked about the default entry point. We need the owner withdraw entry point for the owner to be able to withdraw some amount from the contract. And then we will check that it's indeed the owner calling. We check that the amount they leave in the contract is sufficient. And then we send the amount they request to them if everything is good. We'll have the set delegate entry point that takes an address. It's technically an option on an address as a parameter. It will simply check that the caller is the owner. Only the owner may decide which baker to delegate to. And then they will simply change the delegate to this address. We need the deposit entry point for the lender to deposit funds. And when we do that, we check that there's not already some amount been deposited. So we cannot increase how much we have in the contract. We can simply deposit once and then withdraw. And if we want to start again, we can deposit a bigger amount or a smaller amount. So when we deposit, keep things simple. We check that the current deposit is 0. And then we update this value and we keep track of when it was deposited. Finally, when the lender tries to withdraw some funds, we check that the caller is indeed the lender. Then we compute how long it has been since the lender deposited the amount, and we subtract the ramp-up duration from that. And finally, we compute how much they should get back, so that's the amount they deposited plus this amount times the yield. So they're guaranteed annual yield rate times the proportion of the year that they got the money for. And then finally, to say that the money has been reimbursed, so we can say deposited amount is back to 0, so that the owner can now withdraw everything because they don't need to leave any reserve anymore since there's nothing deposited. So now we can check the actual code. So we see the constructor that initializes everything, the owner, the lender, deposited amount, deposit date. Here we set the deposit date at 0. We could say, well, nothing has been deposited yet, so why not use an option? But again, an option would make things more complicated. Here it's easier to just set the date at 0. We see that we have our default entry point that doesn't do anything, just pass. We have our set delegate entry point that simply takes the address of the new delegate, technically an option. We check that it's the owner wanting to change the delegate, and then we call sp.setDelegate. So this sets the delegate for the whatever Tez are in the balance of the contract to this address. We have a deposit entry point for the lender to deposit their money. So we check that it's the lender. We check that there's not already some money being deposited, which would cause a mess in all the computations. We then store the amount in deposit amount, and we store the current date in deposit date. Now, when the user wants to withdraw their funds, again, we check that it's indeed the lender. We compute the duration since they put the money in. So for that, we take the deposit date, we add the ramp-up duration, that's the number of seconds. We subtract that from the current time, and then we convert it to NAT. There's an easier way to convert to NAT here. We can simply do as NAT. So that's the duration, and then we take the duration of a year. So that's approximate, but it's good enough. We say year is 365 days, and then we compute the yield for 1 year. So we multiply the deposited amount times the annual yield rate. That's a percentage. Let's say 4%. This would be 4. So that's 1 year yield multiplied by 100. Then using the duration, we compute the duration yield. So how much for, if this is how much for 1 year multiplied by 100, this would be how much for this duration. So we use split tokens to take 1 year yield, and we, for this duration, divided by 1 year times 100. So that gives us how much yield we should get for this duration. Then we simply send that amount plus the deposit itself back to the lender. And then we reset everything, deposited amount to 0 and deposit date to 0. Finally, the owner may withdraw at any time, but always needs to keep a reserve. That's enough to pay for 1 year of interest. So here we check that it's the owner calling owner withdraw. We compute 1 year of yield, again using split tokens. So we take the deposit amount and we take the annual yield rate out of that. So 4% of that amount. And the reserve should be whatever the user has deposited plus that interest. If the amount that the owner is requesting to withdraw leaves enough, so the balance minus whatever we take is more than this reserve that we have to leave, then we can send them that amount. And that's it. If we run it, we can see that we initialize it with an annual yield rate of 4%. Initially, everything is 0. and we set up this random duration, ramp up duration. I think that's 3 weeks. The owner transfers 5 Tez to allow for some amount of deposit. Then a user deposits 100 Tez. Then we check that if we try to deposit again, this doesn't work. We can only have one deposit at a time on the contract. If we try to withdraw with the wrong owner, we cannot do that. If we try to withdraw too much, it doesn't work either. But we can here withdraw 1 Tez, and we still have enough to pay for 1 year of yields. Here we use setDelegate to change the delegate of the contract, so which baker we delegate to. And then here, the owner withdraws after some amount of time that we set here. That corresponds to a year plus the ramp-up period. And we see that they received 104 Tez. So they deposited 100 Tez, and now they get 104 back. So that could be a very nice way to provide a service. But again, this contract has not been audited. This is just for educational purposes, so don't trust it as is. Now it's your turn to work on an exercise where you do some computations. And we'll take this opportunity to play a little bit with interesting NFTs. So the idea is that with smart contract, we could show that you can create digital objects that has an owner that we bought, etc. But you can add interesting properties that can be very unique, either collectibles, or you can even run interesting social experiments. So let's try to do one. We will create an NFT that has a price that automatically increases by 10% after every sale. So the owner of the NFT doesn't set the price at which they sell it. The price is automatically 10% more than whatever they paid for. So pause the video, think of how you would do that, and give it a try. So if we want to create an NFT that has a price that increases by 10% after every sale, we will need to remove the set price entry point from our NFT contract. And then we will need to change the buy entry point so that it automatically sets the new price at 10% more than the previous price after the sale. So if we do that, and you start with an NFT that's worth 1 Tez, after the first sale, it would be 1.10 Tez. After 10 sales, it will be 2.59 Tez. And after 100 sales only, this is exponential, it will be 13,780 Tez. Pause the video and think about how you would change your contract and implement this. Let's look at the solution. The contract we get is actually pretty basic. We have 3 values in the storage: the owner, the metadata, and our price that we set with an initial price. And we only have 1 entry point left, the buy entry point. That simply checks that whoever is trying to buy is sending the right price, then sends that amount to the owner, then changes the owner of the NFT, and then computes the new price using sp.split tokens. So we take the old price and we take 10% of that price and we add it to the old price. And we can give it a try and calling a couple times the buy entry point. And we see, okay, we initialize with 5 Tez. So the first purchase is the actual price 5 Tez. So we transfer 5 Tez back to the owner. Then the next time someone wants to buy, then it became 5.5 Tez, so 10% more. And so we transfer 5.5 Tez to the new owner. And finally, if we try to purchase with the wrong amount, so 6 Tez, it's incorrect because now the price is 6.05, as we verify here. So all good. So the sad thing about this is that if you deploy this contract, all you will get is those initial 5 Tez. If the price keeps increasing and many people buy it and sell it, it would end up being worth tens of thousands. But as the initial creator of this great idea, you will only get 5%. Wouldn't it be nice if you could get a percentage of every sale? And therefore, if your experiment becomes very successful, then you would get a nice reward. So what we want to do is create an NFT that gives royalties to its author. The idea is that every time the NFT is sold, we want the author of the NFT to get 5% of the price of the sale. And of course, the 95% remaining should go to the owner of the NFT. So try to add this feature to your NFT contract. Of course, you will need to add an author in the storage that is separate from the owner. And when you will compute the shares that the owner and the author have, you can use sp.split tokens. So pause the video and give it a try. Let's take a look at the solution. Here we added two fields in the storage, the author and the percentage of each cell that the author should get. Then we modified our buy entry point to compute the share that the author should get. So for that we use split tokens, and we take the price and we compute the author rate, so 5%. And for the owner share, we take whatever is left, so the price that was just paid minus the share of the author. It's important to do that rather than do another split token maybe with 95%, because there's always a risk that with some approximations and running, etc., the total wouldn't be 100%, in which case the sale couldn't happen because you try to send even a tiny bit more than 100%, everything would fail. So it's safe for the last person you send Tez to send whatever is left after everything else has been added. We'll talk about that a bit more in a minute. Then we send the owner share to the owner and the author's share to the author. Finally, we still have our formula to increase the price, and then we update the owner. You could wonder why we didn't send simply the balance to the last person, for example, to the owner, after sending their share to the author. But it's important to have in mind that when you send Tez using sp.send, it's not actually directly sending the Tez to the owner. It's adding a transaction to the list of transactions that will be executed after the end of our entry point. So it's not executed immediately, and it definitely doesn't change the balance. The balance that you read in this entry point stays the same for the whole duration of the entry point. But later on, a transfer will be done to the owner, and then a transfer will be done to the author, or at least will be attempted. Again, you need to be careful when splitting the balance. If we did it this way, it's a bit unusual, but if we did it by subtracting to the price the share that the other person would get, so here we do split tokens, we take the price, whatever is sent to the author as a percentage, then 100 minus author rate, so we subtract 95% of the price from the price to get what is sent to the author, and here we do the same with the owner. If we did it in this bit unusual way, but when you look at the computation, everything seems to be good. You send the price minus 95% to the author, and then you send the price minus 5% to the owner. This should give 100%, right? But if you do that with some value of the price, you would end up with running issues where this value is a tiny bit less than 95%. Therefore, the author share is a tiny bit more than 4 or 5%, so it would be, if the rate is 4%, that would be 4.0001, and then the owner share would be 96.0001. So the total would be 100.0002, and therefore this would fail because there's not enough money in the balance of the contract. You cannot send 100 point something % of the amount. This would fail. So again, the best practice is for the last amount that you send, compute it as the total that you have, so the balance of the contract, for example, the price, minus whatever you sent to the others. This would avoid failures due to running issue that would get your contract completely stuck. Unfortunately, there's still a flaw in our contract. So if you look at this piece of code, can you identify the flaw? Please pause the video and think about it. So this is a flaw we already talked about. The author could block any sale. And the reason is that the author here could be the address of a smart contract that has a default entry point that they can switch to reject any payment. So this transaction could be blocked by the author. So the author would say, nope, the NFT I created years ago, I don't want it to be sold anymore. Or maybe they could try to use it to extort money from the current owner that really wants to sell it and needs the money. So this could be dangerous. So again, the best practice is to let the author claim their share using a separate claim entry point that they can call. You could say the owner can do the same and reject the transfer. But in this case, it doesn't really matter. Here, the whole point is that the owner wants to sell. So if they refuse to sell, well, they just don't get their money. This is not a big deal. But for the author, it's really important. They shouldn't be able to block the sale. So the way to do it is to remove this line so that we don't directly send the money to the author, but we add an entry point, claim author rate, that the author can use to get whatever is left in the balance of the contract. So we check that it's indeed the author, and we send them the current balance of the contract. So you may wonder if there could be a flaw if the author called this at the wrong time. So for example, when we buy, we send the Tez to the balance of the contract, then we check, okay, is the amount right? We compute the share of the author, etc. And then we send the owner. But you could think in the meantime, the balance contains all the money that is owed to the owner. So couldn't the author call this right at the right time in the middle of this to steal the balance of the contract? And the answer is no, thankfully, because the execution of an entry point is atomic. Nothing else can happen while this is running. There is no race condition, there's no parallel execution. Everything is serialized. So this code and any transaction generated by the entry point will be completely finished before anyone can call any other entry point. Everything is serialized and done in sequence. So you're safe from that kind of issues. In this module, you will learn how to use records in SmartPy, and we'll apply this to an example, your first dynamic NFT. A record is a data structure that allows you to group several values within a single object, single value. Each of these values has its own name within the record, and the different values may have different types. For example, you could create a record to store data about a person. So you would have their first name, that is a string, their last name, also a string, and for example, their age, that would be a nat. We already manipulated records implicitly when we called a smart contract with multiple parameters. So when you call an entry point and you have to give the name of every parameter that was creating a record, since in reality an entry point only takes one parameter. So if you want to pass multiple ones, you have to use a record. But now we'll work on explicit records. To create a record, you use the syntax sp.record and between parentheses the list of fields with the name equals the value and all separated with commas. So here we have a record with an integer or natural named field 1 and then the string named field 2. Once you have a variable that contains a record, you can access any field simply by using the name of the record dot and the name of the attribute. So here, if you create a record with two values x and y, we can extract the value of x by doing record.x. When you need to describe the type of a record, this is how you do it. So you may notice that anytime we define a type, for example, when we created a pair, or an option, we used square brackets after the name of the type. The record is basically the exception to that for technical reasons related to how Python works. So in this case, we use regular parentheses. So creating a record type looks very similar to creating a record value. So we do sp.record and then between parentheses, the list of fields. And this time the only difference is that instead of providing the value of each field, we provide the type of each field. So here field 1 equals sp.nat and field 2 equals sp.string. You may sometimes end up having to provide the type of a record multiple times within your code, and it can become quite large if you have many fields in a record. So to save your time, you can name the type by creating what we call a type abbreviation that you would put outside of any contract within the main module. So for that, you would create a type by giving the name you want to associate to it. So here I wrote T record as the name for some example. Then colon and the keyword type equals, and then the description of the type. And then within your contract, every time you needed to describe the type of your record, you can put this name instead. Let's work on an example. And we will create a dynamic NFT. So usually an NFT is associated with some static image or maybe some video or some music that you may actually want to store off-chain, and then you only store the hash in the metadata. But for things like games, you may want to have NFTs that have different properties that evolve over time and with a set of rules on how they can evolve. So we'll create this kind of NFT. And we will make our NFT contract an NFT of some creature that we would use in a game. So we will give this creature two attributes, a name and a size, and we want to store both of them in the metadata field of our NFT. Then we'll be able to add a feed entry point where we can pay 1 Tez, and that will increase the size of the creature by 1. So we will increase this attribute by 1 every time we call feed. So let's look at the contract. Here in the constructor, we don't actually change anything because we still store whatever metadata is sent, and we don't need to specify the type. It will be specified directly in the test case or inferred from other aspects of the contract. For set price, nothing changed. Buy, nothing changed, but now we add this new entry point feed where we check that the caller paid 1 Tez, and we simply change the size attribute of metadata and increase it by 1. So that's all we had to change in the contract itself. And in the test, that's where we initialized the storage with the metadata that is composed of a record. So we create sp.record with an attribute name, say let's call it beast, and a size that we initialize at 10. So here we used to just have a single value, a string, and now we provide a record. And that's about it. In our test, we add this call to feed where we pay 1 Tez using Alice's account. You may notice that anyone is allowed to feed the beast. It doesn't have to be the owner. So let's run it, and we can see that now in the metadata, we have this record presented using 2 columns, one for the name, one for the size. And so we have the name beast, size 10, and we set the price and we feed it. And when we check the details, you can see that now the metadata contains a name that's still beast, but then we increase the size to 11. Records are actually not supported by the underlying Michelson language. There is no such thing as a record in Michelson. So what you do to create a record is to use nested pairs. So as you remember, pairs enable you to group 2 values with different types. And so if you create a record with just 2 values, then it's just simply a pair. But if you create a record with 3 values, then we need to use 2 pairs. And the idea is that the first element of the pair would simply be the first of the 3 elements, but the second element of the pair would be another pair with the next 2 elements. So like this. So we have a pair that contains a regular element, an integer, and then another pair with 2 values. In Michelson, we write like this. So a first pair with 42, and then the second element is a pair with 12 and 3. This way of organizing it is what we call the right-com representation. So if we were to add another element, we would again replace the last element of the inside pair and then replace it with another pair that contains 3 and then the next value we would like to add. So if we keep adding, it looks like that. It just looks like a comb with a handle and then different teeth. It would be possible to represent a record in using a different approach. And instead of always using the second element and replacing it with a new pair, we could do the same but on the left side. So take the first element of the pair and then replace it with its own pair. We would still put the value in this order. So if you traverse the tree from left to right, you would obtain all the different values. So this would be what we call the left-com representation. Both are perfectly valid, and both are possible with Michelson, and it's really a matter of convention whether we use right comb or left comb. Different languages actually may use different representations, but if you want to be able to make two contracts compatible and make sure they understand each other, you can specify what layout you want to use. So if you want to use the right comb approach, after the creation of your record, you can add .layout, and then between parentheses, you describe the structure. So here we have the first element of the pair, and then another pair with the two elements, the names of the two elements between double quotes. On the other hand, if we want to use the left comb layout, we would have to do .layout, and then the first pair with A and B, comma, the name of the last element. So sometimes your contract has to interact with another contract that uses a specific layout that may be different from the default layout your language is producing, so that's why you need that. Now it's your turn to work on an exercise. Let's change this dynamic NFT contract to add an extra attribute to the metadata. We will call it strength, and then we will add a train entry point that somebody can call, but only once within a window of 24 hours. So you may never call it more than once within a given 24 hours window. So with this train entry point, if the size is more than 10, it will reduce the size by 1, and then in exchange, increase the strength by 1. So you train, you lose a bit of weight, but you gain some strength. Pause the video and give it a try. Let's look at a solution. So in the constructor, we still don't change anything to the metadata, but we need to add an extra field in the storage to keep track of when is the last time we trained our creature. So we add this last training parameter. We set it at a timestamp 0. Of course, this is way in the past, so we don't need to worry about how soon we're going to be able to train it again. We don't need to use an option. We don't change set price or buy or the feed entry point, but we add this train entry point. We check that the size is not too small for it to be trained, so it should be at least 10. We check that it's been more than 1 day since the last time we trained it. So we add 1 day to last training and we compare that to the current time. And if we're not yet past this, then we output too soon. Then we mark the last training at the current time. And then we apply the changes. We reduce the size by 1 and we increase the strength by 1. In our test, we initialize the strength at 0. And then we try different tests. So we start by feeding the beast to increase the size by 1. Then we train it to increase the strength by 1 and reduce the size by 10. We feed it again to train it at a different time and see if everything works. It would be good here to add scenario. That c1.data.strength equals 2. Then we try to train it again, but the size is still 10. Let's verify that too. So we're too small to train it. So we need to feed it again, then train it again. And then we can verify that the strength is 3 and the size is back to 10. Then we feed it one more time, but we're trying to train it right away. So that's 3 days plus 1 second. And this should fail because it's too soon. But if we wait a bit more, then this should work. And we can check that we had the strength at 4 and the size is back to 10. Let's give it a try. And here, of course, I forgot to put strength within the metadata record, so I need to change that. And add this here, 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 and there. And it's all good. So now we can check that we start with the name beast, size 10, strength 0. And after we feed it, the size increased. After we train it, the strength increased, the size decreased. We feed it again, etc. Then we try too small, too soon, and at the end, as we already checked in the code, the size is at 10 and the strength is back to 4. All good. In this video, you will learn how to use maps and big maps in the storage of your smart contracts. And this will enable you to go from small smart contracts that only store a few informations, a single NFT, a long single string, to large-scale smart contracts that can store whole databases of data, many NFTs, and potentially the assets of millions of users. A map is a data structure that stores key value pairs. And the keys and values in a map can be of almost any type. All the keys have to be of the same type, and all the values have to be of the same type. So for example, we could store data about different countries. We could create a map that stores the population of each country, where the key would be the name of the country, a string, and the value would be the population of a country, a nut. So for France, you would have the population of France. For the key Italy, you would have the population of Italy, etc. Similarly, you could create a map that stores multiple information about each country, where each entry would be a record. So the key would still be a string, but the value would be a record with not only the population, but the size of the country and other information. To create a map, all you have to do is write a pair of curly brackets. That would create an empty map. But you can also create a map that already has a few elements. So you put the key, colon, the value, and then comma, the next element. You can put as many elements as you want in the initial map, separated with commas, and every time the key, colon, the value. If you need to specify the type of your map, you simply write sp.map, and between square brackets, two values separated by comma. First, type of the key, comma, the type of the value. When you want to manipulate entries, you use the name of your map and the value of the key between square brackets. So to add or update an entry, you write the name of your map and then between square brackets, the key that you want to change, and then you can assign a value to it. If you want to delete an entry, you simply write del and then the name of your map and between square brackets, the value of the key that you want to delete from your map. And more generally, anytime you want to access any entry and the value corresponding to a key, you write the name of the map and between square brackets, the value of the key. If you want to check if a map contains a certain entry based on its key, you can write my map dot contains, and then between parentheses, the value of the key. This will return true if the map contains an entry with this key and false otherwise. With a map, you can also get information such as its size. You can write sp.len of your map, and this will return the size of the map, the number of entries in the map. So for example, if I have a map with 2 entries, then if I call sp.len of that map, it would return 2. I can also request the list of items within my map, and we'll talk about list later, but basically if you call for a given map .items, it will return a list where each element will be a record that contains 2 fields, a field key with the value of the key of that element, and a field value with the value of the corresponding entry. So this way we'll see that you can access all the elements of the map and look through them by enumerating elements of the list. If you only want a list of keys, you can use .keys. And so, for example, if you do this map .keys, it will return a list of keys, so 1 and 2 in the list. Similarly, if you only want the values, you use .values, and it will return a list that contains all the values. Before you start manipulating map, there is something really important you have to have in mind, and it concerns costs and limitation associated with storing a lot of data. Between uses of a smart contract, the storage of this contract is serialized. So it is stored as a sequence of bytes in a compact way. And whenever you call the contract, this sequence of bytes needs to be deserialized to make it in the form that is convenient to manipulate. So deserializing is taking this packed byte sequence and then converting it into a format that's really easy to use and manipulate, that is typed, etc., where we can efficiently access the data. But once the entry point is over, the new content of the storage has to be serialized again. until the next call of the smart contract. So convert it again to a simple sequence of bytes. And this is done to save memory and make it possible to store this data on disk in an efficient manner. But deserializing the storage at the beginning of every smart contract call and reserializing it consumes CPU. There's quite a few computations that you need to do to deserialize and reserialize. So as the size of your storage gets bigger, you increase the amount of CPU that you're using to call this smart contract. And we cannot use an infinite amount of CPU for calling a smart contract. We need every node to be able to run it, so it has to be fast enough. And there's only so much computation we can reasonably do to execute all of the transactions in a given block. So to avoid abuse and transactions that take huge amount of CPU to be executed, we have a system called gas that is an estimation of the amount of CPU needed to execute a given transaction, a given smart contract calls, for example. We cannot know exactly how much CPU will be used because it really depends on what kind of computer you're running, what kind of microprocessor, etc. So this is why we need not the exact amount of CPU, but some estimation. That would be the amount of CPU that an average computer would spend to execute this transaction. So for every operation, every addition, every cryptographic operation that we can run in a smart contract, we have an estimation of how much CPU it will consume, and so we have a corresponding gas cost of this operation. So to limit the amount of computation that is done for a transaction and more generally for a block, we use a financial incentive by having the caller of this transaction pay for the spent gas. So as part of the fee they pay to the baker, they pay for the amount of gas needed to execute the transaction. And therefore, they pay for the CPU they will be using on all the nodes. And for each transaction, there's an upper limit of how much gas we can spend. And similarly, for each block, there's a limit on how much gas all of the transactions of the block can spend. So these limitations mean that if the storage of your smart contract gets too big, simply the fact that you need to deserialize and reserialize content before and after the execution of your smart contract means that you could reach this limit and the contract will fail. So if you do a smart contract call and deserializing all of the storage and reserializing it costs more in terms of gas than the maximum amount of gas you can spend in one transaction, then your call will fail and not be executed at all. We already discussed the fact that most types have no limits in terms of how much you can store. So we can store nats and ints that can be as large as you like. Timestamps can be as far in the future as you want. Strings don't have a specific length limits. And similarly, there is no hard-coded limit to how many entries you can store in a map. But in practice, there are two limits. The first one is that every time you increase the storage, so every time you add an entry to your map, you have to pay for that extra storage. And the second limit, again, is that if the storage gets too big, deserializing and reserializing it may exceed the gas limit. So for these two reasons, there's a limit to how many entries you can add in your map. This limit will depend on how big the keys and values are. And again, if this happens to you, your contract will be stuck. Any call will fail, and any funds you have in the contract may be stuck forever. To avoid the issue of exceeding the gas limits of a transaction due to having too much in your storage, we can use a data structure that is similar to map, and it's called big maps. Big maps are pretty much the same as maps, but with a few differences. When your storage contains a big map, instead of deserializing all of the content of the big map and reserializing it at the end of your call, we only deserialize and serialize individual entries in the big map that the contract call uses. So instead of having to deserialize the whole content of the big map, you only deserialize and reserialize the entries that you access to during your smart contract call. So this removes the limitation of how much you can put in a big map. As long as you only access a few entries within a single call of a smart contract, there is no limit on how many entries you can have in your big map. The syntax to use a big map is pretty much the same as a map, except that you will use sp.bigmap instead of sp.map. But many of the operations, like getting the length of the big map, getting the list of all the entries, the keys, the values, are not available for big maps. So that means if you want to get any information about the content of a big map, you have to know the key to the entries. You cannot list all the keys, you cannot enumerate them. All you can say is this key available in my big map, and what is the value for this key? This limitation only applies on-chain. As everything is public on a blockchain, outside of a smart contract, you can request information about a map from a node, and you can find out all of the entries in a big map. But on-chain, from within a smart contract, you cannot list all the entries. You can only request the entries that you already know the key for. So if we recap the syntax of a big map, to create a big map, instead of simply a pair of curly brackets, we have to use sp.bigmap. So this will create an empty big map. And if we want to have values, then the syntax is the same for a map. Curly brackets, the different entries separated with a comma, and for each entry, the key, colon, and the value. If we want to express the type of a big map, we write sp.bigmap, and between square brackets, the type of the key, comma, the type of the value. So very similar to a map, except we add big map here. Accessing, deleting entries, etc. is done exactly the same as for maps, no difference. But getting the size of the big map, getting the list of entries, the keys and values is simply not available, because that would require deserializing the whole big map, which defeats the purpose of using big maps. Let's take an example. So far, our endless wall was using a string to store all of the content. So it was not really endless. If the string got too long, eventually it would be too big to be deserialized within a single call. It would use too much gas just to deserialize the content of our string. So with a big map, we can fix this. Instead of storing a long string, we can store a big map of records. So in our big map, the key would be, for example, the address of the sender, so who is writing on the wall, and the value would be a record that contains the message, a string, and the date, a timestamp. So let's take a look at the contract. We have this truly endless wall contract, and in storage, we have a messages attribute that we initialize with an empty big map. We then indicate what the type of this big map is by using sp.cast, the attribute, and then the type. So sp.bigmap, and in between square brackets, the type of the key, an address. So that would be the address of the user who sends the message. And then the value, a record that contains the content of the message, the text, so a string, but also the date of the last message, a timestamp. In the write message entry point, we have a text parameter, so that's a message that the user wants to write. We create a data that contains the record we would add if this is a new entry, so with the content of the text and the current date. But then we check if our big map already contains an entry for this sender, then instead of using this new record, we fetch the current data we have for the sender, and then we add the new text after a comma, and we update the timestamp to the current time. Finally, we write the data in the big map at the address of the sender. So this will create a new entry if there is none, and it will update the existing entry if there was already one. Note that this is necessary in both cases, so even if we got the existing entry and modified it, this wouldn't be sufficient to actually write the new entry to memory. We always have to have this instruction to write back the data in the big map. So we're not manipulating a reference to some data in the big map. We have to explicitly write again and overwrite the content of this entry. So we have this small test where we simply write a couple messages using Bob's address. And so we can see that initially we have this empty big map. Then after the first call, we have an entry for this key that's Bob's address. And we have his first message and some timestamp, 0. And then after another call, then we see that we updated the text with an extra message. So here we have used a new syntax that we need to introduce, the if and if-else syntax. That's the typical Python if and if-else syntax. So you can write if this condition, colon, and then you have a block of code that you will execute only if this condition is true. And if you want to have an alternative piece of code, you can write if the condition, colon, and then the block, indented block, where you put the code to execute if the condition is true. And then at the same indentation level as the if, we can do else, colon, and then we put here the code that we execute if the condition is not true. We don't use a lot of conditional instructions in smart contracts, so you won't see a lot of if and else, but once in a while it's necessary. Okay, so now it's your turn to work on an exercise. You will create a smart contract that is able to handle multiple NFTs. The approach we used so far to have one contract for each NFT is really not ideal. It can be unnecessarily costly to deploy one contract for each NFT you want to mint. And it also makes it pretty hard to keep track of all the NFTs. So it's a lot better to have a smart contract that can store many NFTs and, for example, a whole collection of NFTs. So pause the video and think about how you would do that, and don't hesitate to start writing the code. So if we want to handle multiple NFTs, we can store all of their content in a big map. Now that we know that, we have to think, okay, what should be the key and what should be the value for this big map? And so we have to think again about what an NFT is. It needs a unique identifier, it needs an owner, some metadata, and a way to transfer or sell it. And in this situation, we will need to be able to create new NFTs within our contract. So we will need a mint entry point to create new NFTs. So if that helps you, pause the video and try to continue working on your contract. If we think more precisely about what we need to have in our storage, we have to think about what we will use as a unique identifier for each NFT. This time the contract address won't be sufficient anymore. It is still necessary so that you cannot simply write a separate contract with NFTs that have the same ideas of our contract. So the address of the contract will be part of the uniqueness of each NFT, but we will need something extra to differentiate between the NFTs that are stored in the same contract. To do that, we can simply assign each NFT in our contract with a number. So we can just start with 1 for the first NFT, 2 for the second, etc. It's really that simple, as long as these numbers are unique. So we can store a NAT that starts at 1, and every time we mint a new NFT, we increment it by 1. So this gives a number for each of our NFT, and we can use it as a key for the big map that will store all the information about our NFTs. Again, if that helps you, please pause the video and continue to work on the code. If not, we can continue with some help. So let's look at the code structure of this new smart contract. In the storage, we want to keep this counter, this next idea that we will use as the value for the key for the next NFT we want to mint. And everything else can be stored in a big map that stores all the information about the NFTs we mint. The key would be this token ID, so the value of the counter that starts with 1 for the first NFT, then 2, etc. And then in the value, we have all of the data associated with this NFT. So we will have a record that contains the owner of this NFT, the current owner, the original author of the NFT, as this is the type of NFT where we still want to pay royalties and increase the price by 10% every time we sell it. Then we have the metadata and the current price. Then we need 2 entry points. One entry point to mint a new NFT where we pass the metadata. So this will create a new entry in the tokens big map with as key the current value of next idea. We can set the owner and the author to the address of the caller. We can set metadata to the value of the parameters and to mint. And then we can initialize price to 1 Tez. Finally, we need to increment next ID so that we have a new idea for the next token that will be minted. Then we need the buy entry point for someone to buy a given token. And so this time we pass a parameter that is the number of the NFT we want to purchase, so it's token ID. First, we can check that this token exists in our big map. Then we can check that the amount sent by the buyer is equal to the token's price. Then we can send 5% of the price to the author, then send the rest to the current owner. Finally, we can replace owner with the new owner, and then we can increase the price by 10%. Let's take a look at the contract. In the storage, we have this counter next ID that we initialize to 1. And then we have the tokens big map that we initialize with an empty big map. You will notice that we don't add a cast instruction to specify what the type of the big map with the type of the key and the type of value. We will use type inference and let it determine those types. In the mint entry point, we use cast to indicate what the type of the metadata is, because all we do is store it, so there's no way in the contract to determine what its type is. So we say this is going to be a string. Then we use the current value of next ID as a key to the new entry we put in our tokens big map. And we store a record that will contain the metadata, a price initialized at 1 Tez, the owner and the author that are the address of the sender. Finally, we increment next ID to have it ready for the next NFT. In the buy entry point, we need to take as parameter the token ID that we want to buy. We check that there is such a token. We fetch the data from the big map. Then we check that the amount sent was indeed the current price. We compute the fee that we have to send to the author. We send everything but that fee to the current owner, and then we send that fee to the author. Finally, we update the address of the owner to this address, and we compute the new price. And that's it. Here we have a very basic test that only runs a call to each entry point. And we can see the content of the storage. So next ID is set to 1. We have this empty big map initially. After the first mint, we can see that in the tokens big map, we have this entry with the key 1, the address of the author, the metadata, the owner, and the price. And then when we buy it, we can see that the owner hasn't changed. And the reason why the owner hasn't changed is that we have forgotten to rewrite the content of the token into the big map. So it's very important here to add self.data.tokens of token idea equals token. Otherwise, all these changes are simply ignored. So if we run it again, this time we can see that the owner goes from TZ1H4 to TZ1HJ. So it has indeed been bought by Bob, and we can see that the price has changed. Of course, it would be good to do a lot more tests to make sure that the contract is good. But keep in mind that passing all the tests and as carefully as you can write your test doesn't mean that there is no bug in your contract. And here in this contract, we have a big flaw that you should be able to recognize that probably wouldn't have been noticed even by extensive tests. Pause the video, take a look at the code, and see if you can find the flaw. And here the flaw is one that we have already mentioned before. When we have those two lines, the author could be a contract that has a default entry point that fails, and this would prevent the sale. So the author of the contract could use this as a way to extort funds from the current owner. Now, how can we fix this flaw? Pause the video and try to change the contract so that it doesn't have this flaw anymore. One idea that you could have is that since the cause of the flaw is that authors can be smart contracts, we could try preventing people from minting their NFTs through a contract. So basically in the mint entry point, you could say, okay, let's check if the sender is a regular user or a smart contract. And there's multiple ways to do it, like comparing the address of the user to the smallest possible address of a smart contract, for example, and other ways. So it is possible in practice, but I really don't recommend it. And the reason is that you don't want to write smart contracts that can only be used by regular users and couldn't be used by other contracts. You really want to be able to benefit from all the potential users of your contract. And as a user, it's really convenient to be able to call your contracts through some other contract. It could be a joint account like we presented earlier, or it could be a multisig that multiple people can control collectively. And the idea is that contracts should be bricks that can interact each other. So if you limit the authors of your NFTs to regular users, you will prevent many useful use cases. So I really don't recommend differentiating between regular users and smart contracts, even though it's possible, and it would indeed prevent this issue. There's a much better way to prevent the issue, but this will require an extra big map. Pause the video, think about it, and try to implement this fix. So the solution is to avoid sending tests directly to the author in the buy entry point. And instead, as we have done before, we let the author claim their own test through a claim entry point. The difference here is that we need to keep track of many different authors and store how much each author is being owed by the contract. So for that, we will create a new big map in the contract that we will call ledger, and it will have as key the address of a user, and the value will be the amount that the contract owes to that user. And so whenever the user calls the claim entry point, we check this ledger. If there's an entry for them, we just send them that amount, and then we delete the entry. Let's take a look at the modified contract. So here in the constructor, we add this new big map, the ledger. The mint entry point doesn't need to be changed at all. So it's only in the buy entry point. Instead of directly sending the author fee to the author, we check if there's already an entry in the ledger. If not, we create one with 0 tes, so we don't owe anything yet to them. Then we add the fee to their entry in the ledger. And that's it. That's all we need to change. Instead of sending tes directly to the author, we add an entry in the ledger. And then we add this claim entry point, where we check if there's an entry for the caller of this entry point in the ledger big map. If not, we just cause an error saying we don't owe any tes to that user. Then we send the amount stored in the ledger to that user. And to say that we don't owe anything anymore, we simply delete the entry in the ledger. So if we run a simple test, we mint an NFT, somebody buys an NFT, and then the author can claim the tes, and they're being transferred their 5% of the sale. All good. So with these big maps, we can start creating really powerful contracts that store data for all kinds of users. In this module, you will learn the basics of Michelson, the low-level language that all high-level languages on Tezos Layer 1 compile to. And this will give you a deeper understanding of what happens behind the scenes when you execute a smart contract. All of the Tezos Layer 1 smart contract languages generate Michelson. They make it easier for you to write smart contracts, but the actual smart contracts that you execute are in the Michelson language. It's a low-level smart contract language that was designed specifically for Tezos. You can think of it as the assembly language for the Tezos Layer 1 blockchain. As a low-level language, it doesn't have any variables. Everything is based on the use of a stack. But even though it's low-level, it offers quite a few features. In particular, it has a static type system with a number of basic types such as int, nat, tes, string, etc. It has built-in data structures such as pairs, lists, maps, sets, or big maps. And it has an API for you to access to the Tezos protocol, such as cryptographic curves, transactions, etc. It benefits from a number of design choices that reduce the risk of bugs. So as we said, Michelson is a stack language. At any time, it has access to a number of values organized like a stack of plates, where each plate contains a value. Most of the Michelson instructions affect a number of values at the top of the stack. There are some instructions that can reach beyond the top of the stack, but they always express the location of the elements they read relative to the top of the stack. So to give you a quick idea of how this stack works, if you want to compute 3 plus 4 times 5, we write this piece of Michelson code. First, we push elements on the stack. So we push 3 at the top of the stack, then 4 becomes the new top of the stack with 3 below it. And then we put 5 at the top. So in the stack we have 3, then 4, then 5. Then we execute the multiplication operation, mul. It will consume the top 2 elements, 4 and 5, compute their product, 20, and then put it at the top of the stack. So after mul, we end up with 3 at the bottom of the stack, and then 20 at the top of the stack. Then we can use the add instruction that will add those 2 values, remove them from the stack, and instead put the result. So we get rid of 20 and 3, and we add 23 instead in the stack. We'll see more examples of that. The hardest aspect when you write Michelson code is to keep track of the content of the stack after each instruction, and we will use commands and tools to help us with that. Let's take a look at a few instructions from the Michelson language. We won't see them all in this module. We will focus on the ones that manipulate the stack or allow you to do some arithmetic operations so that we can practice a little bit manipulating the stack. The first instruction is an instruction to put something on the stack. So we use the word push, then the type, for example, int, nat, tez, string, etc., then the value. So if you want to put the integer 5 at the top of the stack, you write push int 5. Next instruction is an instruction to duplicate whatever is at the top of the stack. For example, if you have 3 at the bottom of the stack and then 5 at the top of the stack, and you call dup, then you end up with 3, 5, and another 5 at the top of the stack. The drop instruction simply gets rid of the top element of the stack. So if we had 3, 5, 5, we end up with 3 and 5 in the stack. We say that it consumes the top element of the stack. The dig instruction is an instruction to move things around within the stack. So you indicate a position related to the top of the stack, and it will move that element to the top of the stack. So if you have 5, 5, 3, and we do dig 2, it will take the third element from the top and bring it to the top. So we end up with 5 at the bottom, 5 in the middle, and then 3 at the top. We took the 3 from the bottom, we brought it back to the top. The arithmetic operations consume elements from the top of the stack. They remove them and then put the result back at the top. So the add instruction takes the top 2 elements in the stack, consumes them, so remove them from the stack and put the result back at the top of the stack. If we have, let's say, 3, 5, 3, then we take the 3 and 5 from the top, add them to get 8, and then we end up with 3 at the bottom and 8 at the top. For the product, we use mul that takes the 2 elements, consumes them, puts the result of the multiplication at the top of the stack. In Michelson, we have pairs. So a pair is a value that contains 2 other values of any type. And we use pairs a lot in Michelson. So if you have a pair in your stack and you want to unpair them so that you get the 2 values as separate elements at different levels of the stack, then you can use unpair. If you want to do the opposite, take 2 elements and then pair them to replace them with a single element that contains them both as a pair, you simply use the pair instruction. Finally, you will see that even basic contracts will need to push an empty list of elements of a given type in the stack. And for that, we use the instruction nil, and then we indicate the type that we want to put on the stack. When you think about what a Michelson contract does, you really have to think about its input and its output, because it's really all it does. Take some input and compute some output. A Michelson contract starts with a stack that contains only a single value, and this value is a pair that contains 2 elements: the parameter of the contract that you pass when you call the contract, and the current value of the storage. So it can read those values, and it also has access to some special values like the balance of the contract, the address of the sender, so whoever called the contract, the timestamp of the block that contains the current transaction this smart contract call belongs to, and the amount that was sent by the caller to the contract, etc. It can also access a table of constants that all smart contracts have access to. And finally, it can obtain values from other smart contracts using on-chain views. But that's all it can read. In particular, it cannot read the storage of other smart contracts or any outside information. It can only read its own storage special values, and then call on-chain views from other contracts to obtain information from them. And as the output, the contract will produce a single element in the resulting stack. And this single value will be a pair of two elements. The first one will be a list of operations to execute after the execution of your smart contract. Your smart contract itself doesn't directly execute operations. If your contract needs to transfer a few tests to an address, what it will do is generate an operation and add it to this list of operations that will be executed once its own execution is over. The second value of the pair is the new value of the storage. So you rewrite the whole new value of the storage. That will replace the one you obtained at the beginning, with an exception for the way we handle big maps, where you can write values individually. So it's important to keep in mind that a smart contract doesn't have any effects other than computing this pair and updating values in big maps. So let's take a look at an example. This is a very basic smart contract in Michelson that takes as a parameter a pair of integers, a and b. And all it will do is compute the expression 2b plus a, and then put this value in the storage. So here we can see the description of the type of the parameter. So the parameter is a pair with two integers. The first one we add an annotation to say that it's named a, and the second one is named b. The storage only contains an integer. We will put the result of the last computation in it. And then we can see that the code is put with the keyword code and then a pair of curly brackets. And then we have the sequence of instructions, one per line, separated with semicolons. So we start by unpairing the value that we have on the stack at the beginning, so the storage and the parameter. So then we have the parameter at the top of the stack and the storage at the bottom. Then we unpair the top of the stack, so the parameter, and we get a and b. We use dig2 to go get the storage back from the two levels below the top back to the top. Then we drop it, we get rid of that element because we don't need the previous value of the storage. We'll replace it with the result of the computation anyway. Then we call dig1 that will get the b, bring it to the top. So we basically swap the top two elements of the stack. Then we push the integer 2 at the top of the stack. We'll multiply it with the second element. So we do 2 times b and we get 2b at the top of the stack. We consume those two elements. Then we call add to add these two elements and replace them with a result. So we get a single integer that's worth 2b plus a. Then, since we need to end up with a list of operation and the new value of the storage, we need to create an empty list of operations. So a nil operation is an instruction that will generate this empty list of operations. And then we pair them so that we end up with a pair that has this empty list of operations, then the new value of the storage. You will notice that we made good use of the comments to keep track of what was in the stack at any time. Remember that the hardest part when you write code in Michelson is to keep track of what's in the stack. So in each comment we write, what do we have on the stack after we execute this instruction? So it's a good practice to put a comment for every line to describe what's in the stack after the execution of this instruction. And then I recommend putting the bottom of the stack on the left and the top of the stack on the right. This way, when the bottom doesn't change, we can see that it's exactly the same and the changes are always on the right. So it's easy to just align the left so that the bottom of the stack doesn't move and only the top of the stack is changed. For example, between this instruction and this instruction, we can clearly that the only change is to add 2 at the top of the stack. If we use VS Code with the Michelson extensions, we can have syntax highlighting, but much better than that, we can see that anytime we select an instruction, on the right side, the first extension will show us what is the current content of the stack, and what it is before we execute this instruction, and what it is after we execute this instruction. So we can see that before we execute the first instruction, we only have one element in the stack, and it's a pair that contains the parameter, itself a pair of two values a and b, and the storage. And we can see that after we execute unpair, we have two values in the stack. So at the bottom we have the storage, an int, and then at the top of the stack we have the parameter or pair ab. And if I click here, then I can see that before I have the 2 integers and the storage, and after I execute drop, I only have the 2 elements, and that's it. So it's very inconvenient to check that the type of what we have in the stack at any moment is what we expect. The second extension allows us to debug Michelson code. So I can click here to execute this code, run and debug. It will ask me the value of the contract parameter. So here, this is a pair, so I write it between curly brackets. And for example, I will write 1 for A and 10 for B. So that's my input parameter. Then it asks me for the value of the storage of type int. So I don't need the storage, I'm not using it in this contract. So I'll just keep it at 0. Then I can debug line by line. And on the left side, I will see the content of the stack. So I can use this to run my code step by step. So I can see that I will unpair this value that contains my parameter and the storage. So I can see that at the bottom of the stack, I have my storage 0, and at the top, I have my pair 1 and 10. We can see that the pair here is represented differently from the syntax I use for input. For the input, I used curly brackets with a semicolon in between. Here it is represented using a pair of parentheses and then a comma in between. So be careful not to mix up the two, but they both represent the same pair. If I unpair this top element in the stack, 110, then I will get 1 at the top, and then 10, and then 0 at the bottom of the stack. Now I execute dig2, so I get the second element from the top of the stack and then bring it back to the top. So we see 0 is now at the top. Then I drop the top element of the stack. Then I do dig1, so I get the element at one position from the top, bring it back to the top. Then I push the value 2. Then I multiply the top 2 elements, so I consume 2 and 10, multiply them to get 20, and then push 20 at the top of the stack. Then I add those two, 20 plus 1, I put 21 back on the stack. Then I generate this empty list of operations that we have here. Here it just shows it as a pair of square brackets, but here we can see that it's indeed a list of operations. And then finally, I can pair them to get the end result. So a pair containing a list of operations to execute after the smart contract and the new value to put in the storage of the smart contract. And that's it. So there's a couple things you need to be careful about when you write your smart contract. The first one is when you debug your smart contract. If at one point you realize you want to make a change to your contract, for example, here you actually wanted to push 3 instead of 2, you should be careful, because when you get to this instruction, we will see that it actually pushed 2 on the stack because it's still running the previous version of the code. The changes you make while you debug don't affect your current debugging session. So that means anytime you want to make a change to your contract, you need to make sure you stop debugging and then start debugging again. Otherwise, it can be really confusing because what you see doesn't correspond to what code you have there, and you can spend a lot of time trying to understand what's going on. Why do I have this result? It doesn't really correspond to what I wanted to do, etc. And that's because you're not actually running the code you see. So always make sure you stop it, run it again, and of course then, when you execute it, you can see that we indeed push 3. Of course here, we really wanted to push 2. Another situation you can run into is when you, for example, add an extra instruction here. You can see that everything is in red, and it tells us that we have a type check error. It doesn't really help us with anything. It just says what we have at the end is not right. It's just not helping us. And that's because since I added an instruction, what I end up at the end on my stack is of the wrong type. I get 2 elements instead of 1, and that really confuses the type checking. And it doesn't help us understand what's going on. It just says type check error. And if you don't remember that you just added this instruction, it can be pretty hard to figure out what is wrong. So there's a trick that you can use to do that, which is to add a fail instruction at the end. And this way, the type checking always works, because a contract that fails doesn't have to return anything in the stack. It just fails, and it's always of the right type. This way, you can check every instruction and see, okay, what do I have in my stack? Is that what I wanted, etc.? And then when you get here, you can see, oh, actually I have one too many elements. This doesn't correspond to what I have, etc. So you can fix the bug. And then once you're good, you can remove this extra fail instruction. So that's a good trick when you're confused and everything is red and you don't know what to do. You'll notice that we put annotations here for each element that we have in the parameter, and that's something you can do to help you better understand what's in the stack. So here we can see that we have this information that this integer is actually A. So basically this annotation was propagated all the way to this position. But as soon as you do the computations, what you end up doesn't have any annotation. It doesn't tell you that this is actually 2b. It just tells you that it's an int. So this can be helpful, but very quickly you don't really benefit from it anymore. So it's much better to use comments that really describe what we have on the stack. One thing you may wonder is, why do I need to learn Michelson? I write just fine in my high-level language, and I can write smart contracts without knowing Michelson. So why do I need to learn Michelson? We teach you a little bit of Michelson because it can be quite useful in a few situations. So for once, deployed contracts that you can check with your block explorers are in Michelson. So if you want to read a contract that has already been deployed and that you want to use, you have to read the Michelson code. That's the only thing that's always available. Sometimes authors make the original smart contract in the high-level language available to you, but not always. So it's good to be able to read the contract. Another thing is that while you write your smart contract, sometimes you want to make sure you understand what's really going on behind the scenes. Is it generating a lot of computation, or is it something very simple even in a low-level language? So it can be a good idea to once in a while look at the Michelson code generated by your high-level language compiler and understand what really happens behind the scenes. Another time where you will need to understand some Michelson is that sometimes you can have compiler errors that are actually expressed in Michelson. It's often type errors. So it's important to have some basic idea of what Michelson is to help you understand these errors. More generally, it's good to have a deep understanding of what's going on behind the scenes. You don't need to be an expert in Michelson, but it's good to know the basics. I advise you to take the habit of reading the Michelson version of contracts you write. Little by little, you will get used to at least reading Michelson code and understanding. It's not too hard to understand. Again, the hardest part is to keep track on what's in the stack after each instruction. As an exercise, you will write your own Michelson smart contract that does some arithmetics. So write a contract that takes a pair of integers, a and b, as a parameter, just like we did in our example, but then this time computes a times 2b plus 3a, and again puts the result back in the storage. Pause the video and give it a try. Let's take a look at the solution. So here we have our contract that takes a and b as a parameter with a storage of type int. So we start by unpairing our storage and parameter, unpairing our two values a and b. Then we get rid of the storage because we won't need it. Then this time we will need to duplicate a, because in our final expression, a times 2b plus 3a, we need a twice. So we duplicate a so that we can make use of it twice. That's something we often need to do in a stack-based language. So now we want to compute 2b. So we dig 2's to obtain b at the top of the stack. Then we push the value 2 and we multiply them to obtain 2b. Now we want to compute 3a, so we dig 1 to get a back to the top. We push 3, we multiply them to get 3a at the top of the stack. Then we want to compute this expression, 2b plus 3a, so we add those two values to get 2b plus 3a at the top of the stack. Then all we have left to compute the final expression is to multiply a with this value 2 plus 3a. So we have our result here, but now we need to add an empty list of operations on the stack. So we call nil operation to add this empty list of operation. We see here that we have indeed a list of operations in the stack, and then the new value of our storage. We pair them and we get the results in the stack. We can give it a try. We can use 1 for A, 10 for B, 0 for the storage. And so we compute, let's compute a few things. So let's see here, after doing the addition, we still have A equals 1 at the bottom, then we have 2B, so that's 20, plus 3A, that's 3, so we get 23 at the top of the stack. Then we multiply that by A, so by 1, and we get 23, and we compute, we have the empty list and 23. If I run it again, but this time with 2 and 10, then I can execute it. So I should get 3 times 2, so that's 6, plus 20 times 2, so that's 26 times 2, 52, which is correct. All good. In this module, you will learn how to install SmartPy in your own environment, which is what we recommend when you start creating contracts for your real projects. The installation procedure of SmartPy is very straightforward. All you need is Python 3 and pip, which is the tool to install modules for Python 3. There's one exception. If you use a Mac and have an Intel processor, you will also need to install Docker. We'll refer you to the corresponding documentation of these tools to install them. If you want to find the latest installation procedure, you can go to smartpy.io, and in the manual, in the installation section, you will find the commands. The version we will use for this demo is a version that's not officially released yet, but that you can find here. So if you go to the corresponding website, you can go in the manual, installation, and here you find the installation procedure where you have one command that you should run. And that's all you need to install SmartPy, as long as you have the prerequisite Python, pip, and maybe Docker. For our demo, we will do this in the Gitpen environment we prepared, and you can try it yourself in the same environment if you don't want to install it on your own computer. So we'll create a new workspace with this environment where we don't have anything specific to SmartPy installed yet. So you may need to create a gitpod.io account using your GitLab or GitHub authentication if you don't already have a Gitpod account. Then it asks you to create a new workspace, which we will do. It may take a couple minutes. Make sure you have the tab open in your browser with the focus so that it doesn't take too long. So once your Gitpod environment is running, I'll zoom a little bit, but all you do is go copy the command line provided in the SmartPy manual. So we copy this line. We paste it here. It may ask you if you authorize pasting content on Gitpod. So of course you need to authorize. And then you simply execute this command. It downloads everything needed and everything is ready. Now you create a folder. So we'll test our endless wall contract. So I'll create an endless wall folder. And I'll open the VS Code editor where I will put my contract file, but you can use any editor you like. Your contract file should have the py extension. And I will paste the content of our contract. Once you've done that, all you need to do is run python contract.py. I forgot to save. Control S. Run it again. All good. And we see here that it created the test folder with a lot of files. So we'll go through them to understand what just happened. So all you need to do to run a contract and its scenarios is simply to run Python and then your contract. And this will produce a folder for each of the test scenarios you have in your contract. And in each folder, you will have a number of files. You would have the main file, which is log.txt, that will contain all of the steps of the execution. And you will have files for each contract origination with the content of the contract in Michelson, the content of the initial storage. And you will also have files for each call to an entry point. We can see here with the names, those are the files for the contract, for the initial storage, the type of the storage and parameter, etc. And then for each step, we have the files for the parameters of the entry point calls. So if we look more precisely at the content of the log.txt file, it will contain sections for every step of the execution of your scenario. You will have the contract origination with the initial storage of your contract. And you will have an entry for each call to an entry point with the parameter and the resulting new value of the storage. You will also find the comments produced by calls to the scenario.h1, etc. And you will also see lines for calls to scenario.verify, where it will show what condition checked and what the result is. The output of calls to sp.trace that you use for debugging are not visible in log.txt, but they are directly displayed in your terminal as the error output. So here we can see the content of some sp.trace that we added here. So we can see that it's displayed directly in the terminal. And then if we open the log.txt file, we can see the origination of the contract. So our contract simply contains a big map. So here we can see the initial content of the big map, it's empty. Then it will list all the different files with the storage, the types, and the contract. So for the storage, we can see the content either expressed in SmartPy or in Michelson or the Michelson version, so the JSON version of Michelson here. We can see the types of the storage, the parameter, private, and views directly in SmartPy. And you can see the contract itself either in the Michelson JSON representation or directly in Michelson as a .tz file. So you can see what the Michelson code that you generate looks like, and you can see that after every instruction, it shows the content of the stack after the execution of this instruction, with the top element of the stack on the left. So for example here, after unpairing the content, we have the parameter and the storage, and after running now, we have now at the top of the stack. For each section, you can see the corresponding SmartPy code. So you can follow what part of the code corresponds to what part of your SmartPy code. That can be quite useful if you want to understand what your code really generates on-chain. So to recap, for each contract origination, you will have the files with the initial storage in different formats, the file containing the different types in the SmartPy format, and files with the compiled Michelson contract both in the TZ and JSON format. Then for each smart contract that you call, some files will be produced. They will contain the content of the parameter, both in the TZ, JSON, and SmartPy formats. So we can take a look here for a call. We can see that the call had one parameter that was a string with Bob's message. Here we simply have the string, and same here in the Michelson format. So we can see here in the log.txt, we originate the contract, we see the corresponding initial value of the storage. Here we can see the output of a call to scenario.h1. Here we can see that we call write message with the parameter. And we can see here the new value of the storage. So the content of the big map with the key here, which is Bob's address, and then the corresponding entry. And then we make another call, so we can see that the content of the storage changed for the key that is Bob's address. And then finally, when we make a call to send a message as Alice, we see that we have another key in the big map with Alice message. And finally, you can see here when we verify, so if we check our contract here, we have a verification that the timestamp for Bob's message is 0, because we didn't specify any other timestamp. In the log.txt file, we can see this verification with the corresponding condition and the result. So there's everything you need there to check that everything goes well and to look in detail what happened during the execution of your scenario. And remember that for each scenario, you will have a similar folder, so you can organize your test very nicely. Okay, now it's your turn to give it a try and run SmartPy locally. So what you should do is simply reproduce the demo, but with your own smart contract. So you install SmartPy in your own environment. You execute your own smart contract. You can take the one from the previous exercise. Make sure you include contract calls, verifications, comments, and calls to trace to see what happens in each case. And if you have trouble for some reason to install SmartPy in your own environment, on your own machine, you can test all this using our Gitpod environment at this address. So pause the video and give it a try. In this module, we'll talk about dApps, decentralized applications, and what it means to develop your own DApp. A DApp is an application that is built on top of one or more smart contracts. It stands for decentralized application, but it is a regular application with or without a user interface that may interact with smart contracts, but also a wallet, one or more nodes, indexers, decentralized file systems like IPFS, and sometimes a regular backend. But you have to be careful. In spite of their name, decentralized applications, only the smart contract part of a DApp is always decentralized. The interaction with different tools are made available through libraries, and depending on the type of front-end or backend you use, you may use different libraries. On Tezos, we usually use Taquito for web-based dApps. We may also use PyTezos for Python-based dApps, or we can use the Unity SDK for Tezos for dApps that can work on the web, desktop, and mobile using the same code base, and that is particularly useful for games that you develop using the Unity SDK. And there are more such libraries for other languages and platforms. There are also tools like Factory or Complicium that can help you by analyzing contracts and generating bindings and make it easier to develop and debug your dApps. The main capabilities of these libraries are the same, but they run on different platforms and with different ease of use. A key aspect of dApps is their interaction with wallets. The role of the wallet is to allow dApps to interact with smart contracts while providing security for the end user. It keeps the private keys of the end user safe, and it gives them the opportunity to check the transactions before those transactions are sent by the dApp to the node. So the dApp interacts with the wallet at different steps. First, it uses the wallet for the user to authenticate on the dApp. Then it uses the wallet to simulate transactions and check how much the fees will be, the fees to pay to the baker, and the amounts to burn for the storage. Then the wallet is used to sign and emit the transactions, send them to the blockchain. But it can also be used to sign other types of messages or to verify signatures from other users. We use a standard protocol, Beacon, to interact between dApps and wallets, so that you don't have to write code specific to each wallet in your dApps. And connection between the dApps and wallet can be done either through a QR code or through a deep link. dApps can also communicate with nodes, either through the wallet or directly. They do so to obtain information about a given block, for example, its level, its timestamp, the transactions it contains, etc. They can read the balance of an account or a smart contract directly from a node, or they can read the storage of a smart contract. And they can also execute views and obtain other kinds of data. These interactions are done through RPC calls directly to the node. All of the data is available through the nodes, but only block by block. And it's not very convenient to access the data this way. So to make it easier, we use what we call indexers. The role of indexers is to fetch data from the node block by block as the blocks arrive, and then make it easily available to the dApps. So you have APIs to find accounts, contracts, and operations based on many different types of criteria. And you can also obtain aggregated or sorted data. And more generally, you can access data in more digestible formats, in particular for standardized tokens. And the access to data is much faster than if you try to access directly through a node. A good way to get an idea of what is available through an indexer is to look at block explorers. Because behind each block explorer, such as Better Call Dev, TZKT, or TZStat, there is a corresponding indexer that stores all that data and makes it easily available. So typically the work of an indexer is to keep track of new blocks, fetch all of the data, store that data in a relational database with indexes to allow for good access performance, and then reply to simple or complex queries through a REST API. There are a number of public indexers that are available for Tezos, such as tzkt or tzstats, but you can also install your own local copy of these indexers. But keep in mind that they use significant resources because they have to index all of the data from the blockchain. A more lightweight approach consists in using selective or custom indexers that only index the data you really need for your DApp. There are tools like DeepDApp or Dappetizer that make it easy for you to create your own selective or custom indexer. Blockchains, and in particular layer 1s, are not good for storing data in large quantities because every single node on the blockchain stores everything. So the storage on a layer 1 is expensive. In practice, when possible, we only store a hash of the data in the smart contract. We only store the data itself in the smart contract if the smart contract needs to directly interact with the data. But even though you don't store all of the data in the contract itself, it's important to make sure that the data is available in a decentralized manner. So decentralized file systems play this role of storing this data and make it available to everyone. IPFS is currently the most used such decentralized file system. It stands for Interplanetary File System. It consists of a protocol for organizing and transferring data through a peer-to-peer network. And IPFS also represents a number of implementations of this protocol and a decentralized network based on this protocol. On IPFS, or any similar tool, any file is identified by its hash. That has multiple advantages because it guarantees that the content has not been tampered with. You can check that it matches the hash. And even if at some point the content is lost by your system, if some content is not available on IPFS anymore, anyone can add it back. And since it's identified by this hash, as long as the content matches this hash, then you can add it back. And you have to be careful because nodes of IPFS are free to decide what data they store. Just because you put some data on IPFS at some point doesn't mean it stays there forever. So it doesn't guarantee that I have availability. If you want to make sure some content stays available, you can use pinning services that take care of that for a fee. To recap, a DApp is an application that is built on top of one or more smart contracts, and you have to see it as a regular application that may or may not have a user interface and that may interact with smart contracts, with a wallet, with a node, with indexers, with decentralized file systems like IPFS, and maybe with a regular backend. So again, be very careful. In spite of the name, only the smart contract part of a DApp is always decentralized. The front end of a DApp is often hosted on a centralized server, and the dApps often interact with a centralized indexer. They also interact with a specific node or a specific set of nodes, and they often have a centralized backend. So when that's the case, only the smart contract part gets the benefits of decentralization. Furthermore, many smart contracts depend on a third party to make some calls. So you have to keep in mind that the technology makes decentralization possible, but it doesn't require it. So it's possible to write a DApp and smart contracts that are not fully decentralized. So many of the benefits of blockchains can be lost if you don't apply them correctly. You can take the example of what happened with FTX, for example, and see what could go wrong. But you also have to keep in mind that to attract users, you need to make it easy for them. So the hard part is to benefit from all of the aspects of decentralization while still making it easy for users to use. One of the barriers of entry of dApps for your final users is that to call any smart contract, they need to pay fees. And in order to pay a fee, that means you have to buy Tez, which implies doing a KYC, know your customer, prove your identity, etc., even if it's a very small fee. So this is a barrier for many users when starting to use your product, your DApp. So to make it easier, one possibility is for you to pay for your users' fees. Users can set up a wallet, but don't go through the KYC or obtain Tez. And that means instead of signing and paying the fees for a transaction, they can use their wallet to sign a message that will allow a transaction. But then they send this message to your server, and your server receives this message and calls a contract that will then receive the message and do the corresponding transaction. So this way, the users give their authorization by using their wallet to sign the message, but you're the one paying the fee on your server. So that's a method that you can use to make it easier for your users to start using your DApp. And there's a standard on Tezos on how to do that called TZIP17. One issue that can come up when you do DApp, and in particular when you use feeless transactions, comes from the fact that each transaction has to include a counter to avoid replays. But that means from a given address, you can only emit one transaction with one value of the counter per block. But some services, including in the case of feeless transactions, require sending many transactions per block. So to solve this issue, we have a system of batches of transactions. A batch of transactions can contain one or more transactions from the same account, and either all of the transactions in the batch are included and are successful, or they all fail. An issue is that the bigger your batch is, the higher the risk that the batch and all of its transactions will be rejected. So to manage your chances, you will have to split your transactions into several batches that you emit from multiple addresses for a given block. So that's one of the things that you may need to take into consideration when developing advanced dApps, and in particular if you use feeless transactions. So that gives you an overview of the kind of issues you have to deal with when developing dApps. In this module, you will learn how to make inter-contract calls, and this will open many interesting possibilities. The possibility for a contract to call another contract really expands the potential of smart contracts. You can create marketplace contracts that interact with NFT contracts, or DAO, decentralized autonomous organization contracts, that allow people to collectively own and trade assets through the interaction of the DAO contract with other contracts. You can also build decentralized finance contracts that build on top of one another, with lending contracts that allow you to invest in yield farming contracts, etc. Or you could create game contracts that interact with dynamic NFTs. There's really a lot you can build thanks to the possibility of contracts interacting with each other. But all this potential also opens up many potential flaws and risks associated with intercontract calls. For example, if you're not careful, it would be possible to trigger a contract on behalf of a user without them realizing that that contract is called in their name. And intercontract calls can in some cases give attackers access to potentially unlimited funds for their attacks. So when dealing with intercontract calls, it's important to be very careful about what you're doing, and we'll show some examples of that. The syntax of intercontract calls is pretty straightforward. If you have the address of a contract, you can use these two instructions to call an entry point of this contract. So first, you get a contract object by doing sp.contract, and then you have to pass three values. You pass the parameter type of the entry point you want to call, then the address of the contract that has this entry point, and finally the name of the entry point. And this returns an option on the contract because there may not be an entry point for the contract at this address with this parameter type. So since it's an option, if you know for sure that you pass the right argument, you can unwrap the option using unwrap sum and store the result in this contract variable. Once you have this contract variable, you can do the contract call by using sp.transfer, because calling a contract is also transferring some Tez to a contract. Then you pass the value of the parameter for the entry point. It should have the type that you provided here. You indicate how many Tez you want to send as you call this entry point, and you pass the object that you just obtained with the previous instruction. And this will create a transaction to call the entry point with this name from the contract at this address, and with this value as a parameter, setting along this amount of Tez. This transaction is queued in the list of transactions that you execute at the end of the execution of your current entry point. It is never called immediately. To test several contracts that interact each other, in your test you start by creating instances of your contract in the usual way by calling the constructor of each contract. Then you simply have to pass the address of one of the contracts to the other contract. For example, in an entry point call, or it could also be in one of the constructor parameters. So this makes the contract address available for the entry point to run these commands. Let's take an example. With contracts that can interact with other contracts, we could create a contract that serves as an intermediate between the user and another contract. And this adds a lot of new possibilities on how existing contracts can be used. So for example, if a contract has an owner, you could use an intermediate contract to change it to two owners. So if we take the case of an NFT, we can create an NFT joint account contract so that two people can jointly own the same NFT. So let's see how this would work. So we have this NFT for sale contract that represents a single NFT that can be bought and sold. In its storage, we have the current owner, we have its metadata, and we have its current price. Then we have our two entry points, one to buy this NFT at the current price, and one for the owner to set a new price for the NFT. And so the idea is that we can create this NFT joint account that will become the owner of one or more such NFTs. And then we will have two owners for this contract that will be jointly the owner of this contract and therefore both control the associated NFTs. And here, since it's a joint account, each owner has full power on the contract. So either one of them can either buy NFTs, set prices, etc. So for this contract to be able to buy and sell NFTs through this NFT for sale contract, we need the following entry points. The first one will be to buy an NFT. And so for that, we say which NFT we want, what's the address of the contract corresponding to the NFT we want to buy. And this entry point will call the buy entry point of the corresponding NFT, and then the contract will become the new owner for that NFT. Once it owns that NFT, either of the owner could call set NFT price, again indicating which NFT contract this will be, and then passing the new price, and this entry point will in turn call the set price entry point of that NFT contract. Finally, once someone buys the NFT, the funds will be sent back to the owner of the NFT for sale. So it will be sent to the default entry point of our NFT joint account contract. So we need to make sure we have a default entry point that accepts Tez. Otherwise, we would never be able to sell those NFTs. So if we look at our contract in more detail, so we have those two owners that are both addresses. In our buy NFT entry point, we first check that the caller is either owner 1 or owner 2. Then we simply call nft_address.buy with the amount that was sent to buy NFT, so sp.amount. Next, the set NFT price entry point checks again that the caller is either owner 1 or owner 2, and then simply calls the set price entry point of the NFT contract with the new price. Finally, if the default entry point is called, we do nothing. We simply accept the Tez. Let's take a look at the contract. So here in the same file, we can have our NFT for sale contract and our new NFT joint account contract. So the NFT for sale contract is one of the versions we used in the past that has a basic set price entry point that checks if the caller is the owner and then updates the price. And then the buy entry point check that the amount sent is the right amount, sends it to the owner, and then changes the owner. So now we have this NFT joint account contract that simply stores the two owners. And in the buy NFT entry point, we get the address of the NFT contract that we want to interact with. So keep in mind that this joint account could own many different contracts using many different addresses. So every time we want to interact with one of these NFT contracts, we just pass the address. But first, we check that the caller is either owner 1 or owner 2. And then we execute those two instructions I was showing before. So we get the by entry point of this address. Since the by entry point doesn't take any parameter, we have to say that the type of the parameter is nothing. And nothing can be expressed by the type unit. So we use sp.unit as the type when we have no parameter at all. And since it's an option, we need to unwrap it. We store it in this variable. Then we can call transfer. We pass the value of the parameter. So when we have no value to pass, the value for nothing for the type unit is expressed as a pair of parentheses with nothing in it. So that means sending no parameter in a way. But we need to put something here. So we have to put this pair of parentheses that represents the unit value, which means sending nothing. Then we pass the amount. So since we just buy the NFT, we just forward whatever amount was sent by the caller, so one of the two owners, to this entry point, and we just pass it along to the buy entry point of our NFT contract. And then we pass the contract object that we got from the previous line. And that's it. This simply calls the buy entry point of the contract at this address. Very similarly, for the set NFT price entry point, we check if it's the owner 1 or owner 2. Then we obtain the corresponding contract using the same thing. The main difference is that this time the name of the entry point is set price. And this time we have a parameter, the new price, that is of type new Tez. So we indicate this new price here. And again, we unwrap the option. Then we call sp.transfer. We pass the value of the parameter, so the new price that we got from this parameter. This time we don't pay, so we send 0 Tez to the set price entry point, and the contract is what we obtained from the previous instruction. When we test this contract, here we instantiate the two contracts, so one for the NFT, one for the joint account. We add them both to the scenario so that they can be both originated within the scenario. Then we call the set price entry point to set an initial price for this NFT so that we can buy that price. Then with the second contract, with our joint account, we call buy NFT and we give the address of the NFT contract. And we say, okay, Bob, who is one of the two owners of that joint account, is calling the buy NFT entry point and sending 7 Tez to buy this NFT, the NFT with this address that we just created. Then we can try to change the price from the NFT directly. So this won't work. Only the contract is allowed to change the price. And here we see that we try to use this joint account again, called by Eve. So Eve is one of the two owners of the joint account. And we try to buy it at 7 Tez, but this doesn't work. And the reason why this doesn't work is because we didn't add our default entry point yet. So if we want this to work and turn this to a true, we need to add the default entry point so that when somebody, even us, buy the NFT again, then we can receive the money. So we can add a default entry point. That doesn't do anything but pass. And now if we run it, then this time it works. So we basically bought the NFT from ourselves. Not very exciting, but this can only work if we have the default entry point. Then we call the set NFT price to change the price to 50 Tez. So we can see here that the new price has been set to 50 Tez here. If we show contract, we see here the new price, and here we verify that indeed the new price has been set to 50 Tez and that the address is indeed the address of the contract. So not a lot of tests, but this illustrates the different calls we can make and how we can have a joint account contract that can interact with an NFT contract. Unfortunately, this joint account contract has a big flaw. Can you find it and fix it? Take a good look at the contract and see if you can identify the flaw and find a way to fix it. Pause the video and give it a try. So the issue here is a situation that can be pretty sad once you realize what the flaw is. These two users who are the owners of that joint account could jointly buy and sell many NFTs for many years, accumulate funds by selling NFTs, selling them later for a higher price, and accumulating money on their joint account. But there's one small issue. It's the day they decide to retire and get the Tez out of the contract is the day they realize that they forgot to add a way to get the funds out. So it's very important to always remember to add an entry point to claim any profits. If the contract is meant to accumulate funds, make sure you have this way to get the funds out. Otherwise, all the funds you may accumulate all the time by the service your contract is providing will be lost and will be stuck in the contract forever. So the solution, of course, would simply be to add this claim entry point that either owner 1 and owner 2 can call. The idea here is that you have two addresses that you can use to do the same thing. It could be two people that trust each other, or the same person that has two different keys and one that's a safe key in case they lose the first one, for example. And after checking who is calling, all the entry point will have to do is send the balance of the contract to the caller. So it's very easy to fix. The problem is to make sure you don't forget to have this entry point in your smart contract. There's been real situations where people accumulated significant money and had no way to get them out. But now let's imagine you actually did this and you deployed this contract without the claim entry point. So you cannot change the contract itself once it's deployed, right? It is immutable. So the question is, can you find a way that you could still get your funds out of this contract? I mean, imagine that you have millions of Tez stuck in this contract. So you really have to try hard and see if there's any way that you can get those funds out. Pause the video and think about it. So again, assuming that you have millions of Tez stuck in this contract, how can you get them out? There's actually one way to change the contract once it's deployed, at least in theory. Can you tell what that way would be? Pause the video and take a minute to think about it. So this theoretical solution is that on Tezos, anything is possible thanks to on-chain governance. All you have to do to get your funds out is to propose a new amendment to the Tezos protocol. And you can make any changes you like in amendments. So you could propose an amendment that changes your contract so that you can get the Tez out. But the next step would be much harder. The next step would be to convince the community to vote for your new amendment and save you by letting you change your contract. So in theory, it is possible. In practice, unfortunately for you, this is extremely unlikely to succeed. That's because the whole point of a blockchain and of our smart contracts is that you should be able to trust that it won't be changed, that what is written in the contract is what will happen. So it would be really hard to convince the community to go against this principle just so that you can get your Tez out that got stuck there because of your own negligence. But really, you have millions of Tez stuck in your contract. Isn't there a way to get them out? So you can't change the contract. You can't convince the community to let you change the contract and add a claim entry point. But you still have access to those existing entry points, the buy NFT entry point, the set NFT price entry point, and the default entry point. And that's all you have to work with. Calling those entry points is the only way you can interact with your smart contracts. So using just this, can you figure out a way to get your Tez out of your contract? Pause the video and think about it for a while. Imagine that there is millions at stake. Okay, so all we can do with our contract is buy and sell NFTs. But we could use that to our advantage. We could use the Tez in our balance to buy one or more NFTs at their market price using our joint account. So those should be NFTs that are easy to buy and sell and that have a clearly identified market value, so that you know that if you buy them at the marketplace, you will be able to sell them at a similar price. Then you change their price to a very low price, close to zero. And then right after that, you buy them with another account, let's say a regular account, at this very low price. And now that you own it and control it, you can sell them with your regular account to a buyer at the market price, or maybe a bit less than what you paid for. And by doing that, you got your money out. Or most of them. This sounds good, right? There's only one small problem. If you do this, you could actually lose everything. Can you figure out how? Pause the video and think about it for a minute. So the problem is that if you can do it, someone else can too. After you bought the NFT with the joint account and changed their price to a very low price so that you can buy it at this very low price with another account, someone else could buy it too and could buy it before you do. Anyone can buy it at this very low price. So if anyone or even a bot notices that there is this NFT that has a very high value but somehow got a price set to a very low price, then there is a good chance that somebody will notice that and immediately buy it. Then sell it to a buyer at the market price and profit instead of you. So there's a risk that you will lose everything and someone else will make the profit. Thankfully, there's a way that we can prevent this. The idea here is that between the time that you change the price to a very low price and the time that you buy it with another account, you would like to make sure that no one else can do anything and buy it before you do. And you can do this using batches of transactions. And the idea is that on Tezos, a given user can submit a batch of transactions. So it's a sequence of transactions from the same user and that will be executed atomically. That means right after another without anything being able to happen in between. And either nothing happens or the whole sequence of transactions happens with nothing in between. So by creating a batch of transactions from the same user, so there has to be one of the two people who own the joint account, we'll call the joint account to change the price of the NFT. Then with the same account, they will buy that NFT at that very low price. And now we know for sure that no one can buy it before we do, and we managed to get our millions out of the NFT contract. We were pretty lucky because this approach worked in this specific case, but in many cases there would be no such approach. So we got lucky, but it may not be the same next time. Let's look at some other interesting situation that can happen with inter-contract calls. Suppose you are the owner of an NFT that has an automatically increasing price and royalties that you worked on before. And let's assume that you got smart and bought this NFT through a contract that can temporarily prevent sales. So it has a default entry point with a switch that you can turn on or off to allow prevent sales. And you pause the sale. So you own the NFT at some price. The price has increased by 10% since then. And then you pause the sales by making sure no one can buy it because the account that owns it will reject the money and prevent the sale. Now let's say that enough time has passed and for some reason you know that somebody is ready to pay a very high price to acquire this NFT. Somehow it got really famous and someone is really eager to acquire it. Unfortunately for you, the price is already set. So if you unlock the sale, well, that then person is likely to buy it at that price. So the question is, how could you bypass the increasing price rule so that you can sell this NFT that someone really, really wants to buy and is ready to pay a high price for it? So how can you bypass this increasing price rule and sell your NFT for more and take advantage of the fact that somebody is willing to pay a very high price for it? Pause the video and think about it for a minute. One easy way for you to do that is to increase the price by selling it to yourself and increasing the price by 10%, and you keep doing that until you reach the target price that you really think you're able to sell it for. So every time you sell it to yourself, whatever you pay is sent back to you. The only issue is that the 5% of royalties fees will go to the author for every sale. But it's still a good way to increase the price so that you can get the most out of your NFT. You can use a batch of transactions to make sure that nobody else buys it between the time that you unlock the sale and the time that you buy it. Now, knowing that this is possible and you're the author of this automatically increasing price contract, you would like to make sure people don't do that and cheat and go around your rule of the price automatically increasing by exactly 10%. So if you're the author of this smart contract, how can you change the smart contract before you deploy it and prevent users from bypassing this rule? Pause the video and think about it. One idea that wouldn't really work would be to add a rule in your buy entry point to make sure that the current owner of an NFT cannot buy the NFT from themselves. So basically in the buy contract, you could check that the caller, sp.sender, is not the owner. Otherwise you reject the sale. And this wouldn't work because it's very easy for the owner to use a second address to buy the NFT. So they could go back and forth between two addresses, increase the price until that value. And since there's no way to know if two addresses are the same person, there's really no way to fully enforce this increasing price rule and preventing the same person from buying the contract again and again to increase the price. And you really have to keep in mind when you see NFTs that seem to be bought and sold at a very high price. This may make it look like those NFT are really worth a lot, but it could be that it's actually the same person buying it and selling it. It's just money changing from one address to another, but owned by the same person. So it doesn't cost anything to sell and buy an NFT at a very high price if you're selling and buying it from yourself. So that's a good way to inflate the apparent price of an NFT. So you should be very careful about that. So now let's think about a more interesting question. What if you want to sell it for less? How could you bypass the increasing price rule so that you can sell your NFT for less? Let's say it went to a ridiculous price, nobody wants to buy it anymore. You really want to get rid of it and sell it for less than its automated price. And the value of the price in the storage of your contract is really computed by the entry point buy, and there's no way to change it in any other way. All it can do is be increased by 10% when you buy the NFT. So how could you bypass this buy entry point and sell the NFT at a lower price? Pause the video and think about it. One solution could be to not sell the NFT itself, but sell the address that owns the NFT. So for example, you could sell the private key of the account that owns the NFT to someone else, and then they would be in control of that NFT. This is a very dangerous idea, especially for the person buying your private key. The reason is that there is really no trustless way to automatically verify that a private key has been transferred. So we have this issue of who goes first. Do I send you the private key first, or do you send me the Tez first who pay for it? So you cannot use the blockchain to do this kind of thing safely. But most of all, there's no way to prevent the original owner of the private key to sell their private key multiple times. When you sell a private key, then two people now have this private key. And basically it's like a joint account that both people control. So it's not safe at all to buy someone's private key. It just doesn't work. But this could give you an idea for another approach that relies on inter-contract calls. Can you figure out how? Pause the video and think about it. So the idea is that although you cannot sell the address of a regular account, so the private key of the regular account, you can sell a smart contract. And a contract can own an NFT. So instead of buying the NFT with a regular account and then trying to sell that account, you can simply buy it with a new smart contract and then sell that smart contract. So we can custom build a smart contract so that it can purchase or sell NFTs and also be purchased and sold itself. And the rules for selling and purchasing this contract that will own the NFT are completely independent of the rules that set the price of the NFT itself. So in a way, we are wrapping the NFT into another new contract that we can buy and sell. And since this contract owns the NFT, it's really like selling the NFT itself, except that it's wrapped into this other contract. So we can call this contract NFT wrapper. And the idea is that whoever owns the NFT wrapper contract that owns our NFT effectively owns the NFT through this contract. But owning our NFT through this NFT wrapper contract will really allow us to go around any restrictions not only on the price, but also on the royalties. When you sell that new wrapper contract, you don't have to pay royalties to the original author, because you're not even using the buy entry point of the NFT. You're simply using the buy entry point of the wrapper to change the owner of the wrapper. Let's look at how this contract would work. In the storage, we would have three values. One, we need to be able to say if we allow or disallow sales of the NFT it owns. So those will simply be a boolean that we set to true when we allow sales on the NFT and false otherwise. Then we need to store the price of the wrapper and the current owner of the wrapper. Now we have a number of entry points, so we can use this wrapper to buy NFTs, and this will simply call the buy entry point of the NFT contract with that address. So this is just about, okay, let's have this wrapper buy an NFT. Then we can set the price for our wrapper. So when we call it, we check that the caller is the actual owner of the wrapper, and then we replace price with a new price in the storage. We can have this buy entry point for anyone to buy our wrapper. So we check that the amount transferred is equal to the price of our wrapper. We send that price to the current owner, and then we replace the owner with a caller. So we simply sell this wrapper like we sold an NFT before. Now we have this entry point to set the value of this allow sales boolean. All it does is check that the caller is the owner of the wrapper, and then replace allow sales with a new value. And the point of that is that we finally have this default entry point that can control whether the owned NFTs, so the NFT that this wrapper owns, can be sold or not. And if allow sales is true, then the default entry point will accept any test that is sent to them and not doing anything. But if we set allow sales to false, then the default entry point will fail whenever someone tries to buy one of the NFTs it's owned, because that's part of that buy entry point. It's sending test to its owner, so to the wrapper. And if the default entry point says nope, sales are not allowed, then it will fail and the NFT cannot be sold. So we can control whether the NFT we owned can be sold or not. We can buy NFTs, and then we have the entry points for people to buy and sell the wrapper itself. So your exercise is to implement this NFT wrapper. So you will have two contracts. One is the NFT for sale contract you have used previously, and the second contract will be this NFT wrapper contract with this structure. So pause the video and give it a try. So let's look at a solution. Here we have an old NFT for sale contract that has an owner, metadata, and a price, or basic NFT. We have the set price entry point that checks that it's the owner that is calling and then updates the price. And finally, the buy entry point where we check that whoever is trying to buy sends the right price. Then we send that amount to the current owner and we change the owner. Now let's look at the wrapper contract. So we have this allow sales boolean that we initialize when calling the constructor. We have a price and we have the owner of this wrapper contract. We can call the buy NFT entry point to have this wrapper buy one or more NFTs. So we give it the address of the contract that we want to buy. We check that the caller is indeed the owner of the wrapper contract. Then we fetch a contract for the buy entry point associated with that address. Again, there's no parameter, so we put sp.unit as a type. And then we call the entry point with no parameter, so two parentheses for the unit value. And we send the amount that we got so that we can purchase the corresponding NFT. Now we can have the entry points to buy and sell the wrapper itself. So the owner can call set price to set a price for the wrapper. We check that it is indeed the owner that called this, and then we update the price for the NFT wrapper. Then we have the buy entry point. So we check that whatever amount was sent is the price of the wrapper. we send that price back to the owner of the wrapper, and then we change the owner. Very similar to what we do in the NFT itself. It's just the two entry points we need to buy and sell our contract. Then we have the set allow sell entry point that simply lets the owner of the wrapper contract change the value of allow sales. And finally, we have this default entry point that will fail if allow sales is false. We don't really need to write that here. But if allow sales is false, then it will fail and then prevent anyone from buying any of the NFTs that this contract owns. So here we have a test. So we create instances of the two contracts. Initially, we said that the sales are allowed. We add both contracts to our scenario. We set the initial price of the NFT to 7 Tez. Then we have the wrapper contract buy this C1 NFT, and Bob is the owner of that NFT wrapper contract. So Bob can say, buy this C1 NFT contract through my wrapper contract and pay 7 Tez. Now we can verify that indeed the owner of this contract is the second contract, the wrapper contract. Bob can now say, I don't want to allow anyone to buy the NFT I just bought through my wrapper. Bob can then set the price of the wrapper itself to 50 Tez. And then even though the current price of the NFT itself is at 7, we cannot buy it for 7 Tez because buying it would try to send the 7 Tez to the wrapper contract. The wrapper contract has allowed sales at false, so its default entry point will reject the Tez sent to it and therefore reject the sale. But on the other hand, someone like Dan can buy our wrapper contract at 50 Tez and then take control not only of the wrapper contract but also of the NFTs that this wrapper contract owns. So with this idea of a wrapper, you can see that although it is possible to have all kinds of rules, such as paying royalties to the other or having rules on how the price can evolve, smart contracts are also very powerful, and through intercontract calls, we can go around certain rules by wrapping contracts into other contracts. And this idea of wrapping NFTs and tokens in general is also one of the ways that we can transfer NFTs across blockchain. In this module, you will learn how to use lists and enumerate elements of lists using loops. You may be surprised that it comes so late, as in general programming, loops is one of the first things you learn. But in smart contracts, we actually try to avoid using loops and lists, and we'll talk about why. A list is an ordered collection of values of the same type, or we could say a sequence of values of the same type. If you want to create an empty list, just like in Python, you put 2 square brackets, and if you want to create a list with already some elements, you put the elements between the 2 square brackets, separated by commas. To describe the type of a list, we write sp.list, and between square brackets, the type of the elements in the list. So contrary to Python lists, for example, we cannot access any particular element in the list using an index or insert element in the middle or at the end. All we can do is add an element at the beginning. And for that, we can use sp.cons, the new element we want to add at the beginning, and then a list. And this returns a new list that contains all the elements that we already had, plus the new element at the beginning of the list. And finally, you can obtain the length of a list using the len function. The main thing we typically do in a smart contract with lists is loop over the elements of this list, do something with each element. So for example, if we want to add up all the values in our list of numbers, we can initialize a variable total to 0, and then we write a loop similarly to how we would write it in Python. So for the name we want to give to the variable that will contain each element during each iteration of the loop, in, and then the list. So for the variable in and the list, colon, and then indented the operations we want to do using this variable to access the current value. So here we loop through all the elements and then we add each one to the total to compute the sum. If you want to repeat something 3 times or have a variable that goes from 3 to 6, for example, you can create a list using the range function. And if you give it one parameter, it will simply create a list with elements that go from 0 to that value -1. So with range of 3, you get 0, 1, and 2. If you give 2 values, you get all the values between this element and then this element -1. So range of 3 to 7 gives 3, 4, 5, 6. And you can add a step to say that you jump 2 by 2. So this would be 3, then 5, and then we'd stop. So this way you can create a loop with a variable that takes every value between 2 values and potentially with a step. Let's work on an example. We want to change our NFT joint account contract so that we can purchase multiple NFTs at once. This can be a good idea because instead of having to call one transaction every time we want to purchase one NFT, if we have many NFTs to purchase, it can reduce gas fees to purchase multiple NFTs in a single transaction, because each transaction involves signature verification, etc. So it involves extra gas costs and the serialization and deserialization of the storage of the contract you call, etc. So if you can do several in one call, then you can save some gas fees and therefore some money. So let's take a look at the code. Here we have our usual NFT for sale contract where we store one NFT with an owner, the metadata, and the price, and we have a set price and a buy entry point. But in our NFT join account, here instead of having code to buy a single NFT, we pass a list of NFTs to buy. And then with this list, we can do a loop to loop through every NFT in this list. So NFT will contain the current element in the list. And then we call, as we did before, the buy entry point of our NFT contract by passing the amount stored in NFT. So here the idea is that we pass a list of records where each record contains an address. So the address of the NFT contract that contains it, and the price, the amount that we are willing to pay for it. When you call buy NFTs, you have to send the total amount that you will spend buying all these NFTs, and then in the list you indicate the address of each NFT you want to buy, and then how much you're willing to pay for it. And that's it. In the test, we call here joint account buy NFTs, and we pass a list of records with here 2 records, one with the first NFT we minted here, and then an amount of 7 Tez, and then another one with the second NFT with an amount of 5 Tez, which are the current prices of those NFTs after we initialize them at 5 Tez and then change the price of the second one to 7 Tez. So let's give it a try. We can see we originate the 2 NFTs, then we originate the joint account. We set the price to 7 Tez for one of the NFTs, and then we call buy NFTs. And here you can see that the argument is a list where each element is a record with the address and the amount. So we buy the NFT at this address for 7 Tez and the NFT at this address for 5 Tez. And we can see that there were 2 calls to the buy entry point. So one to buy the first NFT at 7 Tez, and then we can see that the transfer of the 7 Tez to the original owner has been done. And here the second purchase. Now it's your turn to practice on an exercise. So the goal here will be to change this NFT joint account contract so that this time both owners have to agree before they buy NFTs. In a way, this becomes a multisig where multiple people have to sign on an operation to happen. But this one will be a very specialized one that can only be used to buy NFTs. And your goal will be to change the buy NFTs entry point so that the process works as follows. So first, one of the 2 owners of the joint account can propose a list of NFTs to buy by calling buy NFTs the first time, with a list of NFTs to buy and the corresponding price. And so during the first call, we don't purchase anything. We simply store that list. For the NFTs to actually be purchased, the other owner of the joint account contract then has to call buy NFTs again, this time with their own list. And then what happens is that the NFTs that are listed in both lists, the one we stored during the first call by the first owner and the one just provided by the new owner, we take the NFTs that are in both lists, and if they are listed with the same number of Tez, the same amount, then the contract buys them. And any NFT listed by the second owner that had not been bought should be left in the stored list so that the first owner can then in turn send another list and maybe confirm some of those proposed NFTs to buy. If the same owner calls buy NFTs twice in a row, we consider that this overwrites any previous list they have sent. So at any time, we only store the list proposed by the last caller. And whenever one of the owner calls buy NFTs and the stored list is from the other owner, then we check the intersection between the list is sent and the list that is stored, check if the prices are the same, and when they are, we buy the corresponding NFTs. So pause the video and give it a try. Let's look at the solution. So we don't change the NFT for sale contract, but we will change the NFT joint account and add in the storage two values: the list proposed by the last caller, initialized to an empty list, and the address of the owner who proposed this list, so whoever called buy NFTs last. And then we change the buy NFTs entry point. We still check that it's only one of the owners calling it. If the caller is the same person who called it last, so if the owner is the last proposer, or if we start with an empty list, then we simply store the list that this caller is proposing, and that's it. If it's the other owner who's calling it, then this time we will compute the intersection with the currently stored list. So there's different ways to do that, but we don't have a lot to work with if we simply use lists. I mean, at the moment, pretty much anything you can do with a list is loop through all the elements. So if we simply use that, we would have to loop through all the elements of the new list, and for each of them, try to search for the same NFT in the stored list. So we have to loop through all the elements in the stored list and see, okay, if the current element in the stored list is the same address as the current element in the new list with the same amount, then we buy this contract. Otherwise, we add it to a new list that we create that will be replacing the old list in the storage of the contract. And then we remember that the last caller is the sender. So this would work, but this is very slow. If we have, let's say, 10 NFTs in each list, then for each of those 10 NFTs in the first list, we would have to loop through 10 NFTs in the new list. So we basically have n squared iteration of this element. So this can get pretty expensive pretty quickly because of all the computation we have to do to compare the two lists. So we can do a lot faster than that. But to do that, we have to use another data structure that you already have learned about. Oh, and here we have a bug. We forgot to store the proposer. So this should be stored whatever happens. So the indentation here was incorrect. Pause the video and think about it for a minute. So to take advantage of a map, we will take the proposed list and put all of its elements in a map where the key is the address of the NFT and the value is the amount. So this is assuming that the same NFT address is not listed twice in our list. That's a rule we can set for the users of the contract. We just say you're not allowed to try to buy the same NFT at two different prices in the same list. So assuming that, we'll have one entry for each NFT in this map. And then when we loop through the new list of NFTs, all we have to do is check if it's in a map using the contains instruction with the address as a key, and then check if the amount for that NFT is the one we have in the new list. If yes, we buy it. If not, we add it to our new list of remaining NFTs. So this makes it a lot faster to find intersection between the two lists, but it's still not the approach I would recommend. Because although this code is less than 20 lines, it's still a bit more complicated than necessary. So the idea is that we want to avoid doing any unnecessary computation within a smart contract if it can be done off-chain. And here there's really no need for the smart contract to handle the negotiation between the two owners to find a way to determine which NFTs they both agree to buy. They could have this negotiation completely off-chain through a DApp. When it's just two people, there's really no need for anything in between them for them to agree on which NFTs they want to buy. The role of the smart contract here is simply to make sure that they do agree before the purchase actually happens. And so the way we do that is that we have a first owner, could be either one of the two, call buy NFTs with a list that they allegedly came up with as a list that they both want to buy. And so we store that list and we store the address of the owner who proposed that list. And then all we have to do is have the other owner call and approve NFTs to say, yes, I agree with the current list, that's fine with me. So we check that they're indeed one of the owner, they're not the proposer, it's not the same person agreeing with themselves. And then we loop through all the NFTs in the list and simply buy them. So that simplifies our contract by quite a bit. And so there are less risk of bugs. But actually in this specific implementation, there's a potential flaw that would make it possible for one of the owners to cheat. Can you figure out how? Pause the video and think about it for a minute. So the way that one owner here could cheat would be to detect when the other owner is calling the approve NFTs entry point, and right before that moment, in the same block potentially, but making sure their transaction is accepted first, they would call buy NFTs again with a new list. So basically they would switch the list of NFTs right before the person approves it and after they send the transaction. So it's too late for them to notice that the list has changed and they're not approving the list they thought they would buy. So we need some way, when the user calls approve NFTs, we need a way to make sure that they are approving the list that is currently stored and not a previous list that they have checked before. So how would you do that? Pause the video and think about it for a minute. So there's several ways that we could do it. One way would be to ask the caller to send the whole list again, and then we compare the two lists and compare every element and check if they're all the same. But that would be a bit more code. We could think about computing the hash of that list and storing it, and then we would have the other users send the hash of the list they approve of, and a hash is guaranteed in practice to correspond to the same data. It's impossible to create another list at the last moment that would have the same hash. So this would be safe enough, but computing a hash is a little bit expensive, so it's maybe not the cheapest way to do it. All we need to do is to have a unique value associated with that list. And it doesn't have to be the hash. It could be a counter. So we could have some counter that we increment every time someone makes a new proposal. And then when we approve, you send the value of that counter. So that would be one way to do it. So we could do here, set to 1. And then here we increment it. And here we check, we pass a counter. And we check the approved counter is equal to the stored counter. So this way we know that buy NFTs hasn't been called at the last minute before we call approved NFTs, and if it has been called, then the approved counter wouldn't match the current counter. So that's a good way to protect against the other user trying to switch the list at the very last moment. So making the code simple is a good way to avoid bugs, but it doesn't guarantee that there's no bug. And you should always think about ways that someone could cheat. It's just easier to think about it if the code is simpler. So as I said in the introduction, we actually try to avoid using lists and loops in smart contracts when we can. And that's because using lists in a contract can be dangerous. Can you figure out why? Pause the video and think about it for a minute. So there's two reasons why lists can be dangerous. As we discussed before, serializing and deserializing the storage cause gas. And so if you have a list in your contract, this can increase the cost of calling your contract. In some cases, it could increase it so much that your contract would get stuck. It wouldn't be possible anymore to deserialize and reserialize the current content of the list. So you should be very careful about having a list in your storage that people can fill arbitrarily up to the point where it's not possible to deserialize it anymore. The second related reason why lists can be dangerous is that simply looping through their elements causes gas. And as the number of iterations increases, the cost increase, and similarly, your contract can get stuck just because you have to loop through a very long list and perform some computation on every item. So it's important to remember only to use lists if you know that their size is bounded. If it's simply a list that you pass as a parameter, it's up to the caller to decide the length of the list they pass as a parameter. There's not much risk. Of course, you're going to pay more if your list is longer, but it's really up to you when you do the call to reduce the number of elements of your list if you want to pay less, or if you want to make sure that the gas cost doesn't exceed the limit of how much you can spend in a single transaction. But if it's a list that you store in your storage, then that's when it becomes dangerous, and you should be really careful and make sure that the length of the list cannot increase indefinitely. So now the question is, if we shouldn't use lists, and we can't use lists in the storage with a length that could increase indefinitely, what would be the alternative? If you feel that you need a list, that type of data structure, so an ordered sequence of elements of the same type, what could you use instead of a list? Pause the video and think about it for a minute. The alternative when you want to store a lot of data with no limits on how much data you can have is always the big map, because that's the only data structure that is not limited by the gas costs. And if you pick the right key, you can use a big map to emulate all kinds of data structures. So for a list, the idea is to use a counter to indicate the position in the list. So you could store two fields in your storage. Let's say field elements, that's your big map. And then a value that counts the number of elements in your big map that starts at 0. And if you want to add an element, all you have to do is write your value with the key being the current value of NB elements, and then you increment NB elements by 1. Then you can create a loop that just loops from 0 to NB elements minus 1, so that you can iterate through all the elements in the big map. But if you loop through all the elements in the big map this way, well, again, if the size of the big map gets too much, then you could get stuck again. Let's say you want to compute the sum of all the elements, but there's too many elements to loop through in a single transaction without exceeding the gas limit, then you have the same problem. So how would you solve that? Pause the video and think about it for a minute. One way to avoid the very long loops and avoid loops that cannot go through in a single contract call is to simply use multiple contract calls. You could split the loop into multiple calls that maybe do only 100 iterations in one call. So you could keep in your storage where you're at in this big loop. So you could have a loop counter in the storage, and then you have this continuous sum entry point where you pass how many iterations you want to go through at the most, and then you loop through them, you increase your counter for every iteration you do, and if you didn't exceed the number of elements in your big map, then you add the corresponding value to your sum. So this could be one way that you can make sure that no matter what, you will be able to loop through all the elements in your big map and compute the sum. This could end up being expensive if there's millions of elements, but you will be able to do that if you're ready to pay the price. But for this specific example of computing the sum, we can do much better. Can you find out how? Pause the video and think about it. So the idea is that instead of looping to compute the sum when we need this sum, it's a lot better to maintain the sum as we add elements. All we did to the list is add elements to it, and maybe we could have a way to remove elements from them, but as long as we don't do anything more complicated, we can maintain the sum as we modify this data structure. So we add this sum elements variable in our storage, and then every time we add an element, we simply add the value to some elements. This way, when we need the sum, we just have to read it in the storage. So this is pretty basic and pretty easy to do, but it's something to really keep in mind, because that's something we use a lot. And this works if you want to compute the sum, if you want to compute the smallest element in a list, or the maximum element in a list, or even the average value in your list. But a lot of times, just like we did a bit earlier, there's other approaches to reduce the gas consumption that really mostly consist in doing work off-chain. That's really the best way to avoid paying too much gas, is to do as much of the computation as possible off-chain. In this video, you will learn a new way that contracts can interact with each other, and that will make it even easier to build projects composed of multiple contracts that interact with each other. And this new way is what we call views. More precisely, on-chain views, but we'll just say views to keep it short. And it's a mechanism that allows contract calls that are really meant for one contract to obtain information about another contract. And views are read-only. So when you call a view of another contract, that view cannot modify the storage of that contract and cannot emit its own operations. So that means it doesn't have any side effects. So by calling that view, you don't have any effect on this contract. All you can do is obtain some information from that contract. There can be some computation to obtain that information, but there won't be any side effect other than returning the data from that smart contract. When you call a view, you can pass arguments as input that will be used by the view in addition to the content of the contract storage of that view. And the view may call other views from other contracts, again with no side effects, no modification of their storage or no emitted operations. Calling a view in itself is not an operation. All it does is return a result as an output. And unlike contract calls or transfers of Tez, they are executed immediately. They are synchronous. So as soon as you call it, the view is called in the other contract, the code of that view in the contract is immediately executed, and the result is immediately available to the caller contract. That's very different from inter-contract calls that we have seen before, where an inter-contract call is really a new transaction that you add to a queue. But here with views, there's no new transactions. You immediately execute the code and obtain the result. So let's take a look at how we create and call an on-chain view. Creating an on-chain view is very similar to creating an entry point. We use a different decorator, sp.onChainView, to indicate that this is a view. Then it's like a method that takes one or more parameters, just like entry points. We can have any kind of computation within the entry point, except for modifying the storage and creating new transactions. And then the other difference with an entry point is that it returns a value with the keyword return. To call a view within an entry point, you write sp.view and then between parentheses a number of values, the name of the view, so that's the name you gave to the method in your contract. Then you provide the contract address, so the address of the contract that contains this view. Then you provide the value of the parameter. So it could be a single value like here, or it could be a record, it could be anything. And then you provide the address of the return type. So here we are returning the address of the owner of a token. So we pass the token and we say the return type is an address. What you will get is then an option on a value from this type. So you have to unwrap it to obtain the actual address. Let's work on an example. There was an issue with our NFT join account contract, which was that if when you pass a list of items you want to buy and a corresponding price, a corresponding amount for each NFT, if one of the NFTs in your list has a price that has changed since you built your list, then the purchase of that NFT will fail. But not only that, since one call will fail, then your whole contract will fail and none of the NFTs will be bought. So that can be a bit frustrating. So to avoid that, we will use views by simply checking the price of an NFT, the current price of an NFT, right before we try to buy it. If it's the wrong price, then we'll just skip it and avoid having the whole transaction being cancelled. So in our basic NFT for sale contract, we will add an on-chain view, get price, that only does one thing, which is to return the current price of the NFT. So we just return that value. And this way, in our join account contract, here, when we are trying to buy a given NFT, we use the get price view. We pass the address of the contract. Our parameter here is of type unit. There's no parameter, so we put a pair of parentheses. And what we get is a price, so the return type will be mutez. And we unwrap the option that we get into a variable price. Then we can check. If the price is the amount we expected to pay, then we do the transaction. And here we know for sure that this transaction will succeed because the price cannot change between the time that we call this contract and the time that the buy code is run. So that makes it really convenient and it's easy enough to use so that before we actually do a transaction with another contract, we can check information about that contract to make sure we do something that will not fail. If we combine intercontract calls and views, we can split complicated contracts into simpler contracts, which is something I really recommend. It has several advantages, but most of all, it makes contracts simple. For example, if we keep the topic of NFTs, we can split two key roles between two contracts. We would have one contract that only takes care of storing the NFTs with their ID, their metadata, their owner. We would call that a ledger contract that just keeps track of who wants what NFT. And we could have a separate contract that will handle all the trading of NFTs. We would call that a marketplace contract. If the ledger contract can allow the marketplace contract to change the owner of NFTs, then we can use this pair of contracts to have people trade NFTs. And we will keep each of the contracts pretty simple. And it will also make it possible to reuse contracts and combine them with new contracts, for example, a new type of marketplace or a new type of NFT. Let's look at the structure of the ledger contract. So we would need to store an admin, that's who is allowed to change the owner of the contracts. That will be our marketplace contract. Then we have our usual next token idea to keep track of the idea for the next token we will mint. Then we have our tokens big map that will store all information. So we use the token ID as a key. And then for each token, we store the address of the owner and the metadata. Then we have three pretty basic entry points. First, the mint entry point, where we pass metadata, and we will simply create a new entry in the tokens big map with the next token ID as a key, the caller as the owner, and the passed metadata as the metadata. Then we increment the next token ID. Then we have an entry point to change the owner of a given token. So we pass the ID of the token and the new owner. We check that the caller is the admin. So the admin is allowed to do anything. We trust this admin. We trust the marketplace because we have read the code before we do that. And then we simply change the owner within the tokens to the new owner. And for the marketplace to be able to interact with the ledger, it will need to be able to find out who's the current owner of a given token. So we have an on-chain view, get owner, that takes as parameter a token ID, and then we'll simply return who is the owner of that token. Now let's look at the NFT marketplace contract. The goal is simply for owners of NFTs to be able to put them for sale at a given price, and then buyers will be able to buy them. So here we will store all the offers in a big map. For the key, we will use a composed key, a pair of two values. The address of the NFT contract, so in which contract is our NFT. We can have a marketplace that can handle multiple collections of NFTs in multiple contracts. Within that collection, we need to know the token ID. So a given offer has a key that is the description of which NFT it is through the address of the contract and the token ID within this contract. And then for the value, we simply have the price at which the seller is willing to sell this NFT. Then we need 3 entry points. One entry point for the owner of an NFT to create an offer. So again, we say what's the contract that stores this NFT, what's the token ID within this contract, and at what price we want to sell it. Using the getOwner view of the NFT contract, we will check that the caller is indeed the owner of this NFT. And if it is, then we'll add an entry to the offers big map. We give a chance for the owner to cancel their offer. So they indicate what's the NFT address and what's the token ID. We check that the caller is the owner of this NFT, again using the view. And we simply remove that entry from offers. And finally, when a buyer wants to buy our NFT, they indicate which contract, which token ID. So basically they indicate which one, they provide the key to the entry in the offers big map. So using that, we check that the amount they send, as they call the buy entry point, matches the price stored in the big map. We transfer that amount to the current owner that we obtain, again, using the getOwner view of the NFT contract. And finally, we change the owner by calling the change owner entry point of that contract. And so we pass them the address of the new owner, that is the caller. And when we're done, we remove the entry from the offers big map. So your job now, using this description, is to implement these two contracts. So you implement the ledger, then the marketplace, and you create the corresponding test to make sure everything works. Pause the video and give it a try. So let's take a look at the solution. We will start with the ledger. So for the ledger, we store the admin. That will be the address of the marketplace contract. We create a tokens big map that will store the content of the ledger, all of our tokens, their price and owners. Then we have this counter next token ID that we initialize at 1. In a mint entry point, we obtain the metadata as a parameter. We indicate that this metadata is a string. There's no other way to find out by just checking the contract. So type inference won't work. So we say this is a string. Then we add an entry to the tokens big map using as a key the next token ID. And the value is a record that contains the owner, so whoever is calling this entry point, and the metadata. And of course, we increment the next token ID so that the next person mints with a different ID. Then we have this on-chain view, getOwner, that takes as parameter the token ID, and that simply returns the owner of that token. Finally, the change owner entry point takes the token ID as parameter and the address of the new owner. We check that the caller is the admin of this NFT contract, so that would be the marketplace, and then we assign the new owner to this token. So that makes it a pretty basic contract, pretty easy to proofread and check. Now let's see how we can create the marketplace contract that interacts with it. It's very simple as well. We have a storage that only contains this big map with the offers. We have an entry point new offer where we indicate which contract and which token ID we are selling at what price. Then we call our view getOwner from the NFT contract. We pass the token ID and the return value is the address of the owner. So we provide that type. And then we unwrap the option to obtain the owner. So here, of course, the idea was to check that it's the owner calling. So we have to add assert owner is SP sender. And once we've checked that, then we create the entry in the offers big map with a key that is a pair containing the address of the NFT contract and the token ID. And the value is simply the price that we are willing to sell this NFT for. Then we simply have a buy entry point for any buyer to try to buy this NFT. It takes as parameter, again, the description of which NFT it is through the contract and the token ID within this contract. So we first check what's the price of the corresponding offer. And if there is no such offer, this will fail. So the contract will fail. So there's no need to check that the offer exists. We simply try to read from it, and it will fail if it doesn't exist. Then we check that the amount sent was indeed the price. So if this is the case, we will change the owner of the NFT by calling the change owner entry point of the contract. So we use those usual two instructions. Obtaining the contract object, we pass the type of the parameter, the address of the contract, and the name of the entry point. For the type of the parameter here, we have used a type definition here, where we say, okay, this is a record that contains a token ID, an integer, and the new owner, an address. This is a good habit when you do intercontract calls. It's a good idea to have the type defined as a type abbreviation at the beginning of your code. So now that we have the contract, we prepare the parameter. So a record with the token ID and the new owner, so the caller, sp.sender. And then we call the contract. So here, it's not going to do a call right away. We are simply adding a transaction to the queue that will call this contract with this parameter and sending 0 Tez. But we know for sure that if this fails, everything will be cancelled. So here, one thing we didn't do is send the amount to the previous owner. So for that, we'll need to obtain the address of the previous owner. So we can just copy that code, and then we can send to the owner the amount. Also creating a transaction that will send this amount to the owner. And at the end, we need to make sure we delete the offer to make sure someone doesn't buy it again right away and immediately take it from this buyer. So here we have a very basic test that doesn't check much, but shows the two calls. We have here created two different ledgers to show that we can have the same marketplace interact with multiple NFTs. And when we create each of these ledgers, we pass as the admin of the NFT ledger the address of the marketplace that we have created here. Then we mint one NFT in each. Then we create an offer in the first ledger for the token ID 1. So this NFT that we have minted here, we say we want to sell it for 10 Tez, and it's Alice selling it, so she's the owner of that NFT. Then someone else can buy the NFT by indicating, okay, I want to buy a token from this contract with this token ID, and it's Bob buying it, and he's paying those 10 Tez. So we can run it, and we can see the origination of the marketplace, then the two ledgers, and then we have the minting of those two NFTs. Then the offer is being made and stored in the big map of offers. And then we have this purchase that sends the Tez to the previous owner and then calls change owner. So we see that here the calls to the views are not shown. They're not individual transactions, so they're not visible. But they have definitely worked to check who to send the Tez to, for example. One thing to know about on-chain views is that although they are called on-chain views, they can also be used off-chain. So this means from a DApp, for example, or from any off-chain piece of software, you can execute this view to obtain some information about a given smart contract. So if you want to know the current owner of an NFT for a given NFT contract, you can do an RPC call, so remote procedure call, to the node to say, hey, I want to execute this view to obtain information about this smart contract. And then you will get the result. Different libraries like Taquito make it easier to do that. And this can be very useful if you want to standardize off-chain read access to contracts. So If you want to know who is the owner of an NFT, of course, you could directly access to the big map. You have access to everything from off-chain. But if you want a standard way to find out and work with all kinds of NFT contracts that maybe store their owners in different ways, if they follow the contract, they should all have this on-chain view that returns the owner of a given token idea. And so the same code will be able to interact with all different contracts through this standardized view. So this means we can write a standard on how to obtain the owner of a contract without having to specify how the owner of an NFT is stored. And very often those views are useful both on-chain and off-chain. One of the reasons they are called on-chain views is that there are other types of views that we have been using in the past and are still using in some cases on Tezos. There is the term off-chain views, or that we call metadata views. So those used to be Michelson code that you could call from off-chain to obtain information about a smart contract, but with nothing executed on-chain. So it's basically the old way to do the off-chain use of the views that we just described. And there's a standard that describes it called TZIP16. It is still part of some well-used standards like FA2 that we'll talk about later. There was another type of views that we were using before on-chain views were created, and this was called lambda views. It was also a standard defined as called TZIP4, and it was not a feature but more of a pattern on how to implement your own views using a system of callbacks. So it was using inter-contract calls, but passing a callback to the contract you're calling to say, hey, compute this information, and then when you're done, send it to this callback. So it served the same purpose on-chain as our on-chain views, but was a lot less convenient to use. And so this new on-chain view concept is basically replacing both those old ways to do views. But again, they are still in use for legacy reasons in existing standards. But for your new contracts, on-chain views are really the way to go and make it really convenient. In this module, we will talk about custom types, a piece of syntax that will save you a lot of time. When you use inter-contract calls or on-chain views, you often have to specify the type of the parameter and the type of the return value, and those types can be a bit long. Here we present a short example of a typical type that we may pass as a parameter, where we specify a destination address, a token ID, an amount, and to match the specifications of standards, we have to specify the corresponding layout. Putting this whole piece of code, every time you have to specify the type for calling a smart contract that uses this kind of parameter, is very inconvenient. And if you ever make changes to the type, then you have to make sure you change it everywhere. But more generally, it makes the code hard to read and hard to maintain. So to avoid this and make things easier, we can give a name to a type directly in the main module. Here, for this type, we declare the name transaction type. We say it's a custom type by putting a colon, then the keyword type, then equals, and then the description of the type. From then on, we can use this name everywhere we need to provide this type. So be very careful. This only works if you put it in the module itself. You cannot define a custom type within a smart contract, for example. So typically you would have all your custom types at the beginning of your module. As an exercise, create a joint account contract with a deadline. So you take the existing joint account contract and change it so that it can purchase NFTs where prices have a deadline. That means to buy the NFT at that price, you have until that date, and after that date, the price is not valid anymore. While you work on this exercise, the whole point is for you to use a custom type to avoid having to put the full type every time you call the smart contract. For this exercise, there probably will be only one call, but the point is to practice creating custom types. Pause the video and give it a try. Let's take a look at the solution. So here we will need a type record that takes the new price and the deadline. So that we call the entry point to update the price, we give both the price and the deadline. So we create a custom type for this that we define at the beginning of our main module. Then When we call the contract here, instead of doing sp.contract and then describing the whole record type in detail, we simply put Entrypoint underscore type, the name of our custom type. And we can give it a try, and it works. All good. In this video, we will talk about the set data structure, and we will work on the membership contract that can be used to define which users are allowed to access specific features of a smart contract. A set is an unordered collection of values of the same type. It's a bit similar to a list, except in a list, the same value can be present multiple times, and we worry about the order of values. But in a set, all we care about is whether a value is or is not in the set. You can do three main operations in a set very efficiently. You can add an element to the set, you can remove an element from a set, and you can check if a given element is or is not in the set. And those three can be done pretty efficiently because internally the values are stored in a balanced tree, sorted by value. The syntax to use sets is pretty straightforward. You can create a set in two ways, using sp.set for empty set, or you can provide the list of values in the set between curly brackets. If you want to specify the type of a set, you write sp.set and between square brackets the type of the values. Then you can do the three operations, adding an element with add and your value. You can remove an element with remove and the value, and you can check if the set contains an element by calling your set.contains of the value, and will return true or false, depending on whether your set contains it. You can obtain the number of elements in the set using len, and then you can obtain the list of elements sorted by values by calling your set.elements. So let's work on an exercise where we will create a membership contract. It can be quite useful to have a contract dedicated to storing a set of members. We can use it to restrict access to features of a smart contract based on some conditions. That's what we call allow listing, so the list of users that are allowed to do something. And we can use it to create artificial scarcity. For example, if an NFT can only be bought by members of a club, then that makes this NFT a bit more exclusive, which can increase its value. We can also use a membership contract to create a community, for example a DAO, a decentralized autonomous organization, where we store the members in a membership contract. And it's often a good idea to separate this data into a dedicated contract that focuses on membership. And then this list of members can be reused in other contracts, not just this initial contract that we meant it for. Okay, so your job for this exercise is to think about how you would implement such a membership contract. And we want to make it exclusive, so the idea is that we only want rich people to be able to join this contract, so this elite club. We don't want them to pay a fee to join, but we want them to prove that they do have access, let's say, to 10,000 Tez. So if you don't have access to 10,000 Tez, you are not allowed to join this exclusive club. We also want to restrict the size of this club to 100 people. And of course, we want members to be able to leave this community if they want to. Your contract will need to have an on-chain view so that any contract can check if a user is a member of this club or not. Pause the video and think about what you would store in this contract and what the entry points would be and would do. So it's a pretty simple contract. In the storage, we can store the threshold, how much you need to show that you have to be able to join the club. We will, of course, store members, the set of addresses that are members of this club, and we can store the maximum size that we want the club to have. Of course, those two values could also be hard-coded, but here we decided to make them values in the storage. Then you have three entry points, or two entry points and one on-chain view. The main entry point is the join entry point for someone to join the club. So first you have to check that the club is not full, so the members doesn't already contain max size entries. Then we check that whoever wants to join is actually sending the amount required to join the club to the contract. We won't keep that value, we will send back here back to the sender. But this is a way to prove that they do have access to this money because they are able to send it to the contract before they get it back. So if they do have this amount and send it to the contract, we can add their address to the members set. Our on-chain view will simply return whether user, so the address passed as a parameter, is in the members set. And then we have a leave entry point where we simply remove whoever is calling this entry point from the set of members. Pause the video and implement this smart contract. Let's take a look at the solution. We can see here that we have a constructor that takes the membership threshold and max size as parameters and stores them, and then it creates this members empty set. In the join entry point, we check that the caller did send the required amount. We check that we still have fewer than max size members in the set. We check that we still have fewer than max size members in our club. Then we add this caller in the set of members, and we send them back the amount since we don't want to keep it in the contract. We have our isMember on-chain view that takes up user as a parameter, and we simply returns whether it is in the member set or not. Finally, you can call the leave entry point, and then we simply remove this address from the members. We have a basic test where we create a rich community by calling this contract with a threshold of 10,000 Tez and a maximum number of members of 100. We then have Alice join by sending the right amount. Bob first tried to join with the wrong amount, so it shouldn't work. Then he tries again with the right amount. From the scenario, we can call the on-chain view to check that Alice is indeed a member and that Carl, who never joined, is not a member. Then we can test that we can leave, so Bob is leaving the community, and here we check that indeed he's not a member anymore. If we can give it a try, we see that we first create an empty set, Alice join, Bob tries to join and fails, Bob then succeeds in joining. We can see that we have Alice and Bob here, and then we send the 10,000 back to Bob, and then Bob leaves, and only Alice is a member. All good. It's important to know when not to use sets, and there are situations where you really shouldn't use them. Pause the video and think about why for a minute. The issue as often is with the amount of storage that you have to serialize or deserialize when you call the contract. If you have a set and this set gets too big, then this amount could be so big that the amount of gas you spend in a transaction exceeds the maximum amount that you're allowed. So your contract could get stuck if your set keeps growing arbitrarily. In our exercise, we don't have this issue because we had a limit of 100 members in the set, so we were safe. It could never grow to more than 100 members. But what if you didn't want to have this size limit? How could you make sure that your contract never gets stuck? Pause the video and think about it for a minute. So as often, when you want to use a data structure that doesn't have any size limit, you can use a big map. And big map can associate a value with a key. Here we don't have a value, but we still can use keys. So we could use the values of the set as keys to our big map. And then for every key, we simply store a unit, which is nothing. So when we want to add a member to our big map, we simply say members of this address equals sp.unit. So it creates the entry even though the entry doesn't contain anything. We can remove it using del, and we can check membership simply by checking if there's an entry for that address. And then we can have membership contract that has as many people as we like without having to worry about the costs. So big map is always what you have to think about when you want to store a lot of data. But you should be careful. It doesn't always solve all of your gas issues. In particular, you have to keep in mind that whenever you access a given entry in your big map, you still have to deserialize and reserialize this entry. So if you store, for example, a full set within a single entry, then it could be risky because that single entry could get really big and then you would end up with the same problem again. So big maps are part of the solution when you want to store a lot of data, but it's not always sufficient. So you should still be careful. In this module, we will talk about variants, a piece of syntax that allows you to create your own types. Let's start with simple variants. A variant is a type that we use to represent one of several predefined values. For example, you could define a type called day of week for values that represent a weekday. So a variable of this type could hold any of these values: Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. Simple variants are similar to enums in some other languages that you may be familiar with. The syntax to create a variant type is to write sp.variant and then between parentheses the list of possible values and a type unit. We'll see later how we can have variants with parameters where the type is different, but for now you simply put a list where each element is a name, then equals sp.unit, meaning nothing. To avoid repeating this every time we use a type, we usually create a named type, a custom type, in the main module. So in our main module, we would write day of week, type, equals, and then sp.variant with all the different values. Then within your smart contract, you can use values of this type, for example in assignments or comparisons. Here, we create an attribute in the storage called day, and with an initial value of Tuesday. So when you use the value, you put the name and then a pair of parentheses. Then you can compare this value to different possible value of this variant. Here we compare to Sunday or Saturday to determine if this is the weekend, and the price for some work is more expensive during the weekend. When you use variants, you need to keep type inference in mind, because if you don't specify the type, it can be determined automatically using type inference, but it will only be determined based on the actual values that you use. So if you have a variant for all the days of the week, but you only use some of the days in your code, then the type inferred by the type inference algorithm will only contain the values that you have used. But you may need the other values in some other cases, so that could be a problem. So in this example, the type inference only creates this variant that only has Tuesday, Sunday, and Saturday. Type inference can't guess that there are other weekdays than the ones you use in your code. If you want to execute different code depending on the value of a variant, you can use sp.match as an alternative to using ifs and else and comparisons. sp.match works like this. You write with sp.match and then between parentheses the value. Then you put one section for each value, where each section starts with, and then sp.case. The name of the variant, and then the corresponding code. In the test scenario, with the current version of SmartPy, the way you use variants within your test is a different syntax from the syntax you use within the smart contract itself. This may change in the future, but that is the case at the moment of recording. To describe a given value of the variant, instead of writing sp.variant and the name of the value like you do in your smart contract, in the scenario you will write sp.variant and then between parentheses the name of the variant between double quotes, comma, the value unit as a pair of parentheses. And then if you want to check if a value is a given variant, instead of writing your value.isVariant and then the name of your variant in parentheses, you write isVariant and then between parentheses the name of the variant between double quotes. Again, most likely in the future version of SmartPy, they should be unified to the same version we use in smart contracts. Let's take a look at a full example that uses variant. Here we define our custom type for the days of the week from Monday to Sunday. Then in our smart contract, we initialize the storage attribute day with the value Tuesday. We use sp.cast to make sure that we don't let the type inference determine the type of day, but we say this is day of week to make sure that all the days are possible. Then in our work entry point, we compare the value to Sunday or Saturday and determine the price based on that. And finally, in our test scenario, we can call setDay with a different syntax to create a value Sunday. And then we can verify that the value has been set to Sunday using this test-specific syntax. We can give it a try and everything works. As an exercise to practice variance, write a contract that has an order drink entry point, and that entry point should take the identifier of a drink as a parameter in the form of a variant. It should charge the user the corresponding prices. So if you order water, you pay nothing. If you order a Coca-Cola, you pay 1 Tez, or if you order Fanta, you pay 2 Tez. And the smart contract should store the items you order in a list named items. Pause the video and give it a try. Let's take a look at the solution. Here we define the custom type drink type as a variant that can have the values Coca, Fanta, water, and we added 7-Up. In our smart contract, we simply define a list. We don't need to specify the types here, but in the order drink entry point, here we cast drink as the type drink type to make sure we have all the different types, including 7-Up, as possible values of our variant. We set the default price as 0, then we use sp.match to check the different possibilities. So 1 Tez for Coca, 2 Tez for Fanta, and 0 Tez for water, etc. We could add more. Then we check that the person who ordered the drink paid the right price. And then we add that drink to the list of items. In our test, we use the other syntax to create variants to order drinks. You can give it a try, and everything works. All good. So you may wonder when you should use simple variants. Simple variants are quite convenient when you already know the final full list of possible values. So in the case of days of the week, we know that they are not expected to change. We're not going to add an 8th day of the week anytime soon. So you're pretty safe with that variant. Or if you create a game of chess, the list of chess pieces is also very unlikely to change in your game. So variants in those situations are a very good way to make sure you never attempt to assign an invalid value, and they make it convenient to use names in your code. The alternative could be using naturals from 0 to 6 for days of the week, and same for chess pieces, but it's very convenient to name each chess piece. But variants could be problematic if you ever want to allow a new value in your list. For example, for a menu item in our examples, where we use drinks, we could easily want to extend the list of drinks. For example, we could add root beer or Sprite. So in this situation, using variants is actually not a great idea. And for anything that could change where new possible values are likely to be added, using numerical values or even string values are preferable to variants. For example, here we have prepared a smart contract split in two. So this restaurant smart contract is pretty much the one we just worked on, where you can order different drinks. But then we added an entry point quick drink that uses another contract that stores the favorite drink of each user. This favorite drink smart contract has a big map, and for each user, it will store the favorite drink that this user has recorded. And then there is a view favorite that can request the favorite drink of a user. And then the restaurant can have an entry point quick drink that checks what the favorite drink of the caller is and then orders that drink. Here it happens to be a free drink if you order your favorite drink. And now let's say we want to have a new version of the restaurant where we allow a new type of drink. So for example, we add Sprite. So we create this drink type new where we have the same list of values, but we add this Sprite value that we might want to use in the new restaurant. Then we favorite drinks contract so that we don't lose all of the data and can keep honoring this quick drink offer. But if we do that, then when we create an instance of the new restaurant, it won't work. We can check it. We can see here that we're missing the variant Sprite in the type variant that we use in line 71. So that's really the type inference that is not happy when here we try to push a drink in our list, because the type of drink is not the same type that we have used in our favorite drinks contract. And there's no way to make them compatible, because from the point of view of the type inference, those two types are really different. So this shows that if you ever want to add a possible value to a variant, you could be stuck and unable to use existing smart contracts that you are used to interact with. You would have to rewrite the favorite drink and then lose all of its data, so that it can be compatible with a new restaurant. So that's clearly one case where it might not be a good idea to use variants, and instead you could just use strings or numbers. So we presented simple variants where you simply have a list of possible values, but you can do a lot more on Tezos with variants. You can have variants with parameters. For example, let's say you want to store a value that represents the current status of a worker. The worker could be available, could be absent, could be away, could be in a call, or could be in a meeting. If you know for sure that this list will never change, then this could be a good use for variants. But in some cases, we may want to add extra information specific to one of the status. So for example, if the status is away, we might want to store the expected date of the next availability of the user. So we would want to add a timestamp to this away status. Or if the person is in a call, you may want to add the URL of the online call so that somebody can join that call. So here, the parameter would be a string. And of course, we could also want to store multiple informations. In this case, you would use a record. For a meeting, you may want to store the floor and the room of the meeting. Associated with the meeting value of the variant, you may want to store a record with a string and an int. If you want to create a variant with one or more parameters, you can create values directly like this. So for no parameters, we do as we have done before, but then you can create a variant with a parameter, where between the parentheses, you simply put the value of the parameter. And here for a record, you simply put the value of the record. Of course, we recommend using a type declaration, as we have suggested before, so that you can have a precise definition of the variant. So here we would say that for the status away, the type is sp.timestamp. This is where you understand why we put sp.unit before. This was to say that there's no information or parameter associated with this status. So for simple variants, you put sp.unit, but for variants with parameter, you put the type of the parameter. So sp.timestamp for away, sp.string for call, and sp.record and the different attributes for meeting. Now, how do you check the value of a variant that has a parameter? So let's say we have a status variable in the storage that has one of the following values. It can be either absent or away and with this timestamp. To test if the status is absent, we can use a simple comparison as we have done before. You can check assert self.data.status equals sp.variant.absent. But this won't work if we want to check if the status is away, whatever the timestamp value is. You cannot just compare to away because it would be away and a value. So if you want to check if a value is of a specific variant, independently of the value of the parameter, you can use this syntax. You can do assert self.data.status.is_variant.away. This will make sure that the status is away with some value. If you want to extract the value of the parameter from a variant, you can use unwrap. So you take your variable status and then .unwrap and the name of your variant. So for example, if you want to extract the time associated with the status away, that we have defined like this, sp.variant.away of this timestamp, then you can extract the value of this timestamp like this. You can say deadline equals self.data.status.unwrap.away. This should return the value sp.timestamp of 12345 that is contained in the variant as we defined here. If the current value of the status is not of the away variant, then it will raise an error. As before, in the current version of SmartPy, as we record this video, the test scenario is still using an old syntax to unwrap the value of a variant. You will write contract.data.status.open_variant of _away. So this is different from what you use in the smart contract itself, where you use status.unwrap.away. We can expect that in the future you will be using this syntax in the test scenarios as well. So earlier, when we were working with simple variants, we used the match and with construct to handle the possible values of a variant. We can use that for variants with parameters as well. At the end of the with line for a given variant, we can use as and the name of a variable. And when the variant matches this case, this variable name will contain the value of the parameter. Here's an example where deadline will contain the value of the parameter when the status is away. So we write with sp.case.away as deadline. And then we can use the value deadline that is basically unwrapped from the value of status and compare it to some value. If the parameter is a record, the variable will simply contain the value of the entire record. Nothing special there. Let's try this on an example. We'll create a contract that manages the status of an employee. And so the employee can be available, absent, away until a certain date, in a call, but we store the URL where the call can be joined, or in a meeting in a given room of a given name and on a given floor where the floor is a natural number. The employee should be able to set their status with a setStatus entry point, and their boss should be able to invite them to a meeting unless they are currently unavailable. Let's take a look at the code. At the beginning of our module, we will define two custom types. The main custom type is for the status, where we have a variant that can be available with no parameter, absent with no parameter, away with a timestamp, call with a string, that is the URL to join the call, and then meeting with the floor and the room. We'll talk about the other type in a little bit. We have a contract, employee status, that will store the status of a given employee. We initialize it with available, and we also store the owner of the contract and the boss of that employee. We have an Entrypoints set status, where the owner of the contract can change the status, so the owner here would be the employee themselves. We have a set status entry point where the employee is allowed to change the status to a new value. So here, this is where we indicate that status is of this type to make sure the type inference doesn't forget any possible value for the variant. Then we have our invite entry point that allows the boss of that employee to invite them to a call or to a meeting. And here we indicate what type of event they want to invite the employee to. So this is why we need to describe this event type that can be a subset of the different values of the status type. So in this other type, we can have two possible values, either a call with a URL or a meeting with a floor and a room. We make sure the caller is the boss, and then we'll have this first section where we determine if the employee can be interrupted and is available for this call. So by default, they can be interrupted. If they're available, that's fine. If they're absent, well, they cannot be interrupted, they're not here. If they're already in a call or already in a meeting, then they cannot be interrupted. But if they mark that they were away until a certain date, then they can be interrupted if that deadline is passed. So if we are after the time that they were supposed to be away. Then we check that indeed they can be interrupted. And then depending on the type of event, we set status to a call or to a meeting. Here you can see that we cannot set the status to the value of the event itself because they're not of the same type. Those are two different variants. So we recreate the call and recreate the meeting here with the meeting information that we extract from the event. And we have a simple corresponding test, and we can check that everything works. All good. Let's do a recap of the syntax you use when you manipulate variants. If you want to define a variant type, you write sp.variant, and then between parentheses, the list of potential values, where each value consists in a name, then equal, and then the type of parameter associated to that name. If there's no type, you can write sp.unit. Then when you want to create a value, you write sp.variant dot and the name of your variant. If there is no parameter, then you just put a pair of parentheses with nothing in between. But you can also put a value of a parameter if it's a variant with a parameter. If you want to check if it's a given variant, when it's a simple variant, you could simply compare it to the exact same value, to sp.variant and then variant name 1. but if it has a parameter, you cannot do that. So you do assert your variable dot is variant dot the name of the variant. So that ignores the parameter and checks if you're that variant. If you want to extract the value of a variant with a parameter, you use unwrap. So you take your variable dot unwrap dot and the name of the variant, and then this will return the value of the parameter. To execute different code depending on the value of a variant, we saw that you can use the sp.match syntax. So you write with sp.match, and then between parentheses your value, and then you have different cases, starting with sp.case, the name of a variant, colon, then the code you execute if that value is of that variant. If the variant has a parameter, you use the same syntax, but you add as value. This is the name of a variable that you give and where the value of the parameter will be put. And then you can use it during this code. At the moment, in a test scenario, you use a syntax that's a bit different. If you want to create a value, you use sp.variant and then between parentheses a string that contains the name of the variant, then the value, and if the value is nothing, you put a pair of parentheses to represent the value unit, nothing. If you want to check if it's a given variant, you can write scenario.verify of your variable .isVariant and then between parentheses the string that represents the name of the variant. If you want to extract the value from a variant in a test scenario, then you write your variable .openVariant and then the name of your variant between double quotes. We discussed earlier when to use simple variants. We can ask the same question about when to use variants with a parameter or when to use parameters with a variant. As we stated before, variants can be convenient if the list of possible values never changes. The same applies in the case of variants with parameters, both for the list of cases for the variant and for each case for the type of the parameter. But you don't need to know all the values of the parameter in advance for this to work. You just need to know their type. The main use of variants with parameters on Tezos is actually an internal use, because in Michelson, entry points are really variants. Each entry point you call has a parameter that corresponds to a different value of a variant, where the name of your entry point is the name of the variant. So the parameter of a smart contract is a variant type with a different entry point and their parameters. Internally, variant types are represented as a binary tree. If we look at the Michelson code for a status example where it can be either absent, available, away, on a call, or on a meeting, internally we have this structure of nested ORs, and we can represent it as a tree with the main OR here with two children, each of them being an OR between two values. This one is between absent and available, and the other one is between away with a parameter timestamp and either a call or a meeting. And when you want to describe a value of a variant, what you describe is a path in that tree where you go left or right at each step. So for example, if you want to describe the value available, you go left and right. So in Michelson, you write left, right unit for the value available. If you wanted to have the value call, you would write right, right, left, and then a string to represent the variant call. So this is good to know if you ever see errors related to variants or even entry points that talk about variants. Okay, so as an exercise to work with variants and parameters, let's create a new version of our fast food contract where we add more choices. And here we listed all the different choices. You can either buy a hamburger, an ice cream, a drink, or a brownie. The hamburger will be 8 Tez by default. It has a parameter for the type of sauce, that is a string, a parameter for the quantity of sauce, that is a natural, and the price will be increased by 0.2 Tez for each sauce beyond the first two. So the first 2 units of sauce will be free, but then after that you need to pay 0.2 Tez for each. Then you can have a side dish with your hamburger. That itself is a variant. It can be either fries or potatoes, and the price will be 0 Tez for fries and 1 Tez for potatoes. So you have a variant within a variant for the hamburger. For the ice cream, we have 2 parameters, the flavor, a simple string, and the extra topping that is a boolean. Do you want extra topping on your ice cream or not? The price by default will be 4 Tez, and if you add an extra topping, you would pay an extra 2 Tez, and we have no choice in what topping it will be. For the drink, we simply have a parameter that is the flavor, and here instead of using a variant, because we know we want to add more types of drinks later, we decided to use a string. And to keep it simple, we said that every drink is 3 Tez. Finally, you can order a brownie. So this will be a variant without a parameter, and we charge 5 Tez. So write a version of our fast food contract that can handle all these different choices. Pause the video and give it a try. Let's look at a solution. Here the main part is to define the variant type. So we define a custom type, food type, that is a variant, where the different possible values are hamburger, ice cream, drink, and brownie. Brownie is a simple variant with parameter type sp.unit, so no parameter. Drink has a string parameter. For ice cream, we have as parameter a record with a flavor, a string, and an extra topping, a boolean. For hamburger, it's a bit more complicated. So hamburger is a record that has a type of sauce that is a string, a quantity of sauce that is a natural, and a side dish that is itself a variant that we here define directly inline. We don't create its own custom type. So we create a variant that is either fries with no parameter or potatoes with no parameter. Then in our place food order entry point, we make sure we cast the parameter as food type using our custom type. Then we initialize the price at 0, and then we will add to it depending on the type of food. So we use sp.match on the parameter food. If it's a hamburger, we extract the parameter in the variable composition. We set the initial price at 8 Tez. We extract the hamburger side, the sauce quantity. We check if the quantity of sauce is more than 2, then we add 0.2 Tez, so 200,000 new Tez for each amount of sauce beyond 2. So here we need to write -2 and do sp.asNat because we know this will be a natural. Then we match the side dish to either the variant fries, in which case we add 0, or the variant potatoes, in which case we add 1. If it's an ice cream, we extract the parameter in composition and we check if there's extra topping, in which case we add 2 Tez. And if it's a drink or a brownie, the price doesn't depend on the value. Then we check that the price is good. We have a test where we buy a hamburger with fries, an ice cream with extra topping, and a Coca, and finally a brownie. We can give it a try, and it works. All good! In this module, you will learn about the FA2 standard, and this will allow you to create tokens contract that can interact with all kinds of existing tools in the Tezos ecosystem. So when we talk about tokens, we talk about any digital representation of an asset or utility. FA2 stands for Financial Asset number 2, and it's a token standard that we use for tokens on Tezos. This token standard enables smart contracts to interact with each other and to interact with tools such as wallets. And it does so by using a set of rules, conditions, and functions that any FA2 contract need to apply. The FA2 standard supports both fungible and non-fungible tokens. There's also the FA 1.2 standard, that is an earlier standard that is simpler but only supports fungible tokens. There's also a new version of FA2 called FA 2.1 that is in preparation, and it is retrocompatible with FA2, so anything you learn about FA2 will also apply to FA 2.1. So the standard defines 3 mandatory entry points that your contract needs to have to be compatible with the FA2 standard. The balance of entry point is meant to return how many tokens of a given token ideas one or more users own. Then the transfer entry point will be used to change the ownership of a number of tokens owned by a user. And then we have an update operators entry point that will update the list of addresses that are allowed to perform transfers for a given token. The standard also defines some value that you should have in the storage of your contract called metadata, and it should contain information about the contract following another standard called TZIP16. We won't go into the details of that standard. There's also a number of optional Michelson storage views: get balance, total supply, all tokens, is operator, and token metadata, which provide pieces of code that you can execute off-chain to obtain information stored in the contract, but obtain them in a standard way. So if we try to implement a very basic FA2 contract, in the storage, we will need to store two things. We will need to store the ledger that keeps track of who owns which token and what information there are about each token. So we will store a big map. The key will be the ID of the token, and the value will be both the owner and the metadata. If we don't have any quantity value, then we will only be able to handle NFT types of token. Then we need to store operators. So that's who is allowed to interact with a given token. We'll store them in a big map, and the key will be composed of the address of the owner who set this operator, the address of the operator who is allowed to perform actions on that token, and the ID of that token. And that's it. There's no value, so the value will be unit. So as long as there's an entry in the operator's big map for a given owner, operator, and token ID, that means this owner allows this operator to perform actions in its name for this token. The balance of entry point takes as parameter two values: a callback that will need to be called to provide the result, and a list of requests, where each request is a record with the owner and the token. And it's basically asking for each of these records, please give me how many of the token this user owns. And then the balance of entry point is supposed to call the callback function passed as parameter and send it a corresponding list of results. And it will do that by sending a list of records where each record contains the content of the request, again with the owner and the token ID, and the balance for that particular token. So it basically says this user owns this much of this token. The transfer entry point is used to transfer tokens from one address to another. Its parameter is a list of batches of transfers, and each batch represents the transfer of one or more tokens from a given owner. So it will contain a field from that will represent the owner, and a list of transfers where each transfer contains a token ID and a destination. So basically each batch will say, we transfer tokens from this owner, this token ID, we transfer this amount to that other person. And we'll say that for this token ID, we transfer this amount to this destination. So when we execute it for each transfer, we will check if the caller is either the owner of that token ID or an operator for this owner and token ID. Here, as we only want to transfer NFTs, we'll simply check if the amount is 1, so is this NFT owned by this owner? So we will check that the owner really owns this token ID. And then when we're done checking all this, we can transfer the ownership of the token to the destination given in the parameter. Finally, we have the update operator, where we want to say, okay, either say that we allow this address to transfer tokens in our name, or on the other hand, we want to remove this operator from the list of operators for a given token. So the parameter of this entry point is a list of updates, where each update will say if it's an addition of operator for a token, or if we are removing an operator for this token. Then we say who is the owner of the token, what operator we want to add, and what's the token ID that we are updating this operator for. So for each update, if it's of type add operator, we will add an entry in the operator's big map we talked about earlier, and the entry will contain the owner of the token, the operator we're adding, and what token this is about. And if it's of type remove operator, we simply remove the corresponding entry. The errors that those entry points may emit are also standardized. So there's a list of different errors, but here are a few. You can have the FA2 token undefined. That's when we make a request about a token ID that doesn't exist at all. or we could have FA2 insufficient balance if you try to transfer more tokens than the owner has. Let's take a look at a simplified FA2 contract so that you have some idea of how it works. So here we define a few types. We define the transaction type, so a record that indicates a destination address for a token ID and a given amount. Then we have the operator type to define who is allowed to transfer tokens for a given owner. So we specify the owner, the address of the operator, and what token ID are we talking about. You will notice that we'll specify a layout because this is a standard. The Michelson representation has to be a very specific way for this to fit the standard. And the representation is that it should be organized as a right com, so a pair where the owner is the first element and the second element is a pair containing the address of the operator and the token ID. So we use .layout to specify that it should have exactly this structure. Then to manage operators, we have a variant that can be either adding an operator, in which case the value is a record with the owner, the operator, and the token ID, and then remove operator, where the value is also of the same type. Then we have our contract. We see that we store a big map of tokens, and next token ID, it started at 1, so every time we mint, we will increment this value and add a new token in the big map. In the mint entry point, we simply take a metadata, that is a string, and then we will create an empty set of operators that are allowed to transfer this token. So it's a set of values where each value is operator type that we just define with the owner, operator, and token ID. Then we create the NFT itself, that is a record with the owner, the metadata, and the set of operators. And now we can increment next token ID so that the next token will have a different ID. So we have the balance of entry point so that people can check how many tokens of a given ID a user has. So the request is a list where each element is a record with the owner and the token ID. So we basically asking how many of this token ID this owner has. And we prepare a list for the results where we add for each request the corresponding answer. We check that this token ID exists, otherwise we have the standard error FA2 token undefined. We fetch it from the big map. We assume by default that the balance is 0, but then if the token owner is the request owner, then their balance is 1. So we add this information to the result, so it's a list, so we use sb.const to add to the result list a record where we specify the request again and the balance that this owner owns for this token ID. So 1 if he owns it, 0 if he doesn't. Finally, we send the result back by using this callback and doing an intercontract call where we send this result and 0 Tez to that callback. We then have our update operator entry point with a list of actions, and each action is either the variant add operator or remove operator. If it is add operator, we unwrap the information from the variant to get the data. We cast it as operator type to make sure we are compatible with the standard. We fetch the token corresponding to the token ID that's in the operator data. We check that the owner of the token is the user who's trying to update the operators for that token. We also check that we are setting the operator for this owner, so the sender is the owner in the operator data. And if that's all good, then we add this operator data to that token. So we say yes, the operator address that's defined in operator data is allowed to make transfers for the token ID in the name of this owner. If the type of the variant is remove operator, then we do something similar, except this time we remove it from the set of operators. Finally, we have the transfer entry point, where we take transfers, a list of transfer as parameters, and each transfer contains a list of transactions of type transaction type. We check that we're trying to transfer one of this NFT, because it's an NFT, you can only have one. We check that the owner of the NFT is indeed who we're trying to transfer from, so that the transfer is valid. We fetch that token, and then we create the operator that indicates that we are looking for an operator for this owner. The operator is a sender, and we manipulate this token ID. So we want to check if this user is an operator in the name of the owner to do transfers for this token ID. So if there is such an operator in our set of operators for this token, then we transfer the ownership of that token ID to this address. And that's about all we have to do for a simplified FA2 contract. Then we have a marketplace contract that will interact with this FA2 contract. It needs to store the address of the corresponding token contract, and it will have a big map of offers. Every time we make an offer, we increment this offer ID. So when somebody makes a new offer, we say, I want to make an offer for this token at this price, in the sense that I'm willing to sell this token at this price. Here we don't check that the seller actually owns that token. We will check it when we do the transfer in the buy entry point. And in the buy entry point, so a buyer will call this buy entry point and say, I accept this offer. So we fetch the offer, we check that the buyer pays the amount specified in the offer. Then we obtain the token contract based on this address. We provide the type of the transfer entry point to obtain the address of the transfer entry point. And then we prepare the parameter. So we create a transaction that is a record with the sender. So that's the destination. So the caller to whom we will transfer the NFT. Here's the token ID of the NFT, and here's the amount of that NFT that they want to transfer. We make sure it's of the right type, transaction type, and then we call the transfer entry point, passing a list of transfers where each transfer is from the seller, from the address of the seller, and we have a list of transactions with only one transaction, which is what we just created here. So the marketplace says, I want to transfer this token that is supposed to be owned by the seller, and I want to transfer it to the caller, the buyer, and the amount is 1 token. So when I ask the transfer, the token will verify that I'm allowed to, and the marketplace is an operator for this owner and this token ID. We will of course check that the seller is the owner of the NFT, and if it is, we will change the ownership. And then I send the price to the seller. And here we have a test where we create a few accounts. We create the ledger itself, we create the marketplace, we mint an NFT. The owner of that NFT, Alice, creates an offer to sell her token for 10 Tez. Then we add an operator to say that the marketplace should be an operator for Alice for the token ID 1. So we add an operator, and then we test it by having Bob try to purchase the token for 10 Tez. And so if we give it a try, it all works. So this should give you an idea of what an FA2 contract is and what a contract that interacts with it is. So here we use the standard for the marketplace to interact with the token, and it should be able to interact with other tokens that are also compatible with the FA2 standard. In this module, you will learn how to develop oracles, a special type of smart contract that allows other contracts to obtain information from the off-chain world. And we will see that this makes many types of applications possible. Many smart contracts need to access off-chain data. For example, if you want to create an insurance contract that can insure an event against some heavy rain, then the insurance contract will need to access to weather data to decide if there was indeed heavy rain during your event, so you should be reimbursed for the corresponding loss. Or you could have decentralized finance contract that need to access exchange rate. For example, some contract may need to determine what the exchange rate between the US dollar and the euro is to take some other decisions. Or you could create supply chain contracts that track shipments and may need to access to the current location of a ship in order to assess the current situation of the stock, for example. Or you could imagine that some contracts may require some heavy computations that cannot reasonably be done on-chain, and so those could be done off-chain with the help of an oracle. Now, if we want to access off-chain data, could we simply call the API of some off-chain service from a smart contract when we need the data? What issues do you think this could cause? Pause the video and think about it for a minute. So, if you tried to call a REST API directly from a contract, assuming this was possible, it really wouldn't work at all. You would have three types of issues. You would have consistency issues. When you execute a smart contract, the result has to be the same on every single node. But if you use a REST API, you have no guarantee that this REST API will always give the exact same answer every time you call it. So when each of the nodes of the network would call this REST API, then some of the nodes may get a different answer from other nodes, and that would create a mess. Then you have performance issues. If the smart contract has to wait for the response from a REST API, that means pausing the execution of all the transactions in the current block. And you need everything to be done in a specific order specified by the sequence of transactions in the block. So while you wait, you don't do anything. So waiting for a REST API within a contract will slow down the execution of each block considerably. Finally, there are reliability issues. The execution of a smart contract needs to always work, no matter what. This includes running the contract weeks or years later when you want to re-execute all of the transactions from Genesis, for example. So the execution of a smart contract and the result can't depend on the availability of some external service at the moment of the execution of the contract. Now, can you think of a way to obtain this data without being confronted with those three issues? Pause the video and think about it. So, one solution is to pay for an off-chain service to fetch the data from the original source of data, and then call your contract with this data as a parameter. So instead of pulling the data from the smart contract, you push it from an off-chain source. Doing that solves all three issues. It solves the consistency issue, because once you created the transaction with the data as a parameter and inject it into a block, every node will get the same transaction, therefore will get the same data. It also solves the performance issue, because when you execute the contract, the data is immediately available to the node. They are just part of the parameters of the transaction, so it doesn't need to wait for anything to execute the contract. Once it's in the block, everything is available. Finally, it solves the reliability issues, because we can rely on the resilient architecture of a decentralized blockchain. Once data is in the block, it's available to all the nodes very quickly. But we're not really solving the problem here. We are just moving the problem somewhere else. Can you think of what could go wrong with this approach? Pause the video and think about it. So the issue is that if you rely on an off-chain service to send the data to the contract, you lose the benefits of decentralization. You lose the reliability aspect of decentralization, because the off-chain service that you rely on could simply stop sending the data to your contract, and your contract would just stop working. You also lose the trust aspect, because you have to trust that the off-chain service will send correct data to your contract. Whoever is in control of it could cheat and make it send invalid data and make it take all kinds of wrong decisions. Finally, it wouldn't solve the censorship issue, because the off-chain service could decide to refuse to send some of the data based on all kinds of different criteria, including refusing to send some data that wouldn't be beneficial to whoever is in charge of that service. So you could say, okay, if I cannot trust some off-chain service to send me the data, what about if I run my own service to fetch data from the original source and then send it to my contract? Would it solve all these issues? I wouldn't need to trust some off-chain service, I would just run it by myself. So pause the video and think about what issues this could create. So the idea is that if you run your own off-chain service to provide data to your contract, then yes, you can trust yourself, but you move the problem again. Because the whole point of a smart contract and of a blockchain is that users of the smart contract don't need to trust a third party. So here, instead of trusting this off-chain service that some other party runs, they will need to trust you, the author of the contract, to keep running your own service. And so the problem is they cannot be certain that you will always keep your service running. They also cannot be certain that you won't change the data yourself before sending it. They really have to trust you, and that's what we want to avoid to need when we use a blockchain. So even the owners of a contract shouldn't need to be trusted once the contract is deployed. So this approach may still be used if you are the original source of the data anyway, and so you need to be trusted no matter what. Then you should directly inject the data in smart contracts. Sometimes the application makes it so that we have to trust you anyway, at least for that part. Another idea, if you're not the original source of the data itself, is to have this original source send the data. Instead of you going to fetch it and then provide it to the contract, you could try to convince the original source of the data to directly call your contract. Then your contract could simply verify that the caller who's sending the data is indeed this official source. You could check their address. The issue is that convincing official sources of data to call many contracts on many blockchains is unrealistic. So for example, if you imagine that we are interested in the weather data and we want to convince a weather agency to call your smart contract and send today's weather to your contract, it's going to be quite hard to convince them to do so. They probably don't worry much about blockchains at the moment. So instead of having those sources try to call every contract that is interested in weather, we could simplify things for them and have a single contract on the blockchain that is dedicated to receiving data from this source. And this type of contract that centralizes all the data from a given type and makes it available to other contracts is what we call an oracle. That's a contract that collects off-chain data one way or another and makes it available for other contracts. But still, even convincing this weather service to send its data to a single oracle contract is not easy at all. Most potential sources of data are not involved in blockchains at all, at least not yet. So we can't really expect them to call oracles themselves. Before we continue, I really want to bring your attention to the fact that incentives for people to inject false data into an oracle can be very strong. Because when you get incorrect data from an oracle, your contract can make really bad decisions. So for example, if you have a contract that relies on knowing the exchange rate between two currencies, but obtains the wrong exchange rate, then it can make a terrible decision that could lose millions of dollars. So it can be very profitable for an attacker to cause an oracle to return an invalid value. If you check the news about blockchains and about attacks and millions that are being lost, many times those millions are lost because of exploits related to oracles, where the value provided by the oracle was manipulated, and as a result, millions were lost or stolen. Here I listed a few examples just within a window of a few months, where several millions of dollars were lost due to oracle manipulations. So it's really important to have ways to obtain accurate data from the off-chain world. So if we can't convince official sources to send their data to many different blockchains and their oracles, something that's a bit easier to convince them to do is to have these original data sources publish signed versions of their data. So instead of simply publishing on an API, here is the weather today in this city, we would just ask them to add a signature to that message. Then we could run a service that would fetch this data, an off-chain service, and that would send it to the oracle contract. And the oracle contract could then verify the signature and therefore check that the data indeed comes from the original data source. Doing this has multiple advantages. Whoever takes the data from the original source API and then sends it to the oracle by calling an entry point of the oracle, we will call them an intermediate, they can't tamper with the data. Because if they change the data, the signature will be invalid, and they can't sign themselves because the signature has to be done with the private key of the original source. So we don't actually need to trust whoever is taking care of transferring the data from the official source to the oracle, because they have no way to change that data. It's also quite reliable because you don't have to trust that some intermediate will do their job. You can rely on multiple people to do it. Anyone can run their version of that service to increase reliability and go themselves call this API, fetch the signed data, and call the oracle to make it available on-chain. Of course, this still assumes that the original source will keep publishing correct signed data. If they stop doing it, then your oracle will stop working. This kind of approach that relies on sources publishing signed data is used on Tezos by what we call harbinger oracles. And the typical source of such data is Coinbase, where we can find exchange rates between different currency pairs. Okay, let's work on an exercise where we have a contract that will use an oracle. So we created a contract called binary bets that lets user bet on the outcome of sport matches. And to keep it simple, we will assume the following. We'll assume that every game is identified by a unique value that we will call game ID. Again, to keep it simple, we'll assume that the game only has two possible outcomes, true or false. True may be that the first player won, and false means the first player lost, and therefore the second player won. And we also assume that there is an official sports federation that publishes the signed result of every game, and that we can trust. So for the exercise, we prepared most of the code of this simple binary bets contract. And your job is to write the code of an oracle and change the binary bets contract so that it calls this oracle to obtain the outcomes of the sport matches and then reward the winner of the bets. Let's take a look at the code. So here we have this binary bets contract that will store a big map of bets with the usual next bet ID that we increment every time someone bets. Then we have the oracle address, and we have the fee that we need to pay the oracle to obtain the result. Oracles are the servers that want to make money, so they may charge a fee when you request some information. Then users can call the create bet entry point to make a bet and propose a bet to someone on a given unique game ID. And they say, I bet that the result will be this. So again, to simplify, we say the result will either be true or false. So I bet that the result will be this, and we set a deadline. We say, okay, the result should be determined before this deadline. If it's not, then that means we couldn't get the data, so we cancel the bet. So we simply create an entry in the bets big map. We say whoever called this entry point is player 1. We don't know player 2 yet, so we just store the smart contract address in player 2 as a way to indicate that there is no player 2. It's easier to do than using options and setting none, but using options would be another possibility. We store the game ID. We say how much we want to bet, so we send that money to say I bet 10 Tez that this team will win. And we store, of course, the expected result, the deadline, and we say this has not been cancelled. Then another player could say, I accept this bet. So they provide the idea of that bet, and then we fetch the bet. We check that the amount they provide is the amount that the other person bet, plus the fee for the oracle. So here, whoever accepts the bet is in charge of paying the fee to the oracle. The person who creates the bet has a small advantage. We check that nobody else already accepted bet, so player 2 is still the address of the contract itself, and we check that the bet has not been cancelled. We store the address of player 2, and we store the bet. And here, since we just accepted the bet, here we create a request on the oracle to say, please send me the result of the game that we bet on, and do so before the deadline that the user set. So this part of the code is for you to write. Then we have a withdraw entry point. That's when something wants to get their money back because the bet was cancelled. So here we get the bet, we check what amount we should be paid back. If we are the player 1, then we can withdraw the funds either because the bet has been cancelled or because nobody else has accepted the bet yet. So in this case, we replace player 1 with self-address to make sure that player 1 cannot call this a second time and be reimbursed twice. Then we make sure that it's set as cancelled, and then we send the amount to whoever was calling. If the caller is not player 1, then we make sure it's player 2, otherwise they have no reason to call this entry point. We check that it has been cancelled, and then we delete player 2 by saying, okay, the address is now the address of the contract, so it's not a real user. And we add to the amount the Oracle fee that player 2 has paid. And then we do the same. So the way it could be cancelled is if somebody calls cancel after a deadline for a given bet. And here, basically the idea is to say if the Oracle didn't provide the result before the deadline that we set, then the bet can be cancelled. So here your work is to call the Oracle and get the information about whether the result was provided or not to the Oracle. And if not, then that means people can be reimbursed, so the bet is cancelled. Finally, when someone has won the bet, they can call claim prize to get their funds. So here we check that the bet hasn't been cancelled. Then we get the result from the Oracle. This should only be called once the Oracle has the result. We can check that off-chain before we make the call. If the caller is player 1, then we check, okay, did they win? Is the result what they expected the result would be? And if it's not player 1, then we make sure it's player 2. And if it is, we make sure that the result is not what the first player expected it to be. So if we don't fail, that means the caller has won. So we send them the amount of the bet times 2. And then we delete the bet so that they cannot claim the price a second time. And we need the default entry point because in case everything is cancelled, we need here the Oracle to reimburse us. And the way they reimburse us is by simply sending the fee back to this contract through the default entry point. So we should have a default entry point to be able to receive the Tez. And here we have started creating the Oracle contract, and it's going to be for you to implement it. But all you know is that the constructor takes an admin and then the public key of the source from which you will get the data. And so the idea is that when you get data from the source, you will verify that it contains a signature that matches this public key. We can now take a look at the test. So here we have created 3 usual accounts and a special account that we call data source. That will be the account that won't be an account that directly interacts with the blockchain, but that will be the account whose key is used to sign the data. So we first create our Oracle. So you provide the address of the admin, Alice, and then the public key of the data source so that we can use it to verify signatures. Then we create the betting contract and we say the fee for the Oracle is 2 Tez. Then we have a first test where everything goes as planned. So we have Alice create a bet on game with ID 1. She expects the result to be true and she says, okay, the result should come before this deadline. And she bets 5 Tez. Then Bob first tries to accept the bet, but by paying only 5 Tez. So this should not be good because Bob needs to pay for the Oracle fee, which he does in the next attempt, paying 7 Tez. Then Alice tries to claim the prize before the Oracle even got the result, so this should not work. So here you will add the part where you send the signed result to the Oracle that the Oracle will verify. After the Oracle got the result, Bob will try to claim the prize, but Bob actually lost because you sent true and Alice bet that the result was true, so Bob lost, but then Alice won, so she can claim the prize and this should work. Then we have a second test case where this time we cancel after the deadline. So in this case, the Oracle never obtains data, so as soon as the deadline passed at 1001, we cancel and everybody should be able to get their money back. And finally, we have another one where this time Bob wins. So your job is to complete this contract by writing the code for the oracle, writing all the different calls, and completing the test to send signed data to the oracle and check that everything works. Pause the video and give it a try. Let's look at a solution. So we will first start by looking at the oracle contract. In the constructor, we store the admin and the public key, but we also create a big map of requests that the oracle will receive. And we also store the fee that will be 2 Tez. When a user requests the result for a given game, they need to pass a bet idea so that we can identify their request using their bet idea for a given caller. We'll see that in a minute. And then of course they need to say for which game ID they request the result and what's the deadline for the oracle to provide this result. We indicate that bet ID and game ID are naturals and deadline is a timestamp. We check that they paid the fee and we will create an entry with the key being the bet ID and the address of the caller, because multiple contracts may call this oracle and each contract uses its own system of ideas for their bet. But for this contract, we have a unique bet ID that identifies this request. We check that there is not already an entry for this bet from that contract. Otherwise, they may overwrite a previous request and mess things up. And then we create the entry where we store that for this bet ID and this sender, this is the game idea that they request information for. This is the deadline. And we set a result that is an option that we initially set at none to indicate that we didn't receive the result yet. When we do receive the result, some service will be constantly looking from off-chain at what requests the oracle has received. And when it sees a new request, it will go fetch the data from the original source, the signed data, and then send the result of that request to this entry point. So when they do that, they know all the information about the bet. So they can provide the bet idea, they can say which contract was doing this request so that we can rebuild the key for that request. And they send the message that will contain the result, plus the signature associated with that message. The message itself will contain the game ID and the result. If you only send the signed result, but without saying which game this is, then the same result could be used for many games. And so people could cheat. It's really important to have all the information in the message so that the message is the proof that the source that signed this message claims that the result for this game is this result. So after getting the key, we fetch the request from our requests big map. We check that the game for this request is indeed the game indicated in the message. And then we check that the signature that we received corresponds to this public key signing this message that we pack. When we check a signature, it has to be a sequence of bytes that we check, so we need to pack the message before we sign it and before we verify its signature. Then we can store the result, and we have to store it as an option, so we store the result as an option on the result that was in the message. Finally, since we did our job, we received the result before the deadline, then we can send the fee to the admin. Actually, here we need to check that we didn't already get the result, so we need to assert that it was none. Otherwise, we could send the result multiple times and get the fee multiple times. The oracle will have an on-chain view so that the contract can immediately fetch the result. It will simply pass the key and it will return the result for this key. And finally, if the contract didn't get the result before the deadline, they can call cancel after deadline to get their fee back, because the oracle didn't perform their service, so they shouldn't get paid. So we say for which bet ID We didn't get the result. We fetch the corresponding request. We check, yes, indeed the deadline is passed. We check that the result is still none, so the actual result of the game has not been provided. Then we send the feedback, and to make sure somebody cannot cancel twice, we delete this request. So now that we have an oracle where we can make requests, receive the results signed by the source, obtain the result from the contract, and cancel the request and get the feedback if nobody sent the results. So in our betting contract, when we accept the bet, then we call the request game entry point from the oracle. We pass the best idea, the game idea, the deadline, and we make the call. When we want to cancel after the deadline, similarly here we call the cancel after deadline entry point here, but we do that after verifying through the get game result view that the result has not been provided, for the result is none. Finally, when we claim the prize, we call the get game result view to obtain the result. We unwrap it, and then we award the player if this player has won based on the result. In the test, here, we send the result to the oracle. So we prepare a message that contains a game ID and the result. We sign that message with the private key of the data source. So of course, this in practice would happen in some service off-chain that sees the request and then calls the smart contract. And here we call the receive result entry point. We say for which bet it is, we say for which contract, we send the message and the corresponding signature. And we do the same here with the version that shouldn't work. Let's give it a try. Everything works. And we can let you play with the code and check that everything works as expected. The oracle was presented was a very simple harbinger type of oracle, but it relied on a single source, which means we have to trust that source. And in a lot of cases, we really don't want to trust a single source, because a source of data could simply avoid publishing data that doesn't benefit them. And similarly, if we rely on a single transmitter, this single transmitter could avoid transmitting data that doesn't benefit them. In some cases, when it's about data that changes on a very frequent basis, maybe the source of the data or the transmitter could decide to only publish or transmit the values that benefit them and skip the ones that don't benefit them, when the value of a token, for example, goes up and down with time. And preventing this behavior from a single source or a single transmitter is really hard. Finally, if you rely on a single source or on a single transmitter, this causes reliability issues if this source or this transmitter stop doing their job. So what we want to do in practice to avoid, especially relying on a single source, is to combine multiple sources of data. So we can fetch data from multiple sources, one available if there are multiple sources. For example, for the weather, there may be different agencies that publish information about the weather, or for the exchange rate between the US dollar and the euro. You can expect a lot of places to be able to provide that information independently. And you could also rely on multiple transmitters to take care of sending this data to the oracle. So you should never rely on single transmitter and check their address. Anyone should be able to send this data. The data is signed anyway, so we don't need to trust the transmitters, so we could have multiple transmitters running at any time. And then the oracles that would get information from multiple sources would have to check that enough sources agree with the result, and enough sources provided the result. And if there's a set of different values, we could take the median of the value as the actual value that the oracle would return. And if this is about a value that changes over time at high frequencies, such as an exchange rate, we also want to average it over a short period of time so that we can avoid flukes. like between two different calls, it goes up or down, up. So you want to average it over a period of time to have a better estimate of what's the current value. We won't go into detail of different ways to do that, but some of the ways to do that include doing some of this work off-chain. So this idea of using messages that are signed by official sources is great, but in practice, unfortunately, very few sources of data publish such signed data for blockchains for the moment. But even if they didn't plan to publish signed data, they actually do so for other reasons. In particular, when you access the website of a service or you access a REST API, you usually do so through the HTTPS protocol. But using HTTPS means that the data is encrypted using the private key of the domain's certificate. So this means you can verify the authenticity of the data when you decrypt the data that the API returns through the public key of the certificate using SSL. So this cannot really be done in a smart contract. You cannot send the full HTTPS response to an oracle and expect the oracle to decrypt it. So what we need is a service that we can trust and that will take care of doing this HTTPS request to the web page or the API of the original source that publishes the data, then decrypt the HTTPS response, extract the data you need from that response, and then sign it and send it to an oracle. So if we do trust the service that does that, then everything is good. But of course the issue is how can we run a service off-chain that does all that and that we can trust? To have such a service, we will need to set it up on an architecture that really guarantees that it runs on unified code. So you write the piece of code that does all that, and you have to run it on an architecture that will tell you, yes, this is the code that what was actually executed. And this service will fetch the data directly from a source using HTTPS request, and then we'll call the Oracle contract with that data, along with the proof that all the code was executed unmodified. And all the Oracle would have to do is check that proof to verify that the service has not been tampered with, and indeed the script that you wanted to execute is the one that was executed. This is actually possible using what we call Trusted Execution Environment, or TEEs for short. TEEs are architectures that guarantee that the software that is run by the service has not been modified and corresponds to a specific hash. So you provide the code, you compute its hash, and the service will be able to provide a proof that the code that was run was the code that matches this hash. And it can also guarantee that the SSL connection it used to fetch the data was secured and the data hasn't been tampered with. There are a number of providers of trusted execution environments, and this really means running some specific hardware in a special mode that guarantees that nobody has tampered with the machine, even the people who have physical access to the machine. There are different solutions to do that, but one of it is to use some Android phones that have the right hardware to be able to provide this kind of security. On Tezos, we can use the Icarus service that specializes in using TEEs using Android and provides a service where we can set up this type of oracles based on the safety net architecture. You run your mobile phone in a special mode where you cannot do anything else. All they can do is execute scripts in such a way that you cannot interfere with them. If you want to learn more about oracles, we invite you to check the in-depth oracles article on opentezos.com.
In this module and the next few ones, you will learn how to detect flaws in smart contract and learn about best practices to avoid these flaws in your own smart contracts. A first flaw is related to the use of the sp.source command. There are two ways in a smart contract to check who called the contract. So far we have used sp.sender that gives you the address of the direct caller of your contract. But you can also use sp.source, which gives the address of the user who is at the origin of the chain of calls of smart contracts. So for example, if a user A calls a contract B, and that contract B then calls a contract C, from within the contract C, sp.sender will correspond to the address of B, so the direct caller of contract C. But sp.source will correspond to the address of A, the user who is at the beginning of the chain of call. So user A called contract B, that called contract C, but since A is the initial caller, that's what you get when you use sp.source. But it's never a good idea to use sp.source. And it can be used for attacks, so I recommend for you never to use sp.source. So for example, if you look at this small smart contract, can you find the flaw and how someone could take advantage of it? So this is a contract for a charity where people can deposit some funds using a deposit entry point here. And then the admin can decide to donate some of the funds that have been given to a specific charity. So you say how much you send and to which charity. So think about how someone could take advantage of a flaw in this contract related to the use of sp.source. Pause the video and think about it for a minute. So the issue is that an attacker could convince the admin of charity fund to donate to a fake charity. And it could be a very small charity and could be just for a few Tez, but when the charity fund donates to the fake charity, the transfer of Tez to this other contract would call the default entry point of that fake charity contract, and that entry point could then call charityfund.donate, and by doing that impersonate the admin. So from the point of view of donate, if we look at the code, here we check that the original caller is the admin. But if we call the fake charity from here, then the fake charity calls donate again, but with a different amount for the donation and with a different charity, then they could trick the admin into donating all of the balance of the contract to some destination address. The different steps would be that the admin calls charityfund.donate of 1 Tez to the fake charity. Then charityfund.donate would transfer some Tez to fake charity, therefore calling the default entry point of fake charity. And then this default entry point would call charityfund.donate, let's say with 1,000 Tez, and with the destination being the attacker address. And so charityfund.donate would check that SP source is indeed the admin and assume, okay, the source is the admin, therefore it's the intention of the admin to do that transfer. And then would transfer 1,000 Tez to the attacker address. So basically the admin thinks they're just donating 1 Tez to some contract, but in practice 1,000 Tez will be spent. So this is very dangerous. There is a very easy way to fix that flaw. It's simply to avoid using sp.source and instead use sp.sender. So to require the admin to make a direct call to charityfund.donate, and this way they cannot be tricked into doing something else. More generally, if a contract uses sp.source to identify who is calling the contract, all you have to do is trick the admin to call a small smart contract you created that only requires a small amount to be transferred, but then your small contract could do anything in the name of the admin with that contract that uses sp.source. So make sure you simply avoid using sp.source. There's never any good reason to use it as far as I know. Here is the code of the fake charity contract. It stores the address of the contract to attack, so the charity fund stores the address of the attacker, and then when its default entry point is called, here when the charity fund sends some Tez to it, then it calls the donate entry point of the charity fund, but with the donation of 1,000 Tez to the address of the attacker. And that's it. All you need to do then is convince the admin to donate 1 Tez from the contract to your fake charity. You can give it a try, and you see that indeed 1,000 Tez are transferred to the attacker's address. A second type of flaw that is extremely common, so you should always be very careful, is when using sp.send, especially if it's a destination that is not the caller of the contract. And even in some case when it is the caller of the smart contract. So you should be very careful when using sp.send. Here is an example of a part of a contract that is likely to have this kind of flaw, where we send 10 Tez to some address and then 10,000 Tez to you, to the caller. Here, Some address could actually be the address of a smart contract. That means when we call send to transfer 10 Tez to this address, it calls the default entry point of that contract, and that default entry point could fail. And this would make the whole smart contract fail, therefore it would prevent the transfer of 10,000 Tez to your address. So you should always be careful. Whenever you send some Tez to some address, you should think about what if this address is actually a smart contract that has a default entry point that rejects the funds. So for example, let's say the destination of this first call is this contract. We see that it has a default entry point that checks if the boolean open is set to true. So we initially set it to true, but we have this set state entry point where the admin can set the state of the open value to true or false. So this way you can control when you're allowed to receive the funds, and therefore control when this contract is going to fail or work. So by using this contract, you could block some user from getting the money that is owed to them, and then extort some extra money from them as a condition for you to enable the transfer of Tez to your contract. So changing the state of open. So you can tell, okay, I know you have 10,000 Tez stuck in this contract. I have the power to unlock it. So give me 1,000 Tez and I will unlock it for you. So that's a way to extort funds. So the best practice to avoid this kind of flaw is to always let users claim their own Tez through a separate claim entry point. We have already seen that in the NFT with royalties contract, where we had this exact issue. And allowing this claim entry point may require you to add a ledger to your contract if there are multiple users that may have Tez in the balance of the contract that need to claim. So if you add a ledger, a big map that for each user address keeps track of how much is owned to them by the contract, then anytime you want to send some Tez to someone, instead of doing a sp.send, you simply add that value to their entry in the ledger. That's something we already did with a multiple NFT with fixed contract that we saw in another module. Another common flaw is related to unlimited computations. And we talked about this already. On Tezos, we have this notion of gas. That is an estimate of the amount of CPU used by a transaction. And when you emit this transaction, you have to pay a fee that covers this gas. But there is a limit to how much gas you can spend in a single transaction. There's also a limit to how much gas you can spend in a given block. But if a contract call exceeds that limit of how much gas you can spend in a transaction, the call will fail. And this may mean funds will get stuck in the contract. So it is very important to make sure that the gas consumption of a contract can't grow indefinitely and exceed that amount. To avoid this kind of flaw, you have to avoid storing data that can grow indefinitely, because you have to remember that the storage of a smart contract has to be deserialized at the beginning of every call to an entry point and has to be reserialized at the end of the entry point. And this costs gas. So you need to make sure that you check this whenever you use lists, sets, and maps, and even basic types that can grow indefinitely. For example, strings can be as long as you want, or int, nut, and timestamp. In general, the idea is to use big maps whenever you want to store unlimited amount of data, because you can have as many entries as you like in a big map. You only pay for the deserialization and serialization whenever you access a specific entry of the big map. But of course, if that entry is too big, then you still could spend too much to deserialize it. So it doesn't guarantee that you won't have any issue. So make sure you don't store too much in a single entry of a big map. Another option in some cases is to consider storing data off-chain. If you don't actually need the data on-chain, you don't need the smart contracts to have access to it, you may store them off-chain. So for example, you could store it on IPFS. So the second part to avoid unlimited computations is to avoid loops, where the number of iterations of the loop can grow indefinitely. And to avoid that, you can usually do the computations off-chain and let the contract focus on verifying that everything you computed is correct. And when you cannot do the computation off-chain, another possibility is to split the computations into multiple contract calls, so that in the first call you do part of the computation, and then in the second call you can continue the computation that might be necessary. the best option is to try to do the computations off-chain whenever you can. For example, let's take a look at this contract. This contract, called TimeSafe, can store deposits that will be stored in the balance of the contract and can only be withdrawn by the owner after a certain deadline. So whenever you deposit some money for the owner, you set a deadline and you say, okay, they will only be able to withdraw that amount after this deadline. And here we add all the deposits in the list, and whenever the user wants to withdraw, we loop through the list, find out all the deposits that have a deadline that is expired, and then count the corresponding amount, and then transfer that amount to the owner. So here, we clearly have a data structure in the storage that can grow indefinitely. Someone could make very small donations and deposit many different amounts, but very tiny amounts, like 1 microtez at a time. So much so that the size of the list would be so big that deserializing the data would take too long and exceed the maximum of gas you can spend in a transaction. So here the idea is that this list can grow indefinitely. Nobody can control how much it can grow. There are some ways to limit it. You could just set a hard limit on how many deposits there can be at a given time, and then delete the deposit when you withdraw the corresponding money. Or you could make it that a deposit has to be at least 100 Tez, so it would be extremely costly for someone to add so much, to make so many deposits that the contract could get stuck. But a better approach is to use a different data structure and use a big map. Here is a version of the contract that uses a big map for the deposits. We count how many deposits there has been so that we can use this as a key for the big map with all the deposits. And whenever somebody calls deposit, we create an entry with the key being the current value of the counter. And in this entry, we record the sender, the deadline, and the amount. And this way, each entry with all the entries in a big map, the data structure can never be so big that just calling an entry point would deserialize the whole thing and then exceed the maximum amount of gas you can spend in a transaction. However, we still have a loop here that goes through all the different elements of the big map by trying every possible counter. And so in practice, we still have to deserialize everything when we try to withdraw. So we can solve the problem for the deposit entry point that can never fail because it's not going to deserialize the whole content of the big map. But then in withdraw, we have a loop. So the loop itself may have too many iterations and exceed the total amount of gas you can spend in a transaction. But more so, you will have to deserialize all of the content of the big map. So that doesn't solve the problem. To solve this problem, instead of a loop that goes through all of the elements, we can do the computation off-chain of which entries have expired deadlines. So instead of looping through every single entry in the big map and then checking if the deadline is expired, we do that computation off-chain, and then when we call withdraw, we send a list of keys where the deadlines have expired. And so the loop here only enumerates all the entries that have been listed in the parameter. It could still be possible that the list is so long that we cannot execute the whole loop, but then we can split the call into multiple calls and then maybe do only half of the list so that we only need to loop through half of them and deserialize half of the entries. The caller has control over how many items they put in the list. So in this case, we are safe. We avoided using the type of data structure that can go indefinitely by instead using a big map, and we avoided doing a loop that can grow indefinitely and instead did the computation off-chain and let the user send a list of items that they get money from. And that solves our problem. In this module, you will learn how you can reduce the amount of fees you need to pay when using a micropayments contract where you have to perform a lot of transactions to buy low-cost items. So the challenge is to create a micropayments contract. Let's say a person A very often wants to buy cheap items from a seller B and wants to pay using Tez. So we will have transactions where user A gives some amount of new Tez to B, a small amount compared to transaction fees. And then B will give some item to A. So A buys an item from B, but at a very small price.
So the question is, how can we do that in the cheapest possible way? We don't want to have to pay a transaction fee for every purchase. If the item is very cheap, we might end up paying more in transaction fees than what we actually need to pay for the item. But we want to do that by still enjoying the security of the blockchain. We don't want B to have to trust A or A to have to trust B, but we can allow for a little bit of risk. So for example, B could accept that maybe they will lose the amount for one sale, but no more than one. So B might accept that they will lose the price of one item purchased by A, but no more than that. So with this constraint, try to think about a way you can reduce the transaction fees to the minimum. Pause the video and think about it for a minute. If we really want to avoid paying too many transaction fees, the best way is to avoid doing transactions, at least on-chain. Every time you do an on-chain transaction, you need to pay a fee. But we could handle most of these transactions off-chain using signed messages. The idea is that we would create a micropayment contract where user A will put some amount of Tez, a deposit, on the micropayment contract that is reserved for A's future purchases from B. So that amount is really strictly reserved for B. And we set a deadline. The idea is that A may withdraw those funds, but only after that deadline. So the idea is that B knows that there is some amount for them that will be available in the contract until that deadline. Once we have that deposit in the micropayment contract, every time A wants to purchase an item from B, instead of doing a transaction on the chain and calling the contract and paying the fee, A will send a signed message to B. So a message would say, I hereby declare that I owe you this amount of money. More precisely, I can say the amount I owe you is now X mu Tez. Signed A. And of course, the signature will be a cryptographic signature that a smart contract could verify. So this message is directly sent to B off-chain without going through any smart contracts. Any way, it could be by email, it could be any means. And then once B receives that message, they have a proof that A owes them money, and so they can send the corresponding item to A. Whenever B wants to get paid, whether it's because the deadline is getting close, so they want to make sure A doesn't withdraw the deposit from the contract, or whether there's quite a bit of money already that they want to have, and they're ready to pay a transaction fee to get that money. Then B could call the micropayment contract and send it the last signed message signed by A that says, I owe this much to B. The smart contract could then verify the signature, and if the signature is valid, then the contract could send whatever amount A owes to B. So to do that, we need to be able to sign and verify signatures. On Tezos, you can sign any piece of data as long as it is in the form of a sequence of bytes. That's the only type of data you can sign. But thankfully, we can convert pretty much any data to a sequence of bytes and back. We can use the pack instruction to convert typed data into a sequence of bytes. And later, we can unpack this content to extract the typed content. So it could be a record, for example. We pack the record, we just get a simple sequence of bytes. Then later on, we can unpack it and get the record back. Once we have a sequence of bytes, we can use a function called makeSignature to generate a signature for a given sequence of byte. And of course, we use a given private key to generate this signature. On the other side, the destination of the message can use checkSignature to verify the validity of a signature, verify that it corresponds to the public key of whoever is sending it. So let's look at the syntax. To pack and unpack data, it's pretty straightforward. You can call sp.pack of your type data. Could be almost anything. Could be a number, could be a record, could be a list, anything you liked. And then you get a pack data that is of type bytes. Then you can unpack this data by calling sp.unpack. You pass the data, and then you pass the description of the type of this data.
This returns an option. It could be none if it's impossible to unpack this data into this type. It could be a different type. So we use unwrap sum to get the original data back. Once we have packed data, we can use make signature to create a corresponding signature, and we pass the secret key of the user and the packed data, and we obtain a signature. When we want to check the signature, we call sp.checkSignature. We pass this time the public key of the user who is supposed to have signed this message. We pass the signature and we pass the packed data. So this verifies if the signature corresponds to this packed data signed by the person who has this public key. We don't need the secret key to verify the signature. And this returns true if this is indeed a signature that corresponds to this message and this public key. With that, your job is to write the corresponding contract with its tests. The storage will simply need to contain a big map with all the deposits. What is the key and the value for each entry is up to you. And we will have 3 entry points. One entry point for someone to deposit some funds for a given seller. So we say who are these funds for. We set a deadline after which we will be able to withdraw the money back, and we send our public key so that we can sign messages and have the contract verify that they come from us. So whatever amount is sent to deposit, sp.amount, will be stored as a deposit from the sender to this destination. So we create an entry in this big map or update it if there's already one. When a seller wants to get paid, they can call claim payments. They say, I want to get some funds from this user, and here is the message they last sent me. And here is the corresponding signature. So the contract will check that the signature is valid for this message. So the signature is indeed a signature for this message using the public key we stored for this source. So the public key we passed here. Once it checked that the signature is valid, it can transfer the amount that the source owes to the caller. And then it will update the corresponding deposit entry. Finally, when a user wants to close their account and withdraw their deposit, they say, I want to close my account that I have with this seller. So we fetch the corresponding entry in the big map. We check that the deadline has passed, and we transfer any funds that haven't been withdrawn yet. Here we purposely left some details for you to work on. So your goal is to implement this contract and try to make sure that there are no flaws that somebody could use to steal some funds or get funds stuck. Pause the video and give it a try. Let's look at a potential solution. Here in the deposit big map, we will create entries where the key is composed of the source and the destination. So a deposit is really some funds we store for a source and a destination. So it makes sense to have an entry for each pair, source of destination. Here we use a record. We could also use a pair as a key. Then we check if there's already an entry, and if not, we create one. We store the deadline, the amount that was sent, the public key, and we also store how much has been spent so far out of this amount. And if there is already an entry, we verify that the new deadline is after the previous deadline. We can only extend the deadline. We cannot bring it closer to the present. Otherwise, it would be too easy for A to get their money back, even though B trusted that that money would be available in the contract. So we can only extend the deadline. And here we update the deadline and we add the newly deposited amount to the amount stored in the deposit. Once there is a deposit for some user reserved for a destination, then this user and this destination, this seller, can freely exchange messages where A sends messages that says, I now owe you this much, and then B says, okay, then I can send you this item, etc. And the amount A owes to B increases. And when the deadline gets near, or when the amount is quite a bit and B wants to get it out of the contract, B can call claim payments. They say, I want to claim the payments from this source. And here's the last message they sent me, this last I owe you. And here is the signature that proves that it comes from them. So we get the key for the corresponding deposit. Then we check the signature. So we check that this signature corresponds to this packed message with this public key. So it has indeed been signed by the public key we stored for this user. Then we unpack the message. And in the message, we store the destination and how much the author of this message owes to this destination. So the total they owe so far since the beginning. We check that the destination is the person who's claiming the payment. Then we compute how much they need to pay to them now. And that amount is the amount indicated in the message, so how much I owe you so far, minus how much we already sent them before, so how much they already spent in the previous message. So the idea is that A always increases the amount they owe to B since the very beginning. Because if A sent, I owe you 10 more Tez than last time, we would need a complicated system to track, okay, when was this message sent? How much did we owe last time, etc. It would be hard to really know how much we need to send to B. But if we simply accumulate how much A has spent in the beginning and then how much we already took from the deposit and sent to B, then it makes the computation simple. So the amount we need to pay is the amount A owes so far minus what we already got from them. We make sure they have enough in their deposit to pay for that amount. If not, that means B accepted payments for which there was no corresponding deposit. So B made a mistake and they could maybe send a previous message where A didn't owe as much. Then we update the amount in the deposit. We subtract the amount we are paying to B. We increase the total amount that we are paying to B so far. We add amount to pay. And then we send that amount to the sender. So send that amount to the seller, to B. Finally, when A wants to close their account, we fetch the key. We check that this is after the deadline. And then we send whatever is left in the deposit. And we delete the deposit. In the test, we create different accounts. And here in the test, we create a deposit from Alice that deposits 100 Tez for the seller Bob with the deadline 1,000. Then when Alice wants to spend a little bit of money and purchase something from Bob, she can create a message that says, I now owe 5 Tez to Bob. She has to pack the message and then sign it with her secret key. So this is done offline. She could send more and more of these messages, increasing the amount every time by the price of the item she wants to purchase. And then eventually, when Bob feels, okay, now it's time for me to get paid, Bob will call claim payment, saying, I want to be paid using the deposit from Alice. Here is the last message I received. Here is the corresponding signature Alice sent me. And Bob gets paid. We can give it a try. And we can see that indeed Bob gets paid. Unfortunately, there is a big flaw in this contract. Pause the video and take a minute to try to find it. There's a couple similar flaws in this version of the contract. The first one is that if Alice closes her account, we delete everything, and later on she decides to do some business again with Bob. Then she would deposit some money again, saying, okay, I'm depositing some money, I want to make new purchases. Bob could steal her money. Can you figure out how? Pause the video and think about it for a minute. So the issue is that if Bob saved this message and the corresponding signature, Bob could send the message again to claim payments and get the same amount again. Alice didn't make any new purchase, but Bob still has a copy of this I owe you 5 Tez from Alice, and the signature is still valid, the message is still valid, so claim payments would simply send the 5 Tez to Bob. Now, how can we avoid this? Pause the video and think about it for a minute. So what we really want is to make sure that the same message cannot be used
again by Bob. There's a couple ways to do that. One way would be to never close deposit here. Instead of sending everything and deleting the deposit and resetting everything, and then forgetting that there was already a history between Alice and Bob, we could simply reduce the amount deposited to 0, but keep the record in our big map. This way, we remember that the amount spent so far is already 5 Tez. So if Bob sends a message that says Alice owes me 5 Tez, then we check, well, you already received 5 Tez from Alice, so there's nothing Alice owes you. And if Alice wants to make a new purchase, she would have to say, okay, I now owe you 5 plus X Tez. Then Bob could claim the extra X Tez. So that's one way to do it, never to close the account. Another more typical way to do it is to make each deposit entry a bit more unique by adding some information, adding a counter, similarly to what we do to transactions. If you remember our description of how transactions are verified, transactions have a signature, but to avoid transaction being replayed, we add a counter to each transaction that says how many transactions has this user signed so far. So we could do exactly the same here. When we deposit, we could add some counter that we store, and that the author of the deposit should increment every time they deposit some money. If we are simply adding to the existing funds, we shouldn't count the counter. This is a counter of how many times we recreated the deposit. And then when we claim payments in the packed message, we should have the value of the counter. And here we could check that the counter for the message equals the counter for the deposit. And of course, when we sign messages, we need to add a counter as well. So if we close the contract, created a new one, then we would use a counter 2 so that messages for a given deposit cannot be reused next time we recreate a deposit. And here, when we deposit, we have to send the counter. So counter all good. But we still have a flaw. And the flaw comes from the same idea of the same signed message being replayed, being reused in a different context. So now that we have this counter in the message that says, okay, this is the third time that we create a deposit, and so everything should be reset, and every message from previous deposits are not valid anymore, but still, it would be possible in some cases for Bob to steal money from Alice. Pause the video and think about it for a minute. So the issue here is that we could have multiple instances of this micropayments contract. And there is nothing in the messages that says that those messages are about this contract. So we could even imagine that a very different contract just happens to have a structure of messages that contains a record with a destination, with an amount, and with a counter that would have nothing to do with micropayments. It's just used for something else. And then Alice and Bob happen to be using that other contract. So using a message with the same structure for a different contract, Bob could claim payments and extracts funds from this contract that has nothing to do with this message. And the way to solve that is to add to the message the address of the contract that we are talking about. So here we would need to add contract equals micropayments address to make sure this is about this contract. And then here we would get
contract sp.address, and then we check message.contract equals sp.self address. This time a message destined to a different contract couldn't be reused in our contract. This makes everything a lot safer. So this idea of always having some kind of counter in the messages and identifying for which contract the message is, and really making sure that the information is complete, that says everything we need to verify, then you can avoid this flaw of being able to replace signed messages. In this video, we'll look at a smart contract that enables people to play a geocaching game, and we'll discuss a number of potential flaws in this smart contract. Geocaching is a game where one person hides one or more little treasures somewhere in the world. It could be anywhere. And then they publish hints about the location of these treasures, and the players use these hints to try to find those items. So here, the goal is to create a smart contract that makes it easy to play this game. For each treasure, we assign a unique identifier and a password. So if you find a capsule containing a treasure, you can call a contract to prove that you indeed found the treasure and the password and ID that it contains. And so we could make it into a game where the person who finds the most treasures gets a reward. So the interesting part in this contract is that we will need to be able to verify that a player found a given password, but we can't simply store the passwords directly in the contract. As we discussed before, the storage of the smart contract is public. So if we simply store the passwords in the contract, anyone can simply see the password and then send them to the contract and pretend that they found the treasure. So the question is, how can we verify passwords without storing them? Pause the video and think about it for a minute. So a typical way to verify passwords without saving them is to store the hash of the passwords. That's what most authentication systems use. They store hashes of passwords, typically with added salt, so that they can authenticate users without keeping the actual password in the database. So here we will use a cryptographic hash function that we apply to passwords, and those have a few key properties. For the same input, they always produce the same output that we call the hash of that input. And if you're given a hash, it is virtually impossible to find an input that produces this hash, unless you actually know the original input or unless you try every single possible value, which typically would take way too long for anyone to ever find the correct input value. So the input value, here the actual password that we will hash, needs to be large enough that it's impossible to simply try every single password and check if it gives a given hash. So instead of comparing the password to a stored password, our contract can verify a password by computing its hash and then comparing it to the stored hash. So let's take a look at the first version of this smart contract. In the storage, we will keep a big map with all the treasures. And we will see that for each treasure, the key is an identifier, a simple number that we increment every time we add a treasure. And the value is a record that will contain the hash of the password and a flag that says if somebody found this treasure. Then we will keep the scores of the different players. So for each player, we'll keep their current score. We will maintain the address of the current winner. We initialize it with the owner's address. And then we also need to initialize the score of the owner to 0, so that as soon as somebody finds a treasure, they can become the current winner, and we can compare their score to the score of the owner. We separately store the address of the owner. We store a deadline, after which we will give the award to the winner, and then we count the number of treasures. The owner is able to create a number of treasures, and all he needs to send to the smart contract is the hash of the password. We check that he does that before the deadline and that only the owner can call this contract. We increment the number of treasure
and then we store the information and say this treasure has not been found yet. Then when somebody discovers a treasure, they need to send the ID of the treasure and the corresponding password. So we check that they do so before the deadline. We obtain information about the treasure. We check that it hasn't been found yet. Then we compute the hash of the password that was sent using sp.blake2b, and we compare it to the hash of the treasure. If it's correct, then that means the treasure has been found, and we just have to increment the score of the player. So if there's no entry for that player in the big map, we create one with score 0, and then we increment their score by 1. And if their score is more than the score of the current winner, then they become the new current winner. Finally, after the deadline, the owner can call this award price entry point. We check that he does so after the deadline, and then we simply send the whole balance of the contract to the winner. So whatever the owner decided to send as a reward when they called, for example, create treasure. And then we have a test where we check that everything goes well. Now, unfortunately, there are a couple of flaws with this contract. Pause the video and try to see if you can figure them out already. To help you, remember that flaws in smart contracts can typically have two types of consequences. Either someone can steal some value from the contract and other users, or some value can get stuck in the contract. Pause the video and try to see if this helps you find the bugs in our geocaching contract. So the first flaw is that you can have funds stuck in the contract. And this is due with the way that the award prize entry point has been implemented. How could this piece of code make it so that the funds are stuck in the contract? What could possibly go wrong? And think about it from the point of view of the winner. How could your funds get stuck after you won the game? Pause the video and think about it for a minute. Well, the issue is that here, for the winner to get their prize, we need the owner to call the entry point. But you could imagine that the owner doesn't call the entry point for a number of reasons. For example, they could simply forget to call that entry point, or they may be unable to call it. For example, what if they lost their private key? And they could also do that on purpose. They could say, okay, I'll give you your prize, but you have to do this for me. And they could try to extort money from the winner before they give them their prize. Here, that would be a bit weird, but that could be one of the reasons why the owner doesn't call the entry point that awards money to the winner. And you could say, well, that's the organizer of the prize. I mean, yes, if the organizer of a game is not available anymore and decides not to play, well, yeah, it's okay to imagine. And in this kind of situation, the winner wouldn't get their prize. But the whole point of a blockchain, the whole point of using smart contracts is to avoid having to trust that some specific person will do what they are supposed to do. We don't want to have to trust a third party. And here we don't want to have to trust that the organizer will do what they're supposed to do. So the question for you is, how can we solve this? How can we make sure that we don't have to trust the owner? Pause the video and think about it for a minute. The solution is simply to let the winner, or actually anyone, call the entry point themselves. There's really no need for it to be the owner. We simply verify that the deadline has passed. And then if it has and somebody calls that entry point, then we send the funds to the winner. So the best practice in your smart contract is to avoid unnecessarily requiring that a specific third party performs an action. If there's really no need for that to be the owner of the contract or someone else, then just don't verify it and let anyone call the entry point. So here we can simply delete that line and everything still works just fine, even if the owner forgets to call that entry point. So that fixes the first flaw. Now the second flaw is that somebody can actually steal money that should go to someone. And by that, I mean somebody who didn't find a treasure could still become the winner. So pause the video and think about how you would do that. How could you claim the prize without actually having found any real treasure? So the second flaw is due to the fact that all transactions are public. So as soon as you send a transaction to a node, you can assume that everyone can see it. It will be known by whoever owns that node, and then this node will send the transaction to all its neighbors and then to other neighbors, etc. So all the nodes will receive the transactions before it's even considered for being added in the block. And if you send the password and the ID in your transaction, then everybody sees your password. So anyone can create their own transaction with the same password and pretend that they found that treasure. And to make sure that they get the point and not you, they can add a fee for their transaction that is a bit higher than yours, so that the baker is more likely to take their transactions first before they take yours, and they will get the point and you won't. This kind of attack is what we call BPEV flaws, block producer extractable values, and sometimes also called MEV, maximum extractable value. So the idea is you can have bots that always analyze all the transactions that travel through the peer-to-peer network, and they analyze those transactions to see if there's any valuable information in there. And especially they simulate what would happen if they perform this transaction from their own address. And if the outcome of that transaction benefits them, if they see that after the transaction is over, their balance has been increased, then they will emit the transaction, but with a higher fee than the original one. So there's a whole bunch of bots on all blockchains that look for this kind of transactions and then copy them and send them again, but with their own address and a slightly higher fee. And so since you have many different bots that do that, eventually the fee goes up and up and up, right up to the limit where it's not profitable anymore to keep increasing the fee. So in the end, it's likely to be the baker who will make the most profit because they benefit from that higher fee. So that's why we call it block producer extractable value, because whoever creates the block gets all the benefits of these increased fees. And the baker, the block producer, can even make sure that they are the ones whose transaction is taken, because they get to pick which transaction are added to the next block. So they could just decide, okay, I'm going to get the treasure. I'm going to be the one creating a copy of this transaction and getting the benefits. So one way or another, the block producer is able to take advantage of this flaw. So here, someone who didn't find the treasure could just look for the password in one of the transactions and then claim to have found the treasure by sending the same password, but with a higher fee. So the question is, how can you protect your contract so that this kind of attack wouldn't work? Pause the video and think about it for a couple of minutes. So to protect against block producer extractable values, there are a number of approaches, and none of them is ideal, but we can try to find one that would work well for this contract. A good way to think about this is to try to imagine that you are in a real room with a number of people and there's a transparent box in that room, and your goal is to go around and find treasures, and when you find them, you need to put a piece of paper in that transparent box. And so you can write the password on a piece of paper and you add the ID of the treasure and your name so that you can claim to be the first one who found that treasure. And of course you destroy the password so that another person cannot claim it. And then there will be 10 minutes until the game master opens the box. Then this game master will look at all the messages and check the passwords and count who found the most treasures. So if you imagine this situation, how would you make sure that other people don't copy your password, that they can see through the transparent box, so that they can lie and claim that they found that treasure? And if you can think of a way to do that in this room with this transparent box, think about a way that you could apply this idea to a smart contract. Pause the video and think about it for a minute. So the solution would be that as you write the treasure idea, the password, and your name to a piece of paper, to prevent other people from copying it, you would just simply fold the piece of paper. This way, the game master would have to unfold each piece of paper before counting who found the most treasures. And you would make sure that once the game master starts unfolding the pieces of paper, making them visible for everyone, you wouldn't let anyone else add their own piece of paper to the box. So this way, as the pieces of paper are folded, nobody can read them until it's too late to add a piece of paper in the box. Now, how could you do something similar in your smart contract? on the blockchain. Pause the video and think about it for a minute. So one way we could do this would be to encrypt that information. So instead of sending the treasure ID, password, and your address as a clear message in a transaction, you would first encrypt it. Of course, the contract wouldn't be able to know the decryption key because anything that the contract knows is public. So you cannot have a key in the contract that they would use to decrypt that information. So instead, you wait until the deadline is passed, and then you send the decryption key so that the smart contract can extract the value from your encrypted message. So this way you have to know all the information so that you can encrypt the message before the deadline, and then after the deadline you reveal the message by sending the key that you use to encrypt it so that the smart contract can decrypt it and check if you did indeed find the treasure. It's important to include your address in this encrypted message, otherwise people could still copy your transaction and send the same message and later send the same decryption key. So this approach would work, but it's a bit costly because encryption functions are pretty costly, so you don't want to run them in a smart contract. Can you think of another way to do that? Similar way, but that might be a little bit less costly. Pause the video and think about it for a minute. So a second approach to solve this, but very similar, is what we call the commit and reveal scheme. And the idea is instead of encrypting the information, we simply send a hash of the information. And then in the second phase, we send the actual information. So we have two phases. The first phase is the commit phase, where each player can send the hash of their message containing the ID of the treasurer, the password, and their address. And then we have a reveal phase, where after the deadline, each player can send the message itself. Then the contract can compute the hash of the message, compare it to the one that the user has sent before, and if it is correct, they can award the point to that user. And computing a hash is less costly than using any encryption algorithm. But it's actually possible to make it even faster. And to help you, think that the best way to save gas is to do as much as you can off-chain rather than on-chain. So if there's any computation you can avoid doing in the smart contract itself, but instead do it off-chain, then you can save a lot of CPU, therefore gas. Pause the video and think about it for a minute. So the third approach is to still use this commit and reveal scheme. So you still commit before the first deadline by sending a hash of the message with the ID, the password, and your address. And then you still reveal after the first deadline, where every player sends the actual message. But instead of immediately having the smart contract check if the hash corresponds to their previous message, you let other players check themselves. And if they see a message from a player that doesn't correspond to the hash that this player sent earlier, then they can call an entry point to say, hey, this player is trying to cheat. They're sending a message that doesn't correspond to the hash they sent earlier. And if the player indeed cheated, then the smart contract can check, verify, yes, indeed, this message doesn't match the hash that they sent, so I will eliminate them or maybe even punish them. So this way, we don't always check and compute the hash to verify that the hash of the message corresponds to the hash that the user previously sent. We only do it if somebody complains. So we have a second deadline and people have some time to complain before we award the prize. In practice, you can expect that nobody will try to cheat, so the actual computation of the hash will never need to be done. So let's take a look at the updated contract. So here on top of the treasures and score per users, we store a big map with all the commits that people make once they find the treasure. And we also keep a value of a deposit that every player will have to send to the contract as they register. This way they can be punished if they do something bad, and other people can be rewarded for denunciating anything bad that they did. So we'll see that in a minute. And then this time we will have 3 different deadlines. The deadline for people to commit the hash of their message, the deadline for revealing the actual message, and the deadline for other players to dispute a message if they think somebody tried to cheat. We add a register player entry point so that people can register before the deadline to commit and send their deposit. And we use this as an opportunity to set their score to 0. Then we still have our create treasure entry point for the owner to create treasures. And they still store the hash of the password. Then when somebody finds a treasure, they can send a hash of their message to this commit discover treasure entry point. So they send the ID of the treasure and the corresponding message. And this is a hashed message, so it will be of type sp.bytes. We check that the owner themselves cannot play, so we don't allow the owner to commit a message. We check that this is before the deadline to commit. We check that we didn't already receive this message. This is not really necessary, I can remove that. Then we mark that we received that commit. Then we have the entry point that people call once the commit deadline is passed and it's time to reveal their message. And this time they send the actual password. We check that they do that before the deadline to reveal. We get the corresponding treasure. We check that the treasure has not been found. Then we mark the treasure as found. We store the password for this treasure, and we also store the player who found it. Then we increase the score of that user, assuming that they are not lying, that they actually did send a password that corresponds to their previous commit. And we check, did they get more points than the current winner? And if they did, then we store them as the new current winner. But now, if somebody says, hey, this person claimed to have found this treasure, but that's not true, that's not the case, somebody else found it, then we can call this dispute discovery entry point. We check that it's not too late to dispute it. We obtain the corresponding treasure. We check that indeed somebody claimed that they found it. Then we check, did the password that they send actually correspond to the password for that treasure? So does it match the hash of the treasure? We didn't even check that they send the right password when we called reveal discovered treasure. We assume that the person can be trusted. But here somebody disagrees, so we check, did they send the right password? So we generate the message that they should send that includes the password and the address of the user, so whoever claimed that they won. We compute the hash and we check that indeed this person didn't commit a message corresponding to this hash. So that means this whoever is disputing is correct because the hash of that message was not committed. Then we simply eliminate that player if they have not already been eliminated by someone else. And then we send the deposit from that player to whoever calls this a dispute entry point. If that player was the current winner, then we reset the current winner to the owner. We mark the treasure as not having been found, so that if someone else has actually found it, they can reveal that they found it, so they can call the reveal discover treasure if it's still not too late. And to make sure they have time to do so, we add some time to the reveal deadline, an hour, and we also add 1 hour to the dispute deadline. So one issue here is that we don't have the winner anymore, and we cannot loop through all the different scores to see who is the new winner now that we eliminated someone. So we have to add an extra entry point, update winner, where we will check that this is before the deadline to dispute anything, and then we check that whoever is calling this actually has a higher score than whoever is marked as the current winner. And then if they do, then we update them as the new current winner. So anyone can say, hey, I'm actually the winner. Look, my score is better than whoever has claimed to be the winner so far. Finally, when the deadline for the dispute time is over, then the current winner can claim their funds. So the code here, and especially the code of dispute discover, is a bit more complicated, but in practice, since there is a way for anyone to tell if you cheated, and you will be punished if you cheated, this part of the code is very likely never to be executed, so you won't pay for the cost of it. But you need to make sure that there's no bug in there. So as you can see, preventing block producer extractable value can be a bit complicated, make the code a bit more complicated, but this is necessary to make sure nobody steals your funds. There's actually still a way to cheat, at least in some situations. And this way is to prevent people from scoring for treasures that they found. But this can be costly. So can you think about it for a minute and find a way that somebody could prevent you from getting the points for your treasure if they're really motivated to make sure you don't win? Pause the video and think about it for a minute. So that approach that can be used in some situations is to actually attack the blockchain itself, preventing some transactions from going through by sending so many transactions that this user's transaction may not be accepted. And for that, you have to keep in mind that bakers typically select the most profitable transactions. And most profitable means you add an extra fee on top of the minimum fee that you should send to pay for the gas. So this means that if you send enough transactions with relatively high fees, you could prevent legitimate transactions from being added to blocks. So if you send many transactions with high fees, you will fill the blocks until the deadline, and none of the regular transactions will be added unless somebody notices and pays a higher fee. This would be very costly, but if there's just a little bit of time left for other players to submit their treasures they find at the last minute, then it could be worth it depending on what the reward would be. So the different ways to avoid this kind of situation can be to give enough time between deadlines for this to be really expensive. So of course you could always prevent people from submitting their commit or reveal at the very last moment, but then it's up to them if they don't do that. So make sure you give people enough time so that nobody can block transactions during the whole window of time. And another way to avoid this is for players to be a baker themselves so that they can make sure they give priority to their own commit and reveal transactions. And so this could be either if you're the owner of the contract and you want to make sure nobody can do that for your contract, you can be a baker. And then once in a while, you make sure the transactions for your contract are accepted so that you can guarantee that your service is always reliable. But of course, anyone else, players themselves, could make sure they are bakers so that they can do that themselves. So when the stakes are high, it makes sense for big entities that rely on smart contracts to be bakers themselves so that they can make sure that their transactions go through. In this module, we'll talk about randomness. Picking random numbers in a smart contract is a very interesting but hard problem. So let's say you want to organize a raffle where every participant can register and pay 100 Tez, and after a deadline, one of these participants is picked randomly and they get the whole balance of the contract as a prize. So the questions for you are, how would you structure this contract? What would you store? What would be the entry points, etc.? And most importantly, how would you pick the winner among all these participants? Pause the video and think about it for a minute. The structure of the contract itself is relatively easy. In the storage, you will store all the participants. You need to use a big map to avoid any gas issues. And the key will be an ID, and the value will be the address of the participant. For the ID, we will simply use a counter, and we will count the number of participants. So a natural that we initially set at 0, and every time a new participant registers, we will increment this value. Then we set a deadline for everybody to register. Now we have 2 entry points, one for participants to bid, where we check that they do indeed send 100 Tez to the contract. We check that they do that before the deadline. We assign their address to their ID, so the current number of participants, and then we increment this value by 1. So we basically register that they participated in the raffle. Finally, after the deadline, they can claim their prize. Whoever is the winner will be able to claim their prize. We check who the winner is by picking a random value between 0 and the number of participants minus 1. And then we send the balance of the contract to the corresponding participant. So that's for the structure. Now the hard question is, There is no such random function available on Tezos. So without such a function, how can you pick the winner? Pause the video and think about it for a couple of minutes. In a regular program you run on your computer, when you pick a random number, it usually consists in calling a function that uses a mathematical function that produces a randomish sequence of numbers. So we show here an example of such a basic version of a function where you take the current value, you multiply it with a big prime number, you add some value, etc. And then to make it between 0 and some value, you take the modulo of that value. And then to make sure that every time you run the program, you don't get the same sequence, you initialize with some randomish source of entropy. And we typically will take the current timestamp, because on a regular computer, that can be in microseconds, so that changes all the time, and it's hard to predict. So the question is, can you do that in a smart contract using sp.now for your seed? And if you can or cannot, try to think about why. Pause the video and think about it for a minute. So using sp.now as a source of randomness to initialize the seed of your function is a terrible idea. First, the value of sp.now is expressed in seconds. So there's really not much precision, it doesn't change too often. And since you have blocks every 15 seconds, there's really only a few values that are possible for a given block. But more than that, the baker of the previous block actually gets to pick the exact value. So it's not random at all, it's just some person on the computer, their computer picks it one way or another, but the baker has control over that value. So the idea is that in practice, the value sp.now is not the actual timestamp of the current block in the sense of when was this block created. It's actually 15 seconds plus the actual creation time of the previous block. And the idea is that in each block, there's really two timestamps. There's the timestamp that's the actual time where the block was created, at least according to the baker. And then there is the value of sp.now, that is 15 seconds plus the timestamp of the previous block. So really the baker of the previous block gets to pick what will be the value of sp.now in the next block. So in practice, when you look at the actual value of sp.now, it tends to be every 15 seconds. So it makes it extremely predictable, which makes it a really bad source of randomness. It can be predicted and it can be controlled by a baker. Okay, so now that we get this idea out of the way, can you think of any better ideas? Pause the video and think about it for a minute. Some ideas people tend to have is to use hashes as sources of randomness. When you look at a hash, it looks pretty random. You just change one bit of the input and it changes everything in the output. So it looks pretty random. But be careful, it may look random. It's actually very predictable. If you know the input, of course, the output will always be the same. But more than that, just like the time, the baker can manipulate it, because the hash of a block is really computed based on the content of the block, based on what transactions there are. And so if a baker creates a block with a number of transactions, then compute the hash, and somehow that hash is not good for them. It will not produce the right random number when you run the smart contract. Then they could just try a different set of transactions to obtain a different hash for their block. So they do have some control on the value of the hash simply because it can make multiple attempts at creating a block, and it will give different values for the hash, therefore different random values for whoever is using this hash as a source of randomness. Another reason why you shouldn't use the hash of a block as a source of randomness is simply that you cannot access the hash of a block from a smart contract. So this is clearly not a possibility. Another idea would be to deploy a contract, because when you deploy a contract from a smart contract, you can obtain the hash of the operation that is created. And this is something you can do from within the smart contract. Unfortunately, the value of this hash depends on different things that the baker can control. So the baker, again, can manipulate it in the same way as the hash of the block. So we cannot use that as a source of randomness. Finally, an idea people sometimes have is to use the address of participants. But if you do that, for example, if you add up all the addresses of the different participants to compute a random number, then whoever is the last participant to consider bidding can predict the outcome of their choice. They will see, okay, if I bid, here's what the outcome will be by adding my address to the total number. So they can decide if they want to bid or not, depending on whether it makes them win. So the address of participants, again, is predictable. And so the result would be not only predictable, but controllable by some participants. So that wouldn't work either. Another idea people tend to have is to increase the randomness by mixing different values. Some ideas people have is to get the exchange rate between two currencies. For example, the current exchange rate between the euro and the US dollar. And you would say, well, if somebody could control that, then they could be rich. And obviously nobody can control precisely what the exchange rate will be on the DEX. But then you cannot predict it within maybe a few tens of percents, but of course you can predict the main value. So you don't have too much randomness that come out of that, just a few bits. Then you say, okay, I can combine that with other source of randomness, for example, other pairs of currencies. This is something you should be careful about. When you try to combine different sources of randomness, you get more bits of randomness for sure. So you increase the range of different values you can pick from. But the whole result is actually as weak as the weakest of these sources. So if somebody can manipulate one of the exchange rates one way or another, then they can manipulate the outcome. So it's actually dangerous from the point of view of making sure people cannot control the outcome to mix multiple sources of randomness. Another issue is that the exchange rate of a decentralized exchange can be manipulated. For example, you could do a couple of transactions. You could first buy or sell one of the two currencies of the DEX. That may impact the exchange rate. If you buy dollars, it makes dollars a bit more expensive. And then if right after that you call the contract that will compute the random number, then your initial call will impact the result of your random number selection. Since everything is deterministic, you can compute in advance what the impact of any process of sale of currencies on that DEX will have as a result. So you can just try different values and see which one generates the random value you're looking for. So you can control it and know exactly in advance what the outcome will be. So that doesn't make it a good source of randomness either. Another idea people can have is to use a randomness oracle, so rely on some off-chain source to generate a random number. But it's not as easy as it sounds. If you use a basic oracles, just some guy who's sending random numbers to a smart contract, then whoever that person is controls every single number. And if they forget to send the number, you are also stuck. So this can be dangerous. So you could use more advanced oracles, such as Chainlink VRF, verifiable random functions. This could work if it was available from Tezos, but you're basically moving the problem away. The kind of problem that Chainlink has to solve is exactly what we're trying to solve here. And even in that case, you should be very careful about trusting this kind of oracles. Sometimes there's possibility for collusions between different people that make it not as random as you would like. Finally, as we discussed in oracles, you can use a trusted execution environment oracle like Acorest. This may be the best solution based on oracles at the moment, but again, you need to make sure that the whole solution is safe. And it's not always easy to have all the details about a given oracles to really be convinced that the randomness is really secure. But this last option might be the best for an oracle that produces random numbers at the moment on Tezos. But what we really want is to make sure nobody in particular controls the random value, and that you don't need to trust some entity to keep producing those random values. So we want to use a decentralized source of randomness. How can we do that? It's actually possible. So the idea is for multiple users, and here it could be the participants in the raffle, to cooperate and produce a random number together. And the hard part in that is to make sure that none of the participants can manipulate the outcome and make it be something they like. So to try to think about a decentralized way to do that, try to imagine that you are in a room, in a physical room with 10 people, and as 10 people, you have no dice, no coins, etc. You just each have a pen and a piece of paper. So the question is, in that situation, how would you generate a random number that none of you can control? pause the video and think about it for a minute. So one way that people could pick a winner among themselves would be if each of the 10 people could assign a direct number to each of them. So one way to randomly pick a winner among those 10 people is to first assign a direct number to each of them from 0 to 9. Then each of them would write a random number on their piece of paper and show it to everyone. Then each person could write a number on their piece of paper and show it to everyone. Then anyone can sum all these 10 numbers and obtain a big random number. Then you could take the last digit of this number, of the sum, which would be a value between 0 and 9, and that gives you the winner. Would this work? Try to think about issues with this approach. Pause the video and think about it for a minute. So the issue is that someone could cheat and control the outcome if they wait for everyone to reveal their number, and if they're fast at computing, they just quickly sum up all these numbers, the 9 other people, to obtain the current total. And then from that, they can decide what number they should give, so that when they add this number to the total, it gives a result that makes them win. So that's pretty easy to cheat. How can we avoid this? Pause the video and think about it. So the solution is to use something we presented earlier with the geocaching smart contract. We want to prevent users from changing their numbers once others start revealing theirs. So in our physical room, we could have each person write a random number on their piece of paper, but do so discreetly, and then they immediately turn the paper over to hide the number from others, or they just fold it in half. And then, when everybody is done writing the numbers, we ask everyone to put their pencil down so that they cannot change their numbers anymore. And once it's all done, every participant can reveal their number, show it to everyone, and then everybody can sum up the value and pick the winner. If we do that, there's still a flaw in this process. Can you figure out what it is? Pause the video and think about it for a minute. So the issue is that someone could decide not to reveal their number to help a teammate. So let's say we have these 10 users, numbered from 0 to 9, and they all already committed a random value from 0 to 9 that we have here. But then 2 people, Eve and Gwen, have not revealed yet. But let's say Eve and Gwen are actually friends and teamed up, and they already waited for everyone to reveal, and they know, okay, the current total is 33. Now they get to decide, okay, if Gwen reveals her number, but Gwen doesn't, and we just add all the numbers that we revealed before the deadline, then we add 33 plus 4, so the total would be 37. That would make Iris win, so the last digit would be 7. But if Eve reveals her number, but Gwen doesn't, then the total would be 35, and Gwen would win. So by doing this, just deciding who between Eve and Gwen reveals, then they can decide the best strategy to increase their chance of winning. So basically the 2 of them can generate 3 outcomes that gives them a chance at winning. Either they both reveal, so we get 2 plus 4, or only Eve reveals, so we get 2, or only Gwen reveals, so we get 4, that we add to 33. And for each of these 3 possibilities, it generates a different outcome, a different winner. So they can pick out of these 3 possibilities which one is the best for them. Then the question is, how can we avoid this issue? So the idea here is to force people to reveal, to make sure that nobody is going to want to use this strategy. The first approach is to use a financial incentive. You ask each player to deposit some extra money on top of their bid at the beginning of the game. And if they don't reveal, they simply lose their deposit. So they have a very strong incentive to reveal, because otherwise they would just lose some money. But then the question is, how much would this deposit be? And the issue is that for this to work, as with just a few people, they can control the outcome. If you have 10 people in a team out of 100 people who bid, 10 people can generate 1,023 different outcomes. So they're very likely to have one strategy that makes one of them win. So you pretty much want the deposit to be as large as the reward. So if it's a big raffle where you can win 1 million Tez, nobody will want to deposit 1 million Tez. But this could work for a small raffle. There's another approach that is using brute force, and we'll see in a moment. If it's in the physical room, we have someone steal Gwen's paper and reveal it for everyone. I would call that brute force. And we can actually give people an incentive to do that. If Gwen doesn't reveal, we can reward that person with Gwen's deposit. So if we can do that, Gwen won't dare to cheat. So then the question is, how can we do this on the blockchain? We've already seen it in the geocaching smart contract. If we use incentives but no brute force, we can use a set of phases and deadlines. So we have a registration phase where participants bid and deposit Tez. Each participant is assigned a number. Then we have a commit phase where each user gets to pick a random value and they send a hash of that value to the contract. We have the reveal phase where each user sends their chosen value. This value must match their hash. Finally, after the reveal phase ends and everybody revealed, the winner can collect all the bids, and then everybody who revealed gets their deposit back. So your job is to write a smart contract that uses this approach to organize a raffle. Pause the video and give it a try.
Let's take a look at the solution. In this raffle contract, we store the bid amount, so how much people need to bid to take part in the raffle. Then we store how much they need to deposit for the financial incentives. Then we store two deadlines, the deadline for them to commit the hash of their random number, and then the deadline for them to reveal the random number they picked that corresponds to the hash. In the big map, we store all the information about the players. We will store the address, we will store the hash of their random number, and we will store whether they're already revealed or not. Then we store the number of players, and this will serve as a key for the players' big map. Then we'll store how much has been deposited, how much has been bid, so that we can know what the total price will be. And then we have a total that will be the sum of all the random values. Finally, we need to keep track of how many people have revealed. Then the bid entry point. This is the entry point that people call during the commit phase, where they need to send the hash of the random value that they picked. They need to send their bid and their deposit, so we check that the amount is equal to the sum of both. They need to do so before the deadline to commit, so we check that. Then we store all the information about the player, the address, the hash of their value, and they haven't revealed yet. And we can then increment the number of players and update the total amount of the deposits and the total amount of bids. In the next phase, the reveal phase, each player has to reveal their actual random value. Since we use an ID as the key for players, we ask people to send their ID instead of sending their address, for example, and they can easily find it out off-chain. We check that they call this entry point before the end of the reveal phase. We check that they have not revealed yet, otherwise they would be able to reveal multiple times and then manipulate the outcome. We check that the hash of the random value they sent is the same as the hash that they sent during the commit phase. Then we mark that they now have revealed. We update the total of the random numbers by adding their random value. Then we increment the number of people who revealed. After the deadline to reveal, the winner can claim their prize. So we check that they do so after the deadline. Then we determine who is the winner. To do that, we divide the total of the random values by the number of players, and we take the remainder using sp.mod. And this gives us the ID of the winner of the raffle. We fetch their address. We make sure they're revealed. If they did reveal, they cannot win, so they cannot claim the prize. And then we compute how much we need to send to them. So we send them the prize, the total amount of bids, plus their share of the deposit. So the idea is that if somebody didn't reveal, they don't get their deposit back, and we share it among the other players. So to send their share to the winner, we divide the total amount deposited by the number of people who revealed using split tokens. So they get a fraction of the total deposit, 1 over the number of people who revealed. We send them that amount, and then we delete them from the players so that they cannot try to claim the prize again. Then we have an entry point to send their deposits back to players who did reveal but didn't win. We don't need to check who is calling it. It doesn't matter. I mean, most likely they will be calling it, but there's no need to check it. They need again to send their ID. We check that they try to get their deposit after the deadline. We make sure they're revealed. We get their address, and then we need to compute the amount that needs to be shared between the players who revealed. To do that, we take the total amount of deposits, but then we need to find out if to that total we need to add the prize. If there is no winner, if the winner didn't reveal, then we need to share the prize between all the players who did reveal. So we compute again, similarly as here, the ID of the winner. We check if they are still a player. If not, that means they already claimed their prize, so we don't need to worry about sharing the prize. And if they didn't reveal, then we add the total prize, the total of bids, to the amount to share. Then we divide that amount by the number of people who revealed, we send it to the user, and we delete that user from the players to make sure they cannot claim again. Then we have a test where we have a few people play, commit their hash of their numbers, then reveal them, and some don't reveal, and then the winner can claim their prize, etc. It's a small test. In a real test, you will need to do a lot more than this to check all the different possibilities. We can give it a try, and we see that everything works. All good? Now, the issue with this approach of using financial incentives to force people to reveal is that the amount they need to deposit should be similar to the total amount that they may win. But in a raffle, if you imagine a big raffle where there's 1,000 players and 1,000,000 Tez to win, very few people would have the means to put 1,000,000 Tez as a deposit. And if they did, they probably wouldn't want to risk it just for a small raffle where they have a small chance of winning. So financial intensive work, if it's a small raffle, if it's a deposit can be small enough, but in some cases the deposit itself makes it unlikely that people will take part. So we need a better solution, and for that we will use cryptography. So the solution is to force people to reveal, or at least make sure that their number is revealed by using cryptography and a cryptographic primitive called time lock. In a sense, it's using brute force to reveal number for them, for people who didn't reveal themselves. And time lock is a cryptographic primitive that we will use instead of a hash. So instead of hashing and sending the hash of the number we picked, we send a time lock of that value. And a time lock has the properties that it's like an encryption mechanism, but where if you are given enough time, anyone can actually decrypt it. But it has the property that if you only have a certain number of minutes, let's say X minutes, we could say 10 minutes, then nobody will be able to crack it and decrypt it without the private key. Even if you have the most powerful computer in the world, even if you have a specialized ASIC, so a specialized hardware dedicated to decrypting time locks, or even you have a FPGA that you program to decrypt time locks really fast, you still won't have time to decrypt it in this number of minutes. On the other hand, if you have enough time, let's say 100 times that amount, then anyone can decrypt it, even with a regular computer, without the private key. And so the idea is that the encryption algorithm takes a number of iterations on a single processor. You cannot parallelize the computation, so you cannot use hundreds of computers in the data center. You have to use a single processor. And so given enough time, whatever computer you have, you will be able to decrypt it. So this duration of how long it takes at the minimum with the fastest possible computer you may find has to be more than the amount of time people have in the commit phase. So that between the time that the first person commits their number and the time that the last person can commit theirs, this amount of time should be shorter than the smallest amount that anyone with the fastest computer will need to crack the time lock, crack the chest, and find out what your number was. Then it has to be still small enough that during the reveal phase, if somebody didn't reveal, somebody with a regular computer can crack the value in a reasonable amount of time, let's say 10 hours, and reveal for that person. And the idea is that if somebody doesn't reveal, then someone else can reveal for them and be rewarded. So there's really no point for someone to not reveal because they will lose their deposit and someone will reveal their number for them anyway and be rewarded for doing that computation. So you gain no benefit in not revealing your number. So with this approach, we can have a commit and reveal system where we make sure that everybody's value is revealed and we find the right. In this module, we will talk about re-entrancy flaws. It's a type of flaw that is particularly hard to detect, but easy to prevent. Re-entrancy bugs happen when the contract calls another contract, and then that other contract calls the original contract again in such a way that it breaks the assumptions you make in this original contract. There was a very famous re-entrancy attack that caused the DAO hack on Ethereum in June 2016. And that attack was so serious that it eventually led to the fork of Ethereum into the current Ethereum and Ethereum Classic, as the community split between deciding to rewrite history to avoid the attack or simply accept it with Ethereum Classic. On Tezos, the languages are designed in such a way that re-entrancy bugs are less likely. But we will see that re-entrancy bugs are still possible on Tezos. We will also see a way that we can prevent them. We'll take an example where we have two contracts that manage unique tokens identified by the ideas. The first contract is a ledger contract that simply keeps track of who owns each token. So it has an admin contract that can call it and make changes, and it simply stores a big map of tokens with the token ID as a key and the address of the owner as a value. Then we have an on-chain view to obtain the current owner for a given token ID, and then an entry point to change the owner of a given token ID to a new owner. And only the admin contract is able to change this owner. Then we have a purchaser contract, that is the admin of the ledger contract. And this purchaser contract is simply in charge of purchasing tokens at predefined prices. So we store the address of the ledger contract and in a big map, a list of prices. So for each token ID, we store the corresponding price. And that's the price at which the purchaser is willing to buy a given token. Then the owner of a token is allowed to call the apply offer entry point for a given token ID. Say, okay, I'm willing to sell you that token at the price you listed. So we check that the caller is indeed the owner of the token by calling this view getTokenOwner of the ledger. Then the contract sends the corresponding price to the caller. And one thing to keep in mind is that the transfer of Tez is not immediate, but we create a transfer that will be executed after this entry point is over. Then we call the change owner entry point of the ledger to say, okay, I'm the new owner. So the purchaser contract becomes the new owner of token ID. And again, we add this to the list of operations to execute after the end of this entry point. With that in mind, can you figure out how this contract could be attacked? And by attacked, we mean how could funds or assets be stolen from this contract or get stuck in this contract? Pause the video and think about it for a minute. So the key idea of the attack is to call this apply offer entry point twice and get paid twice before the ownership change actually happens. So while apply offer is taking place and all its consequence is taking place, but before the actual change to the owner is made, we call apply offer a second time. Note that on a blockchain, you cannot run two transactions in parallel. If a user simply creates two transactions to call apply offer twice, the first call will be completely over before the second one can be executed. We don't have concurrent execution of different transactions, so you never need to worry about that. But it's still possible to have a call to apply offer before the owner is changed. Can you figure out how this can be done? Pause the video and think about it for a minute. So let's look at the code of an attacker contract. So we will assume that the contract below is the owner of the token with ID 42,
And we also assume that the purchaser contract lists this token for a price of 100 Tez. So it's ready to purchase it for 100 Tez. And then we will call attacker.attack of the purchaser with token ID 42. In the storage, we will store a number of calls and the token ID for the token that we are trying to attack. During the attack, we set the number of calls to 2. We'll talk about why in a minute. And we store the token ID. And then all we do is accept the offer by calling purchaser.applyOffer, saying, yes, I'm willing to sell you my token 42 for the price you listed, which is 100 Tez. So far, nothing special. You'd simply have a contract that accepts the offer from the purchaser contract. But the trick is to also have a default entry point in this attacker contract. And to have this default entry point also call apply offers. And the idea is that we accept the offer a second time before the ownership of our token is transferred to the purchaser. And to avoid doing that indefinitely, since when we accept the offer a second time, the purchase contract will again send us 100 Tez and call the default entry point again. And so to avoid an infinite recursion, we have this nbCalls variable in the storage that we set initially at 2, and every time the default entry point is called, we decrement it by 1. And when it reaches 0, we stop calling applyOffer. So in practice, we only call it twice. We call it here the first time, and then the first time we receive 100 Tez, then we'll call it again. But the second time we receive 100 Tez, we don't call it anymore. So this contract uses re-entrancy to steal 100 Tez from the purchaser contract. And again, the idea is that when the attacker calls applyOffer for the token ID 42, so the attacker is indeed the owner of token 42, we send 100 Tez to this attacker, but you have to keep in mind that we don't directly transfer 100 Tez, we add a transaction to the list of transactions that will be executed after we execute applyOffer. Then we add another transaction to this list, which is to call the ledger to change the owner of that token to ourselves, to the purchaser contract. Those two transactions are added to a stack of transactions to execute after the applyOffer entry point is completed. So once it's completed, we take the top of the stack, which is this transaction, we transfer 100 Tez to the caller, but we also call the default entry point of the attacker, which then create another call that will be added at the top of the stack, and that calls applyOffer a second time. And when applyOffer is called a second time, we check that the owner is the caller, and it's still the case because we haven't changed the ownership yet. Then we will add 2 transactions to the stack. At the top of the stack, we'll add a transaction to transfer 100 Tez to the attacker again, and then right below it, another call to change the ownership of the token to the attacker. Then we execute the transaction at the top of the stack, which is to transfer 100 Tez to the caller, call the default entry point, but this time nbCalls gets to 0, so nothing happens. And then finally, we have this call to change the ownership of the token to the purchaser that was added to the top of the stack by the second applyOffer call. And then finally, we have the same one, but this one that was created by the first call to applyOffer. So let's look at the succession of steps that happen in detail. We first have the call to our attacker contract to say, okay, let's attack this purchaser contract and try to steal funds through the token we own, so token ID 42. This creates a call to the apply token entry point of the purchaser saying, yeah, I accept the offer to sell token ID 42 to you. Then this applyOffer entry point is executed the first time. It checks that the call is the owner. It creates a transfer of 100 Tez to the attacker and a call to the change owner entry point of the ledger. Then for the first call, the default entry point is executed, decrements the nbCalls from 2 to 1, creates a call to purchaser.applyOffer of 52, and while it does that, 100 Tez a transfer from the purchaser contract to the attacker contract. Then the second call to applyOffer is executed. It checks that the caller is still the owner, so the attacker contract, and creates a second transfer of 100 Tez to the attacker. then a second call to change owner. So this one again is executed first, which calls the default entry point that decrements n equals to 0, so nothing else happens, but 100 Tez are transferred from the purchaser to the attacker again. And finally, we execute the change owner call that was created here in the second call to apply offer. So we set the ownership of the token to purchaser, and then we have finally the initial call to change owner that is executed. That sets the ownership to the token again to purchaser a second time. In the end, the attacker contract received 200 Tez from a token that was priced at 100 Tez, so it stole 100 Tez from the purchaser contract. If we had initially set n equals to 10, it would have stolen 900 Tez from the purchaser contract by accepting the offer 10 times before transferring the ownership of the token to the purchaser contract. So the question is, how can we avoid this type of flaw? So you have to keep in mind that what makes this flaw possible and hard to detect is that a new call to the purchase contract can be initiated in the middle of the execution of its different steps. And our intention in the purchase contract was to simply send Tez to the seller and then take ownership of the token. But what really happened is that we sent Tez to the seller, but then the seller did all kinds of things, including trying to sell its token a second time. And only after that did we take ownership of the token. So with that in mind, how can we avoid this type of flaw? Pause the video and think about it for a minute. So the first approach is to simply order the steps of your contract in a safe way. And the idea is to start with the steps that will prevent future similar calls. So in our example, we could have avoided the flaw by swapping these two instructions. So the instruction to send the 100 Tez to the caller and instruction to change the ownership to the purchase contract. If we simply change the ownership first and then transferred 100 Tez to the caller, then during that transfer, any call to accept the offer again would have been rejected because the attacker contract wouldn't be the owner anymore. So this approach can work if you're really careful. You make all the changes that will prevent future calls first, and then the consequences, and in particular transfers of Tez afterwards. It's possible to avoid them, but as contracts become more complex, it can become really hard to be 100% sure that you cover all cases and that no re-entrancy attack can happen. So there's a second approach that is a bit more radical and that simply prevents any re-entrancy at all, and therefore any re-entrancy attack. The idea is to use a Boolean flag. For example, we can call it isRunning, that we put in the storage of the contract, and that will be set to true while the contract is being used so that it cannot be called a second time. And so the entry point will have this structure. We first check that isRunning is false, then we set isRunning to true, then we do all the logic, including creating calls to other contracts, transfer of Tez, etc. And then we call an entry point that sets isRunning to false. It's important to do it through a call to an entry point, not simply set isRunning to false, because all of these calls created here, all these transfers, will happen after the end of the execution of our entry point. So we cannot just simply set it to false again. We have to call an entry point that will set it to false after all the consequences of this section will be done. If we look at the fixed contract, it will look like that. In apply offer, we first check that isRunning in false, then we set it to true, then we check that the caller is the owner of the token that we are trying to purchase, then we change the ownership of the token to ourselves, so the purchaser contract, then we transfer 100 Tez to the caller, and then finally we call stop running that will check that the caller itself so that no one else can change the value of isRunning, and then we set isRunning to false. So this way, apply offer can't be called during the transfer of Tez to the attacker, and the attack would fail. Here we can look at a more complete version of this attack and test it. We have this ledger that stores tokens and has an admin. We can mint tokens and then check the ownership of a current token or change the owner of a token. Then we have our purchaser contract that has a list of offers. Here we have a system of escrow, so you put funds in a purchaser contract in case somebody wants to sell the token to you
the buyer has the funds available in an escrow big map in the purchase contract. Then when someone accepts an offer, we send the price to the current owner of the token, and then we call change owner to change the ownership. And we can see here the attacker contract that does exactly what we said. We initialize NB calls at 0. We call the accept offer entry point of the purchaser contract. And in the default entry point, we decrement NB calls. And if it's greater than 0, then we call accept offer again. And if we run the test that has an attack for token ID 1, then we can look at the details and see that we get 100 Tez transferred twice, once here and once here. So the attack worked. In this module, we will look at an auction contract that has multiple flaws, and your goal will be to find the flaws in this contract. Let's take a look at this auction contract. In the storage, we will store a map of tokens. Each token will store the metadata of the NFT and the current owner. And the key will be a token ID that will start at 1 and that we increment every time someone mints a new NFT. Then we have a map with all the auctions, where the key is the ID of the token that is put for auction. People can mint NFTs using the mint entry point. They pass the metadata of the NFT they want to mint. We check that they pay a fee of 1 Tez to mint that will be used to fund the website and the advertisement, everything to bring users to this project. And then we simply add an entry to the tokens map that will contain the metadata and the initial owner of the NFT. Then we increment the token ID. When somebody wants to open an auction for a given token, they provide the token ID and a deadline for the auction. That means people will have until this deadline to bid, and the highest bidder will become the new owner of that token. So in this entry point, we store that the caller is the seller, we store the deadline, we store the current top bid, and here instead of using an option to say that there is no top bid, we simply set it at 0, and we say that the top bidder is the sender. So whoever is putting the item on auction bids 0, but then anyone can bid. So that if nobody bids anything, then they can get the ownership of the token back. Then when somebody bids for this token, they indicate what token ID they bid for. We get the data of the corresponding option. We check that they are bidding more than the current top bid for this NFT, and we check that they bid before the deadline. So since they bid more than the current top bidder, we send the amount that the previous top bidder have bid back to them, and then we set the new top bid to be the amount sent by this sender, and then they become the new top bidder. And we save it back into the map. Finally, after the deadline, the seller can claim the top bid and get the funds while transferring the ownership of the token to the top bidder. So we fetch the auction object. We check that this is after the deadline. We check that the caller is the seller of the token. We send them the value of the top bid, and we change the owner of the NFT to the top bidder. Now your job is to find all the bugs from this contract. And there are at least 7 bugs in this small contract. Pause the video and give it a try. So for the first bug, I will give you a hint. Remember that if the storage of a smart contract gets too big, the time it takes to deserialize all of the data in the storage before any contract call and then reserialize it after the end of the entry point may exceed the amount of gas that you can spend in a transaction. So it's always important to think about how large the storage can be and make sure there is no risk of exceeding that maximum amount of gas to spend in a transaction. So with that in mind, can you figure out what the issue is? Pause the video and think about it for a minute. So the issue here is that we used maps to store the NFTs themselves and to store the information about the auctions. But maps are stored directly in the storage, which means deserializing them takes an amount of gas that is proportional to the number of entries. So as people mint more and more tokens and put them into more and more auctions, the size of the storage that you need to deserialize will get bigger, and the gas could exceed the maximum amount you can spend in the transaction. So this is bug number 1, and to fix it, all we need to do is change these into big maps, like this and this. As big map are serialized and deserialized on demand, they're always the data structure you need to use for any data that can keep growing indefinitely. A second bug is in the open auction entry point. There's actually 2 bugs in this entry point because we don't need nearly enough verifications. So pause the video and focus on that entry point for a minute. The first bug in this entry point is that we never check that the sender who is trying to sell this token in an auction is actually the owner of the corresponding entry point. And we don't even check that this token exists. So we need to start by checking, is the caller the actual owner of this? So we can write assert self.data. So we check that the owner of this token is the sender. So they're allowed to sell it. This automatically checks that this token exists, otherwise this would fail anyway. So we don't have to add an extra verification to check that this token ID exists. For the next issue, you can use a method that I always recommend to apply when proofreading a smart contract, which is to think about what would happen if somebody calls a given entry point twice with the same information. So let's imagine that we call open auction a first time with a given token ID, for example 20, and a deadline. So we first check that the caller is the owner of the token 20, and then we create a record and save it in a big map for the key token ID. Then if we call open auction again with the same parameters, we'll again check that the sender is the owner, but then we will overwrite the previous auction with a new record. So in this case, it's fine, we just redo the same thing, but if in the meantime somebody has bid for this auction, then we lose all the information about the top bidder and the top bid. And so basically any funds that any bidder has sent to the contract would be lost because they're not recorded as the top bidder anymore and they won't be reimbursed if someone else bids, etc. So here we have a clear bug that the owner of a token can basically cancel everything that has happened with an auction by creating a new auction. So to fix this, we need to verify there is no auction going on for this token. So we assert that self data auctions does not contain the token ID. The next bug that is reasonably easy to find is on the claim top bid entry point. So focus on this and try to use the techniques that we presented, thinking about what happens if we call an entry point twice, but also what happens if we don't call an entry point, if the person supposed to call it doesn't call it. Pause the video and think about it for a minute. So here, the issue is if somebody doesn't call the entry point. We can see that here we expect the seller, so the owner of the token, to call claim top bid. But the seller may not call it for a number of reasons. It could be because they're not available, because they forgot, or it could be for nefarious reasons. For example, they could say, well, I'm not happy with the auction. I feel I want to get more than the current top bid. So since I have their money stuck in the contract anyway, I will try to pressure them to give me more money. If they don't, well, too bad, their money is stuck, they don't get the NFT, and that's their problem. I don't lose anything. So somebody could pressure the top bidder to try to extort a bit more money, for example. And it's always the case when somebody needs to do something, we have to trust that they will do it. And if we depend on them to do it, then they have some leverage over us. So it's not good to require that the seller called this entry point. The whole point of a blockchain is that we don't want to have to trust someone to do something. So here we could say, well, maybe the top bidder themselves could also run this entry point. And so if the seller doesn't do it, then the top bidder will do it. So we can add here, or sp.sender equals top bidder. But we actually don't really care who calls this entry point. So we can simply delete this line, and as long as somebody calls it, then everything is good. The next bug is actually a bug that we now have in two places. We have it both in this entry point and in this entry point. The version in this entry point is the most dangerous one because somebody could really steal all of the tokens that are put for sale through this auction contract. So try to focus on this entry point and think about a way that somebody could steal all of the tokens that are put for auction. Pause the video and think about it for a minute. So here I may give you another hint. When you send funds to an address, if it's a regular cheesy address of a basic account, you simply send the Tez to that user address. But if the address is that of a smart contract, then what happens is that this calls the default entry point of the contract while sending the Tez to that smart contract. If the smart contract doesn't have a default entry point, the transaction fails. If it has a default entry point, but the default entry point fails, then the transaction fails. So for a contract to be able to receive direct transfers using sp.send and without explicitly calling a smart contract, it needs to have a default entry point like this. That, for example, doesn't do anything. So when you try to transfer some Tez to this contract with sp.send, it will call default. It shouldn't have any parameters, otherwise it's not the right entry point and it will fail. And it shouldn't fail. So here we put pass, so it doesn't do anything and doesn't fail. But if the destination of this transaction either doesn't have a default entry point or has a default entry point that maybe checks for a Boolean, something like that, and maybe has another entry point that allows them to change the value of accept Tez, then they would be able to control at any time if they're allowed transfers of Tez to them or not. So here, if the top bidder is the address of a contract with this kind of default entry point that has a Boolean to accept or reject transfers of Tez, they could bid for the NFT with a very small amount as soon as the NFT is put for auction. Then they could set this to false to reject any future transfers of Tez. If somebody else bids a higher amount for the same token ID, we will check, yes, they bid more, yes, it's before the deadline, but then when we try to reimburse the previous top bidder, that previous top bidder would reject the transfer, and therefore this new bid would fail. And then this initial bidder who's trying to steal the token just has to wait until the deadline and then claim the top bid and get the NFT. So with this, we have a system for anyone to bid a very small amount and then prevent anyone from bidding above them until finally they get the item. So it's really important to be very careful every time you have an entry point that calls sp.send, especially if you're not sending Tez to the caller of the entry point itself. We have the same issue here. Here we're sending Tez to the seller, but the seller could be the address of a smart contract that has a default entry point that may or may not accept Tez, and they could use that as a way to prevent anyone from calling the claim to bid entry point and finalizing the transaction. So we have the same issue here and here. And this issue is an issue we can have quite often in smart contracts. You should be really careful anytime you call sp.send. Now, what do you think the solution would be to fix this issue? Pause the video and think about it for a minute. So one solution people often think about is to prevent contracts from bidding or prevent contracts from trying to sell, etc. So if we know that this is not the address of a smart contract, then we know that it's impossible to block the transfer. But preventing smart contracts from using your smart contract is really cutting yourself from a lot of potential use cases. For example, no entity that is using a multisig contract to collectively take decisions on how to use their assets would not be able to use your contract. There's many occasions where we don't want to directly interact with a contract with a TZ address, but instead through a smart contract. So I really don't recommend testing if the caller is a smart contract or a regular user account, an implicit account. Instead, what we want is to let the top bidder here and let the seller here get their funds back themselves through a separate entry point. But for that, we need to use a ledger that keeps track of how much the contract owes to each user. So here we will add a big map, ledger, where the key will be the user and the value will be the amount that the contract owes to them. So here, instead of sending Tez, we check if there's already an entry for that user. So if it doesn't exist, we create the entry. With 0 Tez, and then we add the amount that we wanted to send them, like this. And we also need to add a claim entry point, where we send to the caller the amount that is in the ledger for them. And then we delete the entry. And here in claim top bid, we can do the same thing. I'll just copy this. But here it's going to be auction seller. And that's it. So that's fixing the next bug. So it's a good habit to have a ledger in your smart contract so that instead of directly sending Tez to different addresses, you just keep it in the ledger and you let people withdraw the funds through a claim entry point. The next bug is in claim top bid. And again, think about what happens if you call the same entry point twice. Pause the video and think about it for a minute. If we call claim top bid the first time, let's say for token ID 20, we check that the deadline to bid is passed. We send the amount of the top bid to the seller through the ledger, and then we change the ownership of the token to the top bidder. Now, if we do it again, we call claim top bid a second time with the same parameter, 20, then we do everything again. We check it's still past the deadline, but then we transfer the amount of the top bid again to the seller. The seller didn't change. Then we assign the ownership of the NFT again to the top bidder. So this doesn't change anything, but here we add the top bid a second time to the seller. So the seller could keep calling this entry point many times and get the amount from the top bid again until the balance of the contract is lower than the top bid. So by doing that, basically the seller would steal funds from top bidders of other auctions that are currently ongoing. To avoid this, we can delete the entry so that the entry point cannot be called again, and maybe another auction can be set later. The last bug that I know of is related to the mint entry point and to the fact that we charge 1 Tez for someone to mint an NFT through this contract. Pause the video and think about what the issue could be with that. Here the issue is that we have accumulated Tez in the balance of the contract, but the owner of the smart contract, whoever is managing the website that goes with the smart contract, has absolutely no way to get this money. So they may look at the contract, see, yes, many people are minting NFTs and accumulating money, etc. Until one day when they say, okay, I want to use this money for something else, to pay for some developer, some marketing, etc. Then they realize that they have absolutely no way to get the Tez out of the contract. This may sound silly, but this kind of issues, forgetting to create an entry point to get the money out of the contract, is something that has happened to multiple companies with their smart contract. So when you test your smart contract, make sure you test the whole life cycle of the contract, including the time where you want to get the money out. So here there's a very easy way to fix that, which is to simply add these Tez to the ledger. But for that, we need to specify who the owner of the smart contract is. So we have to specify an owner and store it. As there is no default owner of a smart contract. Just because you deploy the smart contract doesn't make you the owner. So we have to store it in the storage. There is really no default notion of owner that we can access to. So here, as soon as we get the one Tez, so here we can use this piece of code again. And we add one Tez to the ledger. You may notice that I have copied the same piece of code multiple times. And there is a way to put it in a function, but we will see it later in a module about lambda. So for now, we simply copy this piece of code in each of the smart contracts that uses it. And that's it. To recap, we found 7 flaws in our simple auction smart contracts. We forgot to check that the seller of an NFT was actually the owner of that NFT. There was a way for a bidder to bid a very small amount and then prevent anyone else from outbidding them, and therefore making sure they could win the auction with a very small price and therefore stealing all the tokens. We noticed that the seller could never call claim top bid and maybe use this as a way to extort money from the top bidder. And so we fixed that. We also noticed that the seller or anyone could call claim top bid multiple times and steal Tez from other auctions. And we noticed that the admin, the owner of the contract, could never claim their earnings. So we added a way for them to do that through the ledger. We also noticed that the usage cost of the contract was increasing little by little as people created new tokens, etc. in the map, in the storage, until the contract would be completely stuck once the amount exceeded the total amount of gas we can spend in a transaction, and we simply fixed that by using big maps. And finally, we noticed that it was possible for a seller to delete an auction and everything that was already bid by overwriting the auction with a new one. So you can see that in a very small smart contract, it's quite easy to have many different bugs. And so it's very important not only to test very carefully, have people other than the developer proofread the contract, and also go through checklists and making sure you don't have any of the typical bugs we just presented. On OpenTezos.com, we have a page about all the typical flaws we can have in smart contracts, and you can use that page as a checklist when you review your own contract. In this video, we will talk about a type of contract used in decentralized finance called flash loan. And we will see that with a flash loan, you can become temporarily very rich. So we will start with an exercise. In a previous module about sets, we presented a membership contract that only rich people could join. And the way we did that was that the join entry point that people had to call in order to join this club required you to transfer a large amount of Tez to the contract that the contract will then reimburse you. So in order to join the club, you needed to have access to a large amount of money. So the question for this exercise is, let's say you don't have access to a large amount of funds. Is there a way you could still join this club? Pause the video and take a minute to think about how you could create a smart contract that would make this possible. So the solution is that you have to borrow some Tez.
And so the idea is to create a contract that can lend Tez to users. And of course, users would have to pay back later with some interest. So the question is, how can you have a contract that lends you money, but then makes sure that the user will pay back? Pause the video and think about it for a minute. So the usual way that even banks use to reduce the risk when they lend you money is that you have to have some kind of collateral. It could be a house, it could be anything. On the blockchain, it's typically money, but in a different currency. So let's say you want to borrow some amount of Tez, let's call it X, from a contract. We could deposit some amount of token A, so a different cryptocurrency, that is worth more than X Tez. For example, it could be 130% of X. Then in exchange, we receive this amount X of Tez. Then for some amount of time, we can use those Tez, but at some point in the future, we pay back that amount plus the interest. Once we do that, we can get our deposit back in the token A. So the amount we deposited in the token A was never used, was never invested or anything. It was just kept by the contract so that we could get it back once we returned the amount of Tez. One thing to keep in mind when you do that is that the value of token A may change over time. It's a different cryptocurrency, so the exchange rate between A and the Tez could vary over time. So if the value of your deposit in the form of tokens A becomes so low that it's starting to get close or even lower than the amount that you got, the contract can liquidate the loan to make sure it doesn't lose money. For example, let's say if the value of token A gets close to 110% only of X, then it will use an exchange to exchange your deposit for some Tez. So that's what we call liquidating the loan. So this is the way the contract makes sure that no matter what, it will get the Tez back plus some interest. Either you pay it back, or if you don't pay it back, or if your deposit is starting to lose value, then it will get back the money by liquidating your deposit. So this is a type of loan, but not the one that would work for us, because in our membership contract, the whole point was that we want to join, but we are not rich. We don't have any funds, whether it's in the form of Tez or another token. So we cannot pay in any way, and we cannot provide the collateral. Basically, this kind of loan doesn't work if we're just poor. So if a user doesn't have any funds, how could someone lend to them without taking a risk? So I can give you a hint. In our situation, we only need the money very briefly. So how could we do that? Pause the video and think about it for a minute. So the idea is to do everything in a single transaction. In the same transaction, we could borrow money from a contract, then use that money to join the membership contract and then immediately get it back. Then we could pay the money back to the contract, plus some very small interest. If all this is in the same transaction, then if we fail to pay the money back, then everything will be cancelled, right? Because when it's a single transaction, a single contract call, if one of the part fails, then everything fails and is cancelled. So basically the contract never lends you money if you don't actually pay it back. So there is no risk for the lending contract. So this type of contract, where you borrow some funds without any collateral, use it immediately, and then pay back plus some interest, that's what we call a flash loan contract. So in a flash loan, the key idea is that funds have to be borrowed and repaid within the same transaction. So you borrow some amount from the flash loan contract, you use it for any kind of financial operation that generates a profit, or at least where you don't lose any money. Then you repay the funds plus the interest to the flash loan contract, and you can keep any profit you made. So in the case of our membership contract, your profit is simply that you managed to become a member of this membership contract. So there's really no risk. If anything goes wrong, the transaction fails entirely, so it's as if nothing has happened. Which means anybody can be temporarily as rich as needed, in particular to profit from an opportunity. Okay, so let's work on the implementation of such a contract. Think about how you would implement a simple flash loan contract. You have to have an owner who will deposit Tez on the contract and eventually claim them back when he needs to. Those Tez will be used to lend Tez to other people. Then anyone can borrow these Tez with no limits other than the total balance of the contract, so the amount deposited by the owner. And then the lender needs to repay the loan with interest in the same transaction. So again, there is no risk. If the lender can't repay the loan, the entire transaction is cancelled. Let's look at the structure of such a smart contract. In the storage, we would need to have the owner, so the person who puts the funds in the smart contract to lend to other people. We provide the interest rate, so what percentage of the funds you borrow you have to pay on top of reimbursing the loan itself. We only need to make one loan at a time since we're going to pay it back right away. So there's only one loan in the flash loan contract, so we can store the amount that is being loaned. We need to keep track of whether there is actually a loan in progress. We'll see why a little bit later. We need to know who borrowed this amount, and then we'll need to know if the amount has been repaid. Then we have 5 entry points. We have a deposit entry point where the owner will deposit the initial funds, and a claim entry point where the owner will claim their balance back at the end, plus their interest. Then people can call the borrow entry point and specify how much they want to borrow. And they will need to provide a callback that says what is the next step right after I borrow the money. This entry point will transfer the amount to the sender, and then we'll call this callback. And within this callback, the funds will be used, profit may be made, and then the callback will repay the loan. So after we call a callback, we need to call a function that will check if the loan has indeed been repaid. While the callback is running, at some point it has to call repay and send the funds back to the flash loan contract. And then finally, check repaid will be called, and we will check that the loan was repaid. Otherwise, we fail and everything is cancelled. So the idea is that the contract that borrows the money will call borrow and pass its profit entry point as a callback. So let's say we want to borrow 10,000 Tez, and as soon as we have those funds, the profit entry point should be called. So we call borrow. Borrow transfers 10,000 Tez to the sender. Then it calls this function, callback. Then it calls check repaid to make sure that indeed callback has repaid the loan. The next step is that profit is being called. So the Tez that have been transferred to it can be used to buy something, for example. Then we can sell it for more somewhere else. That's one way to make a profit. And finally, we need to call flashloan.repay with the amount borrowed plus some interest. So when we call repay, the repay entry point, of course, checks that the amount sent is the amount of the loan plus the interest, and it sets the repaid flag to true. Finally, the check repaid entry point is called, and here we check that repaid is true, otherwise we fail. So we make sure that indeed the amount sent was repaid. So based on this, try to implement this flash loan contract and call it from the borrower contract. And note that you will need a total of 3 contracts: the flash loan contract, the membership contract, and the attacker contract, the contract that will borrow the funds so that it can then become a member of the membership contract. We'll pause the video and implement those contracts. Let's take a look at the solution. So here is our flash loan contract. We instantiate it with an owner and some interest rate. We store those two. We mark that the flash loan is not in progress. We have no loan, so we set the loan amount currently to 0. We have to set a borrower to avoid using an option, so we set it to owner. And then we say the flash loan hasn't been repaid, so we set repaid to false. We then have the deposit entry point that the owner can call to deposit some funds that will be used to lend funds to anyone. Only the owner should call it, but we don't have to check it. If somebody else wants to send money to the flash loan contract, that's fine. The owner will be able to claim it, so nobody else is likely to send some Tez. Then we have our borrow entry point that takes an amount someone wants to borrow and the callback to be called after the money has been sent. We check that there is not already a loan in progress. And because if we can borrow while there's a loan in progress, that will complicate things. We would have to keep track of the list of people who borrowed, etc. So we only want to have one loan at a time. So we say it's in progress, the money is being used. So we set it to true, and we won't be able to borrow again until the loan is paid back. We record who is borrowing, we record how much is being loaned, then we send that amount to the caller, and then we call the callback. It has to be an entry point that doesn't take any parameter, so we send unit to it. Then after the callback is executed, we will call the check repaid function. So the callback is supposed to use the money, make some profit, and then call the repay entry point. So here we call the check repaid entry point here to check that indeed repay was called by the callback. So when the callback calls repay, we check that indeed there's a loan in progress, and we check that the amount paid back is equal to the loan amount plus the loan amount times the interest rate. So for example, if the interest rate is 1, then we need to pay back 101% of the loan amount. Then we can mark repaid to true, so the loan has been paid back. So later, when we call check repaid, we check that it's in progress, we check that the loan has been repaid, and we say, okay, the loan is over, it's not in progress anymore, everything goes well, and the whole transaction happens. If check repaid is called, but the callback didn't call repay, then this will fail, and everything will be cancelled, and the money will be safe. Finally, the owner can call claim at any time, unless there's a loan in progress. So we check that it's indeed the owner calling, we check that the loan is not in progress, and then we send the balance of the contract to the owner who's calling claim. We have our membership contract that checks when we joined that the caller sent a certain amount, and then we send it back to them. And then we have the attacker contract that will borrow some funds, then join the membership contract, then pay the funds back to the flash loan. In the constructor, we take the address of the membership contract, the address of the flash loan contract, and then the amount that we will need to pay to join this club. Therefore, that we will need to loan. We store all three. Then we have the impersonate rich person entry point. We'll call the borrow entry point of the flash loan contract, and we will pass it the amount we want to borrow plus the address of the callback entry point. So here we get the attack callback entry point so that we can pass its address when we call the loan contract. So we say we want to borrow this amount. When you're done, please call this callback, which is this entry point. So in the callback, we call the membership entry point and we send it that amount of money so that we can join the club. And then we repay the contract. So we compute the amount to repay, which is the amount we borrow plus 1%. Here we hard-coded that it's 100 Tez. Then we call the repay entry point of the flash loan contract and send that amount of Tez to it so that we can repay the contract. And of course we need a default entry point so that we can receive the funds that the flash loan contract sends to us. And that's it. So then we can see the test. We create a membership contract. We say the amount to have in order to join this club is 10,000 Tez. Then we create the flash loan contract. We say Alice is the owner. The interest rate is 1%. And note that this is not 1% per year or per any unit of time. It's just that any time you borrow, you have to pay back with 1% of interest immediately. Alice sends 100,000 Tez to the flash loan contract so that people can use it to borrow some funds.
Then we create the attacker contract. We pass the address of our membership contract, the address of our flash loan contract, and then the 10,000 Tez, so the amount that we will need to pay to join the club. And we simply call impersonate rich person. We have to send some extra Tez to be able to pay the interest. Let's give it a try. So here we can see that we originate the membership contract. We originate the flash loan contract. Alice deposits 100,000 Tez to the flash loan contract. Then we originate our attacker contract with the address of those two flash loan and membership contract. And then the attack starts. We call impersonate rich person. We pass 500 Tez. So here we borrow some funds, 10,000 Tez, and we say here is the callback. The flash loan transfers 10,000 Tez to the default entry point of our attacker. Then it calls the callback. So this function, where we join the membership contract by sending 10,000 Tez. We get the 10,000 Tez back into the balance of our attacker contract. Then we can repay 10,000 plus 100 Tez back to the flash loan. And so when the flash loan calls check repaid, everything was good, so everything works. But if anything went wrong, and for example, we didn't pay the full amount back, or we paid without interest, let's say we pay only 10 Tez of interest, and if we run it, we can see that this didn't work, so everything was cancelled. All good. In this video, you will learn how to create your own fungible tokens. In particular, you will be able to create your own currency on-chain. Fungible tokens can be used in many different ways. They can represent an existing fungible resource. For example, we can create a stable coin, or we can create an in-game currency represented by a token. We can also use fungible tokens to fractionalize the ownership of a tangible asset. For example, we can have a token that represents a piece of real estate or a piece of art, and the tokens make it a lot easier for the owners of this real estate to split their ownership and then trade it, etc. Fungible tokens can also be used to raise capital for a project, similarly to stock. The fungible aspect of tokens means that different units of the same token are interchangeable. And if you own an amount of token, you can split it into sub-amounts. This is very different from non-fungible tokens, NFT, where each NFT is unique and cannot be split into sub-NFTs. With all that in mind, try to think about the structure of a basic contract that would represent a fungible token. I'll give you a hint. Think about the Tez token. It is a fungible token, and what we want to be able to do with our fungible token is very similar to what we are able to do with the native Tez. So with that in mind, think about how you would structure a contract to handle this. Pause the video and think about it for a minute. So with the native Tez, we have accounts and we have a balance for each account, and we can transfer Tez from one account to another. So we need to be able to do that with our token contract. So we need to store the balance of each user in that token, and we need to be able to transfer tokens to other people. For that, all we need is to have in the storage of our contract or ledger a big map that contains the balances of all the users. The key would be the address of the user, and the value would be the amount of this token that the user owns. And we need a transfer entry point where a user can say, I want to send this amount of token to this destination. And the entry point will check that we have enough tokens in our balance to transfer that amount. If the destination doesn't already have an account, we create it by setting the balance for this address to 0. Then we can do the transfer. We add that amount to the balance of the destination, and then we subtract the amount from the balance of the sender. So that's great. But with the Tez, we can do more than that. So try to think about what else we can do with the Tez that this doesn't support. And I'll give you a hint. Think about what you can do with Tez within smart contracts, or when you use smart contracts. Pause the video and think about it for a minute. I'll give you another hint.
think about how you would write a version of the endless wall contract where it would charge one token instead of charging one Tez to add a message to the wall. What would you need in the ledger contract to be able to support this? Here is the code of the endless wall contract that uses Tez. So what would you need to do to be able to write a similar code, but by charging using your own token instead of one Tez? Pause the video and think about it for a minute. So with the native Tez token, you can transfer Tez to a contract when you call an entry point. Then within the entry point, you can use sp.amount to check how much was sent to the contract, to pay for some service or to deposit some amount, etc. So we need to be able to do something similar with our token. One way would be to call the transfer entry point to send tokens to the address of the contract just before making a call to an entry point, so that we can send some amount of token to the contract we are just about to call. But if we do that, there would be no way for the contract to check how much we just sent to it. So we need a way for the contract to be able to check who transferred how much to it. And we need to make sure that the same transfer of tokens cannot be used for two calls by the same user to the same smart contract. One way to do that would be to store information about every transfer to a given contract call. And we could store that in a big map where we store all the transfers. The key would be the source, so who is calling this entry point and sending tokens to it. And then we will store the destination address, so the address of the smart contract, and how much we are transferring. So we would add an entry to this big map when we make a transfer to a smart contract, and the destination contract would then be able to call some entry point of the token contract over the ledger to check that there is indeed a transfer that has been made with the right amount, and they would then delete that transfer so that it cannot be reused. So that could work, but in practice, the standards we use to write such a fungible tokens contract do it a bit differently so that we can enable more use cases. Instead of keeping track of how much we just sent to the contract we're calling, we will allow the contract to take some money from the caller. So we allow a given contract address to spend some amount of tokens in the name of a given user or contract. So users can say, okay, this contract is allowed to spend this amount of tokens from my balance. And then the contract can directly transfer that amount to itself or to some other destination. So instead of sending some token to the contract and having a way for the contract to check it, we allow the contract to use some of our tokens, and then the contract can do it itself. So instead of storing transfers, we store allowances in the storage of our ledger, where for a given account and a given operator, that's the address of the contract, we allow to use some of our tokens, and we say how many tokens it can spend. We create an allowance by calling an allow entry point that takes the address of the operator that is allowed to spend some of our funds and the amount that we allow this operator to spend. If there's no entry, we create one, and then we add this amount to the entry, so with the account and the operator. Then when we call transfer, we specify the source, because the source may not be the sender. So we say, I want to transfer this amount from this source to this destination. And within the entry point, we check. If the source is not us, then we check if there's an allowance that allows us to spend at least that amount. Then we subtract that amount from the allowance so that you cannot spend it a second time. So now it's your turn to implement this contract. So your job is to write a ledger contract such that a user can create a new token and set an initial amount of tokens that he owns. Then anyone may transfer their tokens to other users. So this first user can distribute their token the way they wish. Then the ledger will keep track of how many tokens each user owns in their balance with a system of accounts and balances. And finally, users can allow contracts to spend some amount of tokens in their name. Once you've done that, use this ledger in a version of the endless wall contract such that anyone can add text to the wall as long as they pay one of your tokens. And the tokens that are paid can be directly transferred to the owner of the Endless Wall contract. To help you, we provide you an incomplete code that you can find either in the Git repository or on OpenTezos. And your goal is to complete the contracts and the tests. Let's take a look at the solution. So in our ledger, we store the balances, so a big map, initialized with the owner of the ledger who owns the total supply that we provide. Then we'll have another big map that will store all the allowances. When we transfer some amount from a source to a destination, we check if the source is not whoever is calling the transfer entry point, then we check that they're allowed to transfer that amount. So we check if there's an entry in the allowances for this source and this caller. We check that the allowed amount is more than what we want to transfer. And then we subtract the amount from the allowed amount. This could be negative, except that we check that it's not, so we can convert it to a natural and then update the allowances. We also check that the balance of the source is sufficient to transfer that amount. Then we update that amount by subtracting the amount we transfer from the balance of the source. Finally, if the destination doesn't already have a balance, we create one with the value 0, and then we add the amount we transfer to their balance. We will use a getBalance on-chain view so that any contract can figure out what's the current balance of a user for this token. And then we have our allow entry point, where a user can allow a given operator, so the address of a smart contract, to spend some amount in their name. It could be a regular user, but in practice, it's almost always a smart contract. If there's no entry in the big map for that key, composed of the sender and the operator, then we create one and we say the allowance is 0, and then we add the amount we want to allow to this allowance. And that's it for the ledger. Now let's look at the modified version of the Endless Wall contract. All we have to do here in the contract is to do the transfer. So we get the entry point transfer from that ledger contract. The type of the parameter will be a source, a destination, and the amount. And then we do the call to the transfer entry point. We say the color of write message is the source, the destination is the owner of the Endless Wall contract, and we transfer one token. We don't need to transfer any Tez, and so this is just a way to say transfer one token from whoever is calling write message to the owner of the Endless Wall contract. Of course, for this to work, the user who is calling write message has to have allowed us to do so. And then we change the text. In our test, we create the ledger. So Alice creates a ledger with 1,000,000 tokens. Then we create an endless wall, where Bob is the owner of that endless wall. But the endless wall needs to know the address of the ledger, so we pass the address of the ledger here to our endless wall constructor that we store here. And then finally, Alice will need to allow the endless wall contract to spend one token in her name. And once she's done that, then she can call write message. And this one token will be taken from her balance and transferred to Bob. We can give it a try. So here we originate the ledger, where only Alice has an entry with 1,000,000 tokens. Then we originate the endless wall with the initial text hello. Then we allow the endless wall contract to spend one token in the name of Alice. Then Alice can call the write message entry point, and this will trigger a transfer of one token to Bob's address. All good. When we create fungible tokens on Tezos, we need to make them compatible with tools and contracts and wallets so that generic tools can be used for you to view your balance and spend your tokens, etc. So we have a set of standards that are used to create fungible tokens.
The first standard was the FA 1.2 standard that is dedicated to contracts that manage fungible tokens only. Then we have the FA2 standard that also supports non-fungible tokens. We talk about it in another module. And at the time of recording, we're about to release the FA 2.1 standard, so an updated version of the FA2 standard. And these standards all include support for some system of operators and or allowances that can be done in different ways, depending on the standard. But the idea is always the same, that we allow some address to do some operations in our name. They also include a view to access the balance of a given user from another contract. And they have additional metadata about the tokens. In this video, we will talk about how you can trade tokens. For example, if you create your own token, you can trade it against Tez or against tokens from other people. And we'll talk about how the value of a token can be calculated. So in the module on fungible tokens, we saw how we could transfer tokens from one address to another and how we could spend tokens in smart contracts using a system of operators and allowances. But we also want to be able to trade our tokens with Tez or to trade them with other tokens. So for example, we can take the simple case of trading between a pair of tokens. We create our token A and we want to be able to trade tokens A versus Tez. So if someone has an amount of token A, they want to be able to sell it for some amount of Tez or vice versa. So the question for you is, think about how you would create a contract that would allow anyone to either quickly purchase tokens A using Tez as a way of payment, or quickly sell tokens A in exchange for Tez. And the important part is to do so at a fair price. How can you make sure the exchange is on the right price? Pause the video and think about it for a minute. So we can think about multiple ways to determine the price. A basic idea would be to set a fixed exchange rate once and for all. So you could say, well, I create this token for my game currency and I will say that one token is worth exactly 0.3 Tez, for example. But if you do that, no trading would probably happen, because if some people think the currency in your game should be worth more than 0.3 Tez for each token, then they will never sell it at that price. Or vice versa, if people who may want to buy your token think, well, it's worth a bit less, then they won't be willing to buy it at that price. The whole point of creating your own currency is for the token to be able to have its value change based on demand. So if your game becomes very popular and lots of people want to earn some currency in your game, then the price should go up, and vice versa. If the game is not too popular, then the price should be able to go down so that people still can buy and sell those tokens. So a fixed exchange rate wouldn't work. Another way would be to try to have a group of people decide together what's the current exchange rate. They could have meetings every day, say, okay, we think it should be lower, it should be higher, let's change it a bit. That would be a bit complicated, and it wouldn't really help because it wouldn't adjust fast enough to the demand. And this group of people wouldn't have a good way to know what's the right exchange rate. It would say, okay, yesterday people bought it but didn't sell it, so it's probably too cheap, or vice versa, and it's probably too expensive. We need a way to instantly adjust to the demand. We could think about using auctions, like we do for NFTs, but auctions are slow. You need to set a deadline in the future. You need to make sure there's people who notice your auction, etc. And they're hard to use because you would put in as an auction a certain amount, and this amount may not match what the buyer wants to purchase. And if you make an offer, well, setting up the offer at the right price is not easy either. So we want something that really determines the right price automatically and instantly. If we want the trading of tokens to be effective, we need liquidity. It should always be possible to buy and sell at any moment. You shouldn't have to wait for someone to be available and agree to sell to you or buy from you. And the prices should be adjusted automatically and instantaneously based on the offer and demand for your token and the token you want to trade it for. So to support that, we
could use a contract that will store some amount of the two tokens that you want to trade. So we will store some amount of token A and some amount of Tez, so that if people want to buy or sell, there is some amount that is available immediately for trading. And this contract will have to automatically adjust the price based on the offer or on the demand for your token. So think about how you would design a contract that will store some amount of tokens A and of Tez, and then will automatically adjust the price based on offer and demand, and will let anyone trade at that price. Pause the video and think about it for a minute. This type of contract is what we call a liquidity pool. And a liquidity pool enables users to easily trade between pairs of tokens. Let's imagine that we have token A and Tez. In our liquidity pool, some investors could deposit initial amounts of token A and a corresponding amount of Tez. These tokens would form a reserve of liquidity for each of the two tokens. Then users would be able to trade amounts of one token for the corresponding amount of the other token at the current price. And this current price, the exchange rate, would be based on the available amounts of both tokens in the pool. We will see that when we do that, any deviation from the real exchange rate based on the offer and demand, the price that people are willing to buy it for or sell it for, can't last very long, because as soon as the price is cheap, then somebody will quickly buy and this will increase the price, or if the price is too much, people will sell and this will reduce the price. And there will be a system of arbitrage opportunities that makes sure that the exchange rate is the right rate. The investors who deposited the liquidity on this liquidity pool will be rewarded using exchange fees, so a percentage of every trade that they will receive in exchange for providing this liquidity. So the main question is, how can we determine the exchange rate that we will use? Typically, liquidity pools use what we call an automated market maker, or AMM mechanism. It's a mechanism that determines the token prices based on the amount of token A and of Tez in the pool, for example of pair A and Tez. There can be a number of different formulas you can use, but the most common formula that is used is called the constant product formula. And with this formula, the prices are such that the product of the balance of both tokens remain constant. So the balance of token A multiplied by the balance of Tez, that is in the reserve of the liquidity pool, should always be equal to some constant K that we set when we create the liquidity pool. And the idea is that with this formula, the more of a given token you have out of the two, the cheaper that token gets. And of course, the less of a token you have, the more expensive it gets, because it's rare, so it's more expensive than if it's really abundant. So the idea is that whenever we buy or sell a given token, we compute the price to make sure that after the transfer, this product is still constant. So with that in mind, let's implement a very basic liquidity pool contract. At the beginning, we will have a single user who will provide liquidity to this pool a single time. Then other users should be able to trade tokens for Tez or vice versa. There should be a way for contracts to be able to check the current exchange rate. And again, the idea is that the balance of the two tokens in the pool should always verify this formula. Token A balance times token B balance equals K. So first, think about what you would store in this smart contract and what would the entry points be. Pause the video and think about it for a minute. So in the storage of the contract, we will need the address of the ledger because we will interact with the ledger that stores the token. We also need the address of the owner, who is the single user who put liquidity at the creation of the liquidity pool, and they will be able to get it out when they want to close the liquidity pool. We need to store the constant K. So since we multiply a natural number with a number of Tez, then K has unit Tez. And finally, on top of the balance in Tez that we will have access to using sp.balance, we also need to store how many tokens the liquidity pool owns. And we could, of course, check in the ledger, but it might be more convenient to store it directly in the storage. Then we will have 5 entry points. The first entry point is for the creator of the liquidity pool to transfer some liquidity. And so they send some amount of Tez to the entry point along with the number of tokens they want to deposit in the balance of the liquidity pool. So you add to the balance in Tez and to the balance in this token some amount. Based on this, you can compute the value k. That's just the product between this amount and the amount of Tez transferred. And so we can store these two values. And then we, of course, need to transfer this number of deposit tokens to the address of the smart contract through the ledger. So this assumes that the caller has allowed the liquidity pool to transfer these tokens to itself. At the very end, the owner should be able to withdraw their liquidity. So when they call it withdraw liquidity, we simply send all the tokens in the balance of the contract and all the Tez in the balance of the contract to the owner. And this closes the liquidity pool. Then we have the two main entry points for users to sell or buy tokens. So our sell tokens entry point, we will say how many tokens we want to sell. But as a safety measure, to make sure we don't sell them for cheaper than what we expect, we indicate how many Tez we expect to get at the minimum when we sell our tokens. So it's a safety measure to make sure that if the price goes temporarily very low, then maybe we just don't want to sell. So we can set some minimum value of how much we will get for those tokens. And so in this entry point, we will compute using the formula how many Tez the tokens that we want to sell are worth. And if this is more than the Tez we requested, then we simply transfer the tokens and Tez accordingly. So we transfer the tokens to the liquidity pool contract, and then we take Tez from the balance of the liquidity pool to send them to the seller. The buy tokens entry point works similarly. We send some amount of Tez to the contract, and we say, with that amount of Tez, I expect to buy at least this number of tokens. If the price of the token goes too high, then maybe I just don't want to buy them. And here again, we start by computing how many tokens I can get for that amount. And if this is more than the minimum that I want to buy, then we transfer the tokens and the Tez accordingly. We keep the Tez sent by the user in the balance, and then we transfer tokens to the caller. Finally, we will have a view, get token price, that will compute and return how much it would cost to buy one token right now. So your job is to implement this contract. And keep in mind that this formula should always be maintained. The product between the balance of one token and the balance of the other token should always be equal to k before and after each call to an entry point. Again, you can start with the incomplete code that we provide in the Git repository or on OpenTezos. Pause the video and give it a try. Let's look at a solution. Here we have our ledger that we didn't change. And here we have this liquidity pool contract where we store the address of the ledger contract, the address of the owner, the constant k that we initialize at 0 before we know the value it will have. And then we keep track of how many tokens the liquidity pool has on its balance. And then this will be used to simplify the calls to the ledger contract. So basically this is a variable where we will store the address of the transfer entry point for that contract so that we don't have to compute it every time. We have the provide liquidity entry point where the owner will deposit some amount of tokens and some amount of Tez initially to the liquidity pool. We check that whoever is calling is the owner. We check that we have never sent anything, so the liquidity pool is not open yet, so the value of k was 0. Then we compute the value of k as the product of the balance of the contract after the transfer of Tez from the user and the number of deposited tokens. So here k is set once and for all. And finally, we keep track of how many tokens the liquidity pool owns. Finally, we do the transfer to obtain those tokens from the user through the ledger. So this is where we initialize this ledger contract op variable with the address of the transfer entry point of the ledger.
You may notice that to avoid having to repeat the type everywhere, we created this perm type that we define here as the record that contains a source, a destination, and some amount, so that we don't have to repeat it every time. Once the owner has provided some liquidity in the form of Tez and some amount of tokens, we have the withdrawal liquidity that will be called at the end by the owner to withdraw all of these tokens. So we check that this is indeed the owner calling, and then we simply send the balance of the contract to the owner and then transfer the tokens themselves to the owner. Finally, we just say no, the tokens owned are 0, and then we set K back to 0 so that maybe the contract can be used again later by the owner. But this effectively closes the liquidity pool for now. Let's look at the get token price on-chain view so that we can figure out how we compute the current price of the token. And here the idea is to compare what the current balance in Tez is to what it would be if we had one less token. And this difference is how much the balance needs to change so that the product between the two balances stays the same. So here we divide K by the number of tokens we currently own. This should tell us what the current balance is. And then we do the same, but with the current amount of tokens owned minus 1. And so this tells us what the balance should be after we sell one token. So if we have the balance before we sell one token and the balance after we sell one token, then the difference between the two should be how many Tez we get for that token. And so this is how we compute the current price of a token. Now in the sell tokens entry point, we do something similar. We compute what the balance would be if we had this number of tokens on top of the token we have. And so we compute how many Tez we are supposed to send by computing the difference between the current balance and what we should have once we obtain those extra tokens. So this is not the same as computing the current price of one token and then multiplying this by the number of tokens sold, because the more you sell token to the liquidity pool, the cheaper they become. Because the more tokens the liquidity pool has, then the cheaper each token becomes. So we cannot simply use the price of the first token and then multiply that by the number of tokens. So this is why we use this formula as a way to check what is the current balance and what should be the balance after we obtain those tokens. And the difference between the two tells us the price that we should pay for those tokens. So here we check that this price is more than what the seller is requesting. And once we have that, it's very easy. We transfer the tokens, we transfer the Tez, and we keep track of how many tokens we still own. The buy tokens works in a similar way. We compute the number of tokens we should get for the price that the user sends, so sp.amount, by computing the difference between how many tokens we currently own and how many tokens we should own based on the new balance that we have. So we divide K by the new balance to determine was the number of tokens we should own after we got this new amount. And again, we check that this number of tokens is more than what the buyer is expected to receive. And if it is, then we send tokens to them and we update the number of tokens we own. Now in the test, we create the ledger, we create the liquidity pool. Alice provides 2,000 tokens and 2,000 Tez and calls provide liquidity to the pool. This means K will be 2,000 times 2,000, so 4 million. Then we have Bob buy at least 90 tokens for 100 Tez. Then Carl buys 1,000 Tez worth of tokens and expect to get at least 500 of them. Then finally, we have Bob sell his tokens, so it allows the liquidity pool to withdraw 96 tokens. That's the number that he will actually be able to buy here. And then calls sell tokens to sell those 96 tokens. And he expects to get at least 200 Tez. So if this works, so Bob spent 100 Tez to buy 96 tokens. Then Carl spent 1,000 Tez to buy a lot of tokens. So this increased the price of a token so that Bob can sell his 96 tokens at least 200 and make a big profit of at least 100 Tez. So let's give it a try. So we can see here that we created the ledger with 1 million tokens. Then we created the liquidity pool with K set to 0, no tokens owned. We provide some liquidity after allowing 2,000 tokens to be provided. We provide 2,000 tokens and 2,000 Tez. The transfer is made for these tokens to be transferred. Then we have Bob buy 100 Tez worth of tokens, and he wants at least 90 tokens for that price. We see that the amount computed for 100 Tez is 96 tokens. Then Carl buys for 1,000 Tez worth of token and expects to get at least 500. And we see that he indeed gets 614 tokens for 1,000 Tez. So we can see that the price of the token went up. For 100 Tez, Bob got 96 tokens, but for 1,000 Tez, Carl only got 614, and the price keeps increasing as the supply of tokens in the liquidity pool gets lower. We can see here that the number of tokens owned is down to 1,290, whereas the balance is up to 3,100. So tokens are getting rare, which means they're getting more expensive. Then Bob allows for his 96 tokens to be transferred back to the liquidity pool and then sells them and says, I should get at least 200 Tez. And we can see that his 96 tokens are taken from him, but then he gets 213.997 Tez. So he indeed made a profit of almost 114 Tez for his initial 100 Tez purchase. So here there's high demand for these tokens, so people who bought tokens early can make a profit. All good? In this video, we will talk about the concept of arbitrage, and we will see that if there are two liquidity pools, or in other words, two exchanges for the same pair of tokens, but the price is not the same for both, then there's an opportunity for arbitrage where we can make some profit. So the idea is that you could have two contracts, two liquidity pools, two exchanges, where the exchange rate between the two tokens A and B, or A and Tez, are different. When this happens, this creates an opportunity for anyone who owns some tokens to purchase some tokens A in the contract with a cheaper price, paying with the other token, and then to sell these tokens in the contract with a higher price. And you get a higher amount of token B than what you initially paid. So you make a profit. This happens all the time on blockchains, but also other markets. And we presented a very simple opportunity where it's just a direct exchange rate between tokens, but there could be paths where you go through intermediate tokens, but then find a way to make a profit with a succession of exchanges. So there's always many users and in practice bots that constantly look for search arbitrage opportunities. And as soon as they see one, they purchase some tokens in one exchange and then sell them for more in the other exchange. By doing that, they make a profit, but they also help to make sure that the exchange rate for a given pair of tokens stays approximately the same across all the different liquidity pool contracts, all the different markets. And you can do this even if you don't have money by using flash loans so that you can take advantage of any such arbitrage situation. If you notice two liquidity pool contracts that have different exchange rates for the tokens A and B, you could borrow tokens of type B from a flash loan contract
Then you can purchase tokens A at the cheaper price using your tokens B that you just borrowed, immediately sell your tokens A at the higher price in the other liquidity pool, getting more tokens B than you spent. And with these tokens, you could reimburse a flash loan and the interest, but still make a profit. So you don't actually need to own any tokens B or A to take advantage of an arbitrage situation, thanks to flash loans. Because flash loans can make you temporarily rich in any of the tokens. And of course, if you make a mistake and cannot reimburse the flash loan, everything is cancelled, so there is no risk for anyone. Let's work on an exercise where you will take advantage of an arbitrage situation. You will use the ledger and liquidity pool contract and create a test that does the following. With a user, Alice, you will create a token with a supply of 10 million tokens. Then Alice will create 2 instances of the liquidity pool contract, and each of those instances she will provide liquidity with 1 million tokens and 1,000 Tez. Once this is ready, we will have Bob purchase 100 Tez worth of tokens from the first liquidity pool, and this will create an arbitrage situation because it will change the price of the tokens that was initially the same in both pools, but now that Bob bought from one pool, it will change the price of the token in this pool. So Carl will take advantage of this arbitrage opportunity and earn some Tez. So using the example contracts that we provide on the Git repo and on OpenTezos, pause the video and write a test where Carl makes as much of a profit as possible in this situation. Let's take a look at the solution. So here we have our ledger contract and the liquidity pool contract that we didn't change. And so in our tests, we here create a ledger in the name of Alice with a total supply of 10 million tokens. Then we create 2 identical liquidity pools, LP1 and LP2. Each liquidity pool is created in the name of Alice, attached to this ledger, and Alice provide 1 million tokens and 1,000 Tez of liquidity. Initially, the price is the same for both tokens. Then we have Bob buy 100 Tez worth of tokens from the first liquidity pool, and he expects to get at least 80,000 tokens. So this creates an arbitrage opportunity because the tokens on the first liquidity pool will be worth more than the tokens on the second liquidity pool because there are now fewer tokens in the first liquidity pool. So Carl can buy some tokens from the second liquidity pool and then sell them for more in the first liquidity pool. And the question is, how many should he buy and at what price? And the idea here is that since Bob only bought a small amount of tokens compared to the whole pool, then the price won't change by much. So we could use some math to compute what's the right amount. By trial and error, we can see that the best amount is to spend 48 Tez, and this will buy 40,802 tokens. And with these numbers, Carl will make a profit of 4.76 Tez. And if he bought for 49 Tez, then the profit would be a bit less. And same for 47 Tez, profit would be a bit less. So maybe the ideal value is not precisely 48 Tez, but this will be close enough. So Carl will buy this amount of Tez worth of tokens, and he expects to get exactly this amount, but that's the minimum he says he wants to get. Then he will sell those tokens back on the first liquidity pool, so it allows this number of tokens to be transferred by the first liquidity pool and then sells them. So let's give it a try. So we can see the creation of the ledger, creation of the first liquidity pool, then we allow transfer of liquidity to this first liquidity pool. We do the same for the second liquidity pool. And then we have Bob who buys 100 Tez worth of token. We see that with this amount he actually got 90,910 token. Then Carl buys for 48 Tez worth of tokens. We see that indeed the number of tokens he bought is 45,802. And that by looking at this value that we actually set this exact value here. Then the tokens are transferred, and then Carl allows for these tokens to be transferred when he sells it, and he calls to sell this amount of token, and he expects, well, he doesn't expect anything, he'll just see what he can get. But we can see here that the tokens are transferred, and then we have 52.76 Tez transferred. So he bought them for 48 Tez, and he sells them on the other liquidity pool for 52.76, making a profit of 4.76 Tez. If we want to better understand what happens, we could check the prices at different moments of the different liquidity pools by calling scenario.verify, and then I get the token price and check that, for example, it's at least 90 mutes, some arbitrary value. And the get token price can be instrumented with some trace instructions to find out what the different values are, what the ratios are, what the current price should be. And so we can run it, then open the console to see here the price of the token return is 1000. So when we call it here, right after we created the liquidity pool, then one token equals 1000 mutes. But after Bob buys some token, then we can run it again, and we see that this time the price increased to 1210 mutes, etc. So you can use this instruction at different places with the two liquidity pools to check exactly what's happening. Very convenient to help you understand. You can play around and see what happens. In this video, we will show that in some situations it's possible to manipulate prices of tokens and cheat if contracts are not protected against this manipulation. Contracts that want to attract a wide audience may offer users to pay in a choice of multiple tokens. So you could accept payment in Tez, but also accept payment in a number of other tokens that people own, so that they don't have to first trade their tokens before they can use your contract. So for example, we could change our membership contract to sell the access to a club. We could set the entry price at 1000 Tez, but people could also pay the equivalent price using token A. For the contract to be able to do that and use the right price, it will need to obtain the exchange rate between those two tokens. But this can be done through the liquidity pool. You could use the view get token price from the liquidity pool to find out what's the current exchange rate. Let's take a look at this version of the membership contract. It will use a ledger. It will use our liquidity pool that we don't change. And here is the membership contract. When we created, we initialize a membership price in Tez. We set the owner, we give the address of the ledger and the address of the liquidity pool. And we have our set of members here. Then users have two ways to join the club. They could join by simply paying the membership price in Tez. So we check that they pay the right amount. We add them to the list of members and we send the amount to the owner. So there's an extra useless line here. But users could also join this club by paying with tokens. And when they call, they say how many tokens they pay. We would then check the current token price by using the get token price on-chain view from the liquidity pool. And then we check that if you multiply the number of tokens that the user is willing to pay with this current price, it should be at least the membership price in Tez. And if that's the case, then we transfer the tokens from the ledger to the owner. And then we add this user to the club. And then we have our tests where we create a ledger, liquidity pool. We provide liquidity to the liquidity pool. Then we create the membership contract with an entry price of 1000 Tez. We have Bob
simply join the club by paying 1,000 Tez. Then we have Carl join by paying 1,000 tokens. Let's give it a try. It worked. So we see that we created the ledger, the liquidity pool. We provide liquidity to the liquidity pool, then create the membership contract. And then we transfer 1,000 Tez from Bob's account so that Bob can join. We can see here that Bob is a member. Then Alice transfers 2,000 tokens to Carl so that Carl can join using tokens. And Carl allows for 1,000 Tez to be spent by the membership contract. And then Carl joins with tokens with 1,000 token. And the tokens are transferred. And so at the current price, paying 1,000 token works. Now the issue is that unfortunately this contract has a very serious flaw. And the question is, can you figure out a way to obtain membership at a very low price? And as a hint, I can tell you that the idea is that the exchange rate can be manipulated. Look at this membership contract and think about how we can manipulate the price so that people can join the club without paying much. Pause the video and think about it for a minute. So the way you can manipulate the price to join the membership contract is that you can manipulate the exchange rate of token A versus Tez. To do that, you would first buy a lot of tokens A from the liquidity pool. This will automatically increase the price of token A by a lot in this liquidity pool. Then you can purchase membership in the club using just a few tokens A, because those tokens are worth a lot now. And then you can sell your tokens A back to the liquidity pool at the same price you bought them. So you temporarily increase the price of token A by a lot by purchasing most of the tokens A from the liquidity pool to make them be worth a lot. Then you use them to purchase membership, and it will check the price using this liquidity pool, and then you can sell all your tokens back. But for this to work, you need to have enough funds to buy tons of tokens A from the liquidity pool, and you also need to make sure that nobody jumps on the arbitrage opportunities, because if you bought a lot of tokens, then people can sell tokens to the liquidity pool because the price is very high before you get to purchase membership in your contract. And remember that there's always bots looking for these opportunities. So as soon as you buy a lot of tokens A, some bot will purchase tokens A from a different pool and then sell them to the liquidity pool to make a profit. And your attack won't work. So for this attack to work, we need to make sure we have enough funds, and we need to make sure nobody can jump on the arbitrage opportunity that you create by buying so many tokens. Because if this happens, when you sell them back, you won't be able to sell them at the right price and you will lose money. So if you assume that you only have 200 Tez, how could you still join this club without spending much? Pause the video and think about it for a minute. So the solution to both issues with our attack is to use a flash loan. You could borrow enough Tez through a flash loan to purchase lots of token A and therefore impact the price, and then you could pay back the loan within the same transaction. And if you do everything within a single transaction, nobody will be able to use arbitrage, because nobody can run any smart contract call or any transaction at all within your transaction. As an exercise, you will try to simulate this using the ledger, the liquidity pool, the flash loan, and the membership contracts. You will create an attack manually in your test that will make it possible to purchase a membership from an account that only spends 200 Tez. To create this attack, you need to be careful with the execution order of a transaction. Remember that when from an entry point you call a smart contract, you're not actually executing that smart contract right away. You're adding it to a stack of transactions that will be executed after the execution of your entry point. And the order of execution of the different transactions is important for you to be able to create this attack. And to help you, we prepared a file that you can find on OpenTezos or on Git with all the contracts you need, and you just have to write a test. Pause the video and give it a try. Let's look at the solution.
So we have our ledger, we have a liquidity pool, we have a flash loan contract, and then our membership contract. And then we will create an attacker contract that it will temporarily use a flash loan to increase the value of our token, then use just a few tokens to pay for the membership, and then pay the loan back. So this attacker will need the address of all the different constructs it will interact with. We will need to calculate how many tokens we buy. So this is a value you can calculate. And we initialize how many Tez we will borrow from the flash loan. And we have the price of membership. And so the attack needs to be in 3 parts. That's because the first part will borrow some Tez from the flash loan. But since we don't get the funds immediately, we cannot do the second part immediately. So what we do is we then call the second part to make sure the second part is executed after we receive the funds from the flash loan. In the second part, we will buy tokens from the liquidity pool and then call the next part, because the next part needs to happen after we receive the tokens from the liquidity pool, so that we can then benefit of the new value of the token in that liquidity pool to purchase the membership. So here we borrow funds from the flash loan. Here we buy a lot of tokens from the liquidity pool. And here we buy the membership at a low price. We sell our tokens back to the liquidity pool, and then we repay the flash loan. We can check the details. And here we can see that we use the view from the liquidity pool to compute how many tokens we need to pay to the membership contract and send here. So we compute here price in tokens by getting the current price of our token, and then we see how many do we need to pay for the membership price. We add 1 to take into account running issues, and that's the amount we will transfer when paying for the membership. Then in the test, we can see that we create the liquidity pool, the ledger, the membership, flash loan. We deposit some funds on the flash loan, and then we simply call our attacker contract after allowing the liquidity pool and the membership address to withdraw some tokens from the funds of the attacker contract. So the question you may now ask is, how do we prevent such attacks? And for that, you need to really understand what's the cause of the flaw. And the cause of the flaw is that the liquidity pool may not always reflect the real exchange rate. It only reflects the real exchange rate if you give enough time for arbitrage opportunities to be taken advantage of by bots or other users. So knowing that, how can we avoid this issue, this type of attack? Pause the video and think about it for a minute. So if you want to prevent attacks based on price manipulations, one way is to keep track of prices within some time frame. So for example, within some number of blocks, like 5 blocks. Then across those 5 blocks, you could use the median price within that time frame as given by the liquidity pool. This gives enough time for bots to take care of arbitrage opportunities, and you avoid flukes in the price of the liquidity pool. And most of all, you make sure you don't take the instant price returned by the liquidity pool based on the current balances. You take a price that has been computed before your current transaction. There's another approach that consists in combining multiple sources, multiple liquidity pools, and again, taking the median of their prices. But you should make sure you don't take instant prices, because multiple liquidity pools could be manipulated at the same time. In this module, you will learn how to generate events from a smart contract, a feature that makes it a bit easier to create dApps that react to smart contracts. So smart contracts may emit events that you can observe from an off-chain app. And so the goal of events is to standardize how external apps can keep track of some aspects of a contract. Instead of having to go look at its storage, analyze transactions in the block, etc., it will simply be able to listen to events. Some examples where events could be used to inform apps and their users. an event that corresponds to the sale of an NFT within a collection, or an update to some value provided by an oracle, or the operation of a new proposal for a multisig or a DAO contract, where the user is expected to participate and vote after checking what the proposal is. In all of those cases, it's convenient for the contract to emit events and for dApps to observe those events so that they can react to it or warn the users about it. To emit an event from an entry point, you can add this instruction, sp.emit, and then you have up to 3 parameters. The first one is the only one that's mandatory, the other 2 are optional. The first one is a value attached to the event. It can have the type of your choice. Here we put a string, but it could be an integer, it could be a record, almost anything you like. Then you have an optional tag, so it's a word with no spaces that is attached to the event and that dApps can use in filters. So you could listen to all of the events that have a specific tag, for example. So finally, there's a with type attribute, and when you set it to true, some extra content will be added to the event that describes the type of the value in a way that is fully annotated. So events have absolutely no effect on chain. It's not going to change anything about the behavior of your smart contract. It's only for off-chain apps to observe. They are emitted by a transaction and are listed in its result in the order that they are emitted. And an app can obtain the list of events emitted by a transaction with their values, their types, and their tags. They can do so through RPC calls directly to the node, or they can use the dedicated API of indexers that support events, for example tzkt. Let's take a look at an example. We'll take the basic countTheCalls contract that simply counts the number of times we call makeCall. But now, when we call makeCall, it will emit 3 events. One just with a string hello, one that will have both a string and a tag, my tag, then finally one a bit more advanced where we include a full record with 2 attributes, a tag, and we include the annotated type of this record. So whenever somebody calls makeCall, all these 3 events will be generated in this order. In the SmartPy IDE, when we run it, we can see that we have this makeCall entry point being called, and then the hello event, the second event, and then this event with a record. That's about it. If you go to a block explorer on the contract that emits event, here we can see in the Michelson code emission of some event with a pair of ints, then you can see that you have an events tab that is only present for contracts that emit events. And if you go to the events tab, then you can see the different events from different transactions. Here we can see one in this block, one in this block, etc. In this module, we'll talk about how we can upgrade contracts, whether it is to fix a bug or add new features. So by design, and thanks to decentralization, a smart contract can't be modified by the author. This is so that users can trust that the contract will always do what it says. But the author of a smart contract sometimes really wants to be able to make some changes. It could be because they need to fix a bug that was found in the contract, or it could be to add a new feature, or make it compatible with a new standard, or to fine-tune the business logic. For example, how rewards are distributed, how votes are counted, etc. So the question is, how can we solve this dilemma? On one side, you want to make it possible to change a contract, but on the other side, you want to allow users to trust that the contract won't be changed to their disadvantage. So how can you solve this dilemma? Pause the video and think about it for a minute. A common solution is the simplest one. You can simply replace the contract with a new one. And sometimes it's just that simple. You simply point your DApp to the new contract. But this approach has limitations. First, you have to warn everyone that a new contract is being used and that the address that the DApp points to has changed. And if users have assets in the old contract, they have to move these assets to the new contract and then stop using the old contract. But these assets may be locked in the old contract, for example, until the deadline that is quite far in the future. Let's start with an exercise where you will take the endless wall contract,
we use a version that has an on-chain view that gives access to messages from each user. And then your goal is to create a new version of this contract where we now require new messages to be at most 30 characters, where we charge 1 Tez per message. And we allow users of the old contract to transfer their messages to the new one for free without paying the 1 Tez per message. So we have our existing endless walk contract here that stores all the messages in a big map and that stores the owner with the right message entry point. And then we have this on-chain view, read messages, that simply returns all the messages for a given user. So start from this contract and write a new version of the contract that can transfer all the messages using this view into the new contract. You will have to have both contracts in your file so that you can create a test that makes them interact with each other. Pause the video and give it a try. Let's take a look at a solution. So here we have the old contract, and here this is the new version of the contract. So we still have a big map to store all the content. We still store the owner, but we also store the address of the old contract so that we can interact with it. In the write message entry point, we simply make the changes to the logic where we charge 1 Tez and we check that the messages are shorter than 30 characters. Everything else is the same as the previous write message. But now we add this new transfer old messages entry point where we call the view read messages from the old contract to obtain the data associated with that user, the user who's calling this transfer old messages entry point. And we simply store this old data in the new contract without charging anything. We assume that the user never called write message, so we simply create or replace the entry with the sender as the address. Finally, we keep the same on-chain view in case we want to upgrade the contract again. And then in the test, we first create the first contract with some message, and then we test the new contract where we write messages, and of course longer messages are not allowed. We need to make sure we pay 1 Tez, but we can also transfer messages from the old contract here by calling transfer old messages as Bob. And then Bob can finally add new messages. An issue with this approach is that it requires the initial contract to have views so that the new contract can access the old data. So the question for you is, how would you manage the transfer of data without having an on-chain view in the old contract? Pause the video and think about it for a minute. So if the old contract doesn't have any views, we have to count on the owner to validate every transfer of data. We can think of 3 approaches to do that. The owner could simply initialize the contract with all of the data from the old one. The issue with this approach is that this could exceed the gas limit for the deployment. The origination transaction would be too large to fit in a single block, and it would also be quite expensive. The next option would be for the owner to have an entry point to transfer bunches of data from the old contract and split the transfer between many different calls. And the main issue with that is that the owner themselves will have to pay for all the storage costs and all the transaction costs required for all these calls. And that could be quite expensive if the contract is very successful. A better option would be for the owner to publish signed messages that allow users to repost each of their old messages. So the idea here is that users should be able to post old messages for free, but for any new message they would have to pay 1 Tez. So the owner can send them signed messages off-chain as a proof that the owner of the contract allows them to post these messages for free. With this approach, each user will pay for the transaction fees and the storage fees for the transfer of their own data. They just don't have to pay the 1 Tez to the owner again. So let's do this as an exercise. You will start with the same initial endless walk contract as in the previous exercise, but this time without the on-chain view. And then you can create a new version of the contract or modify your new version of the contract so that users can repost their old messages for free. So you can assume that off-chain, The owner will publish a signature for every existing message, and the signatures will guarantee that the old messages sent by users were present in the old contract. So you will have to write a test, and in the test generate all the signatures, and then call the new contract in the name of different users with the content of the messages and the corresponding signatures. Pause the video and give it a try. Let's take a look at the solution. Here we have the old contract that we didn't change, except we removed the on-chain view. And here is the new version of the contract. Here we don't store the address of the other contract, we don't interact with the other contract. Instead, we store the public key of the owner that we will be able to use to verify signatures sent to the contract. The write message entry point didn't change, so we only changed the transfer old messages entry point, and we take as parameters the old data packed as a sequence of bytes and the corresponding signature. Then in the entry point, we check that the signature is valid. So we check that it corresponds to the public key of the owner for the signature and this packed data. Then we unpack the data. The data contains the texts of the messages from the user and the corresponding timestamp and the user address. So we unwrap the data and then add it to the big map. And in the tests here, after creating the new contract, we fetch the old data from the old contract. Off-chain, anybody has access to this data, so we can simply fetch that data. We create a record where we add the user address, we pack it into a sequence of bytes, and then we call make signature using the secret key of Alice to generate a signature for this data. And then we call transfer old messages. Let's give it a try. And we can see that everything worked well. In the version we just presented, an issue is that all the messages were duplicated into the new contract, and we had to have each user pay for the storage and transaction fees again. This can be a bit costly, but another issue is that if the data represents assets, duplicating them could be problematic. For example, imagine that the assets are NFTs. If you duplicate NFTs, this would mean both the original NFT and the copy could be sold separately and exist as separate NFTs. So the question for you is, can you think of a solution in the case of an NFT contract that avoids duplicating the NFTs? One solution in the case of an NFT contract is to wrap the NFTs. We already use this approach as a way to go around paying royalties. And the idea is that the new contract can buy an NFT from the old contract and then mint its own version of the NFT. And this copy would become the new official version and could have a different set of rules for trading the NFT compared to the old version. But this can be considered as upgrading a contract. This approach only works when the ownership of assets can be immediately transferred to a new owner. That will be the contract. If you can plan things in advance, there are better approaches available. So you can make upgradability a feature of your contracts. We already saw that if you planned an on-chain view in your contract, this can allow you to duplicate the data. But what we really want is to avoid duplicating the data, but instead move the data or the assets into a new contract without duplicating them. So the question is, how can we make sure that data can be moved into a new version of the contract? Pause the video and think about it for a minute. Really transferring the data to another contract can be costly or complicated. You have to repay for all of the storage costs in the new contract, and you also have to split the transfer into many transactions. So what we really want is to keep the data in the same contract. But since we want to upgrade the contract and have a new contract, a good way to keep the data in the same contract is to separate the logic into a separate contract that interacts with the data contract. So you have one contract that takes care of storing the data, and then one contract that takes care of the logic, and the contract in charge of the logic could easily be replaced. So only the ownership of the data contract would then need to be transferred instead of the ownership of every asset in the old contract. Let's do it as an exercise. So your goal is to create a version of the endless walk contract that is upgradable, and you do that by splitting it in two. You will have one contract that will be in charge of storing the data, and then a second contract that will contain the logic and access the data through the first contract. Then you will show how it can be upgraded by using a new contract that accesses to the data contract. And again, it should only allow messages to be of length less than 30 characters, and it should charge 1 Tez for each new message. Let's take a look at the structure of such a contract. So first we look at the data contract. In the storage, we will have all the content in the big map, wall content. And then we store the owner of the contract, but this time the owner is the address of the other contract, the logic contract. Then we have 2 entry points that will be called by the logic contract. The first one is the write message entry point that takes the message and the user as parameter. The caller will be the logic contract, so we check that indeed only the logic contract can call this entry point. And then we simply store this data into wall content with the user as the key. Then, as the goal is to be able to upgrade the logic contract, we need another entry point, update owner, where the previous logic contract can say, okay, I need to be upgraded. Here is the address of the new contract that will take over the logic. And so we pass the address of the new contract as parameter. And we check that the caller is indeed the current owner before updating to the new owner. Then let's look at the structure of the logic contract that we call upgradable endless wall. In the storage here, we don't store much. We simply store the address of the data contract and the address of the owner of this contract. In the entry points, we simply have the usual write message entry point that takes a message as a parameter. And all it will do is call the write message entry point of the data contract with the message and the address of the caller. Then when we want to upgrade this contract, we call an entry point upgrade with the address of the new contract. We check that it's the owner of this contract that calls, and then we call the data contract to say update the owner to the address of the new contract. So your goal is to implement these 2 contracts and demonstrate the upgrade procedure to a new contract in your tests. And of course, again, the new version of the contract should only allow messages of length below 30 and charge 1 Tez for each new message. Pause the video and give it a try. Let's take a look at a solution. So we start with the data contract. We see here that we have our big map and the address of the owner contract here. In write message, we check that the caller is the owner, so the logic contract. And then we simply add the content as usual in the big map. And then the update owner entry point simply checks that the caller is the old owner and replace it with the new address of the logic contract. Then in the logic contract, we store the owner and the address of the data contract. In the write message, all we do is call the write message entry point of the data contract. And then in the upgrade contract, we call the update owner entry point of the data contract to change the owner, after checking that it is the owner of the logic contract doing the transfer. In the new version of the logic smart contract, we keep exactly the same structure and the same content. The only thing we need to change is to add the assertions about the length of the message and about the 1 Tez price to call write message. And in the test, we first create the first version. We first create the data contract. We pass it to the first version of the logic contract. Then we upgrade to the new version and continue adding messages. We can give it a try. And we can see that we can keep adding messages. And then we have all the messages sent through the old logic contract and the messages sent with the new logic contract. So one issue with this new solution is that sometimes we really don't want the address of our contract to change, because then we need to send everybody to the new address. So to deal with that, we can use a proxy contract. A proxy contract is a contract that forwards all of the calls to the real contract. So it's an intermediate between the user and the real contract. And the address of this real contract can be changed while your proxy contract never changes, as long as the API, the entry points, and the parameter of the entry points stay the same. So let's give it a try as an exercise. Try to make the endless wall contract upgradable using this proxy pattern. Then show how it can be upgraded to add the rules about the length of the message without changing the address that people use to interact with the contract. So here, we would have again two contracts, the inner endless wall contract. We would have the usual storage with the big map and the address of the owner. That will be the proxy contract. And we'll simply have one entry point, write message, that takes as parameter the message and the user, check that the caller is the owner, and update the data. And in the proxy contract, we will store the owner and the address of the inner contract. In the write message contract, we simply call the inner contract write data entry point with the message and the user, that is the caller. And then we have an entry point to upgrade to a new contract. We check that the caller is the owner, and then we replace inner contract with the address of the new contract. So your goal is to implement these two contracts and demonstrate the upgrade to a new inner contract. Pause the video and give it a try. Let's take a look at the solution. So here we have our inner contract with the wall content and the owner. The write message entry point is the usual, nothing special about it. Then we have here our main proxy contract where we store the owner and the address of the inner contract. And whenever we call write message, we simply forward that call to the inner contract. And when we want to upgrade, we simply store the new address of the inner contract. And if we want to upgrade this contract, we only upgrade the inner contract, and so we can update the address of this inner contract and keep using the same address for the main contract. So here we have a new version of the inner contract. It is pretty much the same as the initial one, but with this extra assertion. And here again we have the test that first creates the proxy, then initializes the inner contract, and then we upgrade to the new inner contract. You can give it a try and see that it works. So once more, there is an issue with this approach, which is that when we upgrade the inner contract, all the data is lost. And again, deploying the new inner contract with a copy of all of the data would be too costly. But we could combine the two approaches that we just saw. The proxy contract on one side and splitting the contract between the logic and the data on the other side. So we would have three contracts. So it's starting to be a bit complicated, but it can work. In the next module, we will see another approach that is based on a feature called Lambda. In this module, we will see another approach that can be used to upgrade contracts, and that is using a feature of the language called lambdas. On Tezos, it is possible to store pieces of code in a variable or in the storage of a smart contract using lambdas. A lambda is a piece of code that can be stored, then executed. In particular, it's a piece of code that can take some parameters and that returns a value. This value could contain operations to execute, but by default, they have no side effect. So executing the lambda itself won't change the storage or emit operations. But with SmartPy, there's a syntax that makes it transparent to include feature that allows to do either of these. So let's see how to create a lambda. To create a lambda, we declare a function within the main module that takes one parameter and return a value. We can keep this lambda in the storage by simply using the name of the function as the value. As we do here, we store a default rule that is defined here in the data.rule attribute of the storage. Then we can call it from an entry point. So here, when we call execute rule, we can call self.data.rule and pass the current value as a parameter. And then we get the result and store it again in the contract. So here, this is a rule that simply increments the value that we pass as a parameter. Then we can have another entry point that updates the rule to a new function. So here we can simply change self.data.value equals new rule, where we use a different rule and store it. So a lambda really only takes one parameter. So if we want multiple parameters, we have to use a record. In the definition of your function, you actually declare multiple parameters separated with commas, but these parameters will correspond to different attributes of the record that you will send when you make a call. So here we have two parameters, A and B, and the rule simply adds A and B and returns the result. But when we call this lambda, we need to create a record with the attribute A with the first value, and the attribute b with the second value. So here it looks like separate parameters, but when you make the call, it's a single parameter that is a record containing two attributes. Although internally, lambdas do nothing except doing some computation and returning a value and cannot modify the storage or create transactions, in SmartPy we have added syntax that you can use in Lambda to allow you to modify the storage and create transactions. So in practice, what really happens is that the internal lambdas simply return the changes to apply to the storage and also return a list of transactions to be added to the list of transactions of the entry point. Let's work on an exercise where you will create an upgradable contract using a lambda. So you will start again with the endless wall contract and then make it upgradable by the author using a lambda so that you can support rules about the amount to pay when writing a message and rules about the content of the messages that are allowed. For example, the length of those messages. So everything about that should be handled by a lambda. And then you add an entry point to allow the author of the contract to change this rule. So the initial rule should be that any message is allowed and it's free. And the new rule should be that the message's length should be less than 30 characters and the amount to pay should be 1 Tez. Pause the video and give it a try. Let's take a look at the solution. Here in the main module, we create two versions of the internal rule. The first version doesn't do anything. We don't check anything. We allow every message and it's free. The second rule simply checks that the length of the message is less than 30 characters. It should be strictly less. And you will notice that we don't check anything about the price yet. We'll talk about it in a minute. So in the endless wall contract, we as usual store the content in a big map, the owner, but then we store this extra value that will be a lambda. Verify, that takes care of verifying if we are allowed to send a given message. So we initialize it with default verify message. In the right entry point, we do the usual, but at the beginning, we simply call self.data.verify with the message. And then we have an entry point to change the rule. Set verify, that takes the new rule as parameter, and we verify that it's the owner calling it, and we simply store this new rule. So one issue here is that we didn't plan in our write message entry point that we would be able to change the price of calling message. So since we didn't plan it and didn't pass the amount as parameter, we will be stuck here and cannot verify the price. So when you use a lambda, you have to think ahead of time everything that you want to be able to change. On one side, it's good because people who read this contract know that all you can do is check if this is allowed based on the content of the message. And if they read this, they see, okay, you won't be able to charge ever in the future. So I'm free to use this. It's always going to be free. I don't need to worry about. So in a way, that's a good thing. So you have to think about everything you may want to change in the future. So if we want to make sure we can decide later on to add a price, we need to send the amount to the lambda. But again, we cannot simply send two parameters. We have to create a record. So we create param equals sp.record message like this, and then we send that parameter. And now we need to change each of these lambdas to add the price here and here. And then we can assert price equals 1 Tez. So if we give it a try, we can see that here we didn't send 1 Tez because I just changed the rule. But here we can pay 1 Tez. And then it works. All good. So when using lambdas, as we just saw, you can only change aspects that were already planned to be changed. Another example is that in the code we just presented, we couldn't add a rule about the total length of a text a given user may have. We can only make a rule about the new messages that we add, but not the total amount of text that they store in the contract. But as we said, this is a good thing. It means users can read the contract and know the limitations of what changes you may make in the future, so that they can trust that everything else won't change, which is a really important part of using smart contracts in a decentralized blockchain. In this short module, we will list all the different ways we presented on how to upgrade contracts. We presented 4 different ways. The first one was to simply point the dApps to a new contract, which implied supporting transfers of data or assets to the new contract. But we saw that the transfer may be inconvenient or costly, and that for NFTs, we could use wrapping as a way to transfer the assets. The second approach was to store the data in a separate contract that could be used by the new logic contract. But of course, this means we cannot change the structure of the storage between versions, since we keep this data contract between upgrades. The third version was to use a proxy contract so that we could keep the same address for the contract. But the limitation is that this means the API has to be the same between versions. And finally, we just saw how we can use lambdas to place some of the logic in the storage of the contract. So this means there are limitations to what the owner can change in a contract, which can add trust for the users. But that also means that all the aspects that the owner may want to change need to be thought about in advance. So here we talked about how to upgrade the contract, but in each case the owner could unilaterally make changes to the contract at any moment. So we could limit what the owner could change, but still they could change quite a bit whenever they wanted. But we really want users to be able to trust that the contract won't be changed so easily, as this really defeats the whole point of using a decentralized blockchain. So there are 2 ways to help reduce the risk of a bad surprise for the user when a contract is being upgraded. The first one is to have a delay between the time the change is made public and the time this change is effective. So for example, you could have a 2 weeks delay that allows users of the contract to exit the contract and get their assets out before the change is applied if they dislike that change. But this may not always be possible. The assets could be stuck in the contract for a very long time. Another approach is to use contract governance, basically letting users vote and only apply changes that users approve. This can be done through a multisig or a DAO, a decentralized autonomous organization contract, which we present in the next module. In this module, we will talk about multisig and DAO contracts. Contracts that allow people to work together as one, for example, to collectively manage some assets. So first we'll talk about decentralized autonomous organization, or DAO. A DAO is a smart contract that enables communities to collectively manage resources. The participants in a DAO can contribute funds or resources that are stored in the contract. Then, in exchange, they receive tokens or shares representing their ownership and influence within the DAO. Then they can propose ideas, projects, or changes, then vote to determine which of these ideas are accepted or rejected. And people may receive rewards or incentives based on their contribution, work, or voting participation. So the good thing with DAOs is that the decision process to manage the shared assets is decentralized, fair, and transparent. DAOs can be used in many different situations. For example, you can have collective decision-making on a project development, where you allocate resource, manage the budget, and distribute rewards. DAOs can also be used in various industries, such as finance, art, governance, social impact, and decentralized applications. In finance, DAOs can facilitate decentralized investment funds, lending platforms, or decentralized exchanges. Finally, DAOs can empower communities to collectively manage digital assets, develop open source software, curate content platforms, or govern decentralized protocols. As an example, let's look at the Colibri Finance Protocol. Colibri is a DeFi protocol that allows users to borrow stablecoins against Tez. It uses smart contracts, and each smart contract is referred to as an oven, to collateralize Tez versus the stablecoin KUSD. Each oven has multiple functions. You can deposit some Tez into the oven. You can withdraw Tez from the oven. You can borrow KUSD against the oven using Tez as collateral. Then you can repay KUSD that was borrowed against the oven. Finally, you can liquidate, and your oven is liquidated automatically if your borrowed stablecoin exceeds your Tez deposit. So let's look at how a DAO is used to manage the governance of the Colibri Finance Protocol. KDAO is the governance token used for the Colibri Finance Protocol, and you need to own KDAOs to participate in the governance of the protocol. You can vote or submit proposals. To submit a proposal, you need 1,000 KDAO, and you submit it on the Colibri.finance protocol by pushing a piece of code, a lambda. As an example, we can take a look at proposal 41. It was proposed after a white hat hacker had found 2 critical vulnerabilities in the Colibri protocol that could have led to a drain of all of the funds of the protocol. This white hat hacker disclosed those vulnerabilities, and the developers took actions to patch the bugs. But as a reward, the community decided to make an on-chain proposal via the DAO implementation in order to transfer 50,000 USD to the white hat hacker. We can go to the Colibri governance website to check all the different proposals, and we see here proposal 41, pay security researcher for bug disclosure. And we can see that people voted yes by a wide majority, and some people abstained. And we can click here to see the detail of the proposal with a short description, a link to some details, and here we can see the Michelson code of the lambda that was sent, and that included a transfer of tokens to the researcher. Another example of DAO is the Tezos ecosystem DAO. It was designed to curate and vote on the distribution of Tez for various Tezos ecosystem initiatives. It's governed by a small number of key holders that include the Tezos Commons, Trilitech, Tezos Domain Foundation, the Tezos Foundation itself, and the Tezos India Foundation. Anyone can submit any initiative to the DAO via the Tezos Agora forum. Then the initiatives will be curated by Tezos Commons and proposed to the DAO on-chain. And the objective is to facilitate community engagement in funding decisions and to promote the growth and development of the Tezos ecosystem. Basically, it's a way for people to be rewarded to contribute to the Tezos ecosystem. Now let's take a look at what the smallest DAO could be. We can have a variety of different types of DAOs with different features, including governance tokens, rewards, etc. But they all include a voting system with various rules on how votes are counted, for example with quorums, etc. So a minimal DAO would include a list of participants, a system to propose decisions, and a voting process where decisions are executed when approved by a given number of participants. This kind of minimal DAO is already very useful. It even has its own name. We can call it a multisig. So what is a multisig? It's a contract that requires multiple signatures in order to execute a given transaction. This is a way to enhance security by ensuring that no single party has complete control over a transaction. For example, if you have a company, you don't want to have one single person in charge of the private keys, and instead you can use a multisig where multiple people have to agree before a transaction is confirmed. Multisig contracts operate on the principle of consensus, where a predetermined number of signatures are required to authorize a transaction. Each signature is associated with a specific participant or key holder, and the contract verifies that the required number of signatures is provided. Multisig contracts are commonly used to secure funds or assets, especially in cases where multiple parties are involved or an added layer of trust and oversight is desired. Multisigs can be used in a number of use cases. For example, for escrow services, multisig contracts can be used when funds are held in a contract until specific conditions are met. and multiple parties must provide their approval for the release of the funds. They can be used in decentralized organizations, where they facilitate decentralized decision-making within organizations by requiring multiple key holders to approve proposals or fund allocation. Finally, they can be used to secure wallets. Multisig contracts can be used to create secure wallets where multiple signatures are required to authorize outgoing transactions, which provides enhanced protections against unauthorized access or theft. As an exercise, your job will be to create a multisig contract where in the storage you have a predefined set of participants and a number of required votes to approve a proposal. And you will have an entry point to make a proposal in the form of a lambda to execute with a deadline, and another one to vote for that proposal and have it executed when the number of votes is reached. Pause the video and give it a try. Let's take a look at a solution. So here we have a lambda that we will use as an example of proposal that simply sends some Tez to a given address. In the contract itself, we will have a set of participants, a big map with all the proposals, a number of required votes for a proposal to be accepted, and then the ID that we use as a key for the proposal's big map. In the propose entry point, people can call the propose entry point to send a piece of code, a lambda, with a deadline for people to vote. We check that the caller is one of the participants in the multisig. Then we store the proposal with the next ID, and we store the code, the deadline, number of approvals at 0, and then a set of people who have already voted to make sure people cannot vote twice on the same proposal. Then we increment the ID. When somebody votes, they indicate for what proposal they vote, and then we check that they vote before the deadline, we check that they are indeed a participant in the multisig, and we check that they have not already voted. Then we mark that they have voted, we increment the number of approvals, and then we check if the number of approvals is equal to the required number of votes, then we execute the proposal. We don't need to delete the proposal because we have to be exactly at the number of approved. So if one more person votes, then we will exceed the number of proposals, and so this will not be executed. And in the test, we simply instantiate the multisig with a set of participants and a required number of votes at 2. So both Alice and Bob have to approve a proposal for it to be executed. Then we propose a lambda and have both people vote for it.